Undoubtedly, data science is the most evolutionary technology of the era. It's all about deriving useful insights from data in order to solve real-world complex problems. Hi all, I welcome you to this session on Data Science full course that contains everything that you need to know in order to master data science. Now before we get started, let's take a look at the agenda. The first module is an introduction to data science that covers all the basic fundamentals of data science. Followed by this, we have statistics and probability module where you'll understand the statistics and the math behind data science and machine learning algorithms. The next module is the basics of machine learning where we'll understand what exactly machine learning is, the different types of machine learning, the different machine learning algorithms, and so on. The next module is the supervised learning algorithms module where we'll start by understanding the most basic algorithm, which is linear regression. The next module is the logistic regression module where we'll see how logistic regression can be used to solve classification problems. After this, we'll discuss about decision trees and we'll see how decision trees can be used to solve complex data-driven problems. The next module is random forest. Here we'll understand how random forest can be used to solve classification problems and regression problems with the help of use cases and examples. The next module we'll be discussing is the k-nearest neighbor module where we'll understand how KNN can be used to solve complex classification problems. Followed by this, we'll look at the naive Bayes module, which is one of the most important algorithms in the Gmail spam detection. The next algorithm is support vector machines, where we'll understand how SVMs can be used to draw a hyperplane between different classes of data. Finally, we'll move on to the unsupervised learning module, where we'll understand how k-means can be used for clustering and how you can perform market basket analysis by using association rule mining. The next module is reinforcement learning, where we'll understand the different concepts of reinforcement learning along with a couple of demonstrations. Followed by this, we'll look at the deep learning module, where we'll understand what exactly deep learning is, what are neural networks, the different types of neural networks, and so on. The last module is the data science interview questions module, where we'll understand the important concepts of data science along with a few tips in order to ace the interview. Now before we get started, make sure you subscribe to Edureka YouTube channel in order to stay updated about the most trending technologies. Data science is one of the most in-demand technologies right now. Now this is probably because we're generating data at an unstoppable pace and obviously we need to process and make sense out of this much data. This is exactly where data science comes in. In today's session, we'll be talking about data science in depth. So let's move ahead and take a look at today's agenda. We're going to begin with discussing the various sources of data and how the evolution of technology and introduction of IoT and social media have led to the need of data science. Next, we'll discuss how Walmart is using insightful patterns from their database to increase the potential of their business. After that, we'll see what exactly data science is. Then we'll move on and discuss who a data scientist is, where we'll also discuss the various skill sets needed to become a data scientist. Next, we'll move on to see the various data science job roles such as data analyst, data architect, data engineer, and so on. After this, we'll cover the data lifecycle, where we'll discuss how data is extracted, processed, and finally used as a solution. Once we're done with that, we'll cover the basics of machine learning, where we'll see what exactly machine learning is and the different types of machine learning. Next, we'll move on to the k-means algorithm and we'll discuss a use case of the k-means clustering. After which, we'll discuss the various steps involved in the k-means algorithm. And then we'll finally move on to the hands-on part, where we'll use the k-means algorithm to cluster movies based on their popularity on social media platforms like Facebook. At the end of today's session, we'll also discuss about what a data science certification is and why you should take it up. So guys, there's a lot to cover in today's session. Let's jump into the first topic. Do you guys remember the times when we had telephones and we had to go to PCO booths in order to make a phone call? Now those times were very simple because we didn't generate a lot of data. We didn't even store the contacts in our phones or our telephones. We used to memorize phone numbers back then, or we used to have a diary of all our contacts. But these days we have smartphones which store a lot of data. So there's everything about us in our mobile phones. We have images, we have contacts, we have various apps, we have games. Everything is stored in our mobile phones these days. Similarly, the PCs that we use in the earlier times, it used to process very little data, alright? There was not a lot of data processing needed because technology wasn't evolved that much. So if you guys remember, we used floppy disk back then, and floppy disk was used to store small amounts of data. But later on, hard disks were created, and those used to store GBs of data. But now if you look around, there's data everywhere around us. All right, we have data stored in the cloud. We have data in each and every appliance at our houses. Similarly, if you look at smart cars these days, they're connected to the internet, they're connected to our mobile phones, and this also generates a lot of data. What we don't realize is that evolution of technology has generated a lot of data. All right, now initially there was very little data, and most of it was even structured. Only a small part of the data was unstructured or semi-structured. And in those days, you could use simple BI tools in order to process all of this data and make sense out of it. But now we have way too much data. And in order to process this much data, we need more complex algorithms. We need a better process. All right. And this is where data science comes in. Now, guys, I'm not going to get into the depth of data science yet. I'm sure all of you have heard of IoT or Internet of Things. Now, did you guys know that we produce 2.5 quintillion bytes of data each day? And this is only accelerating with the growth of IoT. Now, IoT or Internet of Things is just a fancy term that we use for network of tools or devices that communicate and transfer data through the internet. So various devices are connected to each other through the internet and they communicate with each other. Right now, the communication happens by exchange of data or by generation of data. Now, these devices include the vehicles we drive. They include our TVs, our coffee machines, refrigerators, washing machines, and almost everything else that we use on a daily basis. Now, these interconnected devices produce an unimaginable amount of data. Guys, IoT data is measured in zettabytes, and 1 zettabyte is equal to trillion gigabytes. So, according to a recent survey by Cisco, it's estimated that by the end of 2019, which is almost here, the IoT will generate more than 500 zettabytes of data per year. And this number will only increase through time. It's hard to imagine data in that much volume. Imagine processing, analyzing, and managing this much of data. It's only going to cause us a migraine. So guys, having to deal with this much data is not something that traditional BI tools can do. Okay, we no longer can rely on traditional data processing methods. That's exactly why we need data science. It's our only hope right now. Now, let's not get into the details yet. Moving on, let's see how social media is adding on to the generation of data. Now, the fact that we are all in love with social media, it's actually generating a lot of data for us. Okay, it's certainly one of the fuels for data creation. Now, all these numbers that you see on the screen are generated every minute of the day. Okay, and this number is just going to increase. So for Instagram, it says that approximately 1.7 million pictures are uploaded in a minute. And similarly on Twitter, approximately 348,000 tweets are published every minute of the day. So guys, imagine in 1 hour how much that would be, and then imagine in 24 hours. So guys, this is the amount of data that is generated through social media. It's unimaginable. Imagine processing this much data, analyzing it, and then trying to figure out, the important insights from this much data. Analyzing this much data is going to be very hard with traditional tools or traditional methods. That's why data science was introduced. Data science is a simple process that will just extract the useful information from data. All right, it's just going to process and analyze the entire data, and then it's just going to extract what is needed. Now, guys, apart from social media and IoT, there are other factors as well which contribute to data generation. These days, all our transactions are done online. Right? We pay bills online, we shop online, we even buy homes online these days. You can even sell your pets on OLX these days. Not only that, when we stream music and we watch videos on YouTube, all of this is generating a lot of data. Not to forget, we've also brought healthcare into the internet world. Now, there are various watches like BitFit, which basically tracks our heart rate and it generates data about our health conditions. Education is also an online thing right now. That's exactly what you are doing right now. So with the emergence of the internet, we now perform all our activities online. Okay, obviously this is helping us, but we are unaware of how much data we are generating. What can be done with all of this data, and what if we could use the data that we generated to our benefit? Well, that's exactly what data science does. Data science is all about extracting the useful insights from data and using it to grow your business. Now, before we get into the details of data science, let's see how Walmart uses data science to grow their business. So guys, Walmart is the world's biggest retailer with over 20,000 stores in just 28 countries. Okay, now it's currently building the world's biggest private cloud which will be able to process 2.5 petabytes of data every hour. Now, the reason behind Walmart's success is how they use the customer data to get useful insights about customers' shopping patterns. Now, the data analysts and the data scientists at Walmart, they know every detail about their customers. They know that if a customer buys Pop-Tarts, they might also buy cookies. How do they know all of this? Like, how do they generate information like this? Now, they use the data that they get from their customers and they analyze it to see what a particular customer is looking for. Now, let's look at a few cases where Walmart actually analyzed the data and they figured out the customer needs. So let's consider the Halloween and the cookie sales example. Now, during Halloween, sales analyst at Walmart took a look at the data, okay, and he found out that a specific cookie was popular across all Walmart stores. So every Walmart store was selling these cookies very well. But he found out that there were 2 stores which were not selling them at all. Okay, so the situation was immediately investigated and it was found that there was a simple stocking oversight, okay, because of which the cookies were not put on the shelves for sale. So because this issue was immediately identified, they prevented any further loss of sales. Now, another such example is that through association rule mining, Walmart found out that strawberry Pop-Tart sales increased by 7 times before a hurricane. So a data analyst at Walmart identified the association between hurricane and strawberry Pop-Tarts through data mining. Now guys, don't ask me the relationship between Pop-Tarts and hurricane, but for some reason, whenever there was a hurricane approaching, people really wanted to eat strawberry Pop-Tarts. So what Walmart did was they placed all the strawberry Pop-Tarts at the checkouts before a hurricane would occur. So this way they increase sales of their Pop-Tarts. Now guys, this is an actual thing. I'm not making it up. You can look it up on the internet. Not only that, Walmart is analyzing the data generated by social media to find out all the trending products. So through social media, you can find out the likes and dislikes of a person, right? So what Walmart did is they're quite smart. They use the data generated by social media to find out what products are trending or what products are liked by customers. Okay, an example of this is Walmart analyzed social media data to find out that Facebook users were crazy about cake pops. Okay, so Walmart immediately took a decision and they introduced cake pops into the Walmart stores. So guys, the only reason Walmart is so successful is because the huge amount of data that they get, they don't see it as a burden. Instead, they process this data, analyze it, and then they try to draw useful insights from it. Okay, so they invest a lot of money, a lot of effort, and a lot of time in data analysis. Okay, they spend a lot of time analyzing data in order to find any hidden patterns. So as soon as they find out hidden pattern or association between any 2 products, they start giving out offers or they start giving discounts or something along that line. So basically, Walmart uses data in a very effective manner. They analyze it very well, they process the data very well, and they find out the useful insights that they need in order to get more customers or in order to improve their business. So guys, this was all about how Walmart uses data science. Now let's move ahead and look at what is data science. Now guys, data science is all about uncovering findings from data. It's all about surfacing the hidden insights that can help companies to make smart business decisions. So all these hidden insights or these hidden patterns can be used to make better decisions in a business. Now, an example of this is also Netflix. So Netflix basically analyzes the movie viewing patterns of users to understand what drives user interest and to see what users want to watch. And then once they find out, they give people what they want. So guys, actually data has a lot of power. You should just know how to process this data and how to extract the useful information from data. Okay, that's what data science is all about. So guys, a big question over here is how do data scientists get useful insights from data? So it all starts with data exploration. Whenever a data scientist comes across any challenging question or any sort of challenging situation, they become detectives. So they investigate leads and they try to understand the different patterns or the different characteristics of the data. Okay, they try to get all the information that they can from the data, and then they use it for the betterment of the organization or the business. Now let's look at who is a data scientist. So guys, a data scientist has to be able to view data through a quantitative lens. So guys, knowing math is one of the very important skills of a data scientist. Okay, so mathematics is important because in order to find a solution, you're going to build a lot of predictive models. And these predictive models are going to be based on hard math. So you have to be able to understand all the underlying mechanics of these models. Most of the predictive models, most of the algorithms require mathematics. Now, there's a major misconception that data science is all about statistics. Now, I'm not saying that statistics isn't important. It is very important, but it's not the only type of math that is utilized in data science. There are actually many machine learning algorithms which are based on linear algebra. So guys, overall, you need to have a good understanding of math. And apart from that, data scientists utilize technology. So data scientists have to be really good with technology. Okay, so their main work is they utilize all the technology so that they can analyze these enormous data sets and work with complex algorithms. So all of this requires tools which are much more sophisticated than Excel. So guys, data scientists need to be very efficient with coding languages, and few of the core languages associated with data science include SQL, Python, R, and SAS. It is also important for a data scientist to be a tactical business consultant. So guys, business problems can be only solved by data scientists. Since data scientists work so closely with data, they know everything about the business. If you have a business and you give the entire data set of your business to a data scientist, he'll know each and every aspect of your business. Okay, that's how data scientists work. They get the entire data set, they study the data set, they analyze it, and then they see where things are going wrong or what needs to be done more or what needs to be excluded. So guys, having this business acumen is just as important as having skills in algorithms or being good with math and technology. So guys, business is also as important as these other fields. Now you know who a data scientist is. Let's look at the skill sets that a data scientist needs. Okay, it always starts with statistics. Statistics will give you the numbers from the data. So a good understanding of statistics is very important for becoming a data scientist. You have to be familiar with statistical tests, distributions, maximum likelihood, estimators, and all of that. Apart from that, you should also have a good understanding of probability theory and descriptive statistics. These concepts will help you make better business decisions. So no matter what type of company or role you're interviewing for, you're going to be expected to know how to use the tools of the trade. Okay, this means that you have to know a statistical programming language like R or Python. And also you'll need to know a database querying language like SQL. Now, the main reason why people prefer R and Python is because of the number of packages that these languages have. And these predefined packages have most of the algorithms in them. So you don't have to actually sit down and code the algorithms. Instead, you can just load one of these packages from their libraries and run it. So programming languages is a must. At the minimum, you should know R or Python and a database querying language. Now let's move on to data extraction and processing. So guys, suppose that you have multiple data sources like MySQL database, Mongo database. Okay, so what you have to do is you have to extract from such sources, and then in order to analyze and query this database, you have to store it in a proper format or a proper structure. Okay, finally, then you can load the data in the data warehouse and you can analyze the data over here. Okay, so this entire process is called extraction and processing. So guys, extraction and processing is all about getting data from these different data sources and then putting it in a format so that you can analyze it. Now next is data wrangling and exploration. Now guys, data wrangling is one of the most difficult tasks in data science. This is the most time consuming task because data wrangling is all about cleaning the data. There are a lot of instances where the data sets have missing values, or they have null values, or they have inconsistent formats or inconsistent values. Now you need to understand what to do with such values. This is where data wrangling or data cleaning comes into the picture. Then after you're done with that, you are going to analyze the data. So guys, after data wrangling and cleaning is done, you're going to start exploring. This is where you try to make sense out of the data. Okay, so you can do this by looking at the different patterns in the data, the different trends, outliers, and various unexpected results and all of that. Next, we have machine learning. So guys, if you're a large company with huge amounts of data, or if you're working at a company where the product is data driven, like if you're working in Netflix or Google Maps, then you have to be familiar with machine learning methods. All right, you cannot process large amount of data with traditional methods. So that's why you need machine learning algorithms. So there are a few algorithms like KNN or K nearest neighbor. There's random forest, there's K-means algorithm, there's support vector machines. All of these algorithms, you have to be aware of all of these algorithms. And let me tell you that most of these algorithms can be implemented using R or Python libraries. Okay, you need to have an understanding of machine learning if you have large amount of data in front of you, which is going to be the case for most of the people right now because data is being generated at an unstoppable pace. Earlier in the session, we discussed how much of data is generated. So for now, knowing machine learning algorithms and machine learning concepts is a very required skill if you want to become a data scientist. So if you're sitting for an interview as a data scientist, you will be asked machine learning algorithms. You will be asked how good you are with these algorithms and how well you can implement them. Next, we have big data processing frameworks. So guys, we know that we've been generating a lot of data, and most of this data can be structured or unstructured as well. So on such data, you cannot use traditional data processing system. So that's why you need to know frameworks like Hadoop and Spark. Okay, these frameworks can be used to handle big data. Lastly, we have data visualization. So guys, data visualization is one of the most important part of data analysis. It is always very important to present the data in an understandable and visually appealing format. So data visualization is one of the skills that data scientists have to master. Okay, if you want to communicate the data with the end users in a better way, then data visualization is a must. So guys, there are a lot of tools which can be used for data visualization. Tools like Tableau and Power BI are few of the most popular visualization tools. So with this, we sum up the entire skill set that is needed to become a data scientist. Apart from this, you should also have data-driven problem-solving approach. You should also be very creative with data. So now that we know the skills that are needed to become a data scientist, let's look at the different job roles. Since data science is a very vast field, there are many job roles under data science. So let's take a look at each role. Let's start off with a data scientist. So guys, data scientists have to understand the challenges of a business and they have to offer the best solution using data analysis and data processing. So for instance, if they are expected to perform predictive analysis, they should also be able to identify trends and patterns that can help the companies in making better decisions. To become a data scientist, you have to be an expert in R, MATLAB, SQL, Python, and other complementary technologies. It can also help if you have a higher degree in mathematics or computer engineering. Next, we have data analysts. So a data analyst is responsible for a variety of tasks, including visualization, processing of massive amount of data, and munging. They have to also perform queries on databases, so they should be aware of the different querying languages. And guys, one of the most important skills of a data analyst is optimization. This is because they have to create and modify algorithms that can be used to pull information from some of the biggest databases without corrupting the data. So to become a data analyst, you must know technologies such as SQL, R, SAS, and Python. So certification in any of these technologies can boost your job application. You should also have a good problem-solving quality. Next, we have a data architect. So a data architect creates the blueprints for a data management so that the databases can be easily integrated, centralized, and protected with the best security measures. Okay, they also ensure that the data engineers have the best tools and systems to work with. So to become a data architect, you have to have expertise in data warehousing, data modeling, extraction, transformation, and loan. Okay, you should also be well versed in Hive, Pig, and Spark. Now, apart from this, there are data engineers. So guys, the main responsibility of a data engineer is to build and test scalable big data ecosystems. Okay, they are also needed to update the existing systems with newer or upgraded versions, and they are also responsible for improving the efficiency of a database. Now, if you're interested in a career as a data engineer, then technologies that require hands-on experience include Hive, NoSQL, R, Ruby, Java, C++, and MATLAB. It would also help if you can work with popular data APIs and ETL tools. Next, we have a statistician. So as the name suggests, you have to have a sound understanding of statistical theories and data organization. Not only do they extract and offer valuable insights, they also create new methodologies for engineers to apply. Now, if you want to become a statistician, then you have to have a passion for logic. There are also good variety of database systems such as SQL, data mining, and other various machine learning technologies. By that, I mean you should be good with math and you should also have a good knowledge about the various database systems such as SQL. And also the various machine learning concepts and algorithms is a must. Next, we have the database administrator. So guys, the job profile of a database administrator is pretty much self-explanatory. They are basically responsible for the proper functioning of all the databases, and they are also responsible for granting permission or revoking its services to the employees of the company. They also have to take care of the database backups and recoveries. So some of the skills that are needed to become a database administrator include database backup and recovery, data security, data modeling, and design. Next, we have the business analyst. Now, the role of a business analyst is a little bit different from all of the other data science jobs. Now, don't get me wrong, they have a very good understanding of the data-oriented technologies. They know how to handle a lot of data and process it, but they are also very focused on how this data can be linked to actionable business insights. So they mainly focus on business growth. Okay, now a business analyst acts like a link between the data engineers and the management executives. So in order to become a business analyst, you have to have an understanding of business finances, business intelligence, and also IT technologies like data modeling, data visualization tools, and etc. At last, we have a data and analytics manager. A data and analytics manager is responsible for the data science operations. Now, the main responsibility of a data and analytics manager is to oversee the data science operation. Okay, he's responsible for assigning the duties to the team according to their skills and expertise. Now, their strengths should include technologies like SAS, R, SQL, and of course, they should have good management skills. Apart from that, they must have excellent social skills, leadership qualities, and an out-of-the-box thinking attitude. And like I said earlier, you need to have a good understanding of technologies like Python, SAS, R, Java, and etc. So guys, these were the different job roles in data science. I hope you all found this informative. Now let's move ahead and look at the data lifecycle. So guys, there are basically 6 steps in the data lifecycle. It starts with a business requirement. Next is the data acquisition. After that, you'll process the data, which is called data processing. Then there is data exploration, modeling, and finally deployment. So guys, before you even start on a data science project, it is important that you understand the problem you're trying to solve. So in this stage, you're just going to focus on identifying the central objectives of the project, and you'll do this by identifying the variables that need to be predicted. Next up, we have data acquisition. Okay, so now that you have your objectives defined, it's time for you to start gathering the data. So data mining is the process of gathering your data from different sources. At this stage, some of the questions you can ask yourself is, what data do I need for my project? Where does it live? How can I obtain it? And what is the most efficient way to store and access all of it? Next up, there is data processing. Now, usually all the data that you collected is a huge mess. Okay, it's not formatted, it's not structured, it's not cleaned. So if you find any data set that is cleaned and it's packaged well for you, then you've actually won the lottery, because finding the right data takes a lot of time and it takes a lot of effort. And one of the major time consuming tasks in the data science process is data cleaning. Okay, this requires a lot of time, it requires a lot of effort, because you have to go through the entire data set to find out any missing values, or if there are any inconsistent values or corrupted data. And you also find the unnecessary data over here and you remove that data. So this was all about data processing. Next, we have data exploration. So now that you have sparkling clean set of data, you are finally ready to get started with your analysis. Okay, the data exploration stage is basically the brainstorming of data analysis. So in order to understand the patterns in your data, you can use histograms. You can just pull up a random subset of data and plot a histogram. You can even create interactive visualizations. This is the point where you dive deep into the data and you try to explore the different models that can be applied to your data. Next up, we have data modeling. So after processing the data, what you're going to do is you're going to carry out model training. Okay, now model training is basically about finding the model that answers the questions more accurately. So the process of model training involves a lot of steps. So firstly, you'll start by splitting the input data into the training data set and the testing data set. Okay, you're going to take the entire data set and you're going to separate it into 2 parts. One is the training and one is the testing data. After that, you'll build the model by using the training data set. And once you're done with that, you'll evaluate the training and the test data set. Now, to evaluate the training and testing data set, you'll be using series of machine learning algorithms. After that, you'll find out the model which is the most suitable for your business requirement.
So this was mainly data modeling. Okay, this is where you build a model out of your training data set, and then you evaluate this model by using the testing data set. Next, we have deployment. So guys, the goal of this stage is to deploy the model into a production or maybe a production like environment. So this is basically done for final user acceptance, and the users have to validate the performance of the models, and if there are any issues with the model or any issues with the algorithm, then they have to be fixed in this stage. So guys, with this we come to the end of the data life cycle. I hope this was clear.
Statistics and probability are essential because these disciples form the basic foundation of all machine learning algorithms, deep learning, artificial intelligence, and data science. In fact, mathematics and probability is behind everything around us. From shapes, patterns, and colors to the count of petals in a flower, mathematics is embedded in each and every aspect of our lives. With this in mind, I welcome you all to today's session. So I'm going to go ahead and discuss the agenda for today with you all. We're going to begin this session by understanding what is data. After that, we'll move on and look at the different categories of data like quantitative and qualitative data. Then we'll discuss what exactly statistics is, the basic terminologies in statistics, and a couple of sampling techniques. Once we're done with that, we'll discuss the different types of statistics which involve descriptive and inferential statistics. Then in the next session, we'll mainly be focusing on descriptive statistics. Here we'll understand the different measures of center, measures of spread, information gain, and entropy. We'll also understand all of these measures with the help of a use case. And finally, we'll discuss what exactly a confusion matrix is. Once we've covered the entire descriptive statistics module, we'll discuss the probability module. Here we'll understand what exactly probability is, the different terminologies in probability. We'll also study the different probability distributions. Then we'll discuss the types of probability, which include marginal probability, joint, and conditional probability. Then we'll move on and discuss a use case wherein we'll see examples that show us how the different types of probability work. And to better understand Bayes' theorem, we'll look at a small example. Also, I forgot to mention that at the end of the descriptive statistics module, we'll be running a small demo in the R language. So for those of you who don't know much about R, I'll be explaining every line in depth. But if you want to have a more in-depth understanding about R, I'll leave a couple of blogs and a couple of videos in the description box. You all can definitely check out that content. Now, after we've completed the probability module, we'll discuss the inferential statistics module. We'll start this module by understanding what is point estimation. We'll discuss what is confidence interval and how you can estimate the confidence interval. We'll also discuss margin of error, and we'll understand all of these concepts by looking at a small use case. We'll finally end the inferential statistic module by looking at what hypothesis testing is. Hypothesis testing is a very important part of inferential statistics. So we'll end the session by looking at a use case that discusses how hypothesis testing works. And to sum everything up, we'll look at a demo that explains how inferential statistics works. All right, so guys, there's a lot to cover today. So let's move ahead and take a look at our first topic, which is what is data. Now, this is a quite simple question. If I ask any of you what is data, you'll say that it's a set of numbers or some sort of documents that I've stored in my computer. Now, data is actually everything. All right, look around you. There is data everywhere. Each click on your phone generates more data than you know. Now, this generated data provides insights for analysis and helps us make better business decisions. This is why data is so important. To give you a formal definition, data refers to facts and statistics collected together for reference or analysis. All right, this is the definition of data in terms of statistics and probability. So, as we know, data can be collected, it can be measured and analyzed, it can be visualized by using statistical models and graphs. Now, data is divided into two major subcategories. All right. So, first we have qualitative data and quantitative data. These are the two different types of data. Under qualitative data, we have nominal and ordinal data. And under quantitative data, we have discrete and continuous data. Now, let's focus on qualitative data. Now, this type of data deals with characteristics and descriptors that can't be easily measured but can be observed subjectively. Now, qualitative data is further divided into nominal and ordinal data. So, nominal data is any sort of data that doesn't have any order or ranking. Okay. An example of nominal data is gender. Now, there is no ranking in gender. There's only male, female, or other, right? There is no one, two, three, four, or any sort of ordering in gender. Race is another example of nominal data. Now, ordinal data is basically an ordered series of information. Okay, let's say that you went to a restaurant. Okay, your information is stored in the form of customer ID. All right, so basically you are represented with a customer ID. Now you would have rated their service as either good or average. All right, that's how ordinal data is. And similarly, they'll have a record of other customers who visit the restaurant along with their ratings. All right. So any data which has some sort of sequence or some sort of order to it is known as ordinal data. All right. So guys, this is pretty simple to understand. Now let's move on and look at quantitative data. So quantitative data basically deals with numbers and things. Okay, you can understand that by the word quantitative itself. Quantitative is basically quantity, right? So it deals with numbers, it deals with anything that you can measure objectively. All right. So there are two types of quantitative data. There is discrete and continuous data. Now, discrete data is also known as categorical data, and it can hold a finite number of possible values. Now, the number of students in a class is a finite number. All right, you can't have infinite number of students in a class. Let's say in your fifth grade, there were 100 students in your class. All right, there weren't infinite number, but there was a definite finite number of students in your class. Okay, that's discrete data. Next, we have continuous data. Now, this type of data can hold infinite number of possible values. Okay, so when you say weight of a person is an example of continuous data, what I mean to say is my weight can be 50 kgs, or it can be 50.1 kgs, or it can be 50.001 kgs, or 50.0001, or it's 50.023, and so on, right? There are infinite number of possible values, right? So this is what I mean by continuous data. All right, this is the difference between discrete and continuous data. And also I'd like to mention a few other things over here. Now, there are a couple of types of variables as well. All right, we have a discrete variable and we have a continuous variable. Discrete variable is also known as a categorical variable. All right, it can hold values of different categories. Let's say that you have a variable called message, and there are two types of values that this variable can hold. Let's say that your message can either be a spam message or a non-spam message. Okay, that's when you call a variable as discrete or categorical variable. All right, because it can hold values that represent different categories of data. Now, continuous variables are basically variables that can store infinite number of values. So the weight of a person can be denoted as a continuous variable. All right, let's say there is a variable called weight, and it can store infinite number of possible values. That's why we'll call it a continuous variable. So guys, basically variable is anything that can store a value, right? So if you associate any sort of data with a variable, then it will become either discrete variable or continuous variable. There is also dependent and independent type of variables. Now we won't discuss all of that in depth because that's pretty understandable. I'm sure all of you know what is independent variable and dependent variable, right? Dependent variable is any variable whose value depends on any other independent variable. So guys, that much knowledge I expect all of you to have. All right. So now let's move on and look at our next topic, which is what is statistics. Now coming to the formal definition of statistics, statistics is an area of applied mathematics which is concerned with data collection, analysis, interpretation, and presentation. Now, usually when I speak about statistics, people think statistics is all about analysis. But statistics has other parts to it. It has data collection is also a part of statistics. Data interpretation, presentation, visualization, all of this comes into statistics. All right, you're going to use statistical methods to visualize data, to collect data, to interpret data. All right. So the area of mathematics deals with understanding how data can be used to solve complex problems. Okay. Now I'll give you a couple of examples that can be solved by using statistics. Okay. Let's say that your company has created a new drug that may cure cancer. How would you conduct a test to confirm the drug's effectiveness? Now, even though this sounds like a biology problem, this can be solved with statistics. All right, you will have to create a test which can confirm the effectiveness of the drug. All right, this is a common problem that can be solved using statistics. Let me give you another example. You and a friend are at a baseball game, and out of the blue, he offers you a bet that neither team will hit a home run in that game. Should you take the bet? All right, here you'll just discuss the probability of whether you'll win or lose. All right, this is another problem that comes under statistics. Let's look at another example. The latest sales data has just come in, and your boss wants you to prepare a report for management on places where the company could improve its business. What should you look for and what should you not look for? Now, this problem involves a lot of data analysis. You'll have to look at the different variables that are causing your business to go down, or that you have to look at a few variables that are increasing the performance of your models and thus growing your business. All right, so this involves a lot of data analysis, and the basic idea behind data analysis is to use statistical techniques in order to figure out the relationship between different variables or different components in your business. Okay, so now let's move on and look at our next topic, which is basic terminologies in statistics. Now, before you dive deep into statistics, it is important that you understand the basic terminologies used in statistics. The two most important terminologies in statistics are population and sample. So, throughout the statistics course or throughout any problem that you're trying to solve with statistics, you will come across these two words, which is population and sample. Now, population is a collection or a set of individuals or objects or events whose properties are to be analyzed. Okay, so basically, you can refer to population as a subject that you're trying to analyze. Now, a sample is just like the word suggests, it's a subset of the population. So, you have to make sure that you choose the sample in such a way that it represents the entire population. All right, it shouldn't focus at one part of the population. Instead, it should represent the entire population. That's how your sample should be chosen. So, a well chosen sample will contain most of the information about a particular population parameter. Now, you must be wondering, how can one choose a sample that best represents the entire population? Now, sampling is a statistical method that deals with the selection of individual observations within a population. So, sampling is performed in order to infer statistical knowledge about a population. All right, if you want to understand the different statistics of a population, like the mean, the median, the mode, or the standard deviation, or the variance of a population, then you're going to perform sampling. All right, because it's not reasonable for you to study a large population and find out the mean, median, and everything else. So why is sampling performed? You might ask, what is the point of sampling? We can just study the entire population. Now, guys, think of a scenario wherein you're asked to perform a survey about the eating habits of teenagers in the US. So, at present, there are over 42 million teens in the US, and this number is growing as we are speaking right now, correct? Is it possible to survey each of these 42 million individuals about their health? Is it possible? Well, it might be possible, but this will take forever to do. Now, obviously, it's not. It's not reasonable to go around knocking each door and asking for what does your teenage son eat and all of that. All right, this is not very reasonable. That's why sampling is used. It's a method wherein a sample of the population is studied in order to draw inference about the entire population. So it's basically a shortcut to studying the entire population. Instead of taking the entire population and finding out all the solutions, you're just going to take a part of the population that represents the entire population, and you're going to perform all your statistical analysis, your inferential statistics on that small sample. All right. And that sample basically represents the entire population. All right. So I'm sure I've made this clear to you all, what is sample and what is population. Now, there are two main types of sampling techniques that I'll discuss today. We have probability sampling and non-probability sampling. Now, in this video, we'll only be focusing on probability sampling techniques because non-probability sampling is not within the scope of this video. All right, we'll only discuss the probability part because we're focusing on statistics and probability, correct? Now again, under probability sampling, we have three different types. We have random sampling, systematic, and stratified sampling. All right. And just to mention the different types of non-probability samplings, we have snowball, quota, judgment, and convenience sampling. All right. Now guys, in this session, I'll only be focusing on probability. So let's move on and look at the different types of probability sampling. So what is probability sampling? It is a sampling technique in which samples from a large population are chosen by using the theory of probability. All right. So there are three types of probability sampling. All right. First, we have the random sampling. Now, in this method, each member of the population has an equal chance of being selected in the sample. All right, so each and every individual or each and every object in the population has an equal chance of being a part of the sample. That's what random sampling is all about. Okay, you're randomly going to select any individual or any object. So this way, each individual has an equal chance of being selected. Correct? Next, we have systematic sampling. Now, in systematic sampling, every nth record is chosen from the population to be a part of the sample. All right. Now, refer this image that I've shown over here. Out of these six groups, every second group is chosen as a sample. Okay, so every second record is chosen here. And this is how systematic sampling works. Okay, you're randomly selecting the nth record and you're going to add that to your sample. Next, we have stratified sampling. Now, in this type of technique, a stratum is used to form samples from a large population. So, what is a stratum? A stratum is basically a subset of the population that shares at least one common characteristics. So, let's say that your population has a mix of both male and female. So, you can create two stratums out of this. One will have only the male subset and the other will have the female subset. All right, this is what stratum is. It is basically a subset of the population that shares at least one common characteristics. All right. In our example, it is gender. So after you've created a stratum, you're going to use random sampling on these stratums and you're going to choose a final sample. So random sampling meaning that all of the individuals in each of the stratum will have an equal chance of being selected in the sample. Correct? So guys, these were the three different types of sampling techniques. Now let's move on and look at our next topic, which is the different types of statistics. So after this, we'll be looking at the more advanced concepts of statistics. All right, so far we discussed the basics of statistics, which is basically what is statistics, the different sampling techniques, and the terminologies in statistics. All right, now we look at the different types of statistics. So there are two major types of statistics, descriptive statistics and inferential statistics. In today's session, we'll be discussing both of these types of statistics in depth. All right, we'll also be looking at a demo which I'll be running in the R language in order to make you understand what exactly descriptive and inferential statistics is. So guys, we're just going to look at the basics, so don't worry if you don't have much knowledge. I'm explaining everything from the basic level. All right. So guys, descriptive statistics is a method which is used to describe and understand the features of specific data set by giving a short summary of the data. Okay, so it is mainly focused upon the characteristics of data. It also provides a graphical summary of the data. Now, in order to make you understand what descriptive statistics is, let's suppose that you want to gift all your classmates a t-shirt. So to study the average shirt size of a student in a classroom, so if you were to use descriptive statistics to study the average shirt size of students in your classroom, then what you would do is you would record the shirt size of all students in the class and then you would find out the maximum, minimum and average shirt size of the class. Okay. So coming to inferential statistics makes inferences and predictions about a population based on the sample of data taken from the population. Okay. So in simple words, it generalizes a large data set and it applies probability to draw a conclusion. Okay. So it allows you to infer data parameters based on a statistical model by using sample data. So if we consider the same example of finding the average shirt size of students in a class, in inferential statistics, you will take a sample set of the class, which is basically a few people from the entire class. All right. You already have had grouped the class into large, medium, and small. All right. In this method, you basically build a statistical model and expand it for the entire population in the class. So guys, that was a brief understanding of descriptive and inferential statistics. So that's the difference between descriptive and inferential. Now, in the next section, we'll go in depth about descriptive statistics. All right. So let's discuss more about descriptive statistics. So like I mentioned earlier, descriptive statistics is a method that is used to describe and understand the features of a specific data set by giving short summaries about the sample and measures of the data. There are two important measures in descriptive statistics. We have measure of central tendency, which is also known as measure of center, and we have measures of variability. This is also known as measures of spread. So measures of center include mean, median, and mode. Now, what is measures of center? Measures of the center are statistical measures that represent the summary of a data set. Okay, the three main measures of center are mean, median, and mode. Coming to measures of variability or measures of spread, we have range, interquartile range, variance, and standard deviation. All right. So now let's discuss each of these measures in a little more depth, starting with the measures of center. Now, I'm sure all of you know what the mean is. Mean is basically the measure of the average of all the values in a sample. Okay, so it's basically the average of all the values in a sample. How do you measure the mean? I hope all of you know how the mean is measured. If there are 10 numbers and you want to find the mean of these 10 numbers, all you have to do is you have to add up all the 10 numbers and you have to divide it by 10. 10 here represents the number of samples in your data set. All right, since we have 10 numbers, we're going to divide this by 10. All right, this will give us the average or the mean. So to better understand the measures of central tendency, let's look at an example. Now the data set over here is basically the cars data set, and it contains a few variables. All right, it has something known as cars. It has mileage per gallon, cylinder type, displacement, horsepower, and real axle ratio. All right, all of these measures are related to cars. Okay. So what you're going to do is you're going to use descriptive analysis and you're going to analyze each of the variables in the sample data set for the mean, standard deviation, median, mode, and so on. So let's say that you want to find out the mean or the average horsepower of the cars among the population of cars. Like I mentioned earlier, what you'll do is you'll check the average of all the values. So in this case, we'll take the sum of the horsepower of each car and we'll divide that by the total number of cars. Okay, that's exactly what I've done here in the calculation part. So this 110 basically represents the horsepower for the first car. All right, similarly, I've just added up all the values of horsepower for each of the cars and I've divided it by 8. Now 8 is basically the number of cars in our data set. All right, so 103.625 is what our mean is or the average of horsepower is. All right. Now let's understand what median is with an example. Okay, so to define median, median is basically a measure of the central value of the sample set is called the median. All right, you can say that it is a middle value. So if you want to find out the center value of the mileage per gallon among the population of cars, first what we'll do is we'll arrange the MPG values in ascending or descending order and choose a middle value. All right, in this case, since we have 8 values, right, we have 8 values, which is an even entry. So whenever you have even number of data points or samples in your data set, then you're going to take the average of the two middle values. If we had 9 values over here, we can easily figure out the middle value and choose that as a median. But since there are even number of values, we're going to take the average of the two middle values. All right. So 22.8 and 23 are my two middle values, and I'm taking the mean of those two, and hence I get 22.9. which is my median. All right. Lastly, let's look at how mode is calculated. So what is mode? Now, the value that is most recurrent in the sample set is known as mode, or basically the value that occurs most often. Okay, that is known as mode. So let's say that we want to find out the most common type of cylinder among the population of cars. All we have to do is we will check the value which is repeated the most number of times. Here we can see that the cylinders come in two types. We have cylinder of type 4 and cylinder of type 6, right? So take a look at the data set. You can see that the most recurring value is 6, right? We have 1, 2, 3, 4, and 5. We have 5, 6, and we have 1, 2, 3. Yeah, we have 3, 4 type cylinders and 5, 6 type cylinders. So basically we have 3, 4 type cylinders and we have 5, 6 type cylinders. Alright, so our mode is going to be 6, since 6 is more recurrent than 4. So guys, those were the measures of the center, or the measures of central tendency. Now let's move on and look at the measures of the spread. Alright. Now, what is the measure of spread? A measure of spread, sometimes also called as measure of dispersion, is used to describe the variability in a sample or population. Okay, you can think of it as some sort of deviation in the sample. All right, so you measure this with the help of the different measure of spreads. We have range, interquartile range, variance, and standard deviation. Now, range is pretty self-explanatory, right? It is the given measure of how spread apart the values in a data set are. The range can be calculated as shown in this formula. So you're basically going to subtract the maximum value in your data set from the minimum value in your data set. That's how you calculate the range of the data. All right. Next, we have interquartile range. So before we discuss interquartile range, let's understand what a quartile is. Alright, so quartiles basically tell us about the spread of a data set by breaking the data set into different quartiles. Okay, just like how the median breaks the data into two parts, the quartile will break it into different quartiles. So to better understand how quartile and interquartile are calculated, let's look at a small example. Now, this data set basically represents the marks of 100 students ordered from the lowest to the highest scores. Alright, so the quartiles lie in the following ranges. Now, the first quartile, which is also known as Q1, it lies between the 25th and the 26th observation. Alright, so if you look at this, I've highlighted the 25th and the 26th observation. So how you can calculate Q1 or first quartile is by taking the average of these two values. Alright, since both the values are 45, when you add them up and divide them by 2, you'll still get 45. Now, the second quartile or Q2 is between the 50th and the 51st observation. So you're going to take the average of 58 and 59 and you'll get a value of 58.5. Now, this is my second quarter. The third quartile or Q3 is between the 75th and the 76th observation. Here again, you'll take the average of the two values, which is the 75th value and the 76th value. All right, and you'll get a value of 71. All right. So guys, this is exactly how you calculate the different quartiles. Now let's look at what is interquartile range. So IQR, or the interquartile range, is a measure of variability based on dividing a dataset into quartiles. Now the interquartile range is calculated by subtracting the Q1 from Q3. So basically Q3 minus Q1 is your IQR. So your IQR is your Q3 minus Q1. Alright. Now this is how each of the quartiles are. Each quartile represents a quarter, which is 25%. Alright. So guys, I hope all of you are clear with interquartile range and what are quartiles. Now let's look at variance. Now variance is basically a measure that shows how much a random variable differs from its expected value. Okay, it's basically the variance in any variable. Now variance can be calculated by using this formula. Right here, X basically represents any data point in your data set. N is the total number of data points in your data set, and X bar is basically the mean of data points. Alright, this is how you calculate variance. Variance is basically computing the squares of deviations. Okay, that's why it says S squared there. Now let's look at what is deviation. Deviation is just the difference between each element from the mean.
Okay, so it can be calculated by using this simple formula where xi basically represents a data point and mu is the mean of the population. All right, this is exactly how you calculate deviation. Now, population variance and sample variance are very specific to whether you're calculating the variance in your population dataset or in your sample dataset. That's the only difference between population and sample variance. So the formula for population variance is pretty explanatory. So xi is basically each data point, mu is the mean of the population, n is the number of samples in your dataset. All right. Now let's look at sample variance. Now, sample variance is the average of square differences from the mean. All right. Here, xi is any data point or any sample in your data set. X bar is the mean of your sample. All right. It's not the mean of your population. It's the mean of your sample. And if you notice, n here is a smaller n. It's the number of data points in your sample. And this is basically the difference between sample and population variance. I hope that is clear. Coming to standard deviation, it is the measure of dispersion of a set of data from its mean. All right, so it's basically the deviation from your mean. That's what standard deviation is. Now, to better understand how the measures of spread are calculated, let's look at a small use case. So let's say Daenerys has 20 dragons. They have the numbers 9, 2, 5, 4, and so on, as shown on the screen. What you have to do is you have to work out the standard deviation. All right, in order to calculate the standard deviation, you need to know the mean, right? So first you're going to find out the mean of your sample set. So how do you calculate the mean? You add all the numbers in your data set divided by the total number of samples in your data set. So you get a value of 7 here. Then you calculate the RHS of your standard deviation formula. All right, so from each data point, you're going to subtract the mean and you're going to square that. All right, so when you do that, you'll get the following result. You'll basically get this 425, 4, 9, 25, and so on. So finally, you'll just find the mean of these squared differences. All right, so your standard deviation will come up to 2.983 once you take the square root. So guys, this is pretty simple. It's a simple mathematic technique. All you have to do is you have to substitute the values in the formula. All right. I hope this was clear to all of you. Now let's move on and discuss the next topic, which is information gain and entropy. Now, this is one of my favorite topics in statistics. It's very interesting. And this topic is mainly involved in machine learning algorithms like decision trees and random forest. All right. It's very important for you to know how information gain and entropy really work and why they're so essential in building machine learning models. We'll focus on the statistic parts of information gain and entropy. And after that, we'll discuss a use case and see how information gain and entropy is used in decision trees. So for those of you who don't know what a decision tree is, it is basically a machine learning algorithm. You don't have to know anything about this. I'll explain everything in depth, so don't worry. Now let's look at what exactly entropy and information gain is. Now guys, entropy is basically the measure of any sort of uncertainty that is present in the data. All right, so it can be measured by using this formula. So here S is the set of all instances in the data set or all the data items in the data set. N is the different type of classes in your data set. Pi is the event probability. Now this might seem a little confusing to you all, but when we go through the use case, you'll understand all of these terms even better. All right. Coming to information gain, as the word suggests, information gain indicates how much information a particular feature or a particular variable gives us about the final outcome. Okay, it can be measured by using this formula. So again, here h of S is the entropy of the whole data set S. Sj is the number of instances with the j value of an attribute A. S is the total number of instances in the data set. V is the set of distinct values of an attribute A. H of Sj is the entropy of subset of instances, and H of A, S is the entropy of an attribute A. Even though this seems confusing, I'll clear out the confusion. All right, let's discuss a small problem statement where we'll understand how information gain and entropy is used to study the significance of a model. So like I said, information gain and entropy are very important statistical measures that let us understand the significance of a predictive model. Okay, to get a more clear understanding, let's look at a use case. All right, now suppose we're given a problem statement.
All right, the statement is that you have to predict whether a match can be played or not by studying the weather conditions. So the predictor variables here are outlook, humidity, wind. Day is also a predictor variable. The target variable is basically play. All right, the target variable is the variable that you're trying to predict. Okay. Now the value of the target variable will decide whether or not a game can be played. All right, so that's why the play has two values. It has no and yes. No meaning that the weather conditions are not good and therefore you cannot play the game. Yes meaning that the weather conditions are good and suitable for you to play the game. All right. So that was a problem statement. I hope the problem statement is clear to all of you. Now to solve such a problem, we make use of something known as decision trees. So guys, think of an inverted tree and each branch of the tree denotes some decision. All right. Each branch is known as the branch node. And at each branch node, you're going to take a decision in such a manner that you'll get an outcome at the end of the branch. All right. Now this figure here basically shows that out of 14 observations, 9 observations result in a yes, meaning that out of 14 days, the match can be played only on 9 days. All right. So here if you see on day 1, day 2, day 8, day 9 and day 11, the outlook has been sunny. All right. So basically we're trying to cluster our data set depending on the outlook. So when the outlook is sunny, this is our data set. When the outlook is overcast, this is what we have. And when the outlook is rain, this is what we have. All right. So when it is sunny, we have 2 yeses and 3 nos. Okay. When the outlook is overcast, we have all 4 as yeses, meaning that on the 4 days when the outlook was overcast, we can play the game. All right. Now, when it comes to rain, we have 3 yeses and 2 nos. All right. So if you notice here, the decision is being made by choosing the outlook variable as the root node. Okay, so the root node is basically the topmost node in a decision tree. Now what we've done here is we've created a decision tree that starts with the outlook node. All right, then you're splitting the decision tree further depending on other parameters like sunny, overcast and rain. All right, now like we know that outlook has 3 values: sunny, overcast and rain. So let me explain this in a more in-depth manner. Okay, so what you're doing here is you're making the decision tree by choosing the outlook variable at the root node. The root node is basically the topmost node in a decision tree. Now the outlook node has 3 branches coming out from it, which is sunny, overcast and rain. So basically outlook can have 3 values. Either it can be sunny, it can be overcast or it can be rainy. Okay, now these 3 values are assigned to the immediate branch nodes, and for each of these values, the possibility of play is equal to yes is calculated. So the sunny and the rain branches will give you an impure output, meaning that there is a mix of yes and no, right? There are 2 yeses here, 3 no's here. There are 3 yeses here and 2 no's over here. But when it comes to the overcast variable, it results in 100% pure subset. All right. This shows that the overcast variable will result in a definite and certain output. This is exactly what entropy is used to measure. All right. It calculates the impurity or the uncertainty. All right. So the lesser the uncertainty or the entropy of a variable, more significant is that variable. So when it comes to overcast, there's literally no impurity in the data set. It is 100% pure subset, right? So we want variables like these in order to build a model. All right. Now we don't always get lucky and we don't always find variables that will result in pure subsets. That's why we have the measure entropy. So the lesser the entropy of a particular variable, the more significant that variable will be. So in a decision tree, the root node is assigned the best attribute so that the decision tree can predict the most precise outcome. Meaning that on the root node, you should have the most significant variable. All right, that's why we've chosen outlook. All right, now some of you might ask me, why haven't you chosen overcast? Now guys, the overcast is not a variable. It is a value of the outlook variable. All right, that's why we've chosen outlook here, because it has 100% pure subset, which is overcast. All right, now the question in your head is, how do I decide which variable or attribute best splits the data? Now right now I know I looked at the data and I told you that here we have 100% pure subset. But what if it's a more complex problem and you're not able to understand which variable will best split the data? So guys, when it comes to decision trees, information gain and entropy will help you understand which variable will best split the data set. All right, or which variable you have to assign to the root node. Because whichever variable is assigned to the root node, it will best split the data set, and it has to be the most significant variable. All right, so how we can do this is we need to use information gain and entropy. So from the total of the 14 instances that we saw, 9 of them said yes, and 5 of the instances said no, that you cannot play on that particular day. All right, so how do you calculate the entropy? So this is the formula. You just substitute the values in the formula. So when you substitute the values in the formula, you'll get a value of 0.940. All right, this is the entropy, or this is the uncertainty of the data present in our sample. Now, in order to ensure that we choose the best variable for the root node, let us look at all the possible combinations that you can use on the root node. Okay, so these are all the possible combinations. You can either have outlook, you can have windy, humidity, or temperature. Okay, these are our 4 variables, and you can have any one of these variables as your root node. But how do you select which variable best fits the root node? That's what we are going to see by using information gain and entropy. So guys, now the task at hand is to find the information gain for each of these attributes. All right, so for outlook, for windy, for humidity, and for temperature, we're going to find out the information gain. All right. Now, a point to remember is that the variable that results in the highest information gain must be chosen because it will give us the most precise and output information. All right. So the information gain for attribute windy, we'll calculate that first. Here we have 6 instances of true and 8 instances of false. Okay, so when you substitute all the values in the formula, you'll get a value of 0.048. So we get a value of 0.048. Now this is a very low value for information gain. All right, so the information that you're going to get from windy attribute is pretty low. So let's calculate the information gain of attribute outlook. All right, so from the total of 14 instances, we have 5 instances which say sunny, 4 instances which are overcast, and 5 instances which are rainy. All right, for sunny, we have 3 yeses and 2 nos. For overcast, we have all the 4 as yes. For rainy, we have 3 yes and 2 nos. Okay, so when you calculate the information gain of the outlook variable, you'll get a value of 0.247. Now compare this to the information gain of the windy attribute. This value is actually pretty good, right? We have 0.247, which is a pretty good value for information gain. Now let's look at the information gain of attribute humidity. Now over here we have 7 instances which say high and 7 instances which say normal, right? And under the high branch node, we have 3 instances which say yes and the rest 4 instances which say no. Similarly, under the normal branch, we have 1, 2, 3, 4, 5, 6, 7 instances which say yes and 1 instance which says no. All right. So when you calculate the information gain for the humidity variable, you're going to get a value of 0.151. Now this is also a pretty decent value, but when you compare it to the information gain of the attribute outlook, it is less, right? Now let's look at the information gain of attribute temperature. All right, so the temperature can hold, repeat. So basically, the temperature attribute can hold hot, mild, and cool. Okay, under hot, we have 2 instances which says yes and 2 instances for no. Under mild, we have 4 instances of yes and 2 instances of no. And under cool, we have 3 instances of yes and 1 instance of no. All right. Now, when you calculate the information gain for this attribute, you'll get a value of 0.029, which is again very less. So what you can summarize from here is, if we look at the information gain for each of these variables, we'll see that for outlook, we have the maximum gain. All right, we have 0.247, which is the highest information gain value. And you must always choose a variable with the highest information gain to split the data at the root node. So that's why we assign the outlook variable at the root node. All right. So guys, I hope this use case was clear. If any of you have doubts, please keep commenting those doubts. Now let's move on and look at what exactly a confusion matrix is. Now the confusion matrix is the last topic for descriptive statistics. Alright, after this, I'll be running a short demo where I'll be showing you how you can calculate mean, median, mode, and standard deviation, variance, and all of those values by using R. Okay, so let's talk about confusion matrix. Now, guys, what is a confusion matrix? Now, don't get confused. This is not any complex topic. Now, a confusion matrix is a matrix that is often used to describe the performance of a model. All right, and this is specifically used for classification models or a classifier. And what it does is it will calculate the accuracy or it will calculate the performance of your classifier by comparing your actual results and your predicted results. All right, so this is what it looks like: true positive plus true negative and all of that. Now this is a little confusing. I'll get back to what exactly true positive, true negative, and all of this stands for. For now, let's look at an example and let's try and understand what exactly confusion matrix is. So guys, I made sure that I put examples after each and every topic because it's important you understand the practical part of statistics. All right, statistics has literally nothing to do with theory. You need to understand how calculations are done in statistics. Okay, so here what I've done is now let's look at a small use case. Okay, let's consider that you're given data about 165 patients, out of which 105 patients have a disease and the remaining 50 patients don't have a disease. Okay, so what you're going to do is you'll build a classifier that predicts by using these 165 observations. You'll feed all of these 165 observations to your classifier and it will predict the output every time a new patient's detail is fed to the classifier, right? Now, out of these 165 cases, let's say that the classifier predicted yes 110 times and no 55 times. All right. So yes basically stands for yes, the person has a disease, and no stands for no, the person does not have a disease. All right. That's pretty self-explanatory. But yeah, so it predicted that 110 times the patient has a disease and 55 times that no, the patient doesn't have a disease. However, in reality, only 105 patients in the sample have the disease and 60 patients do not have the disease, right? So how do you calculate the accuracy of your model? You basically build the confusion matrix. All right, this is how the matrix looks like. N basically denotes the total number of observations that you have, which is 165 in our case. Actual denotes the actual values in the data set, and predicted denotes the predicted values by the classifier. So the actual value is no here and the predicted value is no here. So your classifier was correctly able to classify 50 cases as no. All right. Since both of these are no, so 50 it was correctly able to classify. But 10 of these cases it incorrectly classified. Meaning that your actual value here is no, but your classifier predicted it as yes. All right. That's why there's 10 over here. Similarly, it wrongly predicted that 5 patients do not have diseases, whereas they actually did have diseases, and it correctly predicted 100 patients which have the disease. All right, I know this is a little bit confusing, but if you look at these values, no, no, 50, meaning that it correctly predicted 50 values. No, yes means that it wrongly predicted yes for the values that it was supposed to predict no. All right. Now, what exactly is this true positive, true negative, and all of that? I'll tell you what exactly it is. So, true positive are the cases in which we predicted a yes and they do not actually have the disease. All right. So, it is basically this value. All right. We predicted a yes here, even though they did not have the disease. So, we have 10 true positives, right? Similarly, true negative is we predicted no and they don't have the disease, meaning that this is correct. False positive is we predicted yes, but they do not actually have the disease. All right, this is also known as type 1 error. False negative is we predicted no, but they actually do not have the disease. So guys, basically false negative and true negatives are basically correct classifications. All right. So this was confusion matrix and I hope this concept is clear. Again, guys, if you have doubts, please comment your doubts in the comment section. So guys, that was descriptive statistics. Now, before we go to probability, I promised you all that we'll run a small demo in R. All right, we'll try and understand how mean, median, mode works in R. Okay, so let's do that first. So guys, again, what we just discussed so far was descriptive statistics. All right.
Next, we're going to discuss probability, and then we'll move on to inferential statistics. Okay, inferential statistics is basically the second type of statistics. Okay, now to make things more clearer for you, let me just zoom in. So guys, it's always best to perform practical implementations in order to understand the concepts in a better way. Okay, so here we'll be executing a small demo that will show you how to calculate the mean, median, mode, variance, standard deviation, and how to study the variables by plotting a histogram. Okay, don't worry if you don't know what a histogram is. It's basically a frequency plot. There's no big science behind it. All right. This is a very simple demo, but it also forms the foundation that every machine learning algorithm is built upon. Okay, you can say that most of the machine learning algorithms, actually all the machine learning algorithms and deep learning algorithms have this basic concept behind them. Okay, you need to know how mean, median, mode, and all of that is calculated. So guys, I'm using the R language to perform this, and I'm running this on R Studio. For those of you who don't know R language, I will leave a couple of links in the description box. You can go through those videos. So what we're doing is we're randomly generating numbers and we're storing it in a variable called data. Right? So if you want to see the generated numbers, just run the line data. All right? This variable basically stores all our numbers. All right? Now what we're going to do is we're going to calculate the mean. Now all you have to do in R is specify the word mean along with the data that you're calculating the mean of. And I've assigned this whole thing into a variable called mean, which will hold the mean value of this data. So now let's look at the mean. For that, I've used a function called print and mean. All right, so our mean is around 5.99. Okay, next is calculating the median. It's very simple, guys. All you have to do is use the function median, all right, and pass the data as a parameter to this function. That's all you have to do. So R provides functions for each and everything. All right, statistics is very easy when it comes to R because R is basically a statistical language. Okay, so all you have to do is just name the function, and that function is already inbuilt in your R. Okay, so your median is around 6.4. Similarly, we'll calculate the mode. All right, let's run this function. I basically created a small function for calculating the mode. So guys, this is our mode, meaning that this is the most recurrent value, right? Now we're going to calculate the variance and the standard deviation. For that, again, we have a function in R called as var. All right, all you have to do is pass the data to that function. Okay, similarly, we'll calculate the standard deviation, which is basically the square root of your variance, right? Now we'll print the standard deviation, right? This is our standard deviation value. Now finally, we'll just plot a small histogram. Histogram is nothing but it's a frequency plot, all right? It'll show you how frequently a data point is occurring. So this is the histogram that we've just created. It's quite simple in R because R has a lot of packages and a lot of inbuilt functions that support statistics. All right, it is a statistical language that is mainly used by data scientists or by data analysts and machine learning engineers because they don't have to sit and code these functions. All they have to do is they have to mention the name of the function and pass the corresponding parameters. So guys, that was the entire descriptive statistics module. And now we'll discuss about probability. Okay, so before we understand what exactly probability is, let me clear out a very common misconception. People often tend to ask me this question: what is the relationship between statistics and probability? So probability and statistics are related fields, all right? So probability is a mathematical method used for statistical analysis. Therefore, we can say that probability and statistics are interconnected branches of mathematics that deal with analyzing the relative frequency of events. So they're very interconnected fields, and probability makes use of statistics and statistics makes use of probability. All right, they're very interconnected fields. So that is the relationship between statistics and probability. Now let's understand what exactly is probability. So probability is the measure of how likely an event will occur. To be more precise, it is the ratio of desired outcome to the total outcomes. Now the probability of all outcomes always sum up to 1. The probability will always sum up to 1. Probability cannot go beyond 1. Okay, so either your probability can be 0 or it can be 1, or it can be in the form of decimals like 0.52 or 0.55, or it can be in the form of 0.5, 0.7, 0.9, but its value will always stay between the range 0 and 1. Okay, now the famous example of probability is rolling a dice example. So when you roll a dice, you get 6 possible outcomes, right? You get 1, 2, 3, 4, and 5, 6 phases of a dice. Now each possibility only has one outcome. So what is the probability that on rolling a dice you'll get 3? The probability is 1 by 6, right? Because there's only one phase which has the number 3 on it. Out of 6 phases, there's only one phase which has the number 3. So the probability of getting 3 when you roll a dice is 1 by 6. Similarly, if you want to find the probability of getting a number 5, again the probability is going to be 1 by 6. All right. So all of this will sum up to 1. All right. So guys, this is exactly what probability is. It's a very simple concept. We all learned it in 8th standard onwards, right? Now let's understand the different terminologies that are related to probability. Now there are three terminologies that you often come across when we talk about probability. We have something known as random experiment. Okay, it's basically an experiment or a process for which the outcomes cannot be predicted with certainty. All right, that's why you use probability. You're going to use probability in order to predict the outcome with some sort of certainty. Sample space is the entire possible set of outcomes of a random experiment. An event is one or more outcomes of an experiment. So, if you consider the example of rolling a dice, now let's say that you want to find out the probability of getting a 2 when you roll a dice. Okay, so finding this probability is the random experiment. The sample space is basically your entire possibility. Okay, so 1, 2, 3, 4, 5, 6 phases are there, and out of that you need to find the probability of getting a 2, right? So all the possible outcomes will basically represent your sample space. Okay, so 1 to 6 are all your possible outcomes. This represents your sample space. Now event is one or more outcome of an experiment. So in this case my event is to get a 2 when I roll a dice, right? So my event is the probability of getting a 2 when I roll a dice. So guys, this is basically what random experiment, sample space, and event really means. All right. Now let's discuss the different types of events. There are two types of events that you should know about. There is disjoint and non-disjoint events. Disjoint events are events that do not have any common outcome. For example, if you draw a single card from a deck of cards, it cannot be a king and a queen, correct? It can either be king or it can be queen. Now, non-disjoint events are events that have common outcomes. For example, a student can get 100 marks in statistics and 100 marks in probability. All right. And also the outcome of a ball delivered can be a no ball and it can be a 6. Right. So this is what non-disjoint events are. All right. These are very simple to understand. Right. Now let's move on and look at the different types of probability distribution. All right. I'll be discussing the three main probability distribution functions. I'll be talking about probability density function, normal distribution, and central limit theorem. Okay. Probability density function, also known as PDF, is concerned with the relative likelihood for a continuous random variable to take on a given value. Alright, so the PDF gives the probability of a variable that lies between the range A and B. So basically what you're trying to do is you're going to try and find the probability of a continuous random variable over a specified range. Okay, now this graph denotes the PDF of a continuous variable. Now this graph is also known as the bell curve. Alright, it's famously called the bell curve because of its shape. And there are three important properties that you need to know about a probability density function. Now the graph of a PDF will be continuous over a range. This is because you're finding the probability that a continuous variable lies between the ranges A and B, right? The second property is that the area bounded by the curve of a density function and the x-axis is equal to 1. Basically, the area below the curve is equal to 1, all right, because it denotes probability. Again, the probability cannot range more than 1. It has to be between 0 and 1. Property number 3
is that the probability that a random variable assumes a value between A and B is equal to the area under the PDF bounded by A and B. Okay, now what this means is that the probability value is denoted by the area of the graph. Alright, so whatever value that you get here, which is basically 1, is the probability that a random variable will lie between the range A and B. Alright, so I hope all of you have understood the probability density function. It's basically the probability of finding the value of a continuous random variable between the range A and B. Alright, now let's look at our next distribution, which is normal distribution. Now, normal distribution, which is also known as the Gaussian distribution, is a probability distribution that denotes the symmetric property of the mean, right? Meaning that the idea behind this function is that the data near the mean occurs more frequently than the data away from the mean. So what it means to say is that the data around the mean represents the entire data set. Okay, so if you just take a sample of data around the mean, it can represent the entire data set. Now, similar to the probability density function, the normal distribution appears as a bell curve. All right. Now, when it comes to normal distribution, there are two important factors. All right. We have the mean of the population and the standard deviation. Okay, so the mean in the graph determines the location of the center of the graph, right? And the standard deviation determines the height of the graph. Okay, so if the standard deviation is large, the curve is going to look something like this. All right, it'll be short and wide. And if the standard deviation is small, the curve is tall and narrow. All right, so this was it about normal distribution. Now let's look at the central limit theory. Now the central limit theory states that the sampling distribution of the mean of any independent random variable will be normal or nearly normal if the sample size is large enough. Now that's a little confusing. Okay, let me break it down for you. Now in simple terms, if we had a large population and we divided it into many samples, then the mean of all the samples from the population will be almost equal to the mean of the entire population. All right, meaning that each of the sample is normally distributed, right? So if you compare the mean of each of the sample, it will almost be equal to the mean of the population, right? So this graph basically shows a more clear understanding of the central limit theorem, right? You can see each sample here and the mean of each sample is almost along the same line, right? Okay, so this is exactly what the central limit theorem states. Now, the accuracy or the resemblance to the normal distribution depends on two main factors, right? So the first is the number of sample points that you consider, all right? And the second is the shape of the underlying population. Now, the shape obviously depends on the standard deviation and the mean of a sample, correct? So guys, central limit theorem basically states that each sample will be normally distributed in such a way that the mean of each sample will coincide with the mean of the actual population. All right, in short terms, that's what central limit theorem states. All right, and this holds true only for a large data set. Mostly for a small data set, there are more deviations when compared to a large data set. It's because of the scaling factor, right? The smallest deviation in a small data set will change the value very drastically. But in a large data set, a small deviation will not matter at all. Now let's move on and look at our next topic, which is the different types of probability. Now this is an important topic because most of your problems can be solved by understanding which type of probability should I use to solve this problem, right? So we have three important types of probability. We have marginal, joint, and conditional probability. So let's discuss each of these. Now, the probability of an event occurring unconditioned on any other event is known as marginal probability or unconditional probability. So let's say that you want to find the probability that a card drawn is a heart. All right. So if you want to find the probability that a card drawn is a heart, the probability will be 13 by 52. Since there are 52 cards in a deck and there are 13 hearts in a deck of cards, right? And there are 52 cards in a total deck. So your marginal probability will be 13 by 52. That's about marginal probability. Now let's understand what is joint probability. Now joint probability is a measure of two events happening at the same time. Okay, let's say that the two events are A and B. So the probability of event A and B occurring is the intersection of A and B. So for example, if you want to find the probability that a card is a 4 and a red, that would be joint probability. All right, because you're finding a card that is 4 and the card has to be red in color. So for the answer, this will be 2 by 52 because we have 1 2 in hearts and we have 1 2 in diamonds, correct? So both of these are red in color, therefore our probability is 2 by 52. And if you further down it, it is 1 by 26. Right? So this is what joint probability is all about. Moving on, let's look at what exactly conditional probability is. So if the probability of an event or an outcome is based on the occurrence of a previous event or an outcome, then you call it as a conditional probability. Okay. So the conditional probability of an event B is the probability that the event will occur given that an event A has already occurred, right? So if A and B are dependent events, then the expression for conditional probability is given by this. Now, this first term on the left hand side, which is P B of A, is basically the probability of event B occurring given that event A has already occurred. All right. So like I said, if A and B are dependent events, then this is the expression. But if A and B are independent events, then the expression for conditional probability is like this, right? So guys, P of A and P of B is obviously the probability of A and probability of B, right? Now let's move on. Now, in order to understand conditional probability, joint probability, and marginal probability, let's look at a small use case. Okay. Now, basically, we're going to take a data set which examines the salary package and training undergone by candidates. Okay. Now, in this, there are 60 candidates without training and 45 candidates which have enrolled for Edureka's training. Right now, the task here is you have to assess the training with the salary package. Okay, let's look at this in a little more depth. So in total, we have 105 candidates, out of which 60 of them have not enrolled for Edureka's training and 45 of them have enrolled for Edureka's training. All right, this is a small survey that was conducted, and this is the rating of the package or the salary that they got. Right, so if you read through the data, you can understand. There were 5 candidates without Edureka training who got a very poor salary package. Okay, similarly, there are 30 candidates with Edureka training who got a good package, right? So guys, basically you're comparing the salary package of a person depending on whether or not they've enrolled for Edureka training, right? This is our data set. Now let's look at our problem statement. Find the probability that a candidate has undergone Edureka's training. Quite simple. Which type of probability is this? This is marginal probability, right? So the probability that a candidate has undergone Edureka's training is obviously 45 divided by 105. Since 45 is the number of candidates with Edureka training and 105 is the total number of candidates. So you get a value of approximately 0.42. All right, that's the probability of a candidate that has undergone Edureka's training. Next question. Find the probability that a candidate has attended Edureka's training and also has good package. Now, this is obviously a joint probability problem, right? So how do you calculate this? Now, since our table is quite formatted, we can directly find that people who have gotten a good package along with Edureka training are 30, right? So out of 105 people, 30 people have Edureka training and a good package, right? They're specifically asking for people with Edureka training. Remember that, right? The question is find the probability that a candidate has attended Edureka's training and also has a good package. All right, so you need to consider 2 factors, that is a candidate who's attended Edureka's training and who has a good package. So clearly that number is 30. 30 divided by total number of candidates, which is 105, right? So here you get the answer clearly. Next, we have find the probability that a candidate has a good package given that he has not undergone training. Okay, now this is clearly conditional probability because here you're defining a condition. You're saying that you want to find the probability of a candidate who has a good package given that he's not undergone any training, right? The condition is that he's not undergone any training. All right. So the number of people who have not undergone training are 60, and out of that, 5 of them have got a good package, right? So that's why this is 5 by 60 and not 5 by 105. because here they've clearly mentioned has a good package given that he has not undergone training. So you have to only consider people who have not undergone training, right? So only 5 people who have not undergone training have gotten a good package, right? So 5 divided by 60, you get a probability of around 0.08, which is pretty low, right? Okay, so this was all about the different types of probability. Now let's move on and look at our last topic in probability, which is Bayes' theorem. Now guys, Bayes' theorem is a very important concept when it comes to statistics and probability. It is majorly used in naive Bayes algorithm. Those of you who aren't aware, naive Bayes is a supervised learning classification algorithm, and it is mainly used in Gmail spam filtering, right? A lot of you might have noticed that if you open up Gmail, you'll see that you have a folder called spam, right? All of that is carried out through machine learning, and the algorithm used there is naive Bayes, right? So now let's discuss what exactly the Bayes theorem is and what it denotes. The Bayes theorem is used to show the relation between one conditional probability and its inverse. All right. Basically, it's nothing but the probability of an event occurring based on prior knowledge of conditions that might be related to the same event. Okay, so mathematically, the Bayes theorem is represented like this, right? Like shown in this equation. The left-hand term is referred to as the likelihood ratio, which measures the probability of occurrence of event B given an event A. Okay. On the left-hand side is what is known as the posterior. Right? It is referred to as posterior, which means that the probability of occurrence of A given an event B. Right? The second term is referred to as the likelihood ratio. Alright, this measures the probability of occurrence of B given an event A. Now, P of A is also known as the prior, which refers to the actual probability distribution of A, and P of B is again the probability of B, right? This is the Bayes theorem. Now, in order to better understand the Bayes theorem, let's look at a small example. Let's say that we have 3 bowls. We have bowl A, bowl B, and bowl C. Okay, bowl A contains 2 blue balls and 4 red balls. Bowl B contains 8 blue balls and 4 red balls. Bowl C contains 1 blue ball and 3 red balls. Now, if we draw 1 ball from each bowl, what is the probability to draw a blue ball from a bowl A if we know that we drew exactly a total of 2 blue balls? Right? If you didn't understand the question, please reread it. I shall pause for a second or two. Right? So I hope all of you have understood the question. Okay, now what I'm going to do is I'm going to draw a blueprint for you and tell you how exactly to solve the problem. But I want you all to give me the solution to this problem, right? I'll draw a blueprint. I'll tell you what exactly the steps are, but I want you to come up with a solution on your own, right? The formula is also given to you. Everything is given to you. All you have to do is come up with a final answer, right? Let's look at how you can solve this problem. So first of all, what we'll do is let's consider A. All right, let A be the event of picking a blue ball from bag A, and let X be the event of picking exactly 2 blue balls, right? Because these are the 2 events that we need to calculate the probability of. Now there are 2 probabilities that you need to consider here. One is the event of picking a blue ball from bag A, and the other is the event of picking exactly 2 blue balls. Okay, so these two are represented by A and X respectively. So what we want is the probability of occurrence of event A given X, which means that given that we're picking exactly 2 blue balls, what is the probability that we are picking a blue ball from bag A? So by the definition of conditional probability, this is exactly what our equation will look like, correct? This is basically occurrence of event A given an event X, and this is the probability of A and X, and this is the probability of X alone, correct? Now what we need to do is we need to find these 2 probabilities, which is probability of A and X occurring together and probability of X. Okay, this is the entire solution. So how do you find P, probability of X? This you can do in 3 ways. So first is white ball from A, either white from B or red from C. Now first is to find the probability of X. X basically represents the event of picking exactly 2 blue balls, right? So these are the 3 ways in which it is possible. So you'll pick one blue ball from bowl A and one from bowl B. In the second case, you can pick one from A and another blue ball from C. In the third case, you can pick a blue ball from bag B and a blue ball from bag C. Right? These are the three ways in which it is possible. So you need to find the probability of each of this. Step 2 is that you need to find the probability of A and X occurring together. This is the sum of terms 1 and 2. Okay, this is because in both of these events, you're picking a ball from bag A. Correct? So guys, find out this probability and let me know your answer in the comment section. All right, we'll see if you get the answer right. I gave you the entire solution to this. All you have to do is substitute the value, right? If you want a second or two, I'm going to pause on the screen so that you can go through this in a more clearer way, right? Remember that you need to calculate two probabilities. The first probability that you need to calculate is the event of picking a blue ball from bag A, given that you're picking exactly two blue balls. Okay. The second probability you need to calculate is the event of picking exactly two blue balls. All right. These are the two probabilities you need to calculate. So remember that. And this is the solution. All right, so guys, make sure you mention your answers in the comment section. For now, let's move on and look at our next topic, which is the inferential statistics. So guys, we just completed the probability module, right? Now we'll discuss inferential statistics, which is the second type of statistics. We discussed descriptive statistics earlier, all right? So like I mentioned earlier, inferential statistics, also known as statistical inference, is a branch of statistics that deals with forming inferences and predictions about a population based on a sample of data taken from the population. All right. Now, the question you should ask is, how does one form inferences or predictions on a sample? The answer is you use point estimation. Okay. Now, you must be wondering, what is point estimation? Point estimation is concerned with the use of the sample data to measure a single value which serves as an approximate value or the best estimate of an unknown population parameter. That's a little confusing. Let me break it down to you. For example, in order to calculate the mean of a huge population, what we do is we first draw out the sample of the population and then we find the sample mean, right? The sample mean is then used to estimate the population mean. This is basically point estimate. You're estimating the value of one of the parameters of the population, right? Basically, the mean, you're trying to estimate the value of the mean. This is what point estimation is. There are two main terms in point estimation. There's something known as the estimator and there's something known as the estimate. Estimator is a function of the sample that is used to find out the estimate. All right. In this example, it's basically the sample mean, right? So a function that calculates the sample mean is known as the estimator, and the realized value of the estimator is the estimate, right? So I hope point estimation is clear. Now, how do you find the estimates? There are four common ways in which you can do this. The first one is method of moments. Here what you do is you form an equation in the sample data set and then you analyze a similar equation in the population data set as well, like the population mean, population variance, and so on. So in simple terms, what you're doing is you're taking down some known facts about the population and you're extending those ideas to the sample. All right. Once you do that, you can analyze the sample and estimate more essential or more complex values. Right. Next, we have maximum of likelihood. Now, this method basically uses a model to estimate a value. All right. Now, a maximum of likelihood is majorly based on probability. So there's a lot of probability involved in this method. Next, we have the Bayes estimator. This works by minimizing the errors or the average risk. Okay. The Bayes estimator has a lot to do with the Bayes theorem. All right. Let's not get into the depth of these estimation methods. Finally, we have the best unbiased estimators. In this method, there are several unbiased estimators that can be used to approximate a parameter. Okay. So guys, these were a couple of methods that are used to find the estimate. But the most well-known method to find the estimate is known as the interval estimation. Okay, this is one of the most important estimation methods. All right, this is where confidence interval also comes into the picture, right? Apart from interval estimation, we also have something known as margin of error. So I'll be discussing all of this in the upcoming slides.
So first let's understand what is interval estimate. Okay. An interval or range of values which are used to estimate a population parameter is known as an interval estimation. Right? That's very understandable. Basically, what they're trying to say is you're going to estimate the value of a parameter. Let's say you're trying to find the mean of a population. What you're going to do is you're going to build a range and your value will lie in that range or in that interval. All right, so this way your output is going to be more accurate because you've not predicted a point estimation. Instead, you have estimated an interval within which your value might occur, right? Okay, now this image clearly shows how point estimate and interval estimate are different. So guys, interval estimate is obviously more accurate because you're not just focusing on a particular value or a particular point in order to predict the probability. Instead, you're saying that the value might be within this range between the lower confidence limit and the upper confidence limit. All right, this just denotes the range or the interval. Okay, if you're still confused about interval estimation, let me give you a small example. If I stated that I will take 30 minutes to reach the theater, this is known as point estimation. Okay, but if I stated that I will take between 45 minutes to an hour to reach the theater, this is an example of interval estimation. All right, I hope it's clear now. Now, interval estimation gives rise to two important statistical terminologies. One is known as confidence interval and the other is known as margin of error. All right. So guys, it's important that you pay attention to both of these terminologies. Confidence interval is one of the most significant measures that are used to check how essential a machine learning model is. All right. So what is confidence interval? Confidence interval is the measure of your confidence that the interval estimated contains the population parameter or the population mean or any of those parameters, right? Now, statisticians use a confidence interval to describe the amount of uncertainty associated with the sample estimate of a population parameter. Now, guys, this is a lot of definition. Let me just make you understand confidence interval with a small example. Okay, let's say that you perform a survey and you survey a group of cat owners to see how many cans of cat food they purchase in 1 year. Okay, you test your statistics at the 99% confidence level and you get a confidence interval of 100, 200. This means that you think that the cat owners buy between 100 to 200 cans in a year. And also, since the confidence level is 99%, it shows that you're very confident that the results are correct. Okay, I hope all of you are clear with that. Right, so your confidence interval here will be 100 and 200, and your confidence level will be 99%. Right, that's the difference between confidence interval and confidence level. So within your confidence interval, your value is going to lie, and your confidence level will show how confident you are about your estimation. Right, I hope that was clear. Let's look at margin of error. Now, margin of error for a given level of confidence is the greatest possible distance between the point estimate and the value of the parameter that it is estimating. You can say that it is a deviation from the actual point estimate. Right? Now, the margin of error can be calculated using this formula. Now, ZC here denotes the critical value or the confidence interval, and this is multiplied by standard deviation divided by root of the sample size. All right, n is basically the sample size. Now let's understand how you can estimate the confidence intervals. So guys, the level of confidence, which is denoted by C, is the probability that the interval estimate contains a population parameter. Let's say that you're trying to estimate the mean. All right, so the level of confidence is the probability that the interval estimate contains the population parameter. So this interval between minus ZC and ZC, or the area beneath this curve, is nothing but the probability that the interval estimate contains a population parameter. All right, it should basically contain the value that you are predicting. Right, now these are known as critical values. This is basically your lower limit and your higher limit confidence level. Also, there's something known as the z-score. Now this score can be calculated by using the standard normal table. All right, if you look it up anywhere on Google, you'll find the z-score table or the standard normal table. Okay, to understand how this is done, let's look at a small example. Okay, let's say that the level of confidence is 90%. This means that you are 90% confident that the interval contains the population mean. Okay. So the remaining 10%, which is out of 100%, the remaining 10% is equally distributed on these tail regions. Okay, so you have 0.05 here and 0.05 over here, right? So on either side of C, you'll distribute the other leftover percentage. Now these z-scores are calculated from the table as I mentioned before. All right, 1.645 is calculated from the standard normal table. Okay, so guys, this is how you estimate the level of confidence. So to sum it up, let me tell you the steps that are involved in constructing a confidence interval. First, you'll start by identifying a sample statistic. Okay, this is the statistic that you will use to estimate a population parameter. This can be anything like the mean of the sample. Next, you will select a confidence level. Now, the confidence level describes the uncertainty of a sampling method, right? After that, you'll find something known as the margin of error, right? We discussed margin of error earlier. So you find this based on the equation that I explained in the previous slide. Then you'll finally specify the confidence interval. All right. Now let's look at a problem statement to better understand this concept. A random sample of 32 textbook prices is taken from a local college bookstore. The mean of the sample is so and so, and the sample standard deviation is this. Use a 95% confident level and find the margin of error for the mean price of all textbooks in the bookstore. Okay. Now, this is a very straightforward question. If you want, you can read the question again. All you have to do is you have to just substitute the values into the equation. All right. So, guys, we know the formula for margin of error. You take the z-score from the table. After that, we have deviation, which is 23.44, right? And that's standard deviation. And n stands for the number of samples. Here, the number of samples is 32, basically 32 textbooks. So approximately your margin of error is going to be around 8.12. This is a pretty simple question. All right, I hope all of you understood this. Now that you know the idea behind confidence interval, let's move ahead to one of the most important topics in statistical inference, which is hypothesis testing, right? So basically, statisticians use hypothesis testing to formally check whether the hypothesis is accepted or rejected. Okay. Hypothesis testing is an inferential statistical technique used to determine whether there is enough evidence in a data sample to infer that a certain condition holds true for an entire population. So, to understand the characteristics of a general population, we take a random sample and we analyze the properties of the sample, right? We test whether or not the identified conclusion represents the population accurately, and finally, we interpret their results. Now, whether or not to accept the hypothesis depends upon the percentage value that we get from the hypothesis. Okay, so to better understand this, let's look at a small example. Before that, there are a few steps that are followed in hypothesis testing. You begin by stating the null and the alternative hypothesis. All right, I'll tell you what exactly these terms are. And then you formulate an analysis plan. All right, after that, you analyze the sample data. And finally, you can interpret the results. Right. Now, to understand the entire hypothesis testing, we'll look at a good example. Okay. Now, consider four boys: Nick, John, Bob, and Harry. These boys were caught bunking a class and they were asked to stay back at school and clean their classroom as a punishment. Right? So, what John did is he decided that four of them would take turns to clean their classrooms. He came up with a plan of writing each of their names on chits and putting them in a bowl. Now, every day they had to pick up a name from the bowl and that person had to clean the class. Right? That sounds pretty fair enough. Now, it has been 3 days and everybody's name has come up except John's. Assuming that this event is completely random and free of bias, what is the probability of John not cheating? Right? What is the probability that he's not actually cheating? This can be solved by using hypothesis testing. Okay. So we'll begin by calculating the probability of John not being picked for a day. Right? So we're going to assume that the event is free of bias. So we need to find out the probability of John not cheating, right? First, we'll find the probability that John is not picked for a day, right? We get 3 out of 4, which is basically 75%. Now, 75% is fairly high. So if John is not picked for 3 days in a row, the probability will drop down to approximately 42%. Okay, so 3 days in a row, meaning that is the probability drops down to 42%. Now let's consider a situation where John is not picked for 12 days in a row. The probability drops down to 3.2%. Okay, thus the probability of John cheating becomes fairly high, right? So in order for statisticians to come to a conclusion, they define what is known as the threshold value, right? Considering the above situation, if the threshold value is set to 5%, it would indicate that if the probability lies below 5%, then John is cheating his way out of detention. But if the probability is above the threshold value, then John is just lucky and his name isn't getting picked. So the probability and hypothesis testing give rise to two important components of hypothesis testing, which is null hypothesis and alternate hypothesis. Null hypothesis is basically approving the assumption. Alternate hypothesis is when your result disapproves the assumption. Right? Therefore, in our example, if the probability of an event occurring is less than 5%, which it is, then the event is biased. Hence, it proves the alternate hypothesis.
Undoubtedly, machine learning is the most in-demand technology in today's market. Its applications range from self-driving cars to predicting deadly diseases such as ALS. The high demand for machine learning skills is the motivation behind today's session. So let me discuss the agenda with you first. Now we're going to begin the session by understanding the need for machine learning and why it is important. After that, we'll look at what exactly machine learning is, and then we'll discuss a couple of machine learning definitions. Once we're done with that, we'll look at the machine learning process and how you can solve a problem by using the machine learning process. Next, we'll discuss the types of machine learning, which include supervised, unsupervised, and reinforcement learning. Once we're done with that, we'll discuss the different types of problems that can be solved by using machine learning. Finally, we'll end this session by looking at a demo where we'll see how you can perform weather forecasting by using machine learning. Alright, so guys, let's get started with our first topic. So what is the importance or what is the need for machine learning? Now, ever since the technical revolution, we've been generating an immeasurable amount of data. As per research, we're generating around 2.5 quintillion bytes of data every single day. And it is estimated that by 2020, 1.7 MB of data will be created every second for every person on Earth. Now that is a lot of data. Right now, this data comes from sources such as the cloud, IoT devices, social media, and all of that. Since all of us are very interested in the internet right now, we're generating a lot of data. All right, you have no idea how much data we generate through social media. All the chatting that we do and all the images that we post on Instagram, the videos that we watch, all of this generates a lot of data. Now, how does machine learning fit into all of this? Since we're producing this much data, we need to find a method that can analyze, process, and interpret this much data. All right, and we need to find a method that can make sense out of data. And that method is machine learning. Now, there are a lot of top tier companies and data-driven companies such as Netflix and Amazon, which build machine learning models by using tons of data in order to identify any profitable opportunities. And if they want to avoid any unwanted risks, they make use of machine learning. All right. So through machine learning, you can predict risks, you can predict profits, you can identify opportunities which will help you grow your business. So now I'll show you a couple of examples wherein machine learning is used. All right. So I'm sure all of you have binge watched on Netflix. Now, the most important thing about Netflix is its recommendation engine. All right. Most of Netflix's revenue comes from its recommendation engine. So the recommendation engine basically studies the movie viewing patterns of its users and then recommends relevant movies to them. All right. It recommends movies depending on users' interests, depending on the type of movies the user watches and all of that. All right. So that is how Netflix uses machine learning. Next, we have Facebook's auto tagging feature. Now, the logic behind Facebook's auto tagging feature is machine learning and neural networks. I'm not sure how many of you know this, but Facebook makes use of DeepMind face verification system, which is based on machine learning, natural language processing, and neural networks. So DeepMind basically studies the facial features in an image and it tags your friends and family. Another such example is Amazon's Alexa. Now, Alexa is basically an advanced level virtual assistant that is based on natural language processing and machine learning. Now, it can do more than just play music for you, all right? It can book your Uber, it can connect with other IoT devices at your house, it can track your health, it can order food online, and all of that, okay? So, data and machine learning are basically the main factors behind Alexa's power. Another such example is the Google spam filter. So guys, Gmail basically makes use of machine learning to filter out spam messages. If any of you just open your Gmail inbox, you'll see that there are separate sections. There's one for primary, there's social, there's spam, and there's your general mail. Now, basically, Gmail makes use of machine learning algorithms and natural language processing to analyze emails in real time and then classify them as either spam or non-spam. Now, this is another famous application of machine learning. So, to sum this up, let's look at a few reasons why machine learning is so important. So, the first reason is obviously increase in data generation. So, because of excessive production of data, we need a method that can be used to structure, analyze, and draw useful insights from data. This is where machine learning comes in. It uses data to solve problems and find solutions to the most complex tasks faced by organizations. Another important reason is that it improves decision making. So by making use of various algorithms, machine learning can be used to make better business decisions. For example, machine learning is used to forecast sales. It is used to predict any downfalls in the stock market. It is used to identify risks, anomalies, and so on. Now, the next reason is it uncovers patterns and trends in data. Finding hidden patterns and extracting key insights from data is the most essential part of machine learning. So, by building predictive models and using statistical techniques, machine learning allows you to dig beneath the surface and explore the data at a minute scale. Now, understanding data and extracting patterns manually will take a lot of days. Now, if you do this through machine learning algorithms, you can perform such computations in less than a second. Another reason is that it solves complex problems. So, from detecting genes that are linked to deadly ALS diseases to building self-driving cars and building face detection systems, machine learning can be used to solve the most complex problems. So guys, now that you know why machine learning is so important, let's look at what exactly machine learning is. The term machine learning was first coined by Arthur Samuel in the year 1959. Now, looking back, that year was probably the most significant in terms of technological advancements. Guys, if you browse through the net about what is machine learning, you'll get at least 100 different definitions. Now, the first and very formal definition was given by Tom M. Mitchell. Now, the definition says that a computer program is said to learn from experience E with respect to some class of task T and performance measure P if its performance at tasks in T as measured by P improves with experience E. Alright. Now, I know this is a little confusing, so let's break it down into simple words. Now, in simple terms, machine learning is a subset of artificial intelligence which provides machines the ability to learn automatically and improve from experience without being explicitly programmed to do so. In the sense, it is the practice of getting machines to solve problems by gaining the ability to think. But wait, now how can a machine think or make decisions? Well, if you feed a machine a good amount of data, it will learn how to interpret, process, and analyze this data by using machine learning algorithms. Okay. Now, guys, look at this figure on top. Now, this figure basically shows how a machine learning algorithm or how the machine learning process really works. So the machine learning process begins by feeding the machine lots and lots of data. Okay, by using this data, the machine is trained to detect hidden insights and trends. Now, these insights are then used to build a machine learning model by using an algorithm in order to solve a problem. Okay. So basically, you're going to feed a lot of data to the machine. The machine is going to get trained by using this data. It's going to use this data and it's going to draw useful insights and patterns from it. And then it's going to build a model by using machine learning algorithms. Now, this model will help you predict the outcome or help you solve any complex problem or any business problem. So that's a simple explanation of how machine learning works. Now let's move on and look at some of the most commonly used machine learning terms. So first of all, we have algorithm. Now this is quite self-explanatory. Basically, algorithm is a set of rules or statistical techniques which are used to learn patterns from data. Now, an algorithm is the logic behind a machine learning model. All right. An example of a machine learning algorithm is linear regression. I'm not sure how many of you have heard of linear regression. It's the most simple and basic machine learning algorithm. All right. Next, we have model. Now, model is the main component of machine learning. All right. So, model will basically map the input to your output by using the machine learning algorithm and by using the data that you're feeding the machine. So basically, the model is a representation of the entire machine learning process. So the model is basically fed input, which is a lot of data, and then it will output a particular result or a particular outcome by using machine learning algorithms. Next, we have something known as predictor variable. Now, predictor variable is a feature of the data that can be used to predict the output. So for example, let's say that you're trying to predict the weight of a person depending on the person's height and their age. All right. So over here, the predictor variables are your height and your age because you're using height and age of a person to predict the person's weight. All right. So the height and the age are the predictor variables. Now, weight, on the other hand, is the response or the target variable. So response variable is a feature or the output variable that needs to be predicted by using the predictor variables. All right. After that, we have something known as training data. So guys, the data that is fed to a machine learning model is always split into two parts. First, we have the training data and then we have the testing data. Now, training data is basically used to build the machine learning model. So usually training data is much larger than the testing data because obviously if you're trying to train the machine, then you're going to feed it a lot more data. Testing data is just used to validate and evaluate the efficiency of the model. All right. So that was training data and testing data. So guys, these were a few terms that I thought you should know before we move any further. Okay, now let's move on and discuss the machine learning process. Now this is going to get very interesting because I'm going to give you an example and make you understand how the machine learning process works. So first of all, let's define the different stages or the different steps involved in the machine learning process. So a machine learning process always begins with defining the objective or defining the problem that you're trying to solve. Next stage is data gathering or data collection. Now the data that you need to solve this problem is collected at this stage. This is followed by data preparation or data processing. After that, you have data exploration and analysis. And the next stage is building a machine learning model. This is followed by model evaluation. And finally, you have prediction or your output. Now let's try to understand this entire process with an example. So our problem statement here is to predict the possibility of rain by studying the weather conditions. So let's say that you're given a problem statement and you're asked to use a machine learning process to solve this problem statement. So let's get started. All right. So the first step is to define the objective of the problem statement. Our objective here is to predict the possibility of rain by studying the weather conditions. Now, in the first stage of a machine learning process, you must understand what exactly needs to be predicted. Now, in our case, the objective is to predict the possibility of rain by studying weather conditions, right? So at this stage, it is also essential to take mental notes on what kind of data can be used to solve this problem or the type of approach that you can follow to get to the solution, all right? A few questions that are worth asking during this stage is what are we trying to predict? What are the target features or what are the predictor variables? What kind of input data do we need? And what kind of problem are we facing? Is it a binary classification problem or is it a clustering problem? Now, don't worry if you don't know what classification and clustering is. I'll be explaining this in the upcoming slides. So guys, this was the first step of a machine learning process, which is define the objective of the problem. All right, now let's move on and look at step number 2. So step number 2 is basically data collection or data gathering. Now at this stage, you must be asking questions such as what kind of data is needed to solve the problem? is the data available, and if it is available, how can I get the data? Okay, so once you know the type of data that is required, you must understand how you can derive this data. Data collection can be done manually or by web scraping. But if you're a beginner and you're just looking to learn machine learning, you don't have to worry about getting the data. Okay, there are thousands of data resources on the web. You can just go ahead and download the data sets from websites such as Kaggle. Okay, now coming back to the problem at hand, the data needed for weather forecasting includes measures such as humidity level, temperature, pressure, locality, whether or not you live in a hill station, and so on. So guys, such data must be collected and stored for analysis. Now the next stage in machine learning is preparing your data. The data you collected is almost never in the right format. So basically you'll encounter a lot of inconsistencies in the data set. Okay, this includes missing values, redundant variables, duplicate values, and so on. Removing such values is very important because they might lead to wrongful computations and predictions. So that's why at this stage you must scan the entire data set for any inconsistencies, and you have to fix them at this stage. Now the next step is exploratory data analysis. Now data analysis is all about diving deep into data and finding all the hidden data mysteries. Okay, this is where you become a detective. So EDA or exploratory data analysis is like the brainstorming of machine learning. Data exploration involves understanding the patterns and the trends in your data. So at this stage, all the useful insights are drawn and all the correlations between the variables are understood. So you might ask, what sort of correlations are you talking about? For example, in the case of predicting rainfall, we know that there is a strong possibility of rain if the temperature has fallen low. Okay, so such correlations have to be understood and mapped at this stage. Now, this stage is followed by stage number 5, which is building a machine learning model. So all the insights and the patterns that you derive during data exploration are used to build the machine learning model. So this stage always begins by splitting the data set into two parts, training data and the testing data. So earlier in this session, I already told you what training and testing data is. Now the training data will be used to build and analyze the model, and the logic of the model will be based on the machine learning algorithm that is being implemented. Okay. Now in the case of predicting rainfall, since the output will be in the form of true or false, we can use a classification algorithm like logistic regression. Now, choosing the right algorithm depends on the type of problem you're trying to solve, the data set you have, and the level of complexity of the problem. So in the upcoming sections, we'll be discussing different types of problems that can be solved by using machine learning. So don't worry if you don't know what classification algorithm is and what logistic regression is. Okay. So all you need to know is at this stage, you'll be building a machine learning model by using machine learning algorithm and by using the training data set. The next step in a machine learning process is model evaluation and optimization. So after building a model by using the training data set, it is finally time to put the model to a test. Okay. So the testing data set is used to check the efficiency of the model and how accurately it can predict the outcome. So once you calculate the accuracy, any improvements in the model have to be implemented in this stage. Okay. So methods like parameter tuning and cross-validation can be used to improve the performance of the model. This is followed by the last stage, which is predictions. So once the model is evaluated and improved, it is finally used to make predictions. The final output can be a categorical variable or it can be a continuous quantity. In our case, for predicting the occurrence of rainfall, the output will be a categorical variable. In the sense, our output will be in the form of true or false, yes or no. Yes basically represents that it's going to rain, and no will represent that no, it won't rain. Okay, as simple as that. So guys, that was the entire machine learning process.
A linear regression is one of the easiest algorithms in machine learning. It is a statistical model that attempts to show the relationship between two variables with a linear equation. But before we drill down to linear regression algorithm in depth, I'll give you a quick overview of today's agenda. So we'll start our session with a quick overview of what is regression, as linear regression is one of a type of regression algorithm. Once we learn about regression, its use case, the various types of it, next we'll learn about the algorithm from scratch. where I'll teach you its mathematical implementation first, then we'll drill down to the coding part and implement linear regression using Python. In today's session, we'll deal with linear regression algorithm using least square method, check its goodness of fit or how close the data is to the fitted regression line using the R-square method. And then finally, what we'll do, we'll optimize it using the gradient descent method. In the last part, on the coding session, I'll teach you to implement linear regression using Python. And the coding session would be divided into two parts. The first part would consist of linear regression using Python from scratch, where you will use the mathematical algorithm that you have learned in this session. And in the next part of the coding session, we'll be using scikit-learn for direct implementation of linear regression. Alright, I hope the agenda is clear to you guys. Alright, so let's begin our session with what is regression? Well, regression analysis is a form of predictive modeling technique which investigates the relationship between a dependent and independent variable. A regression analysis involves graphing a line over a set of data points that most closely fits the overall shape of the data. A regression shows the changes in a dependent variable on the y-axis to the changes in the explanatory variable on the x-axis. Fine. Now you'd ask, what are the uses of regression? Well, there are major three uses of regression analysis. The first being determining the strength of predicators. The regression might be used to identify the strength of the effect that the independent variables have on the dependent variable. For example, you can ask a question like, what is the strength of relationship between sales and marketing spending? Or what is the relationship between age and income? Second is forecasting an effect. In this, the regression can be used to forecast effects or impact of changes. That is, the regression analysis help us to understand how much the dependent variable changes with the change in one or more independent variable. Fine. For example, you can ask question like, how much additional sale income will I get for each $1,000 spent on marketing? Third is trend forecasting. In this, the regression analysis predict trends and future values. The regression analysis can be used to get point estimates. In this, you can ask questions like, what will be the price of Bitcoin in next 6 months, right? So next topic is linear versus logistic regression. By now, I hope that you know what a regression is. So let's move on and understand its type. So there are various kinds of regression like linear regression, logistic regression, polynomial regression, and others. All right. But for this session, we'll be focusing on linear and logistic regression. So let's move on and let me tell you what is linear regression and what is logistic regression. Then what we'll do, we'll compare both of them. All right. So starting with linear regression. In simple linear regression, we are interested in things like y equal mx plus c. So what we are trying to find is the correlation between x and y variable. This means that every value of x has a corresponding value of y in it if it is continuous. Alright. However, in logistic regression, we are not fitting our data to a straight line like linear regression. Instead, what we are doing, we are mapping y versus x to a sigmoid function. In logistic regression, what we find out is y 1 or 0 for this particular value of x. So thus we are essentially deciding true or false value for a given value of x. Fine. So as a core concept of linear regression, you can say that the data is modeled using a straight line, where in the case of logistic regression, the data is modeled using a sigmoid function. The linear regression is used with continuous variables. On the other hand, the logistic regression, it is used with categorical variable. The output or the prediction of a linear regression is the value of the variable. On the other hand, the output or prediction of a logistic regression is the probability of occurrence of the event. Now, how will you check the accuracy and goodness of fit? In case of linear regression, you have various methods like measured by loss, R squared, adjusted R squared, etc. While in the case of logistic regression, you have accuracy, precision, recall, F1 score, which is nothing but the harmonic mean of precision and recall. Next is ROC curve for determining the probability threshold for classification or the confusion matrix, etc. There are many. All right. So summarizing the difference between linear and logistic regression, you can say that the type of function you are mapping to is the main point of difference between linear and logistic regression. A linear regression maps a continuous x to a continuous y. On the other hand, a logistic regression maps a continuous x to the binary y. So we can use logistic regression to make category or true-false decisions from the data. Fine, so let's move on ahead. Next is linear regression selection criteria, or you can say when will you use linear regression. So the first is classification and regression capabilities. Regression models predict a continuous variable, such as the sales made on a day, or predict the temperature of a city. Their reliance on a polynomial like a straight line to fit a data set poses a real challenge when it comes towards building a classification capability. Let's imagine that you fit a line with the training points that you have. Now imagine you add some more data points to it. But in order to fit it, what do you have to do? You have to change your existing model. That is, maybe you have to change the threshold itself. So this will happen with each new data point you add to the model. Hence, the linear regression is not good for classification models. Fine. Next is data quality. Each missing value removes one data point that could optimize the regression. In simple linear regression, the outliers can significantly disrupt the outcome. Just for now, you can know that if you remove the outliers, your model will become very good. All right. So this is about data quality. Next is computational complexity. The linear regression is often not computationally expensive as compared to the decision tree or the clustering algorithm. The order of complexity for n training example and x features usually falls in either big O of x square or big O of xn. Next is comprehensible and transparent. The linear regression are easily comprehensible and transparent in nature. They can be represented by a simpler mathematical notation to anyone and can be understood very easily. So these are some of the criteria based on which you'll select the linear regression algorithm. Alright, next is, where is linear regression used? First is evaluating trends and sales estimate. Well, linear regression can be used in business to evaluate trends and make estimates or forecasts. For example, if a company's sales have increased steadily every month for past few years, then conducting a linear analysis on the sales data with monthly sales on the y-axis and time on the x-axis. This will give you a line that predicts the upward trends in the sale. After creating the trend line, the company could use the slope of the lines to forecast sale in future months. Next is analyzing the impact of price changes. Well, linear regression can be used to analyze the effect of pricing on consumer behavior. For instance, if a company changes the price on a certain product several times, then it can record the quantity itself for each price level and then perform a linear regression with sold quantity as a dependent variable and price as the independent variable. This would result in a line that depicts the extent to which the customer reduced their consumption of the product as the price is increasing. So this result would help us in future pricing decisions. Next is assessment of risk in financial services and insurance domain. Well, linear regression can be used to analyze the risk. For example, a health insurance company might conduct a linear regression algorithm. How it can do? It can do it by plotting the number of claims per customer against its age. And they might discover that the old customers tend to make more health insurance claim. Well, the result of such an analysis might guide important business decisions. All right. So by now you have just a rough idea of what linear regression algorithm is, like what it does, where it is used, when you should use it. All right. Now let's move on and understand the algorithm in depth. So suppose you have independent variable on the x-axis and dependent variable on the y-axis. All right. Suppose this is the data point on the x-axis. The independent variable is increasing on the x-axis, and so does the dependent variable on the y-axis. So what kind of linear regression line you would get? You'd get a positive linear regression line. All right, as the slope would be positive. Next is, suppose you have an independent variable on the x-axis, which is increasing. And on the other hand, the dependent variable on the y-axis, that is decreasing. So what kind of line will you get in that case? You'll get a negative regression line in this case, as the slope of the line is negative. And this particular line, that is line of y equal mx plus c, is a line of linear regression, which shows the relationship between independent variable and dependent variable. And this line is only known as line of linear regression. Okay. So let's add some data points to our graph. So these are some observation or data points on our graphs. Let's plot some more. Okay. Now all our data points are plotted. Now our task is to create a regression line or the best fit line. All right. Now once our regression line is drawn, now it's the task of prediction. Now suppose this is our estimated value or the predicted value, and this is our actual value. Okay. So what we have to do, our main goal is to reduce this error, that is to reduce the distance between the estimated or the predicted value and the actual value. The best fit line would be the one which had the least error or the least difference in estimated value and the actual value. All right. In other words, we have to minimize the error. This was a brief understanding of linear regression algorithm. Soon we'll jump to its mathematical implementation. All right. But for then, let me tell you this. Suppose you draw a graph with speed on the x-axis and distance covered on the y-axis with the time remaining constant. If you plot a graph between the speed traveled by the vehicle and the distance traveled in a fixed unit of time, then you will get a positive relationship. All right. So suppose the equation of line is y equal mx plus c. Then in this case, y is the distance traveled in a fixed duration of time. X is the speed of vehicle, m is the positive slope of the line, and c is the y-intercept of the line. All right. Suppose the distance remaining constant, you have to plot a graph between the speed of the vehicle and the time taken to travel a fixed distance. Then in that case, you'll get a line with a negative relationship. All right. The slope of the line is negative. Here the equation of line changes to y equal minus of mx plus c, where y is the time taken to travel a fixed distance, x is the speed of vehicle, m is the negative slope of the line, and c is the y-intercept of the line. All right. Now let's get back to our independent and dependent variable. So in that term, y is our dependent variable and x, that is our independent variable. Now let's move on and see the mathematical implementation of the things. All right. So we have x equal 1, 2, 3, 4, 5. Let's plot them on the x-axis. So 0, 1, 2, 3, 4, 5, 6. All right. And we have y as 3, 4, 2, 4, 5. All right. So let's plot 1, 2, 3, 4, 5 on the y-axis. Now let's plot our coordinates one by one. So x equal 1 and y equal 3. So we have here x equal 1 and y equal 3. So this is our point 1, 3. So similarly, we have 1, 3, 2, 4, 3, 2, 4, 4, and 5, 5. All right. So moving on ahead, let's calculate the mean of x and y and plot it on the graph. All right. So mean of x is 1 plus 2 plus 3 plus 4 plus 5 divided by 5, that is 3. All right. Similarly, mean of y is 3 plus 4 plus 2 plus 4 plus 5, that is 18. So 18 divided by 5, that is nothing but 3.6. All right. So next what we'll do, we'll plot our mean, that is 3, 3.6 on the graph. Okay. So there's a point 3, 3.6. See, our goal is to find or predict the best fit line using the least square method. All right. So in order to find that, we first need to find the equation of line. So let's find the equation of our regression line. All right. So let's suppose this is our regression line, y equal mx plus c. Now we have an equation of line. So all we need to do is find the value of m and c, where m equals summation of x minus x bar multiplied by y minus y bar upon the summation of x minus x bar whole square. Don't get confused. Let me resolve it for you. All right. So moving on ahead, as a part of formula, what we are going to do, we'll calculate x minus x bar. So we have x as 1 minus x bar as 3. So 1 minus 3, that is minus 2. Next we have x equal 2 minus its mean 3, that is minus 1. Similarly, we have 3 minus 3 is 0, 4 minus 3 1, 5 minus 3 2. All right. So x minus x bar, it's nothing but the distance of all the point through the line y equal 3. And what does this y minus y bar implies? It implies the distance of all the point from the line x equal 3.6. Fine. So let's calculate the value of y minus y bar. So starting with y equal 3 minus value of y bar, that is 3.6. So it is 3 minus 3.6. How much? Minus of 0.6. Next is 4 minus 3.6. That is 0.4. Next 2 minus 3.6. That is minus of 1.6. Next is 4 minus 3.6. That is 0.4. Again 5 minus 3.6. That is 1.4. All right. So now we are done with y minus y bar. Fine. Now next we'll calculate x minus x bar whole square. So let's calculate x minus x bar whole square. So it is minus 2 whole square, that is 4, minus 1 whole square, that is 1, 0 square 0, 1 square 1, 2 square 4. Fine. So now in our table we have x minus x bar, y minus y bar, and x minus x bar whole square. Now what we need the product of x minus x bar multiplied by y minus y bar. All right. So let's see the product of x minus x bar multiplied by y minus y bar. That is minus of 2 multiplied by minus of 0.6, that is 1.2. Minus of 1 multiplied by 0.4, that is minus of 0.4. 0 multiplied by minus of 1.6, that is 0. 1 multiplied by 0.4, that is 0.4. And next 2 multiplied by 1.4, that is 2.8. All right. Now almost all the parts of our formula is done. So now what we need to do is get the summation of last two columns. All right. So the summation of x minus x bar whole square is 10, and the summation of x minus x bar multiplied by y minus y bar is 4. So the value of m will be equal to 4 by 10. Fine. So let's put this value of m equals 0.4 in our line y equal mx plus c. So let's fill all the points into the equation and find the value of c. So we have y as 3.6. Remember the mean y? M as 0.4, which we calculated just now. X as the mean value of x, that is 3. And we have the equation as 3.6 equals 0.4 multiplied by 3 plus c. All right. That is 3.6 equal 1.2 plus c. So what is the value of c? That is 3.6 minus 1.2. That is 2.4. All right. So what we had m equals 0.4, c as 2.4. And then finally, when we calculate the equation of regression line, what we get is y equal 0.4 times of x plus 2.4. So this is the regression line. All right. So this is how you are plotting your points. This is your actual point. All right. Now for given m equals 0.4 and c equal 2.4, let's predict the value of y for x equal 1, 2, 3, 4 and 5. So when x equal 1, the predicted value of y will be 0.4 multiplied by 1 plus 2.4, that is 2.8. Similarly, when x equal 2, predicted value of y will be 0.4 multiplied by 2 plus 2.4, that equals to 3.2. Similarly, x equal 3, y will be 3.6. X equal 4, y will be 4.0. X equal 5, y will be 4.4. So let's plot them on the graph, and the line passing through all these predicting points and cutting y-axis at 2.4 is the line of regression. Now your task is to calculate the distance between the actual and the predicted value, and your job is to reduce the distance. All right? Or in other words, you have to reduce the error between the actual and the predicted value. The line with the least error will be the line of linear regression or regression line, and it will also be the best fit line. All right. So this is how things work in computer. So what it performs n number of iteration for different values of m. For different values of m, it will calculate the equation of line where y equal mx plus c, right? So as the value of m changes, the line is changing. So iteration will start from 1, all right, and it will perform n number of iteration. So after every iteration, what it will do, it will calculate the predicted value according to the line and compare the distance of actual value to the predicted value. And the value of m for which the distance between the actual and the predicted value is minimum will be selected as the best fit line. All right. Now that we have calculated the best fit line, now it's time to check the goodness of fit or to check how good a model is performing. So in order to do that, we have a method called R-square method. So what is this R-square? Well, R-squared value is a statistical measure of how close the data are to the fitted regression line. In general, it is considered that a high R-squared value model is a good model. But you can also have a low R-squared value for a good model as well, or a high R-squared value for a model that does not fit at all. All right. It is also known as coefficient of determination or the coefficient of multiple determination. Let's move on and see how R-square is calculated. So these are our actual values plotted on the graph. We had calculated the predicted values of y as 2.8, 3.2, 3.6, 4.0, 4.4. Remember when we calculated the predicted values of y for the equation y predicted equals 0.4 times of x plus 2.4 for every x equal 1, 2, 3, 4 and 5. From there we got the predicted values of y. All right. So let's plot it on the graph. So these are a point and the line passing through these points are nothing but the regression line. All right. Now what you need to do is you have to check and compare the distance of actual minus mean versus the distance of predicted minus mean. All right. So basically what you're doing, you're calculating the distance of actual value to the mean to distance of predicted value to the mean. All right. So there's nothing but R square. In mathematically, you can represent R square as summation of y predicted values minus y bar whole square divided by summation of y minus y bar whole square, where y is the actual value, yp is the predicted value, and y bar is the mean value of y. That is nothing but 3.6. So remember, this is our formula. So next what we'll do, we'll calculate y minus y bar. So we have y as 3, y bar as 3.6. So we'll calculate it as 3 minus 3.6, that is nothing but minus of 0.6. Similarly, for y equal 4 and y bar equal 3.6, we have y minus y bar as 0.4. Then 2 minus 3.6, it is 1.6. 4 minus 3.6, again 0.4, and 5 minus 3.6, it is 1.4. So we got the value of y minus y bar. Now what we have to do, we have to take it square. So we have minus of 0.6 square as 0.36, 0.4 square as 0.16, minus of 1.6 square as 2.56, 0.4 square as 0.16, and 1.4 square as 1.96. Now as a part of formula, what we need our yp minus y bar value. So these are yp values and we have to subtract it from the mean of y. So 2.8 minus 3.6, that is minus 0.8. Similarly, we'll get 3.2 minus 3.6, that is 0.4. And 3.6 minus 3.6, that is 0. 4.0 minus 3.6, that is 0.4. Then 4.4 minus 3.6, that is 0.8. So we calculated the value of yp minus y bar. Now it's our turn to calculate the value of yp minus y bar whole square. Next we have minus of 0.8 square as 0.64, minus of 0.4 square as 0.16, 0 square 0, 0.4 square as again 0.16, and 0.8 square as 0.64. Alright. Now as a part of formula, what it suggests me to take the summation of yp minus y bar whole square and summation of y minus y bar whole square. Alright, let's see. So on summating y minus y bar whole square, what you get is 5.2. And summation of yp minus y bar whole square, you get 1.6. So the value of r square can be calculated as 1.6 upon 5.2. Fine. So the result which you'll get is approximately equal to 0.3. Well, this is not a good fit. Alright. So it suggests that the data points are far away from the regression line. Alright. So this is how your graph will look like when r square is 0.3. When you increase the value of r square to 0.7, so you'll see that the actual value would lie closer to the regression line. When it reaches to 0.9, it comes more close. And when the value approximately equals to 1, then the actual values lies on the regression line itself. For example, in this case, if you get a very low value of r square, suppose 0.02, so in that case, what you'll see that the actual values are very far away from the regression line. Or you can say that there are too many outliers in your data. You cannot forecast anything from the data. All right. So this was all about the calculation of r square. Now you might get a question like, are low values of r square always bad? Well, in some field, it is entirely expected that our r square value will be low. For example, any field that attempts to predict human behavior, such as psychology, typically has r squared values lower than around 50%, through which you can conclude that humans are simply harder to predict than the physical process. Furthermore, if your r squared value is low, but you have statistically significant predicators, then you can still draw important conclusion about how changes in the predicator values are associated with the changes in the response value. Regardless of the r squared, the significant coefficient still represent the mean change in the response for 1 unit of change in the predicator, while holding other predicators in the model constant. Obviously, this type of information can be extremely valuable. Alright? Alright, so this was all about the theoretical concept. Now let's move on to the coding part and understand the code in depth. So for implementing linear regression using Python, I'll be using Anaconda with Jupyter Notebook installed on it. So alright, this is our Jupyter Notebook and we are using Python 3.0 on it. Alright, so we are going to use a data set consisting of head size and human brain of different people. Alright, so let's import our data set. %matplotlib inline. We are importing numpy as np, pandas as pd, and matplotlib. And from matplotlib, we are importing pyplot of that as plt. Alright. Next, we'll import our data headbrain.csv and store it in the data variable. Let's execute the run button and see the output. So this asterisk symbol, it symbolizes that it's still executing. So there's our output. Our data set consists of 237 rows and 4 columns. We have columns as gender, age range, head size in centimeter cube, and brain weights in gram. Fine. So this is a sample data set. This is how it looks. It consists of all these data set. So now that we have imported our data, so as you can see, there are 237 values in the training set. So we can find a linear relationship between the head size and the brain weights. So now what we'll do, we'll collect X and Y. The X would consist of the head size values and the Y would consist of brain weight values. So collecting X and Y, let's execute the run. Done. Next, what we'll do, we need to find the values of B1 or B0, or you can say M and C. So we'll need the mean of X and Y values. First of all, what we'll do, we'll calculate the mean of X and Y. So mean X equal NP dot mean X. So mean is a predefined function of numpy. Similarly, mean underscore Y equal NP dot mean of Y. So what it will return? It will return the mean values of Y. Next, we'll check the total number of values. So M equal length of X. Alright. Then we'll use the formula to calculate the values of B1 and B0 or M and C. Alright, let's execute the run button and see what is the result. So as you can see here on the screen, we have got B1 as 0.263 and B0 as 325.57. Alright. So now that we have our coefficient, so comparing it with the equation y equal mx plus c, you can say that brain weight equals 0.263 multiplied by head size plus 325.57. So you can say that the value of m here is 0.263 and the value of c here is 325.57. All right. So this is our linear model. Now let's plot it and see graphically. Let's execute it. So this is how our plot looks like. This model is not so bad, but we need to find out how good our model is. So in order to find it, there are many methods like root mean square method, the coefficient or determination, or the R-square method. So in this tutorial, I have told you about R-square method. So let's focus on that and see how good our model is. So let's calculate the R-square value. All right. Here SS underscore T is the total sum of square. SS underscore R is the total sum of square of residuals. And R square as per formula is 1 minus total sum of squares upon total sum of square of residuals. Alright. Next, when you execute it, you'll get the value of R square as 0.63, which is pretty very good. Now that you have implemented simple linear regression model using least square method, let's move on and see how will you implement the model using machine learning library called scikit-learn. Alright. So this scikit-learn is a simple machine learning library in Python. Building machine learning model are very easy using scikit-learn. So suppose this is your Python code. So using the scikit-learn libraries, your code shortens to this length. Alright, so let's execute the run button and see. You'll get the same R2 score as. Well, this was all for today's discussion.
Most of the entities in this world are related in one way or another. At times, finding relationship between entities can help you take valuable business decisions. Today I'm going to talk about logistic regression, which is one such approach towards predicting relationships. Now let us see what all we're going to cover in today's training. So we'll start off the session by getting a quick introduction to what is regression. Then we'll see the different types of regression and we'll be discussing the what and why of logistic regression. So in this part, we'll discuss what exactly it is, where it is used, why it is used, and all those things. Moving ahead, we'll compare linear regression versus logistic regression along with the various real-life use cases. And finally, towards the end, I'll be practically implementing logistic regression algorithm. So let's quickly start off with the very first topic, what is regression? Now, regression analysis is a predictive modeling technique. So it always involves predictions. So in this session, we'll just talk about predictive analysis and not prescriptive analysis. Now why? Because in prescriptive analysis, you need to have a good base and a strong hold on the predictive part first. Now it estimates a relationship between the dependent variable and an independent variable. So for those of you who are not aware of these terminologies, let me give you a quick summary of it. So a dependent variable is nothing but a variable which you want to predict. Now let's say I want to know what will be the sales on 26th of this month. So sales becomes your dependent variable, or you can say the target variable. Now this dependent variable or target variable are going to depend on a lot of factors. Let's say the number of products you sold till date, or what is the season out there. Is there the availability of product, or how is the product quality, and all these things. So these are the never ending factors which are nothing but the different features that leads to sale. So these variables are called as your independent variable, or you can say the predictor. Now, if you look at the graph over here, we have some values of x and we have values of y. Now, as you can see over here, if x increases, the value of y also increases. So let me explain you this with an example. Let's say we have data till the value of x, which is 6.75, and somebody asks you what will be the value of y when the value of x is 7. So the way which you can do it or how regression comes into the picture is by fitting a straight line by all these points and getting the value of m and c. So this is straight line, guys, and the formula for the straight line is y is equals to mx plus c. So using this, we can try to predict the value of y. So here if you notice, the x variable can increase as much as it can, but the y variable will increase according to x. So y is basically dependent on your x variable. So for any arbitrary value of x, you can predict the value of y, and this is always done through regression. So that is how regression is useful. Now regression is basically classified into three types: your linear regression, then your logistic regression, and polynomial regression. So today we'll be discussing logistic regression. So let's move forward and understand the what and why of logistic regression. Now this algorithm is most widely used when the dependent variable, or you can say the output, is in the binary format. So here you need to predict the outcome of a categorical dependent variable. So the outcome should be always discrete or categorical in nature. Now by discrete, I mean the value should be binary, or you can say you just have two values. It can either be 0 or 1. It can either be yes or a no, either be true or false, or high or low. So only these can be the outcomes. So the value which you need to predict should be discrete, or you can say categorical in nature. Whereas in linear regression, we have the value of y, or you can say the value you need to predict is in a range. So that is how there is a difference between linear regression and logistic regression. Now you must be having a question, why not linear regression? Now guys, in linear regression, the value of y, or the value which you need to predict, is in a range. But in our case, as in the logistic regression, we just have two values. It can be either 0 or it can be 1. It should not entertain the values which is below 0 or above 1. But in linear regression, we have the value of y in the range. So here, in order to implement logistic regression, we need to clip this part. So we don't need the value that is below 0, or we don't need the value which is above 1. So since the value of y will be between only 0 and 1, that is the main rule of logistic regression, the linear line has to be clipped at 0 and 1. Now once we clip this graph, it would look somewhat like this. So here you are getting a curve which is nothing but three different straight lines. So here we need to make a new way to solve this problem. So this has to be formulated into an equation, and hence we come up with logistic regression. So here the outcome is either 0 or 1, which is the main rule of logistic regression. So with this, our resulting curve cannot be formulated. So hence our main aim to bring the values to 0 and 1 is fulfilled. So that is how we came up with logistic regression. Now here, once it gets formulated into an equation, it looks somewhat like this. So guys, this is nothing but a S curve, or you can say the sigmoid curve or sigmoid function curve. So this sigmoid function basically converts any value from minus infinity to infinity to your discrete values, which a logistic regression wants, or you can say the values which are in binary format, either 0 or 1. So if you see here, the values are either 0 or 1, and this is nothing but just a transition of it. But guys, there's a catch over here. So let's say I have a data point that is 0.8. Now, how can you decide whether your value is 0 or 1? Now, here you have the concept of threshold, which basically divides your line. So here threshold value basically indicates the probability of either winning or losing. So here by winning, I mean the value is equals to 1, and by losing, I mean the value is equals to 0. But how does it do that? Let's say I have a data point which is over here. Let's say my cursor is at 0.8. So here I'll check whether this value is less than my threshold value or not. Let's say if it is more than my threshold value, it should give me the result as 1. If it is less than that, then it should give me the result as 0. So here my threshold value is 0.5. Now I need to define that if my value, let's say 0.8, it is more than 0.5, then the value shall be rounded off to 1. And let's say if it is less than 0.5, let's say I have a value 0.2, then should reduce it to 0. So here you can use the concept of threshold value to find your output. So here it should be discrete, it should be either 0 or it should be 1. So I hope you caught this curve of logistic regression. So guys, this is the sigmoid S curve. So to make this curve, we need to make an equation. So let me address that part as well. So let's see how an equation is formed to imitate this functionality. So over here we have an equation of a straight line, which is y is equals to mx plus c. So in this case, I just have only one independent variable. But let's say if we have many independent variables, then the equation becomes m1x1 plus m2x2 plus m3x3 and so on till mn(xn). Now let us put in b and x. So here the equation becomes y is equals to b1x1 plus b2x2 plus b3x3 and so on till bn(xn) plus c. So guys, your equation of the straight line has a range from minus infinity to infinity. But in our case, or you can say in logistic equation, the value which we need to predict, or you can say the y value, it can have the range only from 0 to 1. So in that case, we need to transform this equation. So to do that, what we had done, we have just divided the equation by 1 minus y. So now if y is equals to 0, so 0 over 1 minus 0 which is equals to 1. So 0 over 1 is again 0. And if we take y is equals to 1, then 1 over 1 minus 1 which is 0. So 1 over 0 is infinity. So here my range is now between 0 to infinity. But again we want the range from minus infinity to infinity. So for that what we'll do, we'll have the log of this equation. So let's go ahead and have the logarithmic of this equation. So here we have just transform it further to get the range between minus infinity to infinity. So over here we have log of y over 1 minus 1, and this is your final logistic regression equation. So guys, don't worry, you don't have to write this formula or memorize this formula. In Python, you just need to call this function which is logistic regression and everything will be automatically for you. So I don't want to scare you with the maths and the formulas behind it, but it's always good to know how this formula was generated. So I hope you guys are clear with how logistic regression comes into the picture. Next, let us see what are the major differences between linear regression versus logistic regression. Now, first of all, in linear regression, we have the value of y as a continuous variable, or the variable which we need to predict are continuous in nature. Whereas in logistic regression, we have the categorical variable. So here the value which you need to predict should be discrete in nature. It should be either 0 or 1, or it should have just two values to it. So for example, whether it is raining or it is not raining. Is it humid outside or it is not humid outside? Now, does it going to snow or it is not going to snow? So these are the few examples where you need to predict where the values are discrete, or you can just predict whether this is happening or not. Next, linear regression solves your regression problems. So here you have a concept of independent variable and a dependent variable. So here you can calculate the value of y which you need to predict using the value of x. So here your y variable, or you can say the value that you need to predict, are in a range. But whereas in logistic regression you have discrete values. So logistic regression basically solves your classification problem. So it can basically classify it and it can just give you result whether this event is happening or not. So I hope it is pretty much clear till now. Next, in linear regression, the graph that you have seen is a straight line graph. So over here you can calculate the value of y with respect to the value of x. Whereas in logistic regression, the curve that we got was a S curve, or you can say the sigmoid curve. So using the sigmoid function, you can predict your y values. So I hope you guys are clear with the differences between the linear regression and logistic regression. Moving ahead, let us see the various use cases wherein logistic regression is implemented in real life. So the very first is weather prediction. Now logistic regression helps you to predict your weather. For example, it is used to predict whether it is raining or not, whether it is sunny, is it cloudy or not. So all these things can be predicted using logistic regression. Whereas you need to keep in mind that both linear regression and logistic regression can be used in predicting the weather. So in that case, linear regression helps you to predict what will be the temperature tomorrow. Whereas logistic regression will only tell you whether it's going to rain or not, or whether it's cloudy or not, whether it's going to snow or not. So these values are discrete. Whereas if you apply linear regression, you'll be predicting things like what is the temperature tomorrow, or what is the temperature day after tomorrow, and all those things. So these are the slight differences between linear regression and logistic regression. Now moving ahead, we have classification problem. So Python performs multi-class classification. So here it can help you tell whether it's a bird or it's not a bird. Then you can classify different kind of mammals. Let's say whether it's a dog or it's not a dog. Similarly, you can check it for reptile, whether it's a reptile or not a reptile. So in logistic regression, it can perform multi-class classification. So this point I have already discussed that it is used in classification problems. Next, it also helps you to determine the illness as well. So let me take an example. Let's say a patient goes for a routine checkup in a hospital. So what doctor will do, it will perform various tests on the patient and will check whether the patient is actually ill or not. So what will be the features? So doctor can check the sugar level, the blood pressure, then what is the age of the patient? Is it very small or is it an old person? Then what is the previous medical history of that patient? And all of these features will be recorded by the doctor. And finally, doctor checks the patient data and determines the outcome of an illness and the severity of illness. So using all the data, a doctor can identify whether a patient is ill or not. So these are the various use cases in which you can use logistic regression. Now I guess enough of theory part. So let's move ahead and see some of the practical implementation of logistic regression. So over here I'll be implementing two projects wherein I have the data set of a Titanic. So over here we'll predict what factors made people more likely to survive the sinking of the Titanic ship. And in my second project, we'll see the data analysis on the SUV cars. So over here we have the data of the SUV cars, who can purchase it, and what factors made people more interested in buying SUV. So these will be the major questions as to why you should implement logistic regression and what output will you get by it. So let's start by the very first project, that is Titanic data analysis. So some of you might know that there was a ship called as Titanic which basically hit an iceberg and it sunk to the bottom of the ocean. And it was a big disaster at that time because it was the first voyage of the ship and it was supposed to be really strongly built and one of the best ships of that time. So it was a big disaster of that time, and of course, there's a movie about this as well. So many of you might have watched it. So what we have data of the passengers, those who survived and those who did not survive in this particular tragedy. So what you have to do, you have to look at this data and analyze which factors would have been contributed the most to the chances of a person's survival on the ship or not. So using the logistic regression, we can predict whether the person survived or the person died. Now, apart from this, we'll also have a look with the various features along with that. So first, let us explore the data set. So over here, we have the index value. Then the first column is passenger ID. Then my next column is survived. So over here, we have two values, a 0 and a 1. So 0 stands for did not survive and 1 stands for survive. So this column is categorical where the values are discrete. Next, we have passenger class. So over here, we have three values, 1, 2, and 3. So this basically tells you that whether a passenger is traveling in the first class, second class, or third class. Then we have the name of the passenger, we have the sex, or you can say the gender of the passenger, whether passenger is a male or female. Then we have the age, we have the SIB SP. So this basically means the number of siblings or the spouses aboard the Titanic. So over here we have values such as 1, 0, and so on. Then we have patch. So patch is basically the number of parents or children aboard the Titanic. So over here we also have some values. Then we have the ticket number, we have the fare, we have the cabin number, and we have the embarked column. So in my embarked column, we have three values. We have S, C, and Q. So S basically stands for Southampton, C stands for Cherbourg, and Q stands for Queenstown. So these are the features that we'll be applying our model on. So here we'll perform various steps and then we'll be implementing logistic regression. So now these are the various steps which are required to implement any algorithm. So now in our case we are implementing logistic regression. So our very first step is to collect your data or to import the libraries that are used for collecting your data and then taking it forward. Then my second step is to analyze your data. So over here I can go to the various fields and then I can analyze the data. I can check did the females or children survive better than the males, or did the rich passenger survive more than the poor passenger, or did the money matter, as in who paid more to get into the ship, were they evacuated first, and what about the workers, does the worker survived, or what is the survival rate if you were the worker in the ship and not just a traveling passenger. So all of these are very interesting questions and you would be going through all of them one by one. So in this stage you need to analyze your data and explore your data as much as you can. Then my third step is to wrangle your data. Now data wrangling basically means cleaning your data. So over here you can simply remove the unnecessary items, or if you have a null values in the data set, you can just clear that data and then you can take it forward. So in this step you can build your model using the trained data set and then you can test it using the test. So over here you will be performing a split which basically split your data set into training and testing data set. And finally you will check the accuracy so as to ensure how much accurate your values are. So I hope you guys got these 5 steps that we're going to implement in logistic regression. So now let's go into all these steps in detail. So number one, we have to collect your data, or you can say import the libraries. So let me just show you the implementation part as well. So I'll just open my Jupyter notebook and I'll just implement all of these steps side by side. So guys, this is my Jupyter notebook. So first let me just rename the Jupyter notebook to, let's say, Titanic data analysis. Now our first step was to import all the libraries and collect the data. So let me just import all the libraries first. So first of all, I'll import pandas. So pandas is used for data analysis. So I'll say import pandas as PD. Then I'll be importing numpy. So I'll say import numpy as NP. So numpy is a library in Python which basically stands for numerical Python, and it is widely used to perform any scientific computation. Next, we'll be importing Seaborn. So Seaborn is a library for statistical plotting. So I'll say import Seaborn as SNS. I'll also import matplotlib. So matplotlib library is again for plotting. So I'll say import matplotlib.pyplot as PLT. Now to run this library in Jupyter Notebook, all I have to write in is percentage matplotlib inline. Next, I'll be importing one module as well so as to calculate the basic mathematical functions. So I'll say import maths. So these are the libraries that I'll be needing in this Titanic data analysis. So now let me just import my data set. So I'll take a variable, let's say Titanic data, and using the pandas, I will just read my CSV, or you can say the data set. I'll write the name of my data set, that is titanic.csv. Now I have already showed you the data set. So over here, let me just print the top 10 rows. So for that, I'll just say, I'll take the variable Titanic data dot head and I'll say the top 10 rows. So now I'll just run this. So to run this, so I just have to press Shift plus Enter, or else you can just directly click on this cell. So over here, I have the index, we have the passenger ID, which is nothing but again the index which is starting from 1. Then we have the survived column, which has the categorical values, or you can say the discrete values, which is in the form of 0 or 1. Then we have the passenger class, we have the name of the passenger, sex, age, and so on. So this is the dataset that I'll be going forward with. Next, let us print the number of passengers which are there in this original dataset. So for that, I'll just simply type in print. I'll say number of passengers. And using the length function, I can calculate the total length. So I'll say length, and inside this, I'll be passing this variable, which is Titanic data. So I'll just copy it from here. I'll just paste it dot index. And next, so let me just print this one. So here the number of passengers which are there in the original data set we have is 891. So around this number were traveling in the Titanic ship. So over here, my first step is done, where you have just collected data, imported all the libraries, and find out the total number of passengers which are traveling in Titanic. So now let me just go back to presentation and let's see what is my next step. So we're done with the collecting data. Next step is to analyze your data. So over here, we'll be creating different plots to check the relationship between variables, as in how one variable is affecting the other. So you can simply explore your dataset by making use of various columns, and then you can plot a graph between them. So you can either plot a correlation graph, you can plot a distribution graph. It's up to you guys. So let me just go back to my Jupyter notebook and let me analyze some of the data. Over here, my second part is to analyze data. So I just put this in header 2. Now to put this in header 2, I just have to go on code, click on markdown, and I just run this. So first let us plot a count plot where you compare between the passengers who survived and who did not survive. So for that I'll be using the Seaborn library. So over here I have imported Seaborn as SNS. So I don't have to write the whole name. I'll simply say sns.countplot. I'll say X is who survived, and the data that I'll be using is the Titanic data. Or you can say the name of variable in which you have stored your data set. So now let me just run this. So over here, as you can see, I have survived column on my x-axis, and on the y-axis, I have the count. So 0 basically stands for did not survive, and 1 stands for the passengers who did survive. So over here, you can see that around 550 of the passengers who did not survive, and there were around 350 passengers who only survived. So here you can basically conclude that there are very less survivors than non-survivors. So this was the very first plot. Now let us plot another plot to compare the sex as to whether out of all the passengers who survived and who did not survive, how many were men and how many were female. So to do that, I'll simply say sns.countplot. I'll add the hue as sex. So I want to know how many females and how many males survived. Then I'll be specifying the data. So I'm using Titanic data set. And let me just run this. Okay, I've done a mistake over here. So over here you can see I have survived column on the x-axis and I have the count on the y. Now, so here your blue color stands for your male passengers and orange stands for your female. So as you can see here, the passengers who did not survive, that has a value 0. So we can see that majority of males did not survive. And if we see the people who survived, here we can see the majority of females survived. So this basically concludes the gender of the survival rate. So it appears on average women were more than 3 times more likely to survive than men. Next, let us plot another plot where we have the hue as the passenger class. So over here we can see which class that the passenger was traveling in, whether it was traveling in class 1, 2 or 3. So for that, I'll just write the same command. I'll say sns.countplot. I'll keep my x-axis as subject only. I'll change my hue to passenger class. So my variable is named as P class. And the data set that I'll be using is Titanic data. So this is my result. So over here you can see I have blue for first class, orange for second class, and green for the third class. So here the passengers who did not survive were majorly of the third class, or you can say the lowest class or the cheapest class to get into the Titanic. And the people who did survive majorly belong to the higher classes. So here 1 and 2 has more rise than the passenger who were traveling in the third class. So here we have concluded that the passengers who did not survive were majorly of third class, or you can say the lowest class. And the passengers who were traveling in first and second class would tend to survive more. Next, let us plot a graph for the age distribution. Over here, I can simply use my data. So I'll be using pandas library for this. I'll declare an array and I'll pass in the column that is age. So I plot and I want a histogram, so I'll say plot.hist. So you can notice over here that we have more of young passengers, or you can say the children between the ages 0 to 10. And then we have the average age people. And if you go ahead, lesser would be the population. So this is the analysis on the age column. So we saw that we have more young passengers and more mediocre age passengers which are traveling in the Titanic. So next, let me plot a graph for fare as well. So I'll say Titanic data. I'll say fare. And again, I'll plot a histogram. So I'll say hist. So here you can see the fare size is between 0 to 100. Now let me add the bin size so as to make it more clear. So over here I'll say bin is equals to, let's say, 20, and I'll increase the figure size as well. So I'll say fig size. Let's say I'll give the dimensions as 10 by 5. Okay, so it is bins. So this is more clear now. Next, let us analyze the other columns as well. So I'll just type in Titanic data, and I want the information as to what all columns are left. So here we have passenger ID, which I guess it's of no use. Then we have to see how many passengers survived and how many did not. We also see the analysis on the gender basis. We saw whether female tend to survive more or the men tend to survive more. Then we saw the passenger class, whether passenger is traveling in the first class, second class, or third class. Then we have the name. So in name we cannot do any analysis. We saw the sex, we saw the age as well. Then we have SIB-SP. So this stands for the number of siblings or the spouses which are aboard the Titanic. So let us do this as well. So I'll say sns.countplot. I'll mention x as SIB-SP, and I'll be using the Titanic data. So you can see the plot over here. So over here you can conclude that it has the maximum value on 0. So you can conclude that neither a children nor a spouse was on board the Titanic. Now second most highest value is 1. And then we have very less values for 2, 3, 4, and so on. Next, if I go above, we saw this column as well. Similarly, you can do for Parj. So next we have Parj, or you can say the number of parents or children which were aboard the Titanic. So similarly, you can do this as well. Then we have the ticket number. So I don't think so any analysis is required for ticket. Then we have fare. So fare we have already discussed. As in the people who tend to travel in the first class usually pay the highest fare. Then we have the cabin number and we have embarked. So these are the columns that we'll be doing data wrangling on. So we have analyzed the data and we have seen quite a few graphs in which we can conclude which variable is better than the another, or what is the relationship they hold. So third step is my data wrangling. So data wrangling basically means cleaning your data. So if you have a large data set, you might be having some null values, or you can say NaN values. So it's very important that you remove all the unnecessary items that are present in your data set. So removing this directly affects your accuracy. So I'll just go ahead and clean my data by removing all the NaN values and unnecessary columns which has a null value in the data set. So next I'll be performing data wrangling. So first of all, I'll check whether my data set is null or not. So I'll say Titanic data, which is the name of my data set, and I'll say is null. So this will basically tell me what all values are null and it will return me a Boolean result. So this basically checks the missing data and your result will be in Boolean format, as in the result will be true or false. So false means if it is not null and true means if it is null. So let me just run this. So over here you can see the values as false or true. So false is where the value is not null and true is where the value is null. So over here you can see in the cabin column we have the very first value which is null. So we have to do something on this. So you can see that we have a large data set, so the counting does not stop, and we can actually see the sum of it. We can actually print the number of passengers who have the NaN value in each column. So I'll say Titanic underscore data is null and I want the sum of it. So I'll say dot sum. So this will basically print the number of passengers who have the NaN values in each column. So we can see that we have missing values in each column, that is 177. Then we have the maximum value in the cabin column. And we have very less in the embarked column, that is 2. So here if you don't want to see these numbers, you can also plot a heat map and then you can visually analyze it. So let me just do that as well. So I'll say sns.heatmap. I'll say y tick labels to false. So I'll just run this. So as we have already seen that there were three columns in which missing data value was present. So this might be age. So over here, almost 20% of age column has a missing value. Then we have the cabin columns. So this is quite a large value. And then we have two values for embarked column as well. Add a CMAP for color coding. So I'll say CMAP. So if I do this, so the graph becomes more attractive. So over here, your yellow stands for true, or you can say the values are null. So here we have concluded that we have the missing value of age, we have a lot of missing values in the cabin column, and we have very less value which is not even visible in the embarked column as well. So to remove these missing values, you can either replace the values and you can put in some dummy values to it, or you can simply drop the column. So here let us first pick the age column. So first let me just plot a box plot and they will analyze with having a column as age. So I'll say sns dot box plot. I'll say x is equals to passenger class. So it's P class. I'll say y is equals to age. And the data set that I'll be using is Titanic set. So I'll say data is equals to Titanic data. You can see the age in first class and second class tends to be more older rather than we have it in the third class. Well, that depends on the experience, how much you earn, or might be there n number of reasons. So here we concluded that passengers who were traveling in class 1 and class 2 are tend to be older than what we have in the class 3. So we have found that we have some missing values in M. Now one way is to either just drop the column or you can just simply fill in some values to that. So this method is called as imputation. Now to perform data wrangling or cleaning, let us first print the head of the data set. So I'll say Titanic.head, sorry, it's Titanic underscore data. Let's say I just want the 5 rows. So here we have survive, which is again categorical. So in this particular column, I can apply logistic regression. So this can be my Y value or the value that I need to predict. Then we have the passenger class, we have the name, then we have ticket number, fare, cabin. So over here we have seen that in cabin we have a lot of null values, or you can say the NaN values, which is quite visible as well. So first of all, we'll just drop this column. So for dropping it, I'll just say Titanic underscore data, and I'll simply type in drop and the column which I need to drop. So I have to drop the cabin column. I'll mention the axis equals to 1 and I'll say in place also to true. So now again I'll just print the head and let us see whether this column has been removed from the data set or not. So I'll say Titanic dot head. So as you can see here, we don't have cabin column anymore. Now you can also drop the NA values. So I'll say Titanic data dot drop all the NA values, or you can say NaN, which is not a number. And I'll say in place is equals to true. It's Titanic. So over here, let me again plot the heat map and let's say or the values which were before showing a lot of null values, has it been removed or not. So I'll say sns.heatmap, I'll pass in the data set. I'll check it is null. I'll say y tick labels is equals to false. And I don't want color coding, so again I'll say false. So this will basically help me to check whether my values has been removed from the data set or not. So as you can see here, I don't have any null values. So it's entirely black. Now you can actually know the sum as well. So I'll just go above. So I'll just copy this part and I'll just use the sum function to calculate the sum. So here that tells me that data set is clean, as in the data set does not contain any null value or any NaN value. So now we have wrangled our data, you can say clean our data. So here we have done just one step in data wrangling, that is just removing one column out of it. Now you can do a lot of things. You can actually fill in the values with some other values, or you can just calculate the mean and then you can just fit in the null values. But now if I see my data set, so I'll say Titanic data dot head. But now if I see over here, I have a lot of string values. So this has to be converted to categorical variables in order to implement logistic regression. So what we will do, we will convert this to categorical variable into some dummy variables. And this can be done using pandas, because logistic regression just take two values. So whenever you apply machine learning, you need to make sure that there are no string values present, because it won't be taking these as your input variables. So using string, you don't have to predict anything. But in my case, I have the survived columns. So I need to predict how many people tend to survive and how many did not. So 0 stands for did not survive and 1 stands for survive. So now let me just convert these variables into dummy variables. So I'll just use pandas and I'll say pd.getDummies. You can simply press tab to autocomplete. I'll say Titanic data, and I'll pass the sex. So you can just simply click on Shift plus Tab to get more information on this. So here we have the type data frame and we have the passenger ID survived and the passenger class. So if you run this, you'll see that 0 basically stands for not a female and 1 stands for it is a female. Similarly for male, 0 stands for it's not male and 1 stands for male. Now we don't require both these columns because one column itself is enough to tell us whether it's male or you can say female or not. So let's say if I want to keep only male, now I'll say if the value of male is 1, so it is definitely a male and it is not a female. So that is how you don't need both of these values. So for that, I'll just remove the first column, let's say female. So I'll say drop first and true. So over here it has given me just one column which is male and has the value 0 and 1. Now let me just set this as a variable, let's say sex. So over here I can say sex dot head. I just want to see the first 5 rows. Oh, sorry, it's dot. So this is how my data looks like. Now here we have done it for sex. Then we have the numerical values in age. We have the numerical values in spouses. Then we have the ticket number. We have the fare and we have embarked as well. So in embarked, the values are in S, C and Q. So here also we can apply this get dummy function. So let's say I'll take a variable, let's say embark. I'll use the pandas library. I'll enter the column name that is embarked. So let me just print the head of it. So I'll say embark.head. So over here we have C, Q and S. Now here also we can drop the first column because these two values are enough whether the passenger is either traveling for Q that is Queenstown, S for Southampton, and if both the values are 0 then definitely the passenger is from Cherbourg, that is the third value. So you can again drop the first value. So I'll say drop and true. Let me just run this. So this is how my output looks like. Now similarly you can do it for passenger class as well. So here also we have three classes 1, 2 and 3. So I'll just copy the whole statement. So let's say I want the variable name, let's say PCL. I'll pass in the column name that is P class and I'll just drop the first column. So here also the values would be 1, 2 or 3 and I'll just remove the first column. So here we just left with 2 and 3. So if both the values are 0, then definitely the passenger is traveling in the first class. Now we have made the values as categorical. Now my next step would be to concatenate all these new rows into a data set. Or you can say Titanic data. Using the pandas, we'll just concatenate all these columns. So I'll say p.concat and I'll say we have to concatenate sex, we have to concatenate embark and PCL. And then I'll mention the access to 1. I'll just run this. Okay, I need to print the head. So over here you can see that these columns have been added over here. So we have the male column which basically tells whether a person is male or it's a female. Then we have the embarked which is basically Q and S. So if it's traveling from Queenstown, the value would be 1, else it would be 0. And if both of these values are 0, it is definitely traveling from Cherbourg. Then we have the passenger class as 2 and 3. So if the value of both these is 0, then the passenger is traveling in class 1. So I hope you got this till now. Now these are the irrelevant columns that we have it over here. So we can just drop these columns. We'll dropping P class, the embarked column, and the sex column. So I'll just type in Titanic data dot drop and I'll mention the columns that I want to drop. So I'll say I'll even delete the passenger ID because it's nothing but just the index value which is starting from 1. So I'll drop this as well. Then I don't want name as well, so I'll delete name as well. Then what else we can drop? We can drop the ticket as well. And then I'll just mention the access and I'll say in place is equals to true. Okay, so my column name starts from uppercase. So these has been dropped. Now let me just print my data set again. So this is my final data set, guys. We have the survived column which has the value 0 and 1. Then we have the passenger class. Oh, we forgot to drop this as well. So no worries, I'll drop this again. So now let me just run this. So over here we have the survive, we have the age, we have the SIB SP, we have the parch, we have fair, male, and these we have just converted. So here we have just performed data wrangling, or you can say clean the data, and then we have just converted the values of gender to male, then embarked to Q and S, and the passenger class to 2 and 3. So this was all about my data wrangling or just cleaning the data. Then my next step is training and testing your data. So here we will split the dataset into train subset and test subset. And then what we'll do, we'll build a model on the train data and then predict the output on your test dataset. So let me just go back to Jupyter and let us implement this as well. Over here, I need to train my dataset. So I'll just put this in heading 3. So over here, you need to define your dependent variable and independent variable. So here, my y is the output, or you can say the value that I need to predict. So over here, I'll write Titanic data. I'll take the column which is survived. So basically, I have to predict this column whether the passenger survived or not. And as you can see, we have the discrete outcome, which is in the form of 0 and 1. And rest all the things, we can take it as a features or you can say independent variable. So I'll say Titanic data dot drop. So we'll just simply drop this survived and all the other columns will be my independent variable. So everything else are the features which leads to the survival rate. So once we have defined the independent variable and the dependent variable, next step is to split your data into training and testing subset. So for that, we'll be using sklearn. I just type in from sklearn.cross validation, import train test split. Now here, if you just click on shift and tab, you can go to the documentation and you can just see the examples over here. I'll click on plus to open it. And then I just go to examples and see how you can split your data. So over here you have xtrain, xtest, ytrain, ytest. And then using this train test split, you can just pass in your independent variable and dependent variable and just define a size and a random state to it. So let me just copy this and I'll just paste it over here. Over here we'll train, test, then we have the dependent variable train and test, and using the split function we'll pass in the independent and dependent variable, and then we'll set a split size. So let's say I'll put it at 0.3. So this basically means that your data set is divided in 0.3, that is in 70-30 ratio, and then I can add any random state to it. So let's say I'm applying 1. This is not necessary. If you want the same result as that of mine, you can add the random state. So this will basically take exactly the same sample every time. Next, I have to train and predict by creating a model. So here logistic regression will grab from the linear regression. So next I'll just type in from sklearn.linear model, import logistic regression. Next I'll just create the instance of this logistic regression model. So I'll say log model is equals to logistic regression. Now I just need to fit my model, so I'll say log model dot fit and I'll just pass in my x train and y train. Alright, so here it gives me all the details of logistic regression. So here it gives me the class weight, dual, fit, intercept and all those things. Then what I need to do, I need to make prediction. So I'll take a variable, let's say predictions, and I'll pass on the model to it. So I'll say log model dot predict and I'll pass in the value that is x test. So here we have just created a model, fit that model, and then we had made predictions. So now to evaluate how my model has been performing, so you can simply calculate the accuracy or you can also calculate a classification report. So don't worry guys, I'll be showing both of these methods. So I'll say from sklearn.metrics, import classification report. So over here I'll use classification report and inside this I'll be passing in y test and the predictions. So guys, this is my classification report. So over here I have the precision, I have the recall, we have the F1 score, and then we have support. So here we have the value of precision as 75, 72 and 73, which is not that bad. Now in order to calculate the accuracy as well, you can also use the concept of confusion matrix. So if you want to print the confusion matrix, I'll simply say from sklearn.metrics, import confusion matrix first of all, and then we'll just print this. So here my function has been imported successfully. So I'll say confusion matrix and I'll again pass in the same variables, which is y test and predictions. So I hope you guys already know the concept of confusion matrix. So I'll just tell you in a brief what confusion matrix is all about. So confusion matrix is nothing but a 2 by 2 matrix which has 4 outcomes. This basically tells us that how accurate your values are. So here we have the column as predicted no, predicted y, and we have actual no and an actual yes. So this is the concept of confusion matrix. So here let me just feed in these values which we have just calculated. So here we have 105, 105, 21, 25 and 63. So as you can see here, we have got four outcomes. Now 105 is the value where our model has predicted no, and in reality it was also a no. So here we have predicted no and an actual no. Similarly, we have 63 as a predicted yes. So here the model predicted yes, and actually also it was a yes. So in order to calculate the accuracy, you just need to add the sum of these two values and just divide the whole by the sum. So here these two values tells me where the model has actually predicted the correct output. So this value is also called as true negative. This is called as false positive. This is called as true positive, and this is called as false negative. Now in order to calculate the accuracy, you don't have to do it manually. So in Python, you can just import accuracy score function and you can get the results from that. So I'll just do that as well. So I'll say from sklearn.metrics import accuracy score, and I'll simply print the accuracy. And I'll pass in the same variables, that is y-test and predictions. So over here it tells me the accuracy as 78, which is quite good. So over here, if you want to do it manually, you have to plus these two numbers, which is 105 plus 63. So this comes out to almost 168. And then you have to divide it by the sum of all the four numbers. So 105 plus 63 plus 21 plus 25. So this gives me a result of 214. So now if you divide these two numbers, you'll get the same accuracy, that is 78%, or you can say 0.78. So that is how you can calculate the accuracy. So now let me just go back to my presentation and let's see what all we have covered till now. So here we have first split our data into train and test subset. Then we have built our model on the train data and then predicted the output on the test data set. And then my fifth step is to check the accuracy. So here we have calculated accuracy to almost 78%, which is quite good. You cannot say that accuracy is bad. So here it tells me how accurate your results are. So here my accuracy score defines that, and hence we got a good accuracy. So now moving ahead, let us see the second project, that is SUV data analysis. So in this, a car company has released new SUV in the market. And using the previous data about the sales of their SUV, they want to predict the category of people who might be interested in buying this. So using the logistic regression, you need to find what factors made people more interested in buying this SUV. So for this, let us see a data set where I have user ID, I have gender as male and female, then we have the age, we have the estimated salary, and then we have the purchased column. So this is my discrete column, or you can say the categorical column. So here we just have the value, that is 0 and 1. And this column we need to predict whether a person can actually purchase a SUV or not. So based on these factors, we will be deciding whether a person can actually purchase a SUV or not. So we know the salary of a person, we know the age. And using these, we can predict whether a person can actually purchase a SUV or not. So let me just go to my Jupyter notebook and let us implement logistic regression. So guys, I will not be going through all the details of data cleaning and analyzing the part. So that part, I'll just leave it on you. So just go ahead and practice as much as you can. Alright. So my second project is SUV predictions. Alright. So first of all, I have to import all the libraries. So I say import numpy as np. And similarly, I'll do the rest of it. Alright. So now let me just print the head of this data set. So this we've already seen that we have columns as user ID, we have gender, we have the age, we have the salary, and then we have to calculate whether the person can actually purchase a SUV or not. So now let us just simply go on to the algorithm part. So we'll directly start off with the logistic regression, or how you can train a model. So for doing all those things, we first need to define your independent variable and a dependent variable. So in this case, I want my x, that is an independent variable. I say dataset.iloc. So here I'll be specifying all the rows. So colon basically stands for that. And in the columns, I want only 2 and 3 dot values. So here it should fetch me all the rows and only the second and third column, which is age and estimated salary. So these are the factors which will be used to predict the dependent variable, that is purchase. So here my dependent variable is purchase. And the dependent variable is of age and salary. So I'll say dataset.iloc. I'll have all the rows and I just want fourth column, that is my purchased column dot values. Alright, so I've just forgot one square bracket over here. Alright. So over here I have defined my independent variable and dependent variable. So here my independent variable is age and salary, and dependent variable is the column purchase. Now you must be wondering, what is this ilog function? So ilog function is basically an indexer for pandas data frame, and it is used for integer based indexing, or you can also say selection by index. Now let me just print these independent variables and dependent variable. So if I print the independent variable, I have the age as well as the salary. Next, let me print the dependent variable as well. So over here, you can see I just have the values in 0 and 1. So 0 stands for did not purchase. Next, let me just divide my dataset into training and test subset. So I'll simply write in from sklearn.crosssplit.crossvalidation import train test. Next, I'll just press shift and tab. And over here, I'll go to the examples and just copy the same line. So I'll just copy this. I'll remove the points. Now I want the text size to be, let's say, 25. So I have divided the train and test split in 75-25 ratio. Now let's say I'll take the random state as 0. So random state basically ensures the same result. Or you can say the same samples taken whenever you run the code. So let me just run this. Now you can also scale your input values for better performing. And this can be done using standard scaler. So let me do that as well. So I'll say from sklearn.preprocessing import standard scaler. Now, why do we scale it? Now, if you see our data set, we are dealing with large numbers. Well, although we are using a very small data set, so whenever you're working in a prod environment, you'll be working with large data set where you'll be using thousands and hundred thousands of tuples. So their scaling down will definitely affect the performance by a large extent. So here, let me just show you how you can scale down these input values. And then the pre-processing contains all your methods and functionality which is required to transform your data. So now let us scale down for test as well as a training data set. So I'll first make an instance of it. So I'll say standard scaler. Then I'll have xtrain. I'll say sc.fit, fit underscore transform. And I'll pass in my xtrain variable. And similarly, I can do it for test, wherein I'll pass the xtest. Alright. Now my next step is to import logistic regression. So I'll simply apply logistic regression by first importing it. So I'll say from sklearn.linear model import logistic regression. Now over here I'll be using classifier. So I'll say classifier dot is equals to logistic regression. So over here I'll just make an instance of it. So I'll say logistic regression. And over here I'll just pass in the random state which is 0. And now I'll simply fit the model. And I simply pass in xtrain and ytrain. So here it tells me all the details of logistic regression. Then I have to predict the value. So I'll say ypred is equals to classifier, then predict function, and then I just pass in xtest. So now we have created the model, we have scaled down our input values, then we have applied logistic regression, we have predicted the values, and now we want to know the accuracy. So to know the accuracy, first we need to import accuracy score. So I'll say from sklearn.metrics import accuracy score, and using this function we can calculate the accuracy, or you can manually do that by creating a confusion matrix. So I'll just pass in my y test and my y predicted. Alright, so over here I get the accuracy as 89%. So if we want to know the accuracy in percentage, so I just have to multiply it by 100, and if I run this, so it gives me 89%. So I hope you guys are clear with whatever I have taught you today. So here I have taken my independent variables as age and salary, and then we have calculated that how many people can purchase the SUV. And then we have calculated our model by checking the accuracy. So over here we get the accuracy as 89, which is great. Alright guys, so that is it for today. So I'll just discuss what all we have covered in today's training. So first of all, we had a quick introduction to what is regression and where regression is actually used. Then we have understood the types of regression and then got into the details of what and why of logistic regression. We have compared linear versus logistic regression. We have also seen the various use cases where you can implement logistic regression in real life. And then we have picked up two projects, that is Titanic data analysis and SUV prediction. So over here we have seen how you can collect your data, analyze your data, then perform modeling on that data, train the data, test the data, and then finally you have calculated the accuracy. So in your SUV prediction, you can actually analyze, clean your data, and you can do a lot of things. So you can just go ahead, pick up any data set and explore it as much as you can.
Open your eyes and see around. You will find dozens of applications of machine learning which you are using and interacting with in your daily life, be it using the face detection algorithm in Facebook or getting the recommendation for similar products from Amazon. Machine learning is applied almost everywhere. So hello and welcome all to this YouTube session. We'll learn about how to build a decision tree. This session is designed in a way that you get most out of it. Alright, so this decision tree is a type of classification algorithm which comes under the supervised learning technique. So before learning about decision tree, I'll give you a short introduction to classification, where we'll learn about what is classification, what are its various types, where it is used or what are its use cases. Now once you get your fundamental clear, we'll jump to the decision tree part. Under this, first of all, I'll teach you to mathematically create a decision tree from scratch. Then once you get your concepts clear, we'll see how you can write a decision tree classifier from scratch in Python using the CART algorithm. Alright, I hope the agenda is clear to you guys. What is classification? I hope every one of you must have used Gmail. So how do you think the mail is getting classified as a spam or not a spam mail? Well, there's nothing but classification. So what it is? Well, classification is the process of dividing the data set into different categories or groups by adding label. In other way, you can say that it is a technique of categorizing the observation into different category. So basically what you're doing is you're taking the data, analyzing it, and on the basis of some condition, you finally divide it into various categories. Now, why do we classify it? Well, we classify it to perform predictive analysis on it. Like when you get the mail, the machine predicts it to be a spam or not a spam mail. And on the basis of that prediction, it adds the irrelevant or spam mail to the respective folder. In general, this classification algorithm handled questions like, is this data belongs to A category or a B category? Like, is this a male or is this a female? Something like that. Now the question arises, where will you use it? Well, you can use this for fraud detection or to check whether the transaction is genuine or not. Suppose I'm using a credit card here in India. Now, due to some reason, I had to fly to Dubai. Now, if I'm using the credit card over there, I'll get a notification alert regarding my transaction. They would ask me to confirm about the transaction. So this is also kind of predictive analysis, as the machine predicts that something fishy is in the transaction, as 24 hours ago, I made the transaction using the same credit card in India, and 24 hours later, the same credit card is being used for the payment in Dubai. So the machine predicts that something fishy is going on in the transaction. So in order to confirm it, it sends you a notification alert. Alright, well, this is one of the use case of classification. You can even use it to classify different items like fruits on the basis of its taste, color, size, or weight. A machine well trained using the classification algorithm can easily predict the class or the type of fruit whenever new data is given to it. Not just the fruit, it can be any item. It can be a car, it can be a house, it can be a signboard, or anything. Have you noticed that while you visit some sites or you try to log in into some, you get a picture capture for that, right? Where you have to identify whether the given image is of a car or it's of a pole or not. You have to select it. For example, there are 10 images and you're selecting 3 images out of it. So in a way, you're training the machine, right? You're telling that these 3 are the picture of a car and rest are not. So who knows, you're training it for something big, right? So moving on ahead, let's discuss the types of classification. Alright. Well, there are several different ways to perform a same task. Like in order to predict whether a given person is a male or a female, the machine had to be trained first. Alright. But there are multiple ways to train the machine, and you can choose any one of them. Just for predictive analytics, there are many different techniques, but the most common of them all is the decision tree, which we'll cover in depth in today's session. So as a part of classification algorithm, we have decision tree, random forest, naive Bayes, k nearest neighbor, logistic regression, linear regression, support vector machines, and so on. There are many. Alright, so let me give you an idea about few of them. Starting with decision tree. Well, decision tree is a graphical representation of all the possible solution to a decision. The decisions which are made, they can be explained very easily. For example, here is a task which says that should I go to a restaurant or should I buy a hamburger? You are confused on that. So for that, what you'll do, you'll create a decision tree for it. Starting with the root node will be, first of all, you'll check whether you are hungry or not. Alright. If you're not hungry, then just go back to sleep. Right. If you are hungry and you have $25, then you'll decide to go to restaurant. And if you're hungry and you don't have $25, then you'll just go and buy a hamburger. That's it. Alright. So this is about decision tree. Now moving on ahead, let's see what is a random forest. Well, random forests build multiple decision trees and merges them together to get a more accurate and stable prediction. Alright, most of the time, random forest is trained with a bagging method. The bagging method is based on the idea that the combination of learning model increases the overall result. If you're combining the learning from different models and then clubbing it together, what it will do, it will increase the overall result. Fine. Just one more thing. If the size of your data set is huge, then in that case, one single decision tree would lead to a overfit model. Same way, like a single person might have its own perspective on the complete population, as the population is very huge, right? However, if we implement the voting system and ask different individual to interpret the data, then we would be able to cover the pattern in a much meticulous way. Even from the diagram, you can see that in section A, we have a large training data set. What we do, we first divide our training data set into n subsamples, alright, and we create a decision tree for each subsample. Now in the B part, what we do, we take the vote out of every decision made by every decision tree. And finally, we club the vote to get the random forest decision. Fine. Let's move on ahead. Next, we have naive Bayes. So naive Bayes is a classification technique which is based on Bayes' theorem. It assumes that presence of any particular feature in a class is completely unrelated to the presence of any other feature. Naive Bayes is simple and easy to implement algorithm. And due to its simplicity, this algorithm might outperform more complex model when the size of the dataset is not large enough. Alright, a classical use case of naive Bayes is a document classification. In that, what you do, you determine whether given text corresponds to one or more categories. In the text case, the features used might be the presence or absence of any keyword. So this was about naive. From the diagram, you can see that using naive Bayes, we have to decide whether we have a disease or not. First, what we do, we check the probability of having a disease and not having the disease, right? Probability of having a disease is 0.1, while on the other hand, probability of not having a disease is 0.9. Okay, first let's see when we have disease and we go to doctor, all right? So when we visited the doctor and the test is positive, so probability of having a positive test when you're having a disease is 0.80, and probability of a negative test when you already have a disease, that is 0.20. This is also a false negative statement as the test is detecting negative, but you still have the disease, right? So it's a false negative statement. Now let's move ahead when you don't have the disease at all. So probability of not having a disease is 0.9. And when you visit the doctor and the doctor is like, yes, you have the disease, but you already know that you don't have the disease. So it's a false positive statement. So probability of having a disease when you actually know there is no disease is 0.1. And probability of not having a disease when you actually know there is no disease. So, and the probability of it is around 0.90. Fine. It is same as probability of not having a disease. Even the test is showing the same result. It's a true positive statement. So it is 0.9. Alright. So let's move on ahead and discuss about KNN algorithm. So this KNN algorithm, or the K nearest neighbor, it stores all the available cases and classifies new cases based on the similarity measure. The K in the KNN algorithm is the nearest neighbor we wish to take vote from. For example, if k equal 1, then the object is simply assigned to the class of that single nearest neighbor. From the diagram, you can see the difference in the image when k equal 1, k equal 3, and k equal 5, right? Well, the modern systems are now able to use the k nearest neighbor for visual pattern recognition to scan and detect hidden packages in the bottom bin of a shopping cart at the checkout. If an object is detected which matches exactly to the object listed in the database, then the price of the spotted product could even automatically be added to the customer's bill. While this automated billing practice is not used extensively at this time, but the technology has been developed and is available for use. If you want, you can just use it. And yeah, one more thing. K nearest neighbor is also used in retail to detect patterns in the credit card users. Many new transaction scrutinizing software applications use KNN algorithms to analyze register data and spot unusual pattern that indicate suspicious activity. For example, if register data indicates that a lot of customers' information is being entered manually rather than through automated scanning and swapping, then in that case, this could indicate that the employees who are using the register are in fact stealing customers' personal information, or if a registered data indicates that a particular good is being returned or exchanged multiple times, this could indicate that employees are misusing the return policy or trying to make money from doing the fake returns. Right. So this was about KNN algorithm. Since our main focus for this session will be on decision tree, so starting with what is decision tree? But first let me tell you, why did we choose decision tree to start with? Well, these decision tree are really very easy to read and understand. It belongs to one of the few models that are interpretable, where you can understand exactly why the classifier has made that particular decision. Right. Let me tell you a fact that for a given data set, you cannot say that this algorithm performs better than that. It's like you cannot say that decision tree is better than naive Bayes or naive Bayes is performing better than decision tree. It depends on the data set, right? You have to apply hit and trial method with all the algorithms one by one and then compare the result. The model which gives the best result is the model which you can use it for better accuracy for your data set. Alright? So let's start with what is decision tree. Well, a decision tree is a graphical representation of all the possible solutions to a decision based on certain conditions. Now you might be wondering why this thing is called as decision tree. Well, it is called so because it starts with a root and then branches off to a number of solutions just like a tree, right? Even the tree starts from a root and it starts growing its branches once it gets bigger and bigger. Similarly, in a decision tree, it has a root which keeps on growing with increasing number of decisions and the conditions. Now let me tell you a real life scenario. I won't say that all of you, but most of you must have used it. Remember, whenever you dial the toll-free number of your credit card company, it redirects you to his intelligent computerized assistant, where it asks you questions like press 1 for English, or press 2 for Hindi, press 3 for this, press 4 for that, right? Now, once you select one, now again it redirects you to a certain set of questions like press 1 for this, press 1 for that, and similarly, right? So this keeps on repeating until you finally get to the right person, right? You might think that you are caught in a voicemail hell, but what the company was actually doing, it was just using a decision tree to get you to the right person. Alright, I'd like you to focus on this particular image for a moment. On this particular slide, you can see an image where the task is, should I accept a new job offer or not? Alright, so you have to decide that. For that, what you did, you created a decision tree. Starting with the base condition or the root node was that the basic salary or the minimum salary should be $50,000. If it is not $50,000, then you are not at all accepting the offer. Alright. So if your salary is greater than $50,000, then you will further check whether the commute is more than 1 hour or not. If it is more than 1 hour, you will just decline the offer. If it is less than 1 hour, then you are getting closer to accepting the job offer. Then further, what you'll do, you'll check whether the company is offering free coffee or not, right? If the company is not offering the free coffee, then you'll just decline the offer. And if it is offering the free coffee, then yeah, you will happily accept the offer, right? So this is just an example of a decision tree. Now let's move ahead and understand a decision tree. Well, here is a sample data set that I'll be using it to explain you about the decision tree. Alright. In this data set, each row is an example, and the first two columns provide features or attributes that describes the data, and the last column gives the label or the class we want to predict. And if you like, you can just modify this data by adding additional features and more example, and our program will work in exactly the same way. Fine. Now this data set is pretty straightforward except for one thing. I hope you have noticed that it is not perfectly separable. Let me tell you something more about that. As in the second and fifth examples, they have the same features but different labels. Both have yellow as their color and diameter as 3, but the labels are mango and lemon. Fine. Let's move on and see how our decision tree handles this case. Alright. In order to build a tree, we'll use a decision tree algorithm called CART. The SCART algorithm stands for Classification and Regression Tree Algorithm. Alright. Let's see a preview of how it works. Alright. To begin with, we'll add a root node for the tree. And all the nodes receive a list of rows as input. And the root will receive the entire training data set. Now each node will ask true and false question about one of the feature, and in response to that question, we'll split or partition the dataset into two different subsets. These subsets then become input to two child nodes we add to the tree, and the goal of the question is to finally unmix the labels as we proceed down, or in other words, to produce the purest possible distribution of the labels at each node. For example, the input of this node contains only one single type of label. So we could say that it's perfectly unmixed. There is no uncertainty about the type of label, as it consists of only grapes, right? On the other hand, the labels in this node are still mixed up. So we would ask another question to further drill it down, right? But before that, we need to understand which question to ask and when. And to do that, we need to quantify how much question helps to unmix the label. And we can quantify the amount of uncertainty at a single node using a metric called Gini impurity. And we can quantify how much a question reduces that uncertainty using a concept called information gain. We'll use these to select the best question to ask at each point. And then what we'll do, we'll iterate the steps, we'll recursively build the tree on each of the new node. We'll continue dividing the data until there are no further questions to ask. And finally, we reach to our leaf. Alright. Alright, so this was about decision tree. So in order to create a decision tree, first of all, what you have to do, you have to identify different set of questions that you can ask to a tree. Like, is this color green? And what will be these questions? These questions will be decided by your data set. Like, is this color green? Is the diameter greater than or equal to 3? Is the color yellow? Right. Questions resembles to your data set. Remember that. All right. So if my color is green, then what it will do, it will divide into two parts. First, the green mango will be in the true, while on the false, we have lemon and the mango. All right. If the color is green or the diameter is greater than or equal to 3 or the color is yellow. Decision tree terminologies. So starting with root node. Root node is the base node of a tree. The entire tree starts from a root node. In other words, it is the first node of a tree. It represents the entire population or sample, and this entire population is further segregated or divided into two or more homogeneous sets. Fine. Next is the leaf node. Well, leaf node is the one when you reach at the end of the tree, right? That is, you cannot further segregate it down to any other level. So that is the leaf node. Next is splitting. Splitting is dividing your root node or your node into different subpart on the basis of some condition. All right. Then comes the branch or the subtree. Well, this branch or subtree gets formed when you split the tree. Suppose when you split a root node, it gets divided into two branches or two subtrees, right? Next is the concept of pruning. Well, you can say that pruning is just opposite of splitting. What we are doing here, we are just removing the subnode of a decision tree. We'll see more about pruning later in this session. All right, let's move on ahead. Next is parent or child node. Well, first of all, root node is always the parent node, and all other nodes associated with that is known as child node. Well, you can understand it in a way that all the top node belongs to a parent node, and all the bottom node which are derived from a top node is a child node. The node producing a further node is a child node, and the node which is producing it is a parent node. Simple concept, right? Let's use the cart algorithm and design a tree manually. So first of all, what do you do? You decide which question to ask and when. So how will you do that? So let's first of all visualize the decision tree. So this is the decision tree which we'll be creating manually. All right. First of all, let's have a look at the data set. You have outlook, temperature, humidity, and windy as your different attributes. On the basis of that, you have to predict that whether you can play or not. So which one among them should you pick first? Answer: determine the best attribute that classifies the training data. All right. So how will you choose the best attribute, or how does a tree decide where to split, or how the tree will decide its root node? Well, before we move on and split a tree, there are some terminologies that you should know. All right. First being the Gini index. So what is this Gini index? This Gini index is the measure of impurity or purity used in building a decision tree in cart algorithm. All right. Next is information gain. This information gain is the decrease in entropy after a data set is split on the basis of an attribute. Constructing a decision tree is all about finding an attribute that returns the highest information gain. Alright, so you'll be selecting the node that would give you the highest information gain. Alright. Next is reduction in variance. This reduction in variance is an algorithm which is used for continuous target variable or regression problems. The split with lower variance is selected as a criteria to split the population. See, in general term, what do you mean by variance? Variance is how much your data is varying, right? So if your data is less impure or it is more pure, then in that case, the variation would be less as all the data are almost similar, right? So this is also a way of splitting a tree. The split with lower variance is selected as a criteria to split the population, all right? Next is the chi-square. chi-square, it is an algorithm which is used to find out the statistical significance between the differences between subnodes and the parent nodes. Fine, let's move ahead. Now the main question is, how will you decide the best attribute? For now, just understand that you need to calculate something known as information gain. The attribute with the highest information gain is considered the best. Yeah, I know your next question might be like, what is this information gain? But before we move on and see what exactly information gain is, let me first introduce you to a term called entropy, because this term will be used in calculating the information gain. Well, entropy is just a metric which measures the impurity of something, or in other words, you can say that it's the first step to do before you solve the problem of a decision tree. As I mentioned here something about impurity, so let's move on and understand what is impurity. Suppose you have a basket full of apples and another bowl which is full of same label which says apple. Now if you are asked to pick one item from each basket and bowl, then the probability of getting the apple and its correct label is 1. So in this case, you can say that impurity is 0. Alright. Now what if there are 4 different fruits in the basket and 4 different labels in the bowl? Then the probability of matching the fruit to a label is obviously not 1. It's something less than that. Well, it could be possible that I picked banana from the basket, and when I randomly pick the label from the ball, it says a cherry. Any random permutation and combination can be possible. So in this case, I would say that impurities is non-zero. I hope the concept of impurity is clear. So coming back to entropy, as I said, entropy is the measure of impurity. From the graph on your left, you can see that as the probability is 0 or 1, that is either they are highly impure or they are highly pure, then in that case the value of entropy is 0. And when the probability is 0.5, then the value of entropy is maximum. Well, what is impurity? Impurity is the degree of randomness, how random a data is. So if the data is completely pure, in that case the randomness equals 0. Or if the data is completely impure, even in that case the value of impurity will be 0. Question like, why is it that the value of entropy is maximum at 0.5 might arise in your mind, right? So let me discuss about that. Let me derive it mathematically. So as you can see here on the slide, the mathematical formula of entropy is minus of probability of yes. Let's move on and see what this graph has to say mathematically. Suppose S is our total sample space and it's divided into 2 parts, yes and no. Like in our data set, the result for playing was divided into 2 parts, either yes or no, which we have to predict either we have to play or not, right? So for that particular case, you can define the formula of entropy as entropy of total sample space equals negative of probability of yes multiplied by log of probability of yes with a base 2 minus probability of no multiplied by log of probability of no with base 2, where S is your total sample space and P of yes is the probability of yes and P of no is the probability of no. Well, if the number of yes equal number of no, that is probability of S equals 0.5, right? Since you have equal number of yes and no. So in that case, value of entropy will be 1. Just put the value over there. All right. Let me just move to the next slide. I'll show you this. All right. Next is if it contains all yes or all no, that is probability of a sample space is either 1 or 0. Then in that case, entropy will be equal to 0. Let's see it mathematically one by one. So let's start with the first condition where the probability was 0.5. So this is our formula for entropy, right? So this is our first case, right, which we discussed that when the probability of yes equal probability of no, that is in our data set, we have equal number of yes and no. All right. So probability of yes equal probability of no, and that equals 0.5. Or in other words, you can say that yes plus no equal to total sample space. All right. Since the probability is 0.5, so when you put the values in the formula, you get something like this. And when you calculate it, you'll get the entropy of the total sample space as 1. All right. Let's see for the next case. What was the next case? Either you have total yes or you have total no. So if you have total yes, let's see the formula when we have total yes. So you have all yes and 0 no. Fine. So probability of yes equal 1. And yes is the total sample space, obviously. So in the formula, when you put that thing up, you will get entropy of sample space equal negative times of 1 multiplied by log of 1. As the value of log 1 equals 0, so the total thing will result to 0. Similarly is the case with no. Even in that case, you'll get the entropy of total sample space as 0. So this was all about entropy. All right. Next is What is information gain? Well, information gain, what it does, it measures the reduction in entropy. It decides which attribute should be selected as the decision node. If S is our total collection, then information gain equals entropy, which we calculated just now, that minus weighted average multiplied by entropy of each feature. Don't worry, we'll just see how to calculate it with an example. Let's manually build a decision tree for our dataset. So this is our dataset, which consists of 14 different instances, out of which we have 9 yes and 5 no. Alright. So we have the formula for entropy, just put over that. Since 9 yes, so total probability of yes equals 9 by 14 and total probability of no equals 5 by 14. And when you put up the value and calculate the result, you will get the value of entropy as 0.94. Alright, so this was your first step, that is compute the entropy for the entire data set. Alright. Now you have to select that out of outlook, temperature, humidity, and windy, which of the node should you select as the root node? Big question, right? How will you decide that this particular node should be chosen as the base node? And on the basis of that only, I'll be creating the entire tree. How you'll select that? Let's see. So you have to do it one by one. You have to calculate the entropy and information gain for all of the different nodes. So starting with outlook. So outlook has three different parameters: sunny, overcast, and rainy. So first of all, select how many number of yes and no are there in the case of sunny. Like when it is sunny, how many number of yes and how many number of no's are there. So in total, we have 2 yes and 3 no's in case of sunny. In case of overcast, we have all yes. So if it is overcast, then we'll surely go to play. It's like that. All right. And next it is rainy. Then total number of yes equal 3 and total number of no equals 2. Fine. Next, what we do, we calculate the entropy for each feature. For here, we are calculating the entropy when outlook equals sunny. First of all, we are assuming that outlook is our root node, and for that, we are calculating the information gain for it. All right. So in order to calculate the information gain, remember the formula. It was entropy of the total sample space minus weighted average multiplied by entropy of each feature. All right. So what we are doing here, we are calculating the entropy of outlook when it was sunny. So total number of yes when it was sunny was 2 and total number of no, that was 3. Fine. So let's put up in the formula. Since the probability of yes is 2 by 5 and the probability of no is 3 by 5, so you will get something like this. All right. So you are getting the entropy of sunny as 0.971. Fine. Next, you'll calculate the entropy for overcast. When it was overcast, remember it was all yes, right? So the probability of yes equal 1. And when you put over that, you'll get the value of entropy as 0. Fine. And when it was rainy, rainy has 3 yes and 2 no's. So probability of yes in case of sunny is 3 by 5 and probability of no in case of sunny is 2 by 5. And when you add the value of probability of yes and probability of no to the formula, you get the entropy of sunny as 0.971. Fine. Now you have to calculate how much information you're getting from outlook. That equals weighted average. All right. So what was this weighted average? Total number of yes and total number of no. Fine. So information from outlook equals 5 by 14. From where does this 5 came over? We are calculating the total number of sample space within that particular outlook when it was sunny, right? So in case of sunny, there was 2 yes and 3 no's. All right. So weighted average for sunny would be equal to 5 by 14. All right. Since the formula was 5 by 14 multiplied by entropy of each feature. All right. So as calculated, the entropy for sunny is 0.971. Right. So what we'll do, we'll multiply 5 by 14 with 0.971. Right. Well, this was a calculation for information when outlook equals sunny, but outlook even equals overcast and rainy. For in that case, what we'll do, again, similarly, we'll calculate for everything for overcast and sunny. For overcast, weighted average is 4 by 14 multiplied by its entropy, that is 0. And for sunny, it is same 5 by 14, 3 yes and 2 no's multiplied by its entropy, that is 0.971. And finally, we'll take the sum of all of them, which equals to 0.693, right? Next, we'll calculate the information gained. This, what we did earlier was information taken from Outlook. Now we are calculating what is the information we are gaining from Outlook, right? Now this information gained, that equals to total entropy minus the information that is taken from Outlook, all right? So total entropy we had 0.94 minus information we took from Outlook is 0.693. So the value of information gained from Outlook results to 0.247. All right. So next, what we have to do, let's assume that Wendy is our root node. So Wendy consists of two parameters, false and true. Let's see how many yes and how many no's are there in case of true and false. So when Wendy has false as its parameter, then in that case, it has 6 yes and 2 no's. And when it has true as its parameter, it has 3 yes and 3 no's. Alright. So let's move ahead and similarly calculate the information taken from Wendy and finally calculate the information gained from Wendy. Alright. So first of all, what we'll do, we'll calculate the entropy of each feature, starting with Wendy equal true. So in case of true, we had equal number of yes and equal number of no. Well, remember the graph when we had the probability as 0.5 as total number of yes equal total number of no. And for that case, the entropy equals 1. So we can directly write entropy of true when it's Wendy is 1. As we had already proved it, when probability equals 0.5, the entropy is the maximum that equals to 1. All right. Next is entropy of false when it is Wendy. All right. So similarly, just put the probability of yes and no in the formula and then calculate the result. Since you have 6 yes and 2 no's, so in total you'll get the probability of yes as 6 by 8 and probability of no as 2 by 8. All right. So when you will calculate it, you will get the entropy of false as 0.811. All right. Now let's calculate the information from Wendy. So total information collected from Wendy equals information taken when Wendy equal true plus information taken when Wendy equal false. So we'll calculate the weighted average for each one of them and then we'll sum it up to finally get the total information taken from Wendy. So in this case, it equals to 8 by 14 multiplied by 0.811 plus 6 by 14 multiplied by 1. What is this 8? 8 is total number of yes and no in case when Wendy equals false, right? So when it was false, so total number of yes that equals to 6 and total number of no that equal to 2. That sum ups to 8. All right. So that is why the weighted average results to 8 by 14. Similarly, information taken when Wendy equals true equals to 3 plus 3, that is 3 yes and 3 no, equals 6 divided by total number of sample space, that is 14, multiplied by 1. That is entropy of true. All right. So it is 8 by 14 multiplied by 0.811 plus 6 by 14 multiplied by 1, which results to 0.892. This is information taken from Wendy. All right. Now, how much information you are gaining from Wendy? So for that, what you'll do, so total information gained from Wendy, that equals to total entropy minus information taken from Wendy. All right. That is 0.94 minus 0.892. That equals to 0.048. So 0.048 is the information gained from Wendy. Similarly, we calculated for the rest too. So for Outlook, as you can see, the information was 0.693 and its information gain was 0.247. In case of temperature, the information was around 0.911 and the information gain that was equal to 0.029. In case of humidity, the information gain was 0.152 and in the case of windy, the information gain was 0.048. So what we'll do, we'll select the attribute with the maximum mode. Fine. Now we have selected Outlook as our root node and it is further subdivided into three different parts: sunny, overcast, and rain. So in case of overcast, we have seen that it consists of all yes. So we can consider it as a leaf node. But in case of sunny and rainy, it's doubtful as it consists of both yes and both no. So you need to recalculate the things, right? Again, for this node, you have to recalculate the things. All right. You have to again select the attribute which is having the maximum information gain. All right. So this is how your complete tree will look like. All right. So let's see when you can play. So you can play when Outlook is overcast. All right. In that case, you can always play. If the outlook is sunny, you will further drill down to check the humidity condition. All right. If the humidity is normal, then you will play. If the humidity is high, then you won't play, right? When the outlook predicts that it's rainy, then further you'll check whether it's windy or not. If it has a weak wind, then you'll go and opt for play. But if it has strong wind, then you won't play, right? So this is how your entire decision tree would look like at the end. Now comes the concept of pruning. It says that what should I do to play? Well, you have to do pruning. Pruning will decide how you will play. What is this pruning? Well, this pruning is nothing but cutting down the nodes in order to get the optimal solution. All right. So what pruning does, it reduces the complexity. All right. As here you can see on the screen that it's showing only the result for yes. That is, it's showing all the result which says that you can play. Before we drill down to a practical session, a common question might come in your mind. You might think that a tree-based model better than linear model, right? You can think like, if I can use a logistic regression for classification problem and linear regression for regression problem, then why there is a need to use the tree? Well, many of us have this question in their mind, and well, there's a valid question too. Well, actually, as I said earlier, you can use any algorithm. It depends on the type of problem you're solving. Let's look at some key factor which will help you to decide which algorithm to use and when. So the first point being, if the relationship between dependent and independent variable is well approximated by a linear model, then linear regression will outperform tree-based model. Second case, if there is a high non-linearity and complex relationship between dependent and independent variables, a tree model will outperform a classical regression model. In third case, if you need to build a model which is easy to explain to people, a decision tree model will always do better than a linear model, as the decision tree models are simpler to interpret than linear regression. Alright? Now let's move on ahead and see how you can write a decision tree classifier from scratch in Python using the CART algorithm. Alright? For this, I'll be using Jupyter Notebook with Python 3.0 installed on it. Alright? So let's open the Anaconda and the Jupyter Notebook. Where is that? So this is our Anaconda navigator, and I'll directly jump over to Jupyter Notebook and hit the launch button. I guess everyone knows that Jupyter Notebook is a web-based interactive computing notebook environment where you can run your Python codes. So my Jupyter Notebook, it opens on my local host 8891. So I'll be using this Jupyter Notebook in order to write my decision tree classifier using Python. For this decision tree classifier, I have already written the set of codes. Let me explain you just one by one. So we'll start with initializing our training data set. So there's our sample data set for which each row is an example. The last column is a label and the first two columns are the features. If you want, you can add some more features and example for your practice. Interesting fact is that this data set is designed in a way that the second and the fifth example have almost the same features, but they have different labels. Alright, so let's move on and see how the tree handles this case. As you can see here, both of them, the second and the fifth column, have the same features. What they differ in is just their label. Fine. So let's move ahead. So this is our training data set. Next, what we are doing, we are adding some column labels. So they are used only to print the trees. Fine. So what we'll do, we'll add header to the columns. Like the first column is of color, second is of diameter, and third is of label column. Alright. Next, what we'll do, we'll define a function as unique values in which we'll pass the rows and the columns. So this function, what it will do, it will find the unique values for a column in the data set. So there's an example for that. So what we are doing here, we are passing training data as our row and column number as 0. So what we are doing, we are finding unique values in terms of color. And in this, since the row is training data and the column is 1, so what we are doing here, so we are finding the unique values in terms of diameter. Fine. So this is just an example. Next, what we'll do, we'll define a function as class count and we'll pass the rows into it. So what it does, it counts the number of each type of example within a data set. So in this function, what we are basically doing, we are counting the number of each type of example in the data set. Or what we are doing, we are counting the unique values for the label in the data set. As a sample, you can see here, we can pass that entire training data set to this particular function as class underscore count. What it will do, it will find all the different types of label within the training data set. As you can see here, the unique label consists of mango, grape, and lemon. So next, what we'll do, we'll define a function is numeric and we'll pass a value into it. So what it will do, it will just test if the value is numeric or not, and it will return if the value is an integer or a float. For example, you can see is numeric, we are passing 7, so it is an integer, so it will return an int value. And if we are passing red, it's not a numeric value, right? So moving on ahead, we'll define a class named as question. So what this question does, this question is used to partition the data set. This class, what it does, it just records a column number. For example, 0 for color, alright, and a column value, for example, green. Next, what we are doing, we are defining a match method, which is used to compare the feature value in the example to the feature value stored in the question. Let's see how. First of all, what we are doing, we are defining an init function. And inside that, we are passing the self, column, and the value as parameter. So next, what we do, we define a function as match. What it does, it compares the feature value in an example to the feature value in this question. Fine. Next, we'll define a function as REPR, which is just a helper method to print the question in a readable format. Next, what we are doing, we are defining a function partition. Well, this function is used to partition the data set. Each row in the data set, it checks if it matches the question or not. If it does, so it adds it to the true rows, or if not, then it adds to the false rows. All right. For example, as you can see here, let's partition the training data set based on whether the rows are red or not. Here we are calling the function question and we are passing a value of 0 and red to it. So what it will do, it will assign all the red rows to true underscore rows and everything else will be assigned to false underscore rows. Fine. Next, what we'll do, we'll define a Gini impurity function and inside that we'll pass the list of rows. So what it will do, it will just calculate the Gini impurity for the list of rows. Next, what we are doing here, we're defining a function as information gain. So what this information gain function does, it calculates the information gain using the uncertainty of the starting node minus the weighted impurity of the child node. The next function is find the best split. Well, this function is used to find the best question to ask by iterating over every feature or value and then calculating the information gain. For the detailed explanation on the code, you can find the code in the description given below. All right. Next, we'll define a class as leaf for classifying the data. It holds a dictionary of class like mango for how many times it appears in the row from the training data that reaches this leaf. All right. Next is the decision node. So this decision node, it will ask a question. This holds a reference to the question and to the two child nodes. On the basis of it, you are deciding which node to add further to which branch. All right. So next what we are doing, we are defining a function of build tree and inside that we are passing our number of rows. So this is the function that is used to build the tree. So initially what we did, we defined all the various functions that we'll be using in order to build a tree. So let's start by partitioning the data set for each unique attribute. Then we'll calculate the information gain and then return the question that produces the highest gain. And on the basis of that, we'll split the tree. So what we are doing here, we are partitioning the data set, calculating the information gain, and then what this is returning, it is returning the question that is producing the highest gain. All right. Now, if gain equals 0, return leaf rows. So what it will do, so if we are getting no for the gain, that is gain equals 0, then in that case, since no further question could be asked, so what it will do, it will return a leaf. Fine. Now true underscore rows or false underscore rows equal partition with rows and the question. So if we are reaching till this position, then you have already found a feature or value which will be used to partition the dataset. Then what you will do, you will recursively build the true branch and similarly recursively build the false branch. So return decision underscore node and inside that will be passing question, true branch and false branch. So what it will do, it will return a question node. And this question node just records the best feature or the value to ask at this point. Fine. Now that we have built our tree, next what we'll do, we'll define a print underscore tree function, which will be used to print the tree. Fine. So finally, what we are doing in this particular function, that we are printing our tree. Next is the classify function, which will use it to decide whether to follow the true branch or the false branch, and then compare to the feature or value stored in the node to the example we are considering. And last, what we'll do, we'll finally print the prediction at the leaf. So let's execute it and see. Okay, so this is our testing data. All right, so we printed our leaf as well. Now that we have trained our algorithm with our training data set, now it's time to test it. So this is our testing data set. So let's finally execute it and see what is the result. So this is the result you will get. So first question which is asked by the algorithm is diameter greater than or equal to 3? If it is true, then it will further ask if the color is yellow. Again, if it is true, then it will predict mango as 1 and lemon with 1. All right. And in case it is false, then it will just predict the mango. Now this was the true part. Now next coming to if diameter is not greater than or equal to 3, then in that case it's false. And what it will do, it will just predict the grape. Fine. Okay, so this was all about the coding part. Now let's conclude this session, but before concluding, let me just show you one more thing. Now there's a scikit-learn algorithm cheat sheet which explains you which algorithm you should use and when. Alright, it's built in a decision tree format. Let's see how it is built. So first condition, it will check whether you have 50 samples or not. If your samples are greater than 50, then it will move ahead. If it is less than 50, then you need to collect more data. If your sample is greater than 50, then you have to decide whether you want to predict a category or not. If you want to predict a category, then further you will see that whether you have labeled data or not. If you have labeled data, then that would be a classification algorithm problem. If you don't have the labeled data, then it would be a clustering problem. Now, if you don't want to predict a category, Then what do you want to predict? Predict a quantity? Well, if you want to predict a quantity, then in that case, it would be a regression problem. If you don't want to predict a quantity and you want to keep looking further, then in that case, you should go for dimensionality reduction problems. And still, if you don't want to look and the predicting structure is not working, then you have tough luck for that. I hope this decision tree session clarifies all your doubt over decision tree algorithm.
Let's begin this tutorial by looking at the topics that we'll be covering today. So first of all, we'll start away by getting a brief introduction of random forest, and then we'll go as to see why we actually need random forest, right? Why not anything else but actually random forest? So once we understand its need at first place, then we'll go on to learn more about what is random forest, and we'll also look at various fascinating examples of random forest so that we get a very clear understanding of it. So further, we'll also delve inside into understand the working of random forest as to how exactly random forest works. We'll also watch out the random forest algorithm step by step, right? So that you're able to write any piece of code, any domain specific algorithm on your own. Now, I personally believe that any learning is really incomplete if it's not put into application. So for its completion, we'll also implement random forest in R with a very simple use case, that is diabetes prevention. So let's get started with the introduction then. Now, random forest is actually one of the classifiers which is used for solving classification problems. Now, since some of you might not be really aware of what classification is, so let's quickly understand classification first, and then we'll try to relate it to the random forest. So basically, classification is a machine learning technique in which you already have predefined categories under which you can classify your data. So it's nothing but a supervised learning model where you already have a data based on which you can train your machine, right? So your machine actually learns from this data. So whatever all that predefined data that you already have, it actually works as a fuel for your machine, right? So let's say for an example, ever wondered how your Gmail gets to know about the spam emails and filters it out from the rest of the genuine emails? Any guesses? All right, I'll give you a hint. Try to think something on the line that what would it actually look for? What can be the possible parameters based on which you can decide, all right, this is a genuine email or this is a spam email? So there are certain parameters that your classifier will actually look for, like the subject line or the text or the HTML tags, and also the IP address of the source. From where is this mail getting from? So it will analyze all these variables and then it will classify them into the spam or the genuine folder. So let's say for an example, if your subject line states like mad or cute or pretty and some other absurd keywords, your classifier is smart enough and it's trained in such a manner that it will get to know, all right, this is a spam email, and it will automatically filter it out from your genuine emails. So that is how your classifier works basically. So that's pretty much about the classification. Now let's move forward and see what all ways can be there through which you can actually perform classification. So we have three classifiers, namely decision tree, random forest, and naive Bayes, right? So speaking briefly about decision tree at first. So decision tree actually splits your entire data set in the structure of a tree, and it makes decision at every node and hence called decision tree. So no Big Bang theory, right? So you have certain data set, there are certain nodes. At each node, it will further split into the child nodes, and at each node, it will make a decision. So final decision will be in the form of positive and negative, right? So let's say, for an example, you want to purchase a car, right? So what all will be the parameters? Let's say I go and I want to purchase a car, and I will keep certain parameters in my mind. That would be what exactly is my income, what is my budget, what is the particular brand that I want to go for, what is the mileage of the car, what is the cylinder capacity of the car, and so on and so forth, right? So I'll make my decision based on all these parameters, right? And that is how you make decisions. And further, if you really want to know more about decision tree as to how it exactly works, you can also check out our decision tree tutorial as well. So let's begin now to the random forest now. So random forest is an ensemble classifier actually. Now let's understand what this word ensemble means. So ensemble methods actually use multiple machine learning algorithms to obtain better predictive performance. So particularly talking about random forest, so random forest uses multiple decision trees for prediction, right? So you are ensembling a lot of decision trees to come up to your final outcome. As you can also look here in the image, that your entire data set is actually further split into 3 subsets, right? And each subset further leads to a particular decision tree. So here you have 3 decision trees, and each decision tree will lead to a certain outcome. Now what random forest will do is it will compile the results from all the decision trees, and then it will lead to a final outcome, right? So it's compilation of all the multiple decision trees. That's all about the random forest. Now let's see what lies there in naive Bayes, right? So naive Bayes is a very famous classifier which is made on a very famous rule called Bayes theorem. You might have studied about naive Bayes theorem in your 10th standard as well. So let's just see what Bayes theorem describes. So Bayes theorem actually describes the probability of an event based on certain prior knowledge of conditions that might be related to the event, right? So for example, if cancer is related to age, right? So then person's age can be used to more accurately assess probability of having a cancer than without having the knowledge of age. So if you know the age, then it will become handy in predicting the occurrence of cancer for a particular person, right? So the outcome of first event here is actually affecting your final outcome, isn't it? Yeah. So this is how naive Bayes classifier actually works. So that was all to give an overview of naive Bayes classifier. And this is all pretty much about the types of classifiers. Now we'll try to find out the answer to this particular question as to why we need random forest. Fine. So like human beings learn from their past experiences. So unlike human beings, a computer does not have experiences. Then how does machine takes decisions? Where does it learn from? Well, a computer system actually learns from the data, which represents some past experiences of an application domain. So now let's see how random forest helps in building up the learning model with a very simple use case of credit risk detection. Now, needless to say that credit card companies have a very nested interest in identifying financial transactions that are illegitimate and criminal in nature. And also I would like to mention this point that according to the Federal Reserve Payments Study, Americans used credit cards to pay for 26.2 billion purchases in 2012. And the estimated loss due to unauthorized transactions that year was US $6.1 billion. Now, in the banking industry, measuring risk is very critical because the stakes are too high. So the overall goal is actually to figure out who all can be fraudulent before too much financial damage has been done. So for this, a credit card company receives thousands of applications for new cards, and each application contains information about an applicant, right? So here, as you can see that from all those applications, what we can actually figure out is our predictive variables, like what is the marital status of that person, what is the gender of the person, what is the age of the person, and the status, which is actually whether it is a default payer or a non-default payer. So default payments are basically when payments are not made in time and according to the agreement signed by the cardholder. So now that account is actually said to be in the default. So You can easily figure out the history of the particular card holder from this. Then we can also look at the time of payment, whether he has been a regular payer or a non-regular one, what is the source of income for that particular person, and so forth. So to minimize loss, the bank actually needs certain decision rule to predict whether to approve a particular loan of that particular person or not. Now here is where the random forest actually comes into the picture, right? Now let's see how random forest can actually help us in this particular scenario. Now we have taken randomly 2 parameters out of all the predictive variables that we saw previously. Now we have taken 2 predictive variables here. The first one is the income and the second one is the age, right? And similarly, parallelly, 2 decision trees have been implemented upon those predicted variables. Now let's first assume the case of the income variable, right? So here we have divided our income into 3 categories. The first one being the person earning over $35,000, second from $15,000 to $35,000, the third one earning in the range of $0 to $15,000. Now, if a person is earning over $35,000, which is a pretty good income, pretty decent, so now we'll check out for the credit history. Now here the probability is that if a person is earning a good amount, then there is very low risk that he won't be able to pay back. Already earning good, so the probability is that his application of loan will get approved, right? So there is actually low risk or moderate risk, but there's no real issue of high risk as such. We can approve the applicant's request here. Now let's move on and watch out for the second category where the person is actually earning from $15,000 to $35,000, right? Now here the person may or may not pay back. So in such scenarios, we'll look for the credit history as to what has been his previous history. Now if his previous history has been bad, like he has been a defaulter in the previous transactions, will definitely not consider approving his request and he'll be at the high risk end, which is not good for the bank. If the previous history of that particular applicant is really good, then we will, just to clarify our doubt, we'll consider another parameter as well, that will be our debt. Now if he's already in really high debt, then the risks again increases and there are chances that he might not repay in the future. So here we'll not accept the request of the person having high debt. If the person is in the low debt and he has been a good payer in his past history, then there are chances that he might pay back and we can consider approving the request of this particular applicant. Now let's look at the third category, which is a person earning from $0 to $15,000. Now this is something which actually raises the eyebrow, and this person will actually lie in the category of high risk. All right, so the probability is that his application of loan will probably get rejected. Now we'll get one final outcome from this income parameter, right? Now let us look at our second variable, that is age, which will lead into the second decision tree. Now let us say if the person is young, right? So now we'll look forward to if it is a student. Now, if it is a student, then the chances are high that he won't be able to repay back because he has no earning source, right? So here the risks are too high and the probability is that his application of loan will get rejected. Fine. Now, if the person is young and he's not a student, then we'll probably go on and look for another variable, that is bank balance. Now let's look if the bank balance is less than 5 lakhs. So again, the risk arises and the probability is that his application of loan will get rejected. Now, if the person is young, he is not a student, and he has a bank balance of greater than 5 lakhs, he's got a pretty good and stable bank balance, then the probability is that his loan of application will get approved of. Now let us take another scenario. If he's a senior, right? So if he's a senior, we'll probably go and check out for his credit history. How well has he been in his previous transactions? What kind of a person he's like, whether he's a defaulter or he's a non-defaulter. Now, if he's a very fair kind of person in his previous transactions, then again the risk arises and the probability of his application getting rejected actually increases, right? Now, if he has been an excellent person as per his transactions in the previous history, so now again here there is least risk and the probabilities that his application of loan will get approved. So now here these two variables, income and age, have led to two different decision trees, right? And these two different decision trees actually led to two different results. Now what random forest does is it will actually compile these two different results from these two different decision trees, and then finally it will lead to a final outcome. That is how random forest actually works, right? So that is actually the motive of the random forest. Now let us move forward and see what is random forest, right? You can get an idea of the mechanism from the name itself, random forest. So a collection of trees is a forest, that's why called forest probably. And here also the trees are actually because being trained on subsets which are being selected at random, and therefore they are called random forests. So a random forest is a collection or an ensemble of decision trees, right? Here, a decision tree is actually built using the whole data set considering all features. But actually in random forest, only a fraction of the number of rows is selected, and that too at random, and a particular number of features which are actually selected at random are trained upon, and that is how the decision trees are built upon, right? So similarly, a number of decision trees will be grown and each decision tree will result into a certain final outcome, and random forest will do nothing but actually just compile the results of all those decision trees to bring out the final result. As you can see in this particular figure, that a particular instance actually has resulted into three different decision trees, right? So now tree 1 results into a final outcome called class A, and tree 2 results into class B. Similarly, tree 3 results into class B. So random forest will compile the results of all these decision trees, and it will go by the call of the majority voting. Now, since here two decision trees have actually voted into the favor of the class B, that is decision tree 2 and 3, therefore the final outcome will be in the favor of the class B. And that is how random forest actually works upon. Now, one really beautiful thing about this particular algorithm is that it is one of the versatile algorithms which is capable of performing both regression as well as classification. Now, let's try to understand random forest further with a very beautiful example. All right, this is my favorite one. So let's say you want to decide if you want to watch Edge of Tomorrow or not, right? So in this particular scenario, you will have two different actions to work upon. Either you can just straight away go to your best friend and ask him about, all right, whether should I go for Edge of Tomorrow or not? Will I like this movie? Or you can ask a bunch of friends and take their opinion in consideration, and then based on the final result, you can go out and watch Edge of Tomorrow, right? So now let's just take the first scenario. So where you go to your best friend, ask about whether you should go out to watch Edge of Tomorrow or not. So your friend will probably ask you certain questions, like the first one being here, genre. So let's say your friend asks you if you really like the adventurous kind of movies or not. So you say, yes, definitely, I would love to watch adventure kind of movie. So the probability is that you will like Edge of Tomorrow as well, since Edge of Tomorrow is also a movie of adventure and sci-fi kind of genre, right? So let's say you do not like the adventure genre movie. So then again, the probability reduces that you might really not like Edge of Tomorrow, right? So from here, you can come to a certain conclusion, right? Let's say your best friend puts you into another situation where he'll ask you, all right, do you like Emily Blunt? And you say, definitely I like Emily Blunt. And then he puts another question to you. Do you like Emily Blunt to be in the main lead? And you say, yes. Then again, the probability arises that you will definitely like Edge of Tomorrow as well. Because Edge of Tomorrow has the Emily Blunt in the main lead cast. So And if you say, oh, I do not like Emily Blunt, then again the probability reduces that you would like Edge of Tomorrow too, right? So this is one way where you have one decision tree and your final outcome, your final decision will be based on your one decision tree, or you can say your final outcome will be based on just one friend. Now, definitely you're not really convinced. You want to consider the options of your other friends also, so that you can make very precise and crisp decision, right? You go out and you approach some other bunch of friends of yours. So now let's say you go to 3 of your friends and you ask them the same question, whether I would like to watch Edge of Tomorrow or not. So you go and approach 3 of your friends, friend 1, friend 2, and friend 3. Now you will consider each of theirs vote, and then your decision now will be dependent on the compiled results of all of your 3 friends, right? Now here, let's say you go to your first friend and you ask him whether you would like to watch Edge of Tomorrow or not. And your first friend puts you to one question. Did you like Top Gun? And you say, yes, definitely, I did like the movie Top Gun. Then the probability is that you would like Edge of Tomorrow as well, because Top Gun is actually a military action drama, which also Tom Cruise. So now again, the probability arises that yes, you will like Edge of Tomorrow as well. And if you say, no, I didn't like Top Gun, then again, the chances are that you wouldn't like Edge of Tomorrow, right? Then another question that he puts you across is that, do you really like to watch action movies? And you say, yes, I would love to watch them. Then again, the chances are that you would like to watch Edge of Tomorrow. So from your friend one, you can come to one conclusion. Now here, since the ratio of liking the movie to don't like is actually 2:1, so the final result is actually you would like Edge of Tomorrow. Now you go to your second friend and you ask the same question. So now your second friend asks you, did you like Far and Away when we went out and the last time when we watched it? And you say, no, I really didn't like Far and Away. Then you would say, then you are definitely going to like Edge of Tomorrow. Why it is so? Because Far and Away is actually, since most of you might not be knowing it, so Far and Away is genre of romance, and it revolves around a girl and a guy falling in love with each other and so on. So the probability is that you wouldn't like Edge of Tomorrow. So he asks you another question. Did you like Oblivion? And do you really like to watch Tom Cruise? And you say yes. And again, the probability is that you would like to watch Edge of Tomorrow. Now, why? Because Oblivion again is a science fiction casting Tom Cruise, full of strange experiences, and where Tom Cruise is the savior of the mankind. Well, that is the same kind of plot in Edge of Tomorrow as well. So here it is pure yes that you would like to watch Edge of Tomorrow. So you get another second decision from your second friend. Now you go to your third friend and ask him. So probably your third friend is not really interested in having any sort of conversation with you. So it just simply asks you, did you like Godzilla? And you say, no, I didn't like Godzilla. So he said, definitely you wouldn't like Edge of Tomorrow. Why so? Because Godzilla is also actually a science fiction movie from the adventure genre. So now you've got 3 results from 3 different decision trees from 3 different friends. Now you compile the results of all those friends, and then you make a final call that yes, would you like to watch Edge of Tomorrow or not? So this is some very real time and very interesting example where you can actually implement random forest into ground reality. Now let us look at various domains where random forest is actually used. So because of its diversity, random forest is actually used in various diverse domains, right? So be it banking, be it medicine, be it land use, be it marketing, name it, and random forest is there. So in banking particularly, random forest is being actually used to make it out whether the applicant will be a defaulter pair or it will be a non-defaulter one, so that it can accordingly approve or reject the applications of loan, right? So that is how random forest is being used in banking. Talking about medicine, random forest is widely used in medicine field to predict beforehand what is the probability if a person will actually have a particular disease or not. right? So it's actually used to look at the various disease trends. Let's say you want to figure out what is the probability that a person will have diabetes or not. And so what would you do? You'll probably look at the medical history of the patient, and then you will see, all right, this has been the glucose concentration, what was the BMI, what was the insulin levels in the patient in the previous 3 months, what is the age of this particular person, and you will make different decision trees based on each one of these predicted variables. And then you will finally compile the results of all those variables, and then you will make a final decision as to whether the person will have diabetes in the near future or not. That is how random forest will be used in medicine sector. Now, random forest is also actually used to find out the land use. For example, I want to set up a particular industry in certain area. So what would I probably look for? I look for what is the vegetation over there, what is the urban population over there, right? And how much is the distance from the nearest modes of transport, like from the bus station or the railway station. And accordingly, I will split my parameters and I will make decision on each one of these parameters. And finally, I'll compile my decision of all these parameters, and that will be my final outcome. So that is how I'm finally going to predict whether I should put my industry at this particular location or not, right? So these three examples have actually been majorly around classification problem, because we are trying to classify whether or not. We're actually trying to answer this question, whether or not, right? Now let's move forward and look how marketing is revolving around random forest. So particularly in marketing, we try to identify the customer churn. So this is particularly the regression kind of problem, right? Now how? Let's see. So customer churn is nothing but actually the number of people which are actually, or the number of customers who are losing out. So who are going out of your market. Now you want to identify what will be your customer churn in near future. So most of the e-commerce industries are actually using this, like Amazon, Flipkart, etc. So they particularly look at your each behavior as to what has been your past history, what has been your purchasing history, what do you like based on your activity around certain things, around certain ads, around certain discounts, or around certain kind of materials, right? If you like a particular top, your activity will be more around that particular top. So that is how they track each and every particular move of yours, and then they try to predict whether you will be moving out or not. So that is how they identify the customer churn. So these all are various domains where random forest is used, and this is not the only list. So there are numerous other examples which actually are using random forest. That makes it so special actually. Now let's move forward and see how random forest actually works. Right? So let us start with the random forest algorithm first. Let's just see it step by step as to how random forest algorithm works. So the first step is to actually select certain M features from T, where M is less than T. So here T is the total number of the predictor variables that you have in your data set. And out of those total predictor variables, you will select some randomly, some few features out of those. Now, why we are actually selecting a few features only? The reason is that if you will select all the predictive variables or the total predicted variables, then each of your decision tree will be same. So your model is not actually learning something new. It is learning the same previous thing, because all those decision trees will be similar, right? Now, if you actually split your predicted variables and you select randomly a few predicted variables only, let's say there are 14 total number of variables, and out of those you randomly pick just 3, right? So every time you will get a new decision tree. So there will be variety, right? So the classification model will be actually much more intelligent than the previous one. Now it has got varied experiences, so definitely it will make different decisions each time. And then when you will compile all those different decisions, it will be a new, more accurate and efficient result, right? So the first important step is to select certain number of features out of all the features. Now let's move on to the second step. Let's say for any node D, Now the first step is to calculate the best split at that point. So you know that decision tree, how decision tree is actually implemented. So you pick up the most significant variable, right? And then you will split that particular node into further child nodes. That is how the split takes place, right? So you will do it for m number of variables that you have selected. Let's say you have selected 3, so you will implement the split at all those 3 nodes in one particular decision tree, right? The third step is split of the node into 2 daughter nodes. So now you can split your root node into as many nodes as you want to, but here we'll split our node into 2 daughter nodes as to this or that. So it will be an answer in terms of this or that, fine. Our fourth step will be to repeat all these 3 steps that we've done previously, and we'll repeat all this splitting until we have reached all the n number of nodes, right? So we need to repeat until we have reached till the leaf nodes of our decision tree. That is how we will do it, right? Now, after these 4 steps, we will have our one decision tree. But random forest is actually about multiple decision trees. So here our 5th step will come into the picture, which will actually repeat all these previous steps for d number of times. Now here d is the d number of decision trees. Let's say I want to implement 5 decision trees. So my 5th step will be to implement all the previous steps 5 times. So here the iteration is for 5 number of times, right? Now, once I have created these 5 decision trees, still my task is not complete yet. Now my final task will be to compile the results of all these 5 different decision trees, and I will make a call on the majority voting, right? Here, as you can see in this picture, I had n different instances. Then I created n different decision trees, and finally I will compile the result of all these n different decision trees, and I will take my call on the majority voting, right? So whatever my majority vote says, that will be my final result. So this is basically an overview of the random forest algorithm, how it actually works. Let's just have a look at this example to get much better understanding of what we have learned. So let's say I have this data set which consists of 4 different instances, right? So basically it consists of the weather information of previous 14 days, right? From D1 till D14. And this basically outlook, humidity and wind, this basically gives me the weather condition of those 14 days. And finally I have play, which is my target variable, whether match did take place on that particular day or not, right? Now my main goal is to find out whether the match will actually take place if I have following these weather conditions with me on any particular day. Let's say if the outlook is rainy that day and humidity is high and the wind is very weak. So now I need to predict whether I will be able to play the match that day or not. Alright, so this is a problem statement. Fine. Now let's see how random forest is used in this to sort it out. Now here the first step is to actually split my entire data set into subsets. Here I have split my entire 14 variables into further smaller subsets, right? Now these subsets may or may not overlap, like there is certain overlapping between D1 till D3 and D3 till D6, fine? So there is an overlapping of D3. So it might happen that there might be overlapping. So you need not really worry about the overlapping. But you have to make sure that all those subsets are actually different, right? So here I have taken 3 different subsets. My first subset consists of D1 till D3. My second subset consists of D3 till D6. And my third subset consists of D7 till D now. Now I will first be focusing on my first subset. Now here let's say that particular day the outlook was overcast. Fine. If yes, it was overcast, then the probability is that the match will take place. So overcast is basically when your weather is too cloudy. So if that is the condition, then definitely the match will take place. Now let's say it wasn't overcast, then you will consider the second most probable option, that will be the wind, and you will make your decision based on this now. Whether wind was weak or strong. If wind was weak, then you will definitely go out and play the match, else you would not. So now the final outcome out of this decision tree will be play, because here the ratio between the play and no play is 2:1. So we get to a certain decision from a first decision tree. Now let us look at the second subset. Now since second subset has different number of variables, so that is why this decision tree is absolutely different from what we saw in our first subset. So let's say if it was overcast, then you will play the match. If it isn't the overcast, then you would go and look out for humidity. Now further, it will get split into two, whether it was high or normal. Now we'll take the first case. If the humidity was high and wind was weak, then you will play the match. Else, if humidity was high but wind was too strong, then you would not go out and play the match, right? Now let us look at the second daughter node of humidity. If the humidity was normal and the wind was weak, then you will definitely go out and play the match, else you won't go out and play the match. So here, if you look at the final result, then the ratio of plays to no play is 3:2. Then again, the final outcome is actually play, right? So from second subset, we get the final decision of play. Now let us look at our third subset, which consists of D7 till D9. Here, if again the overcast is yes, then you will play match, else you will go and check out for humidity. And if the humidity is really high, then you won't play the match, else you will play the match. Again, the probability of playing the match is yes, because the ratio of no play is 2:1, right? So three different subsets, three different decision trees, three different outcomes, and one final outcome after compiling all the results from these three different decision trees. All right. So I hope this gives a better perspective, a better understanding of random forest, like how it really works. All right. So now let's just have a look at various features of random forest, right? So the first and the foremost feature is that it is one of the most accurate learning algorithms, right? So why it is so? Because single decision trees are actually prone to having high variance or high bias. And on the contrary, actually random forests, it averages the entire variance across the decision trees. So let's say if the variance is say X for decision tree, but for random forests, let's say we have implemented n number of decision trees parallelly. So my entire variance gets averaged upon, and my final variance actually becomes X upon n. So that is how the entire variance actually goes down as compared to other algorithms, right? Now, second most important feature is that it works well for both classification and regression problems. And by far, I have come across, this is one and the only algorithm which works equally well for both of them, be it classification kind of problem or a regression kind of problem, right? Then it really runs efficient on large databases. So basically it's really scalable, even if you work for the lesser amount of database, or if you work for really huge volume of data, right? So that's a very good part about it. Then the fourth most important point is that it requires almost no input preparation. Now, why am I saying this is because it has got certain implicit methods which actually take care and remove all the outliers and all the missing data, and you really don't have to take care about all that thing while you are in the stages of input preparation. So random forest is all here to take care of everything else. And next is it performs implicit feature selection. Right. So while we are implementing multiple decision trees, so it has got implicit method which will automatically pick up some random features out of all your parameters, and then it will go on and implementing different decision trees. So for example, if you just give one simple command that, all right, I want to implement 500 decision trees, no matter how, so random forest will automatically take care and it will implement all those 500 decision trees, and those all 500 decision trees will be different from each other. And this is because it has got implicit methods which will automatically collect different parameters itself out of all the variables that you have, right? Then it can be easily grown in parallel. Why it is so? Because we are actually implementing multiple decision trees, and all those decision trees are running, or all those decisions trees are actually getting implemented parallelly. So if you say I want 1,000 trees to be implemented, so all those 1,000 trees are getting implemented parallelly. So that is how the computation time reduces down, right? And the last point is that it has got methods for balancing error in unbalanced data sets. Now, what exactly unbalanced data sets are? Let me just give you an example of that. So let's say you're working on a data set, fine, and you create a random forest model and get 90% accuracy immediately. Fantastic, you think, right? So now you start diving deep, you go a little deeper, and you discover that 90% of that data actually belongs to just one class. Damn, now your entire data set, your entire decision is actually biased to just one particular class. So random forest actually takes care of this thing, and it is really not biased towards any particular decision tree or any particular variable or any class. So it has got methods which looks after it, and they does all the balance of errors in your data sets. So that's pretty much about the features of random forests.
K nearest neighbor is a simple algorithm which uses entire dataset in its training phase. Whenever a prediction is required for unseen data, what it does is it searches through the entire training dataset for k most similar instances, and the data with the most similar instance is finally returned as the prediction. So hello and welcome all to this YouTube session, and in today's session we'll be dealing with KNN algorithm. So without delaying any further, let's move on and discuss agenda for today's session. So we'll start our session with what is KNN, where I'll brief you about the topic and we'll move ahead to see what are its popular use cases or how the industry is using KNN for their benefit. Once we are done with it, we'll drill down to the working of algorithm in depth. While learning the algorithm, you will also understand the significance of K, or what does this K stands for in the nearest neighbor algorithm. And then we'll see how the prediction is made using KNN algorithm manually or mathematically. Alright? Now, once we are done with the theoretical concept, we'll start the practical or the demo session, where we'll learn how to implement KNN algorithm using Python. So let's start our session. So starting with, what is KNN algorithm? Well, K nearest neighbor is a simple algorithm that stores all the available cases and classify the new data or case based on a similarity measure. It suggests that if you are similar to your neighbors, then you are one of them, right? For example, if apple looks more similar to banana, orange, or melon, rather than a monkey, rat, or a cat, then most likely apple belong to the group of fruits. Alright? Well, in general, KNN is used in search application where you're looking for similar items. That is, when your task is some form of find items similar to this one, then you call this search as a KNN search. But what is this K in KNN? Well, this K denotes the number of nearest neighbor which are voting class of the new data or the testing data. For example, if K equal 1, then the testing data are given the same label as the closest example in the training set. Similarly, if K equal 3, the labels of the 3 closest classes are checked and the most common label is assigned to the testing data. So this is what a K in KNN algorithm means. So moving on ahead, let's see some of the example of scenarios where KNN is used in the industry. So let's see the industrial application of KNN algorithm, starting with recommender system. Well, the biggest use case of KNN search is a recommender system. This recommender system is like an automated form of a shop counter guy. When you ask him for a product, not only shows you the product, but also suggests you or displays you a relevant set of products which are related to the item you're already interested in buying. This KNN algorithm applies to recommending products like in Amazon, or for recommending media like in case of Netflix, or even for recommending advertisement to display to a user. If I'm not wrong, almost all of you must have used Amazon for shopping, right? So just to tell you, more than 35% of Amazon.com's revenue is generated by its recommendation engine. So what's their strategy? Amazon uses recommendation as a targeted marketing tool in both the email campaigns and on most of its website pages. Amazon will recommend many products from different categories based on what you're browsing, and it will pull those products in front of you which you're likely to buy, like the frequently bought together option that comes at the bottom of the product page to tempt you into buying the combo. Well, this recommendation has just one main goal, that is, increase average order value, or to upsell and cross-sell customers by providing product suggestion based on items in their shopping cart, or based on the product they are currently looking at on-site. So next industrial application of KNN algorithm is concept search, or searching semantically similar documents and classifying documents containing similar topics. So as you know, the data on the internet is increasing exponentially every single second. There are billions and billions of documents on the internet. Each document on the internet contains multiple concepts. That could be a potential concept. Now, there's a situation where the main problem is to extract concept from a set of documents, as each page could have thousands of combinations that could be potential concepts. An average document could have millions of concepts. Combine that to the vast amount of data on the web. Well, we are talking about an enormous amount of data set and sample. So what we need here, we need to find the concept from the enormous amount of data set and samples, right? So for this purpose, we'll be using KNN algorithm. More advanced example could include handwriting detection like in OCR or image recognition or even video recognition. All right. So now that you know various use cases of KNN algorithm, let's proceed and see how does it work. So how does a KNN algorithm work? Let's start by plotting these blue and orange point on our graph. So these blue points, they belong to class A, and the orange ones, they belong to class B. Now you get a star as a new point, and your task is to predict whether this new point, it belongs to class A or it belongs to class B. So to start the prediction, the very first thing that you have to do is select the value of K. Just as I told you, K in KNN algorithm refers to the number of nearest neighbors that you want to select. For example, in this case, K equals 3. So what does it mean? It means that I'm selecting 3 points which are the least distance to the new point. Or you can say I'm selecting 3 different points which are closest to the star. Well, at this point of time, you can ask, how will you calculate the least distance? So once you calculate the distance, you'll get 1 blue and 2 orange points which are closest to the star. Now, since in this case, as we have a majority of orange points, so you can say that for K equals 3, the star belongs to class B. Or you can say that the star is more similar to the orange points. Moving on ahead. Well, what if K equal to 6? Well, for this case, you have to look for 6 different points which are closest to the star. So in this case, after calculating the distance, we find that we have 4 blue points and 2 orange points which are closest to the star. Now, as you can see that the blue points are in majority, so you can say that for K equals 6, the star belongs to class A, or the star is more similar to blue points. So by now, I guess you know how a KNN algorithm works and what is the significance of K in KNN algorithm. So how will you choose the value of K? So keeping in mind this K is the most important parameter in KNN algorithm. So let's see, when you build a K nearest neighbor classifier, how will you choose the value of K? Well, you might have a specific value of K in mind, or you could divide up your data and use something like cross-validation technique to test several values of K in order to determine which works best for your data. For example, if n equal 1000 cases, then in that case, the optimal value of K lies somewhere in between 1 to 19. But yes, unless you try it, you cannot be sure of it. So you know how the algorithm is working on a higher level. Let's move on and see how things are predicted using KNN algorithm. Remember, I told you the KNN algorithm uses the least distance measure in order to find its nearest neighbors. So let's see how these distances calculated. Well, there are several distance measures which can be used. So to start with, we'll mainly focus on Euclidean distance and Manhattan distance in this session. So what is this Euclidean distance? Well, this Euclidean distance is defined as the square root of the sum of difference between a new point x and an existing point y. So for example, here we have point P1 and P2. Point P1 is 1, 1 and point P2 is 5, 4. So what is the Euclidean distance between both of them? So you can say that Euclidean distance is the direct distance between 2 points. So what is the distance between the point P1 and P2? So we can calculate it as 5 minus 1 whole square plus 4 minus 1 whole square, and we can root it over, which results to 5. So next is the Manhattan distance. Well, this Manhattan distance is used to calculate the distance between real vector using the sum of their absolute difference. In this case, the Manhattan distance between the point P1 and P2 is mod of 5 minus 1 plus mod value of 4 minus 1, which results to 3 plus 4, that is 7. So this slide shows the difference between Euclidean and Manhattan distance from point A to point B. So Euclidean distance is nothing but the direct or the least possible distance between A and B, whereas the Manhattan distance is the distance between A and B measured along the axis at right angle. Let's take an example and see how things are predicted using KNN algorithm, or how the KNN algorithm is working. Suppose we have a data set which consists of height, weight, and t-shirt size of some customers. Now when a new customer comes, we only have his height and weight as the information. Now our task is to predict what is the t-shirt size of that particular customer. So for this, we'll be using the KNN algorithm. So the very first thing what we need to do, we need to calculate the Euclidean distance. So now that you have a new data of height 161 centimeter and weight as 61 kg, so the very first thing that we'll do is we'll calculate the Euclidean distance, which is nothing but the square root of 161 minus 158 whole square plus 61 minus 58 whole square. And square root of that is 4.24. Let's drag and drop it. So these are the various Euclidean distance of other points. Now let's suppose k equal to 5. Then the algorithm, what it does, it searches for the 5 customer closest to the new customer. That is more similar to the new data in terms of its attribute. For k equal 5, let's find the top 5 minimum Euclidean distance. So these are the distance which we are going to use: 1, 2, 3, 4, and 5. So let's rank them in the order. First, this is second, this is third, then this one is fourth, and again this one is 5. So this is our order. So for k equal 5, we have 4 t-shirts which come under size M and 1 t-shirt which comes under size L. So obviously, best guess or the best prediction for the t-shirt size of height 161 centimeter and weight 61 kg is M. Or you can say that our new customer fit into size M. Well, this was all about the theoretical session, but before we drill down to the coding part, let me just tell you why people call KNN as a lazy learner. Well, KNN for classification is a very simple algorithm, but that's not why they are called lazy. KNN is a lazy learner because it doesn't have a discriminative function from the training data, but what it does, it memorizes the training data. There is no learning phase of the model, and all of the work happens at the time a prediction is requested. So as such, this is the reason why KNN is often referred to as lazy learning algorithm. So this was all about the theoretical session. Now let's move on to the coding part. So for the practical implementation of the hands-on part, I'll be using the IRIS dataset. So this dataset consists of 150 observation. We have 4 features and 1 class label. The 4 features include the sepal length, the sepal width, petal length, and the petal width, whereas the class label decides which flower belongs to which category. So this was the description of the dataset which we are using. Now let's move on and see what are the step-by-step solution to perform a KNN algorithm. So first we'll start by handling the data. What we have to do, we have to open the dataset from the CSV format and split the dataset into train and test part. Next, we'll check the similarity, where we have to calculate the distance between 2 data instances. Once we calculate the distance, next we'll look for the neighbor and select k neighbors which are having the least distance from a new point. Now, once we get our neighbor, then we'll generate a response from a set of data instances. So this will decide whether the new point belongs to class A or class B. Finally, we'll create the accuracy function, and in the end, we'll tie it all together in the main function. So let's start with our code. For implementing KNN algorithm using Python, I'll be using Jupyter Notebook Python 3.0 installed on it. Now let's move on and see how KNN algorithm can be implemented using Python. So there's my Jupyter Notebook, which is a web-based interactive computing notebook environment with Python 3.0 installed on it. It's at the launch. Yeah, it's launching. So there's our Jupyter Notebook, and we'll be writing our Python codes on it. So the first thing that we need to do is load our file. Our data is in CSV format without a header line or any code. We can open the file, the open function, and read the data line using the reader function in the CSV module. So let's write a code to load our data file. Let's execute the run button. So once you execute the run button, you can see the entire training data set as the output. Next, we need to split the data into a training data set that KNN can use to make prediction and a test data set that we can use to evaluate the accuracy of the model. So we first need to convert the flower measure that were loaded as string into numbers that we can work. Next, we need to split the dataset randomly into train and test. A ratio of 67:33 for test is to train is a standard ratio which is used for this purpose. So let's define a function as load dataset that loads a CSV with a provided file name and split it randomly into training and test dataset using the provided split ratio. So this is our function load dataset, which is using file name, split ratio, training dataset, and testing dataset as its input. All right, so let's execute the run button and check for any errors. So it's executed with 0 errors. Let's test this function. So this is our training set, testing set, load data set. So this is our function load data set, and inside that we are passing our file iris data with a split ratio of 0.66 and training data set and test data set. Let's see what our training data set and test data set it's dividing into. So it's giving a count of training data set and testing data set. The total number of training data set it has split into is 97, and total number of test data set we have is 53. So total number of training data set we have here is 97, and total number of test data set we have here is 53. All right, okay. So our function load data set is performing well. So let's move ahead to step 2, which is similarity. So in order to make prediction, we need to calculate the similarity between any 2 given data instances. This is needed so that we can locate the k most similar data instances in the training dataset and in turn make a prediction. Given that all 4 flower measurements are numeric and have same unit, we can directly use the Euclidean distance measure, which is nothing but the square root of the sum of squared differences between two arrays of the number. Given that all the 4 flower measurements are numeric and have same unit, we can directly use the Euclidean distance measure, which is nothing but the square root of the sum of squared difference between two arrays of the number. Additionally, we want to control which field to include in the distance calculation. So specifically, we only want to include first 4 attributes. So our approach will be to limit the Euclidean distance to a fixed length. All right. So let's define our Euclidean function. So this is our Euclidean distance function, which takes instance 1, instance 2, and length as parameters. Instance 1 and instance 2 are the 2 points of which you want to calculate the Euclidean distance, whereas this length and denote that how many attributes you want to include. Okay. So there's our Euclidean function. Let's execute it. It's executing fine without any errors. Let's test the function. Suppose the data 1 or the first instance consists of the data point as 222 and it belongs to class A, and data 2 consists of 444 and it belongs to class B. So when we calculate the Euclidean distance of data 1 to data 2, and what we have to do, we have to consider only first 3 features of them. All right, so let's print the distance. As you can see here, the distance comes out to be 3.464. All right, so this is nothing but the square root of 4 minus 2 whole square. So this distance is nothing but the Euclidean distance, and it is calculated as square root of 4 minus 2 whole square plus 4 minus 2 whole square. That is nothing but 3 times of 4 minus 2 whole square, that is 12. And square root of 12 is nothing but 3.464. All right, so now that we have calculated the distance, now we need to look for k nearest neighbors. Now that we have a similarity measure, we can use it to collect the k most similar instances for a given unseen instance. Well, this is a straightforward process of calculating the distance for all the instances and selecting a subset with the smallest distance value. And now what we have to do, we have to select the smallest distance values. So for that, we'll be defining a function as getNeighbors. So for that, what we'll be doing, we'll be defining a function as getNeighbors. What it will do, it will return the k most similar neighbors from the training set for a given test instance. All right. So this is how our getNeighbors function look like. It takes training dataset and test instance and k as its input. Here the k is nothing but the number of nearest neighbor you want to check for. All right. So basically what you'll be getting from this getNeighbors function is k different points having least Euclidean distance from the test instance. All right, let's execute it. So the function executed without any errors. So let's test our function. So suppose the training dataset includes the data like 222 and it belongs to class A, and other data includes 444 and it belongs to class B, and our testing instance is 555. And now we have to predict whether this test instance belongs to class A or it belongs to class B. All right. For k equal 1, we have to predict its nearest neighbor and predict whether this test instance, it will belong to class A or will it belong to class B. All right, so let's execute the run button. All right, so on executing the run button, you can see that we have output as 444 and B. Our new instance 555 is closest to point 444, which belongs to class B. All right, now once you have located the most similar neighbor for a test instance, next task is to predict a response based on those neighbors. So how we can do that? Well, we can do this by allowing each neighbor to vote for their class attribute and take the majority vote as the prediction. Let's see how we can do that. So we have a function as getResponse which takes neighbors as the input. Well, this neighbor was nothing but the output of this getNeighbor function. The output of getNeighbor function will be fed to getResponse. All right, let's execute the run button. It's executed. Let's move ahead and test our function getResponse. So we have a neighbor as 111, it belongs to class A, 222, it belongs to class A, 333, it belongs to class B. So this response, what it will do, it will store the value of getResponse by passing this neighbor value. All right, so what we want to check is we want to predict whether our test instance 555, it belongs to class A or class B when the neighbors are 111A, 222A, and 333B. So let's check our response. Now that we have created all the different functions which are required for a KNN algorithm, so important main concern is how to evaluate the accuracy of the prediction. An easy way to evaluate the accuracy of the model is to calculate a ratio of the total correct prediction to all the prediction made. So for this, I'll be defining a function as getAccuracy, and inside that I'll be passing my test dataset and the predictions. GetAccuracy function, check it, executed without any error. Let's check it for a sample dataset. So we have our test data set as 111, which belongs to class A, 222, which again belongs to class 333, which belongs to class B. And my predictions is for first test data, it predicted that it belongs to class A, which is true. For next, it predicted that it belongs to class A, which is again true. And for the next, again it predicted that it belongs to class A, which is false in this case, because the test data belongs to class B. Alright. So in total, we have 2 correct prediction out of 3. Alright. So the ratio will be 2 by 3, which is nothing but 66.66. So our accuracy rate is 66.66. So now that you have created all the functions that are required for KNN algorithm, let's compile them into one single main function. Alright. So this is our main function, and we are using iris dataset with a split of 0.67 and the value of k is 3. Let's see what is the accuracy score of this. Check how accurate our model is. So in training dataset, we have 113 values, and in the test dataset, we have 37 values. These are the predicted and the actual values of the output. Okay. So in total, we got an accuracy of 97.29%, which is really very good. All right. So I hope the concept of this KNN algorithm is clear to you guys.
In a world full of machine learning and artificial intelligence surrounding almost everything around us, classification and prediction is one of the most important aspects of machine learning. So before moving forward, let's have a quick look at the agenda. I'll start off this video by explaining you guys what exactly is naive Bayes. Then we'll understand what is Bayes' theorem, which serves as a logic behind the naive Bayes algorithm. Moving forward, I'll explain the steps involved in the naive Bayes algorithm one by one, and finally I'll finish off this video with a demo on the naive Bayes using the sklearn package. Now, naive Bayes is a simple but surprisingly powerful algorithm from predictive analysis. It is a classification technique based on Bayes' theorem with an assumption of independence among predictors. It comprises of 2 parts, which is naive and Bayes. In simple terms, naive Bayes classifier assumes that the presence of a particular feature in a class is unrelated to the presence of any other feature, even if these features depend on each other or upon the existence of the other features. All of these properties independently contribute to the probability whether a fruit is an apple or an orange or a banana. So that is why it is known as naive. Now, naive Bayes model is easy to build and particularly useful for very large data sets. In probability theory and statistics, Bayes' theorem, which is alternatively known as the Bayes law or the Bayes rule, describes the probability of an event based on prior knowledge of the conditions that might be related to the event. Now, Bayes' theorem is a way to figure out conditional probability. The conditional probability is the probability of an event happening, given that it has some relationship to one or more other events. For example, your probability of getting a parking space is connected to the time of the day you park, where you park, and what conventions are you going on at that time. Bayes' theorem is slightly more nuanced. In a nutshell, it gives you an actual probability of an event given information about the tests. Now, if we look at the definition of Bayes' theorem, we can see that given a hypothesis H and the evidence E, Bayes' theorem states that the relationship between the probability of the hypothesis before getting the evidence, which is the P of H, and the probability of the hypothesis after getting the evidence, that is P of H given E, is defined as probability of E given H into probability of H divided by probability of E. It's rather confusing, right? So let's take an example to understand this theorem. So suppose I have a deck of cards, and if a single card is drawn from the deck of playing cards, the probability that the card is a king is 4 by 52, since there are 4 kings in a standard deck of 52 cards. Now, if king is an event, this card is a king, the probability of king is given as 4 by 52, that is equal to 1 by 13. Now, if the evidence is provided, for instance, someone looks at the card, that the single card is a face card, the probability of king, given that it's a face, can be calculated using the Bayes theorem by this formula. Now, since every king is also a face card, the probability of face, given that it's a king, is equal to 1. And since there are 3 face cards in each suit, that is the jack, king, and queen, the probability of the face card is equal to 12 by 52, that is 3 by 13. Now, using Bayes' theorem, we can find out the probability of king, given that it's a face. So our final answer comes to 1 by 3, which is also true. So if you have a deck of cards which is having only faces, now there are 3 types of faces, which are the jack, king, and queen. So the probability that it's a king is 1 by 3. Now this is the simple example of how Bayes' theorem works. Now if we look at the proof, as in how this Bayes' theorem evolved. So here we have probability of A given B and probability of B given A. Now for a joint probability distribution over the sets A and B, the probability of A intersection B, the conditional probability of A given B is defined as the probability of A intersection B divided by probability of B. And similarly, probability of B given A is defined as probability of B intersection A divided by probability of A. Now we can equate probability of A intersection B and probability of B intersection A as both are the same thing. Now from this method, as you can see, we get our final Bayes theorem proof, which is the probability of A given B equals probability of B given A into probability of B divided by the probability of A. Now while this is the equation that applies to any probability distribution over the events A and B, it has a particular nice interpretation in case where A is represented as the hypothesis H and B is represented as some observed evidence E. In that case, the formula is P of H given E is equal to P of E given H into probability of H divided by probability of E. Now, this relates the probability of hypothesis before getting the evidence, which is P of H, to the probability of the hypothesis after getting the evidence, which is P of H given E. For this reason, P of H is known as the prior probability, while P of H given E is known as the posterior probability, and the factor that relates the two is known as the likelihood ratio. Now using these terms, Bayes theorem can be rephrased as the posterior probability equals the prior probability times the likelihood ratio. So now that we know the maths which is involved behind the Bayes theorem, let's see how we can implement this in a real life scenario. So suppose we have a data set in which we have the outlook, the humidity, and we need to find out whether we should play or not on that day. So the outlook can be sunny, overcast, rain, and the humidity are high, normal, and the wind are categorized into two features, which are the weak and the strong winds. So first of all, we'll create a frequency table using each attribute of the data set. So the frequency table for the outlook looks like this. We have sunny, overcast, and rainy. The frequency table of humidity looks like this, and the frequency table of wind looks like this. We have strong and weak for wind and high and normal ranges for humidity. So for each frequency table, we will generate a likelihood table now. Now the likelihood table contains the probability of a particular day. Suppose we take the sunny and we take the play as yes and no. So the probability of sunny, given that we play yes, is 3 by 10, which is 0.3. The probability of x, which is the probability of sunny, is equal to 5 by 14. Now these are all the terms which are just generated from the data which we have here. And finally, the probability of yes is 10 out of 14. So if we have a look at the likelihood of yes, given that it's a sunny, we can see using Bayes theorem, it's the probability of sunny given yes into probability of yes divided by the probability of sunny. So we have all the values here calculated. So if we put that in our Bayes theorem equation, we get the likelihood of yes as 0.59. Similarly, the likelihood of no can also be calculated here. It's 0.40. Now similarly, we are going to create the likelihood table for both the humidity and the wind. So for humidity, the likelihood for yes, given the humidity is high, is equal to 0.42, and the probability of playing no, given the wind is high, is 0.58. Now similarly for table wind, the probability of yes, given that the wind is weak, is 0.75, and the probability of no, given that the wind is weak, is 0.25. Now suppose we have a day which has high rain, which has high humidity, and the wind is weak. So should we play or not? Now so for that, we use the Bayes theorem here again. So the likelihood of yes on that day is equal to the probability of outlook rain, given that it's a yes, into probability of humidity, given that it's a yes, and the probability of wind that is weak, given that we are playing yes, into the probability of yes, which equals to 0.019. And similarly, the likelihood of no on that day is equal to 0.016. Now if we look at the probability of yes for that day of playing, we just need to divide it with the likelihood sum of both the yes and no. So the probability of playing tomorrow, which is yes, is 0.5, whereas the probability of not playing is equal to 0.45. Now, this is based upon the data which we already have with us. Now that you have an idea of what exactly is naive Bayes, how it works, and we have seen how it can be implemented on a particular data set, let's see where it is used in the industry. Now, starting with our first industrial use case, which is news categorization, or we can use the term text classification to broaden the spectrum of this algorithm. News in the web are rapidly growing in the era of information age, where each news site has its own different layout and categorization for grouping news. Now, these heterogeneity of layout and categorization cannot always satisfy individual users' need. So, remove these heterogeneity and classifying the news articles according to the user preference is a formidable task. Companies use web crawler to extract useful text from HTML pages, the news articles, and each of these news articles is then tokenized. Now, these tokens are nothing but the categories of the news. Now, in order to achieve better classification result, we remove the less significant words, which are the stop words from the documents or the articles, and then we apply the naive Bayes classifier for classifying the news contents based on the news code. Now, this is by far one of the best examples of naive Bayes classifier, which is spam filtering. Now, the naive Bayes classifier are a popular statistical technique for email filtering. They typically use bag of words features to identify the spam email, an approach commonly used in text classification as well. Now, it works by correlating the use of tokens with the spam and the non-spam emails, and then the Bayes theorem, which I explained earlier, is used to calculate the probability that an email is or not a spam. So naive Bayes spam filtering is a baseline technique for dealing with spam that can tailor itself to the email's need of an individual user and give low false positive spam detection rates that are generally acceptable to users. It is one of the oldest ways of doing spam filtering, with its roots in the 1990s. Particular words have particular probabilities of occurring in spam email and in illegitimate email as well. For instance, most emails users will frequently encounter the word lottery or the lucky draw in spam email, but will seldom see it in other emails. The filter doesn't know these probabilities in advance and must be trained so it can build them up. To train the filter, the user must manually indicate whether a new email is spam or not. For all the words in each training email, the filter will adjust the probability that each word will appear in a spam or legitimate email in the database. Now, after training, the word probabilities, also known as the likelihood functions, are used to compute the probability that an email with a particular set of words, as it belongs to either category. Each word in the email contributes to the email's spam probability. This contribution is called the posterior probability and is computed again using the Bayes theorem. Then the email spam probability is computed over all the words in the email, and if the total exceeds a certain threshold, say 90 or 95%, the filter will mark the email as spam. Now, object detection is the process of finding instances of real-world objects such as faces, bicycles, and buildings in images or video. Now, object detection algorithms typically use abstracted features and learning algorithm to recognize instance of an object category. Here again, naive Bayes plays an important role of categorization and classification of objects. Now, medical area produces increasingly voluminous amount of electronic data, which are becoming more and more complicated. The produced medical data has certain characteristics that make their analysis very challenging and attractive as well. Among all the different approaches, the naive Bayes is used. It is the most effective and the efficient classification algorithm and has been successfully applied to many medical problems. Empirical comparison of naive Bayes versus 5 popular classifiers on 15 medical data sets shows that naive Bayes is well suited for medical application and has high performance in most of the examined medical problems. Now, in the past, various statistical methods have been used for modeling in the area of disease diagnosis. These methods require prior assumptions and are less capable of dealing with massive and complicated nonlinear and dependent data. One of the main advantages of naive Bayes approach, which is appealing to physicians, is that all the available information is used to explain the decision. This explanation seems to be natural for medical diagnosis and prognosis. That is, it is very close to the way how physicians diagnose patients. Now, weather is one of the most influential factors in our daily life, to an extent that it may affect the economy of a country that depends on occupation like agriculture. Therefore, as a countermeasure to reduce the damage caused by uncertainty in weather behavior, there should be an efficient way to predict the weather. Now, weather predicting has been a challenging problem in the meteorological department since years. Even after the technological and scientific advancement, the accuracy in prediction of weather has never been sufficient. Even in current day, this domain remains as a research topic in which scientists and mathematicians are working to produce a model or an algorithm that will accurately predict the weather. Now, a Bayesian approach-based model is created by where posterior probabilities are used to calculate the likelihood of each class label for input data instance, and the one with the maximum likelihood is considered as the resulting output. Now, earlier we saw a small implementation of this algorithm as well, where we predicted whether we should play or not based on the data which we have collected earlier. Now, there is a Python library which is known as scikit-learn. It helps to build naive Bayes and model in Python. Now, there are three types of naive Bayes model under scikit-learn library. The first one is the Gaussian. It is used in classification and it assumes that the feature follow a normal distribution. The next we have is multinomial. It is used for discrete counts. For example, let's say we have a text classification problem, and here we consider Bernoulli trials, which is one step further, and instead of word occurring in the document, we have count how often word occurs in the document. You can think of it as the number of times outcomes number is observed in the given number of trials. And finally, we have the Bernoulli type of naive Bayes. The binomial model is useful if your feature vectors are binary. Bag of words model where the ones and the zeros are words occur in the document and the words which do not occur in the document respectively. Based on your data set, you can choose any of the given discussed model here, which is the Gaussian, the multinomial, or the Bernoulli. So let's understand how this algorithm works and what are the different steps one can take to create a Bayesian model and use naive Bayes to predict the output. So here, to understand better, we are going to predict the onset of diabetes. Now, this problem comprises of 768 observations of medical details for Paima Indian patients. The record describes instantaneous measurement taken from the patients such as their age, the number of times pregnant, and the blood work group. Now, all the patients are women aged 21 and older, and all the attributes are numeric, and the units vary from attribute to attribute. Each record has a class value that indicate whether the patient suffered on onset of diabetes within 5 years or the measurements. Now, these are classified as 0. Now, I've broken the whole process down into the following steps. The first step is handling the data, in which we load the data from the CSV file and split it into training and test data sets. The second step is summarizing the data, in which we summarize the properties in the training data sets so that we can calculate the probabilities and make predictions. Now, the third step is making a particular prediction. We use the summaries of the data set to generate a single prediction. And after that, we generate predictions given a test data set and a summarized training data sets. And finally, we evaluate the accuracy of the predictions made for a test data set as the percentage correct out of all the predictions made. And finally, we tie it together and form our own model of naive Bayes classifier. Now, the first thing we need to do is load our data. The data is in the CSV format without a header line or any quotes. We can open the file with the open function and read the data lines using the read functions in the CSV module. Now, we also need to convert the attributes that were loaded as strings into numbers so that we can work with them. So let me show you how this can be implemented. Now, for that, you need to install Python on your system and use the Jupyter Notebook or the Python shell. Here I'm using the Anaconda Navigator, which has all the things required to do programming in Python. We have the Jupyter Lab, we have the Notebook, we have the Qt console, even we have RStudio as well. So what you need to do is just install the Anaconda Navigator. It comes with the pre-installed Python also. So the moment you click launch on the Jupyter Notebook, it will take you to the Jupyter homepage in your local system, And here you can do programming in Python. So let me just rename it as Paima India Diabetes. So first we need to load the data set. So I'm creating here a function load CSV. Now before that we need to import certain CSV, the math and the random method. So as you can see, I've created a load CSV function which will take the Paima Indian Diabetes data.csv file using the csv.reader method, and then we are converting every element of that data set into float. Originally all the elements are in string, but we need to convert them into float for our calculation purposes. Now next we need to split the data into training data sets that naive Bayes can use to make the prediction, and test data set that we can use to evaluate the accuracy of the model. We need to split the data set randomly into training and testing data set in the ratio of usually which is 70 to 30, but for this example I'm going to use 67 and 33. Now 70 and 30 is a common ratio for testing algorithms, so you can play around with this number. So this is our split data set function. Now the naive Bayes model is comprised of summary of the data in the training data set. Now this summary is then used while making predictions. Now the summary of the training data collected involves the mean, the standard deviation of each attribute by class value. Now for example, if there are 2 class values and 7 numerical attributes, then we need a mean and the standard deviation for each of these 7 attributes and the class value, which makes it the 14 attribute summaries. So we can break the preparation of this summary down into the following subtasks, which are the separating data by class, calculating mean, calculating standard deviation, summarizing the data sets, and summarizing attributes by class. So the first task is to separate the training data set instances by class value so that we can calculate statistics for each class. We can do that by creating a map of each class value to a list of instances that belong to the class and sort the entire dataset of instances into the appropriate list. Now the separate by class function just does the same. So as you can see, the function assumes that the last attribute is the class value. The function returns a map of class value to the list of data instances. Next, we need to calculate the mean of each attribute for a class value. Now the mean is the central middle or the central tendency of the data, and we use it as the middle of our Gaussian distribution when calculating the probabilities. So this is our function for mean. Now we also need to calculate the standard deviation of each attribute for a class value. Now standard deviation is calculated as a square root of the variance, and the variance is calculated as the average of the squared differences for each attribute value from the mean. Now one thing to note that here is that we are using n-1 method, which subtracts 1 from the number of attributes values when calculating the variance. Now that we have the tools to summarize the data for a given list of instances, we can calculate the mean and standard deviation for each attribute. Now the zip function groups the values for each attribute across our data instances into their own lists so that we can compute the mean and standard deviation values for each attribute. Now next comes the summarizing attributes by class. We can pull it all together by first separating our training data sets into instances grouped by class, then calculating the summaries for each attribute. Now we are ready to make predictions using the summaries prepared from our training data. Making predictions involve calculating the probability that a given data instance belongs to each class, then selecting the class with the largest probability as the prediction. Now we can divide this whole method into 4 tasks, which are the calculating Gaussian probability density function, calculating class probability, making a prediction, and then estimating the accuracy. Now to calculate the Gaussian probability density function, we use the Gaussian function to estimate the probability of a given attribute value given the known mean and the standard deviation of the attribute estimated from the training data. As you can see, the parameters are x, mean, and the standard deviation. Now in the calculate probability function, we calculate the exponent first, then calculate the main division. This lets us fit the equation nicely into 2 lines. Now the next task is calculating the class probabilities. Now that we can calculate the probability of an attribute belonging to a class, we can combine the probabilities of all the attributes values for a data instance and come up with a probability of the entire data instance belonging to the class. So now that we have calculated the class probabilities, it's time to finally make our first prediction. Now we can calculate the probability of the data instance belonging to each class value, and we can look for the largest probability and return the associated class. And for that, we are going to use this function predict, which uses the summaries and the input vector, which is basically all the probabilities which are being input for a particular label. Now finally, we can estimate the accuracy of the model by making predictions for each data instances in our test data. For that, we use the get predictions method. Now this method is used to calculate the predictions based upon the test data sets and the summary of the training data set. Now the predictions can be compared to the class values in our test data set, and classification accuracy can be calculated as an accuracy ratio between the zeros and the 100%. Now the get accuracy method will calculate this accuracy ratio. Now finally, to sum it all up, we define our main function, where we call all these methods which we have defined earlier one by one to get the accuracy of the model which we have created. So as you can see, this is our main function in which we have the file name, we have defined the split ratio, we have the data set, we have the training and test data set, we are using the split data set method. Next, we are using the summarize by class function, we are using the get prediction and the get accuracy method as well. So guys, as you can see, the output of this one gives us that we are splitting the 768 rows into 514, which is the training, and 254, which is the test dataset rows. And the accuracy of this model is 68%. Now we can play with the amount of training and test data sets which are to be used here. So we can change the split ratio to 70s to 30, 80s to 20 to get different sort of accuracy. So suppose I change the split ratio from 0.67 to 0.8. So as you can see, we get the accuracy of 62%. So splitting it into 0.67 gave us a better result, which was 68%. So this is how you can implement a naive Bayes Gaussian classifier. These are the step-by-step methods which you need to do in case of using the naive Bayes classifier. But don't worry, we do not need to write all this many lines of code to make a model. This is where the scikit-learn library comes into picture. The scikit-learn library has a predefined method, or I'll say a predefined function of naive Bayes, which converts all of these lines of code into merely just 2 or 3 lines of codes. So let me just open another Jupyter notebook. So let me name it as sklearn naive Bayes. Now here we are going to use the most famous dataset, which is the iris dataset. Now the iris flower dataset is a multivariate dataset introduced by the British statistician and biologist Roland Fisher. And based on this Fisher's linear discriminant model, this dataset became a typical test case for many statistical classification techniques in machine learning. So here we are going to use the Gaussian NB model, which is already available in the sklearn. As I mentioned earlier, there were 3 types of naive Bayes, which are the Gaussian, multinomial, and the Bernoulli. So here we are going to use the Gaussian NB model, which is already present in the sklearn library, which is the scikit-learn library. So first of all, what we need to do is import the sklearn datasets and the metrics, and we also need to import the Gaussian NB. Now once all these libraries are loaded, we need to load the dataset, which is the iris dataset. Now next, what we need to do is fit a naive Bayes model to this dataset. So as you can see, we have so easily defined the model, which is the Gaussian NB, which contains all the programming which I just showed you earlier, all the methods which are taking the input, calculating the mean, the standard deviation, separating it by class, then finally making predictions and calculating the prediction accuracy. All of these comes under the Gaussian NB method, which is inside already present in the sklearn library. We just need to fit it according to the dataset which we have here. So next, if we print the model, we see which is the Gaussian NB model. Now next, what we need to do is make the predictions. So the expected output is dataset.target, and the predicted is using the predicted model. And the model we are using is the Gaussian NB here. Now to summarize the model which we created, we calculate the confusion matrix and the classification report. So guys, as you can see, the classification report, we have the precision of 0.96, we have the recall of 0.96, we have the F1 score and the support. And finally, if we print our confusion matrix, as you can see, it gives us this output. So as you can see, using the Gaussian NV method, just putting it into the model and using any of the data set, fitting the model which you created into a particular data set and getting the desired output is so easy with the scikit-learn library. So guys, this is it. I hope you understood a lot about the naive Bayes classifier, how it is used, where it is used, and what are the different steps involved in the classification technique, and how the scikit-learn makes all of those techniques very easy to implement in any data set which we have.
SVM or support vector machine is one of the most effective machine learning classifier, and it has been used in various fields such as face recognition, cancer classification, and so on. Today's session is dedicated to how SVM works, the various features of SVM, and how it is used in the real world. So without any further ado, let's take a look at the agenda for today. We're going to begin the session with an introduction to machine learning and the different types of machine learning. Next, we'll discuss what exactly support vector machines are, and then we'll move on and see how SVM works and how it can be used to classify linearly separable data. We'll also briefly discuss about how nonlinear SVMs work, and then we'll move on and look at the use case of SVM in colon cancer classification. And finally, we'll end the session by running a demo where we'll use SVM to predict whether a patient is suffering from a heart disease or not. Okay, so that was the agenda. Let's get started with our first topic. So what is machine learning? Machine learning is a science of getting computers to act by feeding them data and letting them learn a few tricks on their own. Okay, we're not going to explicitly program the machine. Instead, we're going to feed it data and let it learn. The key to machine learning is the data. Machines learn just like us humans. We humans need to collect information and data to learn. Similarly, machines must also be fed data in order to learn and make decisions. So let's say that you want a machine to predict the value of a stock. Alright? In such situations, you just feed the machine with relevant data, after which you develop a model which is used to predict the value of the stock. Now, one thing to keep in mind is the more data you feed the machine, the better it'll learn and make more accurate predictions. Obviously, machine learning is not so simple. In order for a machine to analyze and get useful insights from data, it must process and study the data by running different algorithms on it. Alright? And today we'll be discussing about one of the most widely used algorithms called the support vector machine. Okay, now that you have a brief idea about what machine learning is, let's look at the different ways in which machines learn. First, we have supervised learning. In this type of learning, the machine learns under guidance. Alright, that's why it's called supervised learning. Now at school, our teachers guided us and taught us. Similarly, in supervised learning, machines learn by feeding them labeled data and explicitly telling them, hey, this is the input and this is how the output must look. Okay, so guys, the teacher in this case is the training data. Next, we have unsupervised learning. Here, the data is not labeled and there is no guide of any sort. Okay, the machine must figure out the data set given and must find hidden patterns in order to make predictions about the output. An example of unsupervised learning is an adult like you and me. We don't need a guide to help us with our daily activities. We figure things out on our own without any supervision. Alright, that's exactly how unsupervised learning works. Finally, we have reinforcement learning. Let's say you were dropped off at an isolated island. What would you do? Now, initially, you'd panic and you'd be unsure of what to do, where to get food from, how to live, and all of that. But after a while, you will have to adapt. You must learn how to live in the island, adapt to the changing climate, learn what to eat and what not to eat. You're basically following the hit and trial concept because you're new to this surrounding and the only way to learn is experience and then learn from your experience. This is exactly what reinforcement learning is. It is a learning method wherein an agent interacts with its environment by producing actions and discovers errors or rewards. Alright, and once it gets trained, it gets ready to predict the new data presented to it. Now, in our case, the agent was you, basically stuck on the island, and the environment was the island. Alright, okay, now let's move on and see what SVM algorithm is all about. So guys, SVM or support vector machine is a supervised learning algorithm which is mainly used to classify data into different classes. Now, unlike most algorithms, SVM makes use of a hyperplane which acts like a decision boundary between the various classes. In general, SVM can be used to generate multiple separating hyperplanes so that the data is divided into segments. Okay, and each of these segments will contain only one kind of data. It's mainly used for classification purpose, wherein you want to classify a data into two different segments, depending on the features of the data. Now, before moving any further, let's discuss a few features of SVM. Like I mentioned earlier, SVM is a supervised learning algorithm. This means that SVM trains on a set of labeled data. SVM studies the label training data and then classifies any new input data depending on what it learned in the training phase. A main advantage of support vector machine is that it can be used for both classification and regression problems. Alright. Now, even though SVM is mainly known for classification, the SVR, which is the support vector regressor, is used for regression problems. Alright, so SVM can be used both for classification and for regression. Now, this is one of the reasons why a lot of people prefer SVM, because it's a very good classifier, and along with that, it is also used for regression. Okay. Another feature is the SVM kernel functions. SVM can be used for classifying non-linear data by using the kernel trick. The kernel trick basically means to transform your data into another dimension so that you can easily draw a hyperplane between the different classes of the data. Alright, non-linear data is basically data which cannot be separated with a straight line. Alright, so SVM can even be used on non-linear data sets. You just have to use the kernel functions to do this. Alright, so guys, I hope you all are clear with the basic concepts of SVM. Now let's move on and look at how SVM works. So guys, in order to understand how SVM works, let's consider a small scenario. Now for a second, pretend that you own a farm. Okay, and let's say that you have a problem and you want to set up a fence to protect your rabbits from the pack of wolves. Okay, but where do you build your fence? One way to get around the problem is to build a classifier based on the position of the rabbits and wolves in your pasture. So what I'm telling you is you can classify the group of rabbits as one group and draw a decision boundary between the rabbits and the wolf. Alright. So if I do that and if I try to draw a decision boundary between the rabbits and the wolves, it looks something like this. Okay. Now you can clearly build a fence along this line. In simple terms, this is exactly how SVM works. It draws a decision boundary, which is a hyperplane between any two classes in order to separate them or classify them. Now I know you're thinking, how do you know where to draw a hyperplane? The basic principle behind SVM is to draw a hyperplane that best separates the two classes. In our case, the two classes are the rabbits and the wolves. So you start off by drawing a random hyperplane and then you check the distance between the hyperplane and the closest data points from each class. These closest or nearest data points to the hyperplane are known as support vectors. And that's where the name comes from, support vector machine. So basically the hyperplane is drawn based on these support vectors. So guys, an optimum hyperplane will have a maximum distance from each of these support vectors. Alright. So basically the hyperplane which has the maximum distance from the support vectors is the most optimum hyperplane. And this distance between the hyperplane and the support vectors is known as the margin. Alright. So to sum it up, SVM is used to classify data by using a hyperplane such that the distance between the hyperplane and the support vectors is maximum. So basically your margin has to be maximum. Alright. That way you know that you're actually separating your classes. Alright. Because the distance between the two classes is maximum. Okay. Now let's try to solve a problem. Okay. So let's say that I input a new data point. Okay. This is the new data point. And now I want to draw a hyperplane such that it best separates the two classes. Okay. So I start off by drawing a hyperplane like this. And then I check the distance between the hyperplane and the support vectors. Okay, so I'm trying to check if the margin is maximum for this hyperplane. But what if I draw a hyperplane which is like this? Alright, now I'm going to check the support vectors over here. Then I'm going to check the distance from the support vectors. And for this hyperplane, it's clear that the margin is more. Alright, when you compare the margin of the previous one to this hyperplane, it is more. So the reason why I'm choosing this hyperplane is because the distance between the support vectors and the hyperplane is maximum in this scenario. Okay, so guys, this is how you choose a hyperplane. You basically have to make sure that the hyperplane has a maximum margin. All right, it has to best separate the two classes. All right. Okay, so far it was quite easy. Our data was linearly separable, which means that you could draw a straight line to separate the two classes. All right. But what will you do if the data set is like this? You possibly can't draw a hyperplane like this. All right. It doesn't separate the two classes at all. So what do you do in such situations? Now, earlier in the session, I mentioned how a kernel can be used to transform data into another dimension that has a clear dividing margin between the classes of data. All right. So kernel functions offer the user this option of transforming nonlinear spaces into linear ones. Nonlinear data set is the one that you can't separate using a straight line. All right. In order to deal with such data sets, you're going to transform them into linear data sets and then use SVM on them. Okay, so a simple trick would be to transform the two variables x and y into a new feature space involving a new variable called z. All right. So guys, so far we were plotting our data on two-dimensional space, correct? We were only using the x and the y axis. So we had only those two variables, x and y. Now, in order to deal with this kind of data, a simple trick would be to transform the two variables x and y into a new feature space involving a new variable called z. Okay, so we're basically visualizing the data on a three-dimensional space. Now, when you transform the 2D space into a 3D space, you can clearly see a dividing margin between the two classes of data. All right, now you can go ahead and separate the two classes by drawing the best hyperplane between them. Okay, that's exactly what we discussed in the previous slides. So guys, why don't you try this yourself? Try drawing a hyperplane which is the most optimum for these two classes. All right. So guys, I hope you have a good understanding about nonlinear SVMs. Now let's look at a real world use case of support vector machines. So guys, SVM as a classifier has been used in cancer classification since the early 2000s. So there was an experiment held by a group of professionals who applied SVM in a colon cancer tissue classification. So the dataset consisted of about 2000 transmembrane protein samples and only about 50 to 200 gene samples were input into the SVM classifier. Now this sample which was input into the SVM classifier had both colon cancer tissue samples and normal colon tissue samples. Alright. Now the main objective of the study was to classify gene samples based on whether they are cancerous or not. Okay, so SVM was trained using the 50 to 200 samples in order to discriminate between non-tumor from tumor specimens. So the performance of the SVM classifier was very accurate for even a small data set. Alright, we had only 50 to 200 samples, and even for the small data set, SVM was pretty accurate with its results. Not only that, its performance was compared to other classification algorithms like naive Bayes, and in each case, SVM outperformed naive Bayes. So after this experiment, it was clear that SVM classified the data more effectively and it worked exceptionally good with small data sets.
Let's go ahead and understand what exactly is unsupervised learning. So sometimes the given data is unstructured and unlabeled, so it becomes difficult to classify the data into different categories. So unsupervised learning helps to solve this problem. This learning is used to cluster the input data in classes on the basis of their statistical properties. So, for example, we can cluster different bikes based upon their speed limit, their acceleration, or the average that they are giving. So, unsupervised learning is a type of machine learning algorithm used to draw inferences from datasets consisting of input data without labeled responses. So, if you have a look at the workflow or the process flow of unsupervised learning, so the training data is collection of information without any label. We have the machine learning algorithm, and then we have the clustering models. So what it does is that distributes the data into different clusters. And again, if you provide any unlabeled new data, it will make a prediction and find out to which cluster that particular data or the data set belongs to, or the particular data point belongs to. So one of the most important algorithms in unsupervised learning is clustering. So let's understand exactly what is clustering. So clustering basically is the process of dividing the datasets into groups consisting of similar data points. And it means grouping of objects based on the information found in the data, describing the objects or their relationships. So
clustering models focus on identifying groups of similar records and labeling records according to the group to which they belong. Now, this is done without the benefit of prior knowledge about the groups and their characteristics. And in fact, we may not even know exactly how many groups are there to look for. Now, these models are often referred to as unsupervised learning models since there is no external standard by which to judge the model's classification performance. There are no right or wrong answers to these models. And if we talk about why clustering is used, so the goal of clustering is to determine the intrinsic group in a set of unlabeled data. Sometimes the partitioning is the goal, or the purpose of clustering algorithm is to make sense of an exact value from the large set of structured and unstructured data. So that is why clustering is used in the industry. And if you have a look at the various use cases of clustering in the industry, so first of all, it's being used in marketing. So discovering distinct groups in customer databases, such as customers who make a lot of long distance calls, customers who use internet more than calls. They're also used in insurance companies for like identifying groups of corporation insurance policy holders with high average claim rate, farmers crash crops, which is profitable. They are used in seismic studies, identifying probable areas of oil or gas exploration based on seismic data. And they're also used in the recommendation of movies, if you'd say. They are also used in Flickr photos. They're also used by Amazon for recommending the product which category it lies in. So basically, if we talk about clustering, there are three types of clustering. So first of all, we have the exclusive clustering, which is the hard clustering. So here an item belongs exclusively to one cluster, not several clusters, and the data point belong exclusively to one cluster. So an example of this is the k-mean clustering. So k-mean clustering does this exclusive kind of clustering. So secondly, we have overlapping clustering. So it is also known as soft clusters. In this, an item can belong to multiple clusters as its degree of association with each cluster is shown. And for example, we have fuzzy or the C-means clustering, which is being used for overlapping clustering. And finally, we have the hierarchical clustering. So when two clusters have a parent-child relationship or a tree-like structure, then it is known as hierarchical cluster. So as you can see here from the example, we have a parent-child kind of relationship in the cluster given here. So let's understand what exactly is k-means clustering. So k-means clustering is an algorithm whose main goal is to group similar elements of data points into a cluster. And it is the process by which objects are classified into a predefined number of groups so that they are as much dissimilar as possible from one group to another group, but as much as similar or possible within each group. Now, if you have a look at the algorithm working here, you're right. So first of all, it starts with identifying the number of clusters, which is k. Then again, we find the centroid. We find the distance objects to the distance object to the centroid, distance of objects to the centroid. Then we find the grouping based on the minimum distance. Has the centroid converged? If true, then we make a cluster. If false, we then again find the centroid. Repeat all of the steps again and again. So let me show you how exactly clustering works with an example here. So first we need to decide the number of clusters to be made. Now, another important task here is how to decide the important number of clusters or how to decide the number of clusters. We'll get into that later. So first, let's assume that the number of clusters we have decided is 3. So after that, then we provide the centroids for all the clusters, which is guessing. The algorithm calculates the Euclidean distance of the point from each centroid and assigns the data point to the closest cluster. Now, Euclidean distance, all of you know, is the square root of the distance, the square root of the square of the distance. So next, when the centroids are calculated again, we have our new clusters. For each data point, then again, the distance from the points to the new clusters are calculated, and then again, the points are assigned to the closest cluster. And then again, we have the new centroid is calculated. Now, these steps are repeated until we have a repetition in the centroids or the new centroids are very close to the very previous ones. So until and unless our output gets repeated or the outputs are very, very close enough, we do not stop this process. We keep on calculating the Euclidean distance of all the points to the centroids Then we calculate the new centroids, and that is how k-means clustering works basically. So an important part here is to understand how to decide the value of k, or the number of clusters, because it does not make any sense if you do not know how many clusters you're going to make. So to decide the number of clusters, we have the elbow method. So let's assume, first of all, compute the sum squared error, which is the SSE, for some value of a. For example, let's take 2, 4, 6, and 8. Now the SSE, which is the sum squared error, is defined as the sum of the squared distance between each member of the cluster and its centroid mathematically. And if you mathematically, it is given by the equation which is provided here. And if you plot the k against the SSE, you will see that the error decreases as k gets large. Now this is because the number of cluster increases, they should be smaller, so the distortion is also smaller. Now the idea of the elbow method is to choose the k at which the SSE decreases abruptly. So for example here, if we have a look at the figure given here, we see that the best number of cluster is at the elbow. So as you can see here, the graph here changes abruptly at the number 4. So for this particular example, we're going to use 4 as the number of cluster. So first of all, while working with k-means clustering, there are two key points to know. First of all, be careful about where you start. So choosing the first center at random, choosing the second center that is far away from the first center. Similarly, choosing the nth center as far away as possible from the closest of all the other centers. And the second idea is to do as many runs of k-means, each with different random starting points, so that you get an idea of where exactly and how many clusters you need to make, and where exactly the centroid lies, and how the data is getting converged. Now, k-means is not exactly a very good method, so let's understand the pros and cons of k-means clusterings. We know that k-means is simple and understandable. Everyone learns it at the first go. The items automatically assigned to the clusters. Now, if we have a look at the cons. So first of all, one needs to define the number of clusters. This is a very heavy task as if we have 3, 4, or if we have 10 categories, and if we do not know what the number of clusters are going to be, it's very difficult for anyone to guess the number of clusters. Now, all the items are forced into the clusters. Whether they actually belong to any other cluster or any other category, they are forced to lie in that other category in which they are closest to. Now, this again happens because of the number of clusters with not defining the correct number of clusters, or not being able to guess the correct number of clusters. And most of all, it's unable to handle the noisy data and the outliners, because anyways, machine learning engineers and data scientists have to clean the data. But then again, it comes down to the analysis what they are doing and the method that they are using. So typically people do not clean the data for k-means clustering, or even if they clean, there are noisy and outliners data which affect the whole model. So that was all for k-means clustering. So what we're going to do is now use k-means clustering for the movie data set. So we have to find out the number of clusters and divide it accordingly. So the use case is that, first of all, we have a data set of 5,000 movies, and what we want to do is group the movies into clusters based on the Facebook likes. So guys, let's have a look at the demo here. So first of all, what we're going to do is import deep copy, numpy, pandas, seaborn, the various libraries which we're going to use now. And from matplotlib, we're going to use pyplot, and we're going to use this ggplot. And next, what we're going to do is import the dataset and look at the shape of the dataset. So if we have a look at the shape of the dataset, we can see that it has 5,043 rows with 28 columns. And if you have a look at the head of the dataset, we can see it has 5,043 data points. So what we're going to do is place the data points in the plot. We take the director Facebook likes, and if we have a look at the data columns, we have face, number, and poster, cast, total Facebook likes, director Facebook likes. So what we have done here now is taking the director Facebook likes and the actor 3 Facebook likes, right? So we have 5,043 rows and 2 columns. Now using the k-means from sklearn, what we're going to do is import it first. We're going to import k-means from sklearn.cluster. Remember guys, sklearn is a very important library in Python for machine learning. And the number of cluster, what we're going to do is provide as 5. Now this again, the number of cluster depends upon the SSE, which is the sum squared errors, or we're going to use the elbow method. So I'm not going to go into the details of that again. So we're going to fit the data into the k-means.fit, and if we find the cluster centers then for the k-means and print it, so what we find is an array of 5 clusters, and if we print the label of the k-means cluster. Now next what we're going to do is plot the data which we have with the clusters, with the new data clusters which we have found, and for this we're going to use the Seaborn, and as you can see here, we have plotted the data into the grid, and you can see here we have 5 clusters. So probably what I would say is that the cluster 3 and the cluster 0 are very, very close. So it might depend. See, that's exactly what I was going to say, is that initially the main challenge in k-means clustering is to define the number of centers, which are the k. So as you can see here, that the third center and the zeroth cluster, the third cluster and the zeroth cluster are very, very close to each other. So guys, it probably could have been in one another cluster. And the another disadvantage was that we do not exactly know how the points are to be arranged. So it's very difficult to force the data into any other cluster, which makes our analysis a little different. Works fine, but sometimes it might be difficult to code in the k-means clustering. Now let's understand what exactly is c-means clustering. So the fuzzy c-means is an extension of the k-means clustering. The popular simple clustering technique. So fuzzy clustering, also referred as soft clustering, is a form of clustering in which each data point can belong to more than one cluster. So k-means tries to find the hard clusters where each point belongs to one cluster, whereas the fuzzy c-means discovers the soft clusters. In a soft cluster, any point can belong to more than one cluster at a time with a certain affinity value towards each. Fuzzy c-means assigns the degree of membership, which ranges from 0 to 1 to an object to a given cluster. So there is a stipulation that the sum of fuzzy membership of an object to all the cluster it belongs to must be equal to 1. So the degree of membership of this particular point to both of these clusters are 0.6 and 0.4. And if we add up, we get 1. So that is one of the logic behind the fuzzy c-means. And this affinity is proportional to the distance from the point to the centroid of the cluster. Now then again, we have the pros and cons of fuzzy c-means. So first of all, it allows a data point to be in multiple clusters. That's a pro. It's a more neutral representation of the behavior of genes. Genes usually are involved in multiple functions. So it is a very good type of clustering when we're talking about genes. And again, if we talk about the cons, again, we have to define C, which is the number of clusters, same as K. Next, we need to determine the membership cutoff value also. So that takes a lot of time and it's time consuming, and the clusters are sensitive to initial assignment of centroids. So a slight change or a deviation from the centroids is going to result in a very different kind of, a funny kind of output we get from the fuzzy c-means. And one of the major disadvantages of c-means clustering is that it is a non-deterministic algorithm. So it does not give you a particular output as in such. That's that. Now let's have a look at the third type of clustering, which is the hierarchical clustering. So hierarchical clustering is an alternative approach which builds a hierarchy from the bottom up or the top to bottom and does not require to specify the number of clusters beforehand. Now the algorithm works as in, first of all, we put each data point in its own cluster, identify the closest two cluster and combine them into one more cluster. Repeat the above step till the data points are in a single cluster. Now there are two types of hierarchical clustering. One is agglomerative clustering and the other one is division clustering. So agglomerative clustering builds the dendrogram from bottom level, while the division clustering, it starts all the data points in one cluster, the root cluster. Now again, hierarchical clustering also has some sort of pros and cons. So in the pros, though no assumption of a particular number of clusters is required, and it may correspond to meaningful taxonomies. Whereas if we talk about the cons, once a decision is made to combine two clusters, it cannot be undone. And one of the major disadvantage of these hierarchical clustering is that it becomes very slow if we talk about very, very large data sets. And nowadays, I think every industry are using large data sets and collecting large amounts of data. So hierarchical clustering is not the apt or the best method someone might need to go for. So there's that.
Hello, everyone, and welcome to this interesting session on a priori algorithm. Now, many of us have visited retail shops such as Walmart or Target for our household needs. Or let's say that we are planning to buy the new iPhone from Target. What we would typically do is search for the model by visiting the mobile section of the store and then select the product and head towards the billing counter. But in today's world, the goal of the organization is to increase the revenue. Can this be done by just pitching one product at a time to the customer? Now, the answer to this is clearly no. Hence, organization began mining data relating to frequently bought items. So, market basket analysis is one of the key techniques used by large retailers to uncover associations between items. Now, examples could be the customers who purchase bread have a 60% likelihood to also purchase jam. Customers who purchase laptops are more likely to purchase laptop bags as well. They try to find out associations between different items and products that can be sold together, which gives assisting in the right product placement. Typically, it figures out what products are being bought together and organizations can place products in a similar manner. For example, people who buy bread also tend to buy butter, right? And the marketing team at retail stores should target customers who buy bread and butter and provide an offer to them so that they buy a third item, suppose eggs. So if a customer buys bread and butter and sees a discount offer on eggs, he will be encouraged to spend more and buy the eggs. And this is what market basket analysis is all about. This is what we are going to talk about in this session, which is association rule mining and the a priori algorithm. Now, association rule can be thought of as an if-then relationship. Just to elaborate on that, we have come up with a rule. Suppose if an item A is being bought by the customer, then the chances of item B being picked by the customer too under the same transaction ID is found out. You need to understand here that it's not a causality, rather it's a co-occurrence pattern that comes to the force. Now there are two elements to this rule. First is the if and second is the then. Now if is also known as antecedent. This is an item or a group of items that are typically found in the item set. And the later one is called the consequent. This comes along as an item with an antecedent group or the group of antecedents are purchased. Now, if we look at the image here, A arrow B, it means that if a person buys an item A, then he will also buy an item B, or he will most probably buy an item B. Now, the simple example that I gave you about the bread and butter and the eggs is just a small example. But what if you have thousands and thousands of items? If you go to any professional data scientist with that data, you can just imagine how much of profit you can make if the data scientist provides you with the right examples and the right placement of the items which you can do. And you can get a lot of insights. That is why association rule mining is a very good algorithm which helps the business make profit. So let's see how this algorithm works. So association rule mining is all about building the rules. And we have just seen one rule that if you buy A, then there's a slight possibility or there's a chance that you might buy B also. This type of a relationship in which we can find the relationship between these two items is known as single cardinality. But what if the customer who bought A and B also wants to buy C? Or if a customer who bought A, B, and C also wants to buy D? Then in these cases, the cardinality usually increases and we can have a lot of combination around these data. And if you have around 10,000 or more than 10,000 data or items, just imagine how many rules you're going to create for each product. That is why association rule mining has such measures so that we do not end up creating tens of thousands of rules. Now, that is where the a priori algorithm comes in. But before we get into the a priori algorithm, let's understand what's the maths behind it. Now, there are three types of matrices which help to measure the association. We have support, confidence, and lift. So support is the frequency of item A or the combination of item A or B. It's basically the frequency of the items which we have bought and what are the combination of the frequency of the item we have bought. So with this, what we can do is filter out the items which have been bought less frequently. This is one of the measures, which is support. Now, what confidence tells us? So confidence gives us how often the items A and B occur together, given the number of times A occur. Now, this also helps us solve a lot of other problems because if somebody is buying A and B together and not buying C, we can just rule out C at that point of time. So this solves another problem, is that we obviously do not need to analyze the products which people just buy barely. So what we can do is, according to the sales, we can define our minimum support and confidence. And when you have set these values, we can put these values in the algorithm and we can filter out the data and we can create different rules. And suppose even after filtering, you have like 5,000 rules. And for every item, we create these 5,000 rules. So that's practically impossible. So for that, we need the third calculation, which is the lift. So lift is basically the strength of any rule. Now let's have a look at the denominator of the formula given here. And if you see here, we have the independent support values of A and B. So this gives us the independent occurrence probability of A and B. And obviously, there's a lot of difference between the random occurrence and association. And if the denominator of the lift is more, what it means is that the occurrence of randomness is more rather than the occurrence because of any association. So lift is the final verdict where we know whether we have to spend time on this particular rule, what we have got here or not. Now let's have a look at a simple example of association rule mining. So suppose we have a set of items A, B, C, D, and E, and a set of transactions T1, T2, T3, T4, and T5. And as you can see here, we have the transactions T1 in which we have ABC, T2 ACD, T3 BCD, T4 ADE, and T5 BCE. Now what we generally do is create some rules or association rules such as A gives T or C gives A gives C, B and C gives A. What this basically means is that if a person buys A, then he's most likely to buy D. And if a person buys C, then he's most likely to buy A. And if you have a look at the last one, if a person buys B and C, he's most likely to buy the item A as well. Now, if we calculate the support, confidence, and lift using these rules, as you can see here in the table, we have the rule and the support, confidence, and the lift values. Now let's discuss about a priori. So a priori algorithm uses the frequent item sets to generate the association rule. And it is based on the concept that a subset of a frequent item set must also be a frequent item set itself. Now this raises the question, what exactly is a frequent item set? So a frequent item set is an item set whose support value is greater than the threshold value. Now just now we discussed that the marketing team, according to the sales, have a minimum threshold value for the confidence as well as the support. So frequent item set is that item set whose support value is greater than the threshold value already specified. Now example, if A and B is a frequent item set, then A and B should also be frequent item sets individually. Now let's consider the following transaction to make the things a little easier. So suppose we have transactions 1, 2, 3, 4, 5 and these items are there. So T1 has 1, 3 and 4, T2 has 2, 3 and 5, T3 has 1, 2, 3, 5, T4, 2, 5 and T5 1, 3 and 5. Now the first step is to build a list of item sets of size 1 by using this transactional data. And one thing to note here is that the minimum support count which is given here is 2. Let's suppose it's 2. So the first step is to create item sets of size 1 and calculate their support values. So as you can see here, we have the table C1 in which we have the item sets 1, 2, 3, 4, 5 and the support values. If you remember the formula of support, it was frequency divided by the total number of occurrence. So as you can see here, for the item set 1, the support is 3. As you can see here, that item set 1 appears in T1, T3 and T5. So as you can see, its frequency is 1, 2 and 3. Now as you can see here, the item set 4 has a support of 1 as it occurs only once in transaction 1. But the minimum support value is 2. That's why it's going to be eliminated. So we have the final table, which is the table F1, in which we have the item sets 1, 2, 3, and 5, and we have the support values 3, 3, 4, and 4. Now the next step is to create item sets of size 2 and calculate their support values. Now all the combination of the item sets in the F1, which is the final table in which we discarded the 4, are going to be used for this iteration. So we get the table C2. So as you can see here, we have 1, 2, 1, 3, 1, 5, 2, 3, 2, 5, and 3, 5. Now if you calculate this support here again, we can see that the item set 1, 2 has a support of 1, which is again less than the specified threshold. So we're going to discard that. So if we have a look at the table F2, we have 1, 3, 1, 5, 2, 3, 2, 5, and 3, 5. Again, we're going to move forward and create the item set of size 3 and calculate their support values. Now all the combinations are going to be used from the item set F2 for this particular iterations. Now before calculating support values, let's perform pruning on the dataset. Now what is pruning? Now after the combinations are being made, we divide C3 item sets to check if there is another subset whose support is less than the minimum support value. That is what frequent item set means. So if you have a look here, the item sets we have is 1, 2, 3, 1, 2, 1, 3, 2, 3 for the first one. Because as you can see here, if we have a look at the subsets of 1, 2, 3, we have 1, 2 as well. So we are going to discard this whole item set. Same goes for the second one. We have 1, 2, 5. We have 1, 2 in that, which was discarded in the previous set or the previous step. That's why we're going to discard that also, which leaves us with only two factors, which is 1, 3, 5 item set and the 2, 3, 5. And the support for this is 2 and 2 as well. Now, if we create the table C4 using 4 elements, we're going to have only one item set, which is 1, 2, 3, and 5. And if we have a look at the table here, the transaction table, 1, 2, 3, and 5 appears only 1. So the support is 1. And since C4, the support of the whole table C4 is less than 2, so we're going to stop here and return to the previous item set, that is C3. So the frequent item sets are 1, 3, 5 and 2, 3, 5. Now let's assume our minimum confidence value is 60%. For that, we're going to generate all the non-empty subsets for each frequent item sets. Now for I equals 1, 3, 5, which is the item set, we get the subset 1, 3, 1, 5, 3, 5, 1, 3, and 5. Similarly for 2, 3, 5, we get 2, 3, 2, 5, 3, 5, 2, 3, and 5. Now this rule states that for every subset S of I, the output of the rule gives something like S gives I to S. That implies S recommends I of S. And this is only possible if the support of I divided by the support of S is greater than equal to the minimum confidence value. Now applying these rules to the item set of F3, we get rule 1, which is 1, 3 gives 1, 3, 5 and 1, 3. It means 1 and 3 gives 5. So the confidence is equal to the support of 1, 3, 5 divided by the support of 1, 3. That equals 2 by 3, which is 66% and which is greater than the 60%. So the rule 1 is selected. Now if we come to rule 2, which is 1, 5, it gives 1, 3, 5 and 1, 5. It means if we have 1 and 5, it implies we're also going to have 3. Now if we calculate the confidence of this one, we're going to have support 1, 3, 5 divided by support 1, 5, which gives us 100%, which means rule 2 is selected as well. But again, if we have a look at rule 5 and rule 6 over here, similarly, if we select 3 gives 1, 3, 5 and 3, it means if we have 3, we also get 1 and 5. So the confidence for this comes at 50%, which is less than the given 60% target. So we're going to reject this rule. And same goes for the rule number 6. Now, one thing to keep in mind here is that although the rule 1 and rule 5 look a lot similar, they are not. So it really depends what's on the left hand side of the arrow and what's on the right hand side of the arrow. It's the if then possibility. I'm sure you guys can understand what exactly these rules are and how to proceed with these rules. So let's see how we can implement the same in Python, right? So for that, what I'm going to do is create a new Python file, and I'm going to use the Jupyter Notebook. You're free to use any sort of IDE. I'm going to name it as a priori. So the first thing what we're going to do is we'll be using the online transactional data of a retail store for generating association rules. So firstly, what we need to do is get the pandas and MLXtend libraries imported and read the file. So as you can see here, we are using the online retail.xlss format file. And from MLXtend, we're going to import a priori and association rules. It all comes under MLXtend. So as you can see here, we have the invoice, the stock code, the description, the quantity, the invoice data, unit price, customer ID, and the country. Now next in this step, what we're going to do is do data cleanup, which includes removing the spaces from some of the descriptions and drop the rows that do not have invoice numbers and remove the credit card transactions, because that is of no use to us. So as you can see here, the output in which we have like 532,000 rows with 8 columns. So after the cleanup, we need to consolidate the items into one transaction per row with each product. For the sake of keeping the data set small, we are only looking at the sales for France. So as you can see here, we have excluded all the other sales. We are just looking at the sales for France. Now there are a lot of zeros in the data, but we also need to make sure any positive values are converted to 1 and anything less than 0 is set to 0. So as you can see here, we have still 392 rows. We're going to encode it and see. Check again. Now that you have structured the data properly, in this step what we're going to do is generate frequent item sets that have support at least 7%. Now this number is chosen so that you can get close enough and generate the rules with the corresponding support, confidence, and lift. So guys, as you can see here, the minimum support is 0.7. Now what if we add another constraint on the rules, such as the lift is greater than 6 and the confidence is greater than 0.8. So as you can see here, we have the left hand side and the right hand side of the association rule, which is the antecedent and the consequence. We have the support, we have the confidence, the lift, the leverage, and the conviction. So guys, that's it for this session. That is how you create association rules using the a priori algorithm, which helps a lot in the marketing business. It runs on the principle of market basket analysis, which is exactly what big companies like Walmart, you have Reliance and Target do. Even IKEA does it. And I hope you got to know what exactly is association rule mining, what is lift, confidence, and support, and how to create association rules.
So guys, reinforcement learning is a part of machine learning where an agent is put in an environment and he learns to behave in this environment by performing certain actions. Okay, so it basically performs actions and it either gets rewards on the actions or it gets a punishment and observing the reward which it gets from those actions. Reinforcement learning is all about taking an appropriate action in order to maximize the reward in a particular situation. So guys, in supervised learning, the training data comprises of the input and the expected output. And so the model is trained with the expected output itself. But when it comes to reinforcement learning, there is no expected output. Here, the reinforcement agent decides what actions to take in order to perform a given task. In the absence of a training data set, it is bound to learn from its experience itself. Alright? So reinforcement learning is all about an agent who is put in an unknown environment and he's going to use a hit and trial method in order to figure out the environment and then come up with an outcome. Okay. Now let's look at reinforcement learning with an analogy. So consider a scenario wherein a baby is learning how to walk. This scenario can go about in two ways. Now in the first case, the baby starts walking and makes it to the candy. Here the candy is basically the reward it's going to get. So since the candy is the end goal, the baby is happy. It's positive. Okay, so the baby is happy and it gets rewarded a set of candies. Now another way in which this could go is that the baby starts walking but falls due to some hurdle in between. The baby gets hurt and it doesn't get any candy and obviously the baby is sad, so this is a negative reward. Okay, or you can say this is a setback. So just like how we humans learn from our mistakes by trial and error, reinforcement learning is also similar. Okay, so we have an agent, which is basically the baby, and a reward, which is the candy over here. Okay, and with many hurdles in between. The agent is supposed to find the best possible path to reach the reward. So guys, I hope you all are clear with the reinforcement learning. Now let's look at the reinforcement learning process. So generally, a reinforcement learning system has two main components. All right, the first is an agent and the second one is an environment. Now in the previous case, we saw that the agent was the baby and the environment was the living room wherein the baby was crawling. Okay, the environment is the setting that the agent is acting on, and the agent over here represents the reinforcement learning algorithm. So guys, the reinforcement learning process starts when the environment sends a state to the agent, and then the agent will take some actions based on the observations. In turn, the environment will send the next state and the respective reward back to the agent. The agent will update its knowledge with the reward returned by the environment, and it uses that to evaluate its previous action. So guys, this loop keeps continuing until the environment sends a terminal state, which means that the agent has accomplished all his tasks and he finally gets the reward. Okay, this is exactly what was depicted in this scenario. So the agent keeps climbing up ladders until he reaches his reward. To understand this better, let's suppose that our agent is learning to play Counter-Strike. Okay, so let's break it down. Now, initially the RL agent, which is basically the player one, let's say it's the player one who is trying to learn how to play the game. Okay, he collects some state from the environment. Okay, this could be the first state of Counter-Strike. Now, based on this state, the agent will take some action. Okay, and this action can be anything that causes a result. So if the player moves left or right, it's also considered as an action. Okay, so initially the action is going to be random because obviously the first time you pick up Counter-Strike, you're not going to be a master at it. So you're going to try with different actions and you're just going to pick up a random action in the beginning. Now the environment is going to give a new state. So after clearing that, the environment is now going to give a new state to the agent or to the player. So maybe he's crossed stage 1, now he's in stage 2. So now the player will get a reward R1 from the environment because it cleared stage 1. So this reward can be anything. It can be additional points or coins or anything like that. Okay, so basically this loop keeps going on until the player is dead or reaches the destination. Okay, and it continuously outputs a sequence of states, actions, and rewards. So guys, this was a small example to show you how reinforcement learning process works. So you start with an initial state, and once the player clears that state, he gets a reward. After that, the environment will give another stage to the player. And after it clears that state, it's going to get another reward and it's going to keep happening until the player reaches his destination. Alright, so guys, I hope this is clear. Now let's move on and look at the reinforcement learning definitions. So there are a few concepts that you should be aware of while studying reinforcement learning. Let's look at those definitions over here. So first we have the agent. Now an agent is basically the reinforcement learning algorithm that learns from trial and error. Okay, so an agent takes actions like, for example, a soldier in Counter-Strike navigating through the game, that's also an action. Okay, if he moves left, right, or if he shoots at somebody, that's also an action. Okay, so the agent is responsible for taking actions in the environment. Now, the environment is the whole Counter-Strike game. Okay, it's basically the world through which the agent moves. The environment takes the agent's current state and action as input, and it returns the agent's reward and its next state as output. All right. Next, we have action. Now, all the possible steps that an agent can take are called actions. So like I said, it can be moving right, left, or shooting, or any of that. All right. Then we have state. Now, state is basically the current condition returned by the environment. So whichever state you are in, if you're in state 1 or if you're in state 2, that represents your current condition. All right. Next, we have reward. A reward is basically an instant return from the environment to appraise your last action. Okay, so it can be anything like coins or it can be additional points. So basically a reward is given to an agent after it clears the specific stages. Next, we have policy. Policy is basically the strategy that the agent uses to find out his next action based on his current state. Policy is just the strategy with which you approach the game. Then we have value. Now, value is the expected long-term return with discount. So value and action value can be a little bit confusing for you right now, but as we move further, you'll understand what I'm talking about. Okay, so value is basically the long-term return that you get with discount. Okay, discount I'll explain in the further slides.
Then we have action value. Now action value is also known as Q value. Okay, it's very similar to value except that it takes an extra parameter, which is the current action. So basically here you'll find out the Q value depending on the particular action that you took. All right. So guys, don't get confused with value and action value. We'll look at examples in the further slides and you'll understand this better. Okay, so guys, make sure that you're familiar with these terms because you'll be seeing a lot of these terms in the further slides. All right. Now, before we move any further, I'd like to discuss a few more concepts. Okay, so first we'll discuss the reward maximization. So if you haven't already realized it, the basic aim of the RL agent is to maximize the reward. Now, how does that happen? Let's try to understand this in depth. So the agent must be trained in such a way that he takes the best action so that the reward is maximum. Because the end goal of reinforcement learning is to maximize your reward based on a set of actions. So let me explain this with a small game. Now in the figure you can see there is a fox, there's some meat and there's a tiger. So our agent is basically the fox and his end goal is to eat the maximum amount of meat before being eaten by the tiger. Now since the fox is a clever fellow, he eats the meat that is closer to him rather than the meat which is closer to the tiger. Now this is because the closer he is to the tiger, the higher are his chances of getting killed. So because of this, the rewards which are near the tiger, even if they are bigger meat chunks, they will be discounted. So this is exactly what discounting means. So our agent is not going to eat the meat chunks which are closer to the tiger because of the risk. All right. Now, even though the meat chunks might be larger, he does not want to take the chances of getting killed. Okay, this is called discounting. Okay, this is where you discount because you improvise and you just eat the meat which are closer to you instead of taking risks and eating the meat which are closer to your opponent. All right. Now, the discounting of reward works based on a value called gamma. We'll be discussing gamma in our further slides, but in short, the value of gamma is between 0 and 1. Okay, so the smaller the gamma, the larger is the discount value. Okay, so if the gamma value is lesser, it means that the agent is not going to explore and he's not going to try and eat the meat chunks which are closer to the tiger. Okay. But if the gamma value is closer to 1, it means that our agent is actually going to explore and it's going to try and eat the meat chunks which are closer to the tiger. All right. Now, I'll be explaining this in depth in the further slides. So don't worry if you haven't got a clear concept yet. But just understand that reward maximization is a very important step when it comes to reinforcement learning because the agent has to collect maximum rewards by the end of the game. All right. Now, let's look at another concept which is called exploration and exploitation. So exploration, like the name suggests, is about exploring and capturing more information about an environment. On the other hand, exploitation is about using the already known exploited information to heighten the rewards. So guys, consider the fox and tiger example that we discussed. Now here the fox eats only the meat chunks which are close to him, but he does not eat the meat chunks which are closer to the tiger. Okay, even though they might give him more rewards, he does not eat them. If the fox only focuses on the closest rewards, he will never reach the big chunks of meat. Okay, this is what exploitation is about. You're just going to use the currently known information and you're going to try and get rewards based on that information. But if the fox decides to explore a bit, it can find the bigger reward, which is the big chunks of meat. This is exactly what exploration is. So the agent is not going to stick to one corner. Instead, he's going to explore the entire environment and try and collect bigger rewards. All right. So guys, I hope you all are clear with exploration and exploitation. Now let's look at the Markov's decision process. So guys, this is basically a mathematical approach for mapping a solution in reinforcement learning. In a way, the purpose of reinforcement learning is to solve a Markov decision process. Okay, so there are a few parameters that are used to get to the solution. So the parameters include the set of actions, the set of states, the rewards, the policy that you're taking to approach the problem, and the value that you get. Okay, so to sum it up, the agent must take an action A to transition from a start state to the end state S. While doing so, the agent will receive a reward R for each action that he takes. So guys, a series of actions taken by the agent define the policy, or it defines the approach. And the rewards that are collected define the value. So the main goal here is to maximize the rewards by choosing the optimum policy. Alright, now let's try to understand this with the help of the shortest path problem. I'm sure a lot of you might have gone through this problem when you were in college. So guys, look at the graph over here. So our aim here is to find the shortest path between A and D with minimum possible cost. So the value that you see on each of these edges basically denotes the cost. So if I want to go from A to C, it's going to cost me 15 points. Okay. So let's look at how this is done. Now, before we move and look at the problem, in this problem, the set of states are denoted by the nodes, which is A, B, C, D. And the action is to traverse from one node to the other. So if I'm going from A to B, that's an action. Similarly, A to C, that's an action. Okay. The reward is basically the cost, which is represented by each edge over here. All right. Now, the policy is basically the path that I choose to reach the destination. So let's say I choose A, C, D. Okay, that's one policy. In order to get to D, I'm choosing A, C, D, which is a policy. Okay, it's basically how I'm approaching the problem. So guys, here you can start off at node A and you can take baby steps to your destination. Now, initially you're clueless, so you can just take the next possible node which is visible to you. So guys, if you're smart enough, you're going to choose A to C instead of A, B, C, D or A, B, D. All right. So now if you're at node C, you want to traverse to node D. You must again choose a wise path. All right. You just have to calculate which path has the highest cost or which path will give you the maximum rewards. So guys, this is a simple problem. We're just trying to calculate the shortest path between A and D by traversing through these nodes. So if I traverse from A, C, D, it gives me the maximum reward. Okay, it gives me 65, which is more than any other policy would give me. Okay, so if I go from A, B, D, it would be 40. When you compare this to A, C, D, it gives me more reward. So obviously, I'm going to go with A, C, D. Okay, so guys, this was a simple problem in order to understand how Markov decision process works. All right. So guys, I want to ask you a question. What do you think I did here? Did I perform exploration or did I perform exploitation? Now, the policy for the above example is of exploitation because we didn't explore the other nodes. Okay, we just selected 3 nodes and we traversed through them. So that's why this is called exploitation. We must always explore the different nodes so that we can find a more optimal policy. But in this case, obviously, ACD has the highest reward and we're going with ACD. But generally, it's not so simple. There are a lot of nodes. There are hundreds of nodes to traverse and there are like 50, 60 policies. Okay, 50, 60 different policies. So you make sure you explore through all the policies and then decide on an optimum policy, which will give you a maximum reward. So guys, before we perform the hands-on part, let's try to understand the math behind our demo. Okay. So in our demo, we'll be using the Q-learning algorithm, which is a type of reinforcement learning algorithm. Okay. It's simple. It just means that you have to take the best possible actions to reach your goal or to get the most rewards. All right. Let's try to understand this with an example. So guys, this is exactly what will be running in our demo. So make sure you understand this properly. Okay, so our goal here is we're going to place an agent in any one of the rooms. Okay, so basically these squares you see here are rooms. Okay, 0 is a room, 4 is a room, 3 is a room, 1 is a room, and 2 is a room. 5 is also a room. It's basically a way outside the building. All right, so what we're going to do is we're going to place an agent in any one of these rooms. And the goal is to reach outside the building. Okay, outside the building is room number 5. Okay, so these empty spaces are basically doors, which means that you can go from 0 to 4. You can go from 4 to 3, 3 to 1, 1 to 5, and similarly 3 to 2. But you can't go from 5 to 2 directly. All right, so there are certain set of rooms that don't get connected directly. Okay, so like I've mentioned here, each room is numbered from 0 to 4, and the outside of the building is numbered as 5. And one thing to note here is room 1 and room 4 directly lead to room number 5. All right, so room number 1 and 4 will directly lead out to room number 5. So basically our goal over here is to get to room number 5. Okay, to set this room as a goal, we'll associate a reward value to each door. Okay, don't worry, I'll explain what I'm saying. So if you represent these rooms in a graph, this is how the graph is going to look. Okay, so for example, from 2, you can go to 3 and then 3 to 1, 1 to 5, which will lead us to our goal. These arrows represent the link between the doors. All right, this is quite understandable. Now our next step is to associate a reward value to each of these doors. Okay, so the rooms that are directly connected to our end room, which is room number 5, will get a reward of 100. Okay, so basically our room number 1 will have a reward 5. Now this is obviously because it's directly connected to 5. Similarly, 4 will also be associated with a reward of 100 because it's directly connected to 5. Okay, so if you go out from 4, it'll lead to 5. Now the other nodes are not directly connected to 5. So you can't directly go from 0 to 5. Okay, so for this, we'll be assigning a reward of 0. So basically other doors not directly connected to the target room have a 0 reward. Okay, now because the doors are two-way, the 2 arrows are assigned to each room. Okay, you can see 2 arrows assigned to each room. So basically 0 leads to 4 and 4 leads back to 0. Now we've assigned 0, 0 over here because 0 does not directly lead to 5. But 1 directly leads to 5, and that's why you can see 100 over here. Similarly, 4 directly leads to our goal state, and that's why we've assigned 100 over here. And obviously 5 to 5 is 100 as well. So here all the direct connections to room number 5 are rewarded 100 and all the indirect connections are rewarded 0. So guys, in Q learning, the end goal is to reach the state with the highest reward so that the agent arrives at the goal. Okay. So let me just explain this graph to you in detail. Now these rooms over here labeled 1, 2, 3 to 5, they represent the state an agent is in. So if I state 1, it means that the agent is in room number 1. Similarly, the agent's movement from one room to the other represents the action. Okay, so if I say 1 to 3, it represents an action. All right. So basically the state is represented as node and the action is represented by these arrows. Okay, so this is what this graph is about. These nodes represent the rooms and these arrows represent the actions. Okay, let's look at a small example. Let's set the initial state to 0. So my agent is placed in room number 2 and he has to travel all the way to room number 5. So if I set the initial stage to 2, he can travel to state 3. Okay, from 3 he can either go to 1 or he can go back to 2 or he can go to 4. If he chooses to go to 4, it will directly take him to room number 5. Okay, which is our end goal. And even if he goes from room number 3 to 1, it will take him to room number 5. So this is how our algorithm works. It's going to traverse different rooms in order to reach the goal room, which is room number 5. Now let's try and depict these rewards in the form of a matrix, okay? Because we'll be using this R matrix or the reward matrix to calculate the Q value or the Q matrix. Okay, we'll see what the Q value is in the next step. But for now, let's see how this reward matrix is calculated. Now the minus ones that you see in the table, they represent the null values. Now these minus 1 basically means that wherever there is no link between nodes, it's represented as minus 1. So 0 to 0 is minus 1. 0 to 1, there is no link. Okay, there's no direct link from 0 to 1. So it's represented as minus 1. Similarly, 0 to 2, also there is no link. You can see there's no line over here. So this is also minus 1. But when it comes to 0 to 4, there is a connection and we have numbered it 0 because the reward for a state which is not directly connected to the goal is 0. But if you look at this 1, 5, which is basically traversing from node 1 to node 5, you can see the reward is 100. Okay, that's basically because 1 and 5 are directly connected and 5 is our end goal. So any node which is directly connected to our goal state will get a reward of 100. Okay, that's why I've put 100 over here. Similarly, if you look at the 4th row over here, I've assigned 100 over here. This is because from 4 to 5, there is a direct connection. There's a direct connection which gives them a 100 reward. Okay, you can see from 4 to 5, there is a direct link. Okay, so from room number 4 to room number 5, you can go directly. That's why there's a 100 reward over here. So guys, this is how the reward matrix is made. All right, I hope this is clear to you all. Okay, now that we have the reward matrix, we need to create another matrix called the Q matrix. Okay, here you'll store all the Q values that we'll calculate. Now this Q matrix basically represents the memory of what the agent has learned through experience. Okay, so once he traverses from one room to the final room, whatever he's learned is stored in this Q matrix. Okay, in order for him to remember that the next time he traverses, we use this matrix. Okay, it's basically like a memory. So guys, the rows of the Q matrix will represent the current state of the agent. The columns will represent the possible actions. And to calculate the Q value, you use this formula. All right, I'll show you what the Q matrix looks like. But first, let's understand this formula. Now this Q value we're calculating because we want to fill in the Q matrix. Okay, so this is basically our Q matrix over here. Initially, it's all 0. But as the agent traverses from different nodes to the destination node, this matrix will get filled up. Okay, so basically, it'll be like a memory to the agent. He'll know that, okay, when he traversed using a particular path, he found out that his value was maximum or his reward was maximum over here. So next time, he'll choose that path. This is exactly what the Q matrix is. Okay, let's go back. Now guys, don't worry about this formula for now because we'll be implementing this formula in an example in the next slide. Okay, so don't worry about this formula for now. But here, just remember that this Q basically represents the Q matrix, the R represents the reward matrix, and the gamma is the gamma value, which I'll talk about shortly. And here, you're just finding out the maximum from the Q matrix. So basically, the gamma parameter has a range from 0 to 1. So you can have a value of 0.1, 0.3, 0.5, 0.8, and all of that. So if the gamma is closer to 0, it means that the agent will consider only the immediate rewards, which means that the agent will not explore the surrounding. Basically, it won't explore different rooms. It will just choose a particular room and then it'll try sticking to it. But if the value of gamma is high, meaning that if it's closer to 1, the agent will consider future rewards with greater weight. This means that the agent will explore all the possible approaches or all the possible policies in order to get to the end goal. So guys, this is what I was talking about when I mentioned exploitation and exploration. All right. So if the gamma value is closer to 1, it basically means that you're actually exploring the entire environment and then choosing an optimum policy. But if your gamma value is closer to 0, it means that the agent will only stick to a certain set of policies and it will calculate the maximum reward based on those policies. Now, next we have the Q-learning algorithm that we're going to use to solve this problem. So guys, now this is going to look very confusing to y'all. So let me just explain this with an example. Okay, we'll see what we're actually going to run in our demo. We'll do the math behind it and then I'll tell you what this Q-learning algorithm is. Okay, you'll understand it as I'm showing you the example. So guys, in the Q-learning algorithm, the agent learns from his experience. Okay, so each episode, which is basically when the agent starts traversing from an initial room to the end goal, is equivalent to one training session. And in every training session, the agent will explore the environment. It'll receive some reward until it reaches the goal state, which is 5. So guys, the purpose of training is to enhance the brain of our agent. Okay, only if he knows the environment very well, will he know which action to take. And this is why we calculate the Q matrix. Okay, in Q matrix, we're just going to calculate the value of traversing from every state to the end state, from every initial room to the end room. Okay, so when we calculate all the values or how much reward we're getting from each policy that we take, we know the optimum policy that will give us the maximum reward. Okay, that's why we have the Q matrix. This is very important because the more you train the agent and the more optimum your output will be. So basically here the agent will not perform exploitation. Instead, he'll explore around and go back and forth through the different rooms and find the fastest route to the goal. All right, now let's look at an example. Okay, let's see how the algorithm works. Okay, let's go back to the previous slide. And here it says that the first step is to set the gamma parameter. Okay, so let's do that. Now the first step is to set the value of the learning parameter, which is gamma, and we've randomly set it to 0.8. Okay, the next step is to initialize the matrix Q to 0. Okay, so we've set matrix Q to 0 over here, and then we'll select the initial stage. Okay, the third step is select a random initial state. And here we've selected the initial state as room number 1. Okay, so after you initialize the matrix Q as a 0 matrix, from room number 1, you can either go to room number 3 or room number 5. So if you look at the reward matrix, you can see that from room number 1, you can only go to room number 3 or room number 5. The other values are -1 here, which means that there is no link from 1 to 0, 1 to 1, 1 to 2, and 1 to 4. So the only possible actions from room number 1 is to go to room number 3 and to go to room number 5. All right. Okay, so let's select room number 5. Okay, so from room number 1, you can go to 3 and 5. And we have randomly selected 5. You can also select 3. But for example, let's select 5 over here. Now from room 5, you're going to calculate the maximum Q value for the next state based on all possible actions. So from room number 5, the next state can be room number 1, 4, or 5. So you're going to calculate the Q value for traversing 5 to 1, 5 to 4, 5 to 5, and you're going to find out which has the maximum Q value, and that's how you're going to compute the Q value. So let's implement our formula. Okay, this is the Q learning formula. So right now we're traversing from room number 1 to room number 5. Okay, this is our state. So here I've written Q1, 5. Okay, 1 represents our current state, which is room number 1. Okay, our initial state was room number 1. And we are traversing to room number 5. Okay, it's shown in this figure, room number 5. Now, for this, we need to calculate the Q value. Next, in our formula, it says reward matrix, state, and action. So the reward matrix for 1, 5, let's look at 1, 5. 1, 5 corresponds to 100. Okay, so our reward over here will be 100. So our 1, 5 is basically 100. Then you're going to add the gamma value. Now the gamma value, we've initialized it to 0.8. So that's what we've written over here. And we're going to multiply it with the maximum value that we're going to get for the next state based on all possible actions. Okay, so from 5, the next state is 1, 4, and 5. So if you traverse from 5 to 1, that's what I've written over here. 5 to 4, you're going to calculate the Q value of 5 to 4, and 5 to 5. Okay, that's what I mentioned over here. So Q 5, 1, 5, 4, and 5, 5 are the next possible actions that you can take from state 5. So R 1, 5 is 100. Okay, because from the reward matrix, you can see that 1, 5 is 100. 0.8 is the value of gamma. After that, we'll calculate Q of 5, 1, 5, 4, and 5, 5. Like I mentioned earlier that we're going to initialize matrix Q as 0 matrix. So we're setting the value as 0 because initially, obviously, the agent doesn't have any memory of what is happening. Okay, so he's just starting from scratch. That's why all these values are 0. So Q of 5, 1 will obviously be 0, 5, 4 will be 0, and 5, 5 will also be 0. And to find out the maximum between these, it's obviously 0. So when you compute this equation, you'll get 100. So the Q value of 1, 5 is 100. So if our agent goes from room number 1 to room number 5, he's going to have a maximum reward or a Q value of 100. All right. Now in the next slide, you can see that I've updated the value of Q of 1, 5. Okay, it's set to 100. All right. Now similarly, let's look at another example so that you understand this better. So guys, this is exactly what we're going to do in our demo. It's only going to be coded. Okay, I'm just explaining our code right now. I'm just telling you the math behind it. All right. Now let's look at another example. Okay, this time we'll start with a randomly chosen initial state. Let's say that we've chosen state 3. Okay, so from room 3, you can either go to room number 1, 2, or 4. Randomly, we'll select room number 1. And from room number 1, you're going to calculate the maximum Q value for the next state based on all possible actions. So the possible actions from 1 is to go to 3 and to go to 5. Now, if you calculate the Q value using this formula, so let me explain this to you once again. Now, Q3, 1 basically represents that we're in room number 3 and we're going to room number 1. Okay, so this represents our action. Okay, so we're going from 3 to 1, which is our action, and 3 is our current state. Next, you'll look at the reward of going from 3 to 1. Okay, if you go to the reward matrix, 3, 1 is 0. Okay, now this is because there's no direct link between 3 and 5. Okay, so that's why the reward here is 0. So the value here will be 0. After that, we have the gamma value, which is 0.8. And then we're going to calculate the Q max of 1, 3 and 1, 5. Out of these, whichever has the maximum value, we're going to use that. Okay, so Q of 1, 3 is 0. All right, it's 0. You can see here 1, 3 is 0. And 1, 5, if you remember, we just calculated 1, 5 in the previous slide. Okay, 1, 5 was 100. So here I'm going to put 100. So the maximum here is 100. So 0.8 into 100 will give us 80. So that's the Q value we're going to get if you traverse from 3 to 1. Okay, I hope that was clear. So now we've traversed from room number 3 to room number 1 with a reward of 80. Okay, but we still haven't reached the end goal, which is room number 5. So for our next episode, the state will be room number 1. So guys, like I said, we'll repeat this inner loop because room number 1 is not our end goal. Okay, our end goal is room number 5. So now we need to figure out how to get from room number 1 to room number 5. So from room number 1, you can either go to 3 or 5. That's what I've drawn over here. So if we select 5, we know that it's our end goal. Okay, so from room number 5, then you have to calculate the maximum Q value for the next possible actions. So the next possible actions from 5 is to go to room number 1, room number 4, or room number 5. So you're going to calculate the Q value of 5 to 1, 5 to 4, and 5 to 5 and find out which is the maximum Q value here, and you're going to use that value. All right, so let's look at the formula now. Now again, we're in room number 1 and we want to go to room number 5. Okay, so that's exactly what I've written here, Q1, 5. Next is the reward matrix. So reward of 1, 5, which is 100. All right. Then we've added the gamma value, which is 0.8. And then we're going to find the maximum Q value from 5 to 1, 5 to 4, and 5 to 5. So this is what we're performing over here. So 5, 1, 5, 4, and 5, 5 are all 0. This is because we initially set all the values of the Q matrix as 0. So you get 100 over here.
And the matrix remains the same because we already had calculated q1 comma 5. So the value of 1 comma 5 is already fed to the agent. So when he comes back here, he knows that, okay, he's already done this before. Now he's going to try and implement another method. Okay, he's going to try and take another route or another policy. So he's going to try to go from different rooms and finally land up in room number 5. So guys, this is exactly how our code runs. We're going to traverse through each and every node because we want an optimum policy. Okay, an optimum policy is attained only when you traverse through all possible actions. Okay, so if you go through all possible actions that you can perform, only then will you understand which is the best action which will lead us to the reward. I hope this is clear. Now let's move on and look at our code. So guys, this is our code and this is executed in Python, and I'm assuming that all of you have a good background in Python. Okay, if you don't understand Python very well, I'm going to leave a link in the description. You can check out that video on Python and then maybe come back to this later. Okay, but I'll be explaining the code to you anyway, but I'm not going to spend a lot of time explaining each and every line of code because I'm assuming that you know Python. Okay, so let's look at the first line of code over here. So what we're going to do is we're going to import NumPy. Okay, NumPy is basically a Python library for adding support for large multi-dimensional arrays and matrices, and it's basically for computing mathematical functions. Okay, so first we're going to import that. After that, we're going to create the R matrix. Okay, so this is the R matrix. Next, we're going to create a Q matrix, and it's a 6 into 6 matrix because obviously we have 6 states starting from 0 to 5. Okay, and we're going to initialize the value to 0. So basically the Q matrix is going to be initialized to 0 over here. All right, after that we're setting the gamma parameter to 0.8. So guys, you can play with this parameter and move it to 0.9 or move it lower to 0.8. Okay, you can see what happens then. Then we'll set an initial stage. Okay, initial stage is set as 1. After that, we're defining a function called available actions. Okay, so basically what we're doing here is, since our initial state is 1, we're going to check our row number 1. Okay, this is our row number 1. Okay, this is row number 0, this is row number 1, and so on. So we're going to check the row number 1 and we're going to find the values which are greater than or equal to 0, because these values basically represent the nodes that we can travel to. Now, if you select -1, you can't traverse to -1. Okay, I explained this earlier. The -1 represents all the nodes that we can't travel to, but we can travel to these nodes. Okay, so basically over here, we're checking all the values which are equal to 0 or greater than 0. These will be our available actions. So if our initial state is 1, we can travel to other states whose value is equal to 0 or greater than 0. And this is stored in this variable called available act. All right. Now this will basically get the available actions in the current state. Okay, so we're just storing the possible actions in this available act variable over here. So basically over here, since our initial state is 1, we're going to find out the next possible states we can go to. Okay, that is stored in the available act variable. Now next is this function chooses at random which action to be performed within the range. So if you remember over here, so guys, initially we are in stage number 1. Okay, our available actions is to go to stage number 3 or stage number 5. Sorry, room number 3 or room number 5. Okay, now randomly we need to choose one room. So for that, we're using this line of code. Okay, so here we're randomly going to choose one of the actions from the available act. This available act, like I said earlier, stores all our possible actions, okay, from the initial state. Okay, so once it chooses an action, it's going to store it in next action. So guys, this action will represent the next available action to take. Now next is our Q matrix. Remember this formula that we used. So guys, this formula that we use is what we're going to calculate in the next few lines of code. So in this block of code, we're just executing and computing the value of Q. Okay, this is our formula for computing the value of Q. Current state, comma action, R current state, comma action, gamma into the maximum value. So here basically we're going to calculate the maximum index, meaning that we're going to check which of the possible actions will give us the maximum Q value. All right, if you remember in our explanation over here, this value over here, max Q of 5,1, 5,4 and 5,5, we had to choose a maximum Q value that we get from these three. So basically that's exactly what we're doing in this line of code. We're calculating the index which gives us the maximum value. After we finish computing the value of Q,
we'll just have to update our matrix. After that, we'll be updating the Q value and we'll be choosing a new initial state. Okay, so this is the update function that is defined over here. Okay, so I've just called the function over here. So guys, this whole set of code will just calculate the Q value. Okay, this is exactly what we did in our examples. After that, we have the training phase. So guys, remember, the more you train an algorithm, the better it's going to learn. Okay, so over here, I've provided around 10,000 iterations. Okay, so my range is 10,000 iterations, meaning that my agent will take 10,000 possible scenarios and it'll go through 10,000 iterations to find out the best policy. So here exactly what I'm doing is I'm choosing the current state randomly. After that, I'm choosing the available action from the current state. So either I can go to stage 3 or state 5. Then I'm calculating the next action, and then I'm finally updating the value in the Q matrix. And next, we just normalize the Q matrix. So sometimes in our Q matrix, the value might exceed. Okay, let's say it exceeded to 500, 600. So that time you want to normalize the matrix. Okay, we want to bring it down a little bit. Okay, because larger numbers we won't be able to understand, and computation will be very hard on larger numbers. That's why we perform normalization. You're taking your calculated value and you're dividing it with the maximum Q value into 100. All right, so you're normalizing it over here. So guys, this is the testing phase. Okay, here you'll just randomly set a current state and you won't give in any other data because you've already trained a model. Okay, you're going to give a current state. Then you're going to tell your agent that, listen, you're in room number 1. Now you need to go to room number 5. Okay, so he has to figure out how to go to room number 5 because we've trained him now. All right, so here we've set the current state to 1 and we need to make sure that it's not equal to 5 because 5 is the end goal. So guys, this is the same loop that we executed earlier. So we're going to do the same iterations again. Now, if I run this entire code, let's look at the result. So our current state here we've chosen as 1. Okay, and if we go back to our matrix, you can see that there is a direct link from 1 to 5, which means that the route that the agent should take is 1 to 5. Okay, directly it should go from 1 to 5 because it will get the maximum reward like that. Okay, let's see if that's happening. So if I run this, it should give me a direct path from 1 to 5. Okay, that's exactly what happened. So this is the selected path. So directly from 1 to 5 it went and it calculated the entire Q matrix for me. So guys, this is exactly how it works. Now let's try to set the initial stage as let's say 2. So if I set the initial stage as 2 and if I try to run the code, let's see the path that it gives. So the selected path is 2, 3, 4, 5. Now it chose this path because it's giving us the maximum reward from this path. Okay, this is the Q matrix that it calculated and this is the selected path. All right, so guys, with this we come to the end of this demo. So basically what we did was we just placed an agent in a room, random room, and we asked it to traverse through and reach to the end room, which is room number 5. So basically we trained our agent and we made sure that it went through all the possible paths to calculate the best path.
Now, for a robot, an environment is a place where it has been put to use. Now remember, this robot is itself the agent. For example, an automobile factory where a robot is used to move materials from one place to another. Now the tasks we discussed just now have a property in common. Now these tasks involve an environment and expect the agent to learn from the environment. Now this is where traditional machine learning fails and hence the need for reinforcement learning. Now it is good to have an established overview of the problem that is to be solved using the Q-learning or the reinforcement learning. So it helps to define the main components of a reinforcement learning solution, that is the agent, environment, action, rewards, and states. So let's suppose we are to build a few autonomous robots for an automobile building factory. Now these robots will help the factory personnel by conveying them the necessary parts that they would need in order to build the car. Now these different parts are located at 9 different positions within the factory warehouse. The car part include the chassis, wheels, dashboard, the engine, and so on. And the factory workers have prioritized the location that contains the body or the chassis to be the topmost. Now they have provided the priorities for other locations as well, which we will look into the moment. Now these locations within the factory look somewhat like this. So as you can see here, we have L1, L2, L3, all of these stations. Now, one thing you might notice here that there are little obstacle present in between the locations. So L6 is the top priority location that contains the chassis for preparing the car bodies. Now the task is to enable the robots so that they can find the shortest route from any given location to another location on their own. Now the agents in this case are the robots. The environment is the automobile factory warehouse. So let's talk about the states. So the states are the location in which a particular robot is present in the particular instance of time, which will denote its states. Now machines understand numbers rather than letters, so let's map the location codes to number. So as you can see here, we have mapped location L1 to the state 0, L2 and 1, and so on. We have L8 as state 7 and L9 at state 8. Well, next, what we're going to talk about are the actions. So in our example, the action will be the direct location that a robot can go from a particular location, right? Consider a robot that is at L2 location, and the direct locations to which it can move are L5, L1, and L3. Now, the figure here may come in handy to visualize this. Now, as you might have already guessed, the set of actions here is nothing but the set of all possible states of the robot. For each location, the set of actions that a robot can take will be different. For example, the set of actions will change if the robot is in L1 rather than L2. So if the robot is in L1, it can only go to L4 and L2 directly. Now that we are done with the states and the actions, let's talk about the rewards. So the states are basically 0, 1, 2, 3, 4, and the actions are also 0, 1, 2, 3, 4 up till 8. Now the rewards now will be given to a robot if a location, which is the state, is directly reachable from a particular location. So let's take an example. Suppose L9 is directly reachable from L8, right? So if a robot goes from L8 to L9 and vice versa, it will be rewarded by 1. And if a location is not directly reachable from a particular location, we do not give any reward, a reward of 0. Now the reward is just a number here and nothing else. It enables the robots to make sense of their movements, helping them in deciding what locations are directly reachable and what are not. Now with this queue, we can construct a reward table which contains all the reward values mapping between all possible states. So as you can see here in the table, the positions which are marked green have a positive reward. And as you can see here, we have all the possible rewards that a robot can get by moving in between the different states. Now comes an interesting decision. Now remember that the factory administrator prioritized L6 to be the topmost. So how do we incorporate this fact in the above table? Now this is done by associating the topmost priority location with a very high reward than the usual ones. So let's put 999 in the cell L6, L6. Now the table of rewards with a higher reward for the topmost location looks something like this. We have now formally defined all the vital components for the solution we are aiming for the problem discussed now. We will shift gears a bit and study some of the fundamental concepts that prevail in the world of reinforcement learning and Q-learning. So first of all, we'll start with the Bellman equation. Now consider the following square of rooms, which is analogous to the actual environment from our original problem, but without the barriers. Now suppose a robot needs to go to the room marked in the green from its current position A using the specified direction. Now how can we enable the robot to do this programmatically? One idea would be introduce some kind of a footprint which the robot will be able to follow. Now here a constant value is specified in each of the rooms which will come along the robot's way if it follows the direction specified above. Now in this way, if it starts at location A, it will be able to scan through this constant value and will move accordingly. But this will only work if the direction is prefixed and the robot always starts at the location A. Now consider the robot starts at this location rather than its previous one. Now the robot now sees footprints in two different directions. It is, therefore, unable to decide which way to go in order to get the destination, which is the green room. It happens primarily because the robot does not have a way to remember the directions to proceed. So our job now is to enable the robot with a memory. Now this is where the Bellman equation comes into play. So as you can see here, the main reason of the Bellman equation is to enable the robot with a memory. That's the thing we're going to use. So the equation goes something like this. V of S gives maximum of A, R of S comma A plus gamma of V S dash, where S is a particular state, which is a room, A is the action moving between the rooms, S dash is the state to which the robot goes from S, and gamma is the discount factor. Now we'll get into it in a moment, and obviously R of S comma A is a reward function which takes a state S and action A and outputs the reward. Now V of S is the value of being in a particular state, which is the footprint. Now we consider all the possible actions and take the one that yields the maximum value. Now, there is one constraint, however, regarding the value footprint, that is, the room marked in the yellow just below the green room. It will always have the value of 1 to denote, that is, one of the nearest room adjacent to the green room. Now, this is also to ensure that a robot gets a reward when it goes from a yellow room to the green room. Let's see how to make sense of the equation which we have here. So let's assume a discount factor of 0.9. As you remember, gamma is the discount value or the discount factor, so let's take it 0.9. Now for the room which is marked just below the 1 or the yellow room, which is the asterisk mark, for this room, what will be the V of S? That is the value of being in a particular state. So for this, V of S would be something like maximum of A will take 0, which is the initial of R S comma A, plus 0.9, which is gamma, into 1. That gives us 0.9. Now here the robot will not get any reward for going to a state marked in yellow, hence the R S comma A is 0 here. But the robot knows the value of being in the yellow room, hence V of S dash is 1. Following this, for the other states, we should get 0.9. Then again, if we put 0.9 in this equation, we get 0.81, then 0.729, and then we again reach the starting point. So this is how the table looks with some value footprints computed from the Bellman equation. Now a couple of things to notice here is that the max function helps the robot to always choose the state that gives it the maximum value of being in that state. Now the discount factor gamma notifies the robot about how far it is from the destination. This is typically specified by the developer of the algorithm that would be installed in the robot. Now the other states can also be given their respective values in a similar way. So as you can see here, the boxes adjacent to the green one have 1. And if we move away from 1, we get 0.9, 0.81, 0.729, and finally we reach 0.66. Now the robot now can proceed its way through the green room, utilizing these value footprints even if it's stopped at any arbitrary room in the given location. Now, if a robot lands up in the highlighted sky blue area, it will still find 2 options to choose from. But eventually, either of the paths will be good enough for the robot to take because of the way the value footprints are now laid out. Now, one thing to note here is that the Bellman equation is one of the key equations in the world of reinforcement learning and Q-learning. So if we think realistically, our surroundings do not always work in the way we expect. There is always a bit of stochasticity involved in it. Now this applies to robot as well. Sometimes it might so happen that the robot's machinery got corrupted. Sometimes the robot may come across some hindrance on its way, which may not be known to it beforehand, right? And sometimes even if the robot knows that it needs to take the right turn, it will not. So how do we introduce this stochasticity in our case? Now here comes the Markov decision process. Now consider the robot is currently in the red room and it needs to go to the green room. Now let's now consider the robot has a slight chance of dysfunctioning and might take the left or the right or the bottom turn instead of taking the upper turn in order to get to the green room from where it is now, which is the red room. Now the question is, how do we enable the robot to handle this when it is out in the given environment, right? Now, this is a situation where the decision making regarding which turn is to be taken is partly random and partly under the control of the robot. Now, partly random because we are not sure when exactly the robot might dysfunctional, and partly under the control of the robot because it is still making a decision of taking a turn right on its own and with the help of the program embedded into it. So, a Markov decision process is a discrete time stochastic control process. It provides a mathematical framework for modeling decision making in situations where the outcomes are partly random and partly under the control of the decision maker. Now we need to give this concept a mathematical shape, most likely an equation, which then can be taken further. Now, you might be surprised that we can do this with the help of the Bellman equation with a few minor tweaks. So if we have a look at the original Bellman equation, v of x is equal to maximum of r s comma a plus gamma v of s dash. What needs to be changed in the above equation so that we can introduce some amount of randomness here. As long as we are not sure when the robot might not take the expected turn, we are then also not sure in which room it might end up, in which is nothing but the room it moves from its current room. At this point, according to the equation, we are not sure of the S dash, which is the next state, or the room, but we do know all the probable turns the robot might take. Now, in order to incorporate each of these probabilities into the above equation, we need to associate a probability with each of the turns to quantify the robot if it has got any X% chance of taking this turn. Now, if we do so, we get Ps is equal to maximum of Rs comma a plus gamma into summation of S dash Ps comma a comma S dash into V of S dash. Now, the Ps, A, and S dash is the probability of moving from room S to S dash with the action A. And the summation here is the expectation of the situation that the robot incurs, which is the randomness. Now, let's take a look at this example here. So when we associate the probabilities to each of these turns, we essentially mean that there is an 80% chance that the robot will take the upper turn. Now, if we put all the required values in our equation, we get V of S is equal to maximum of R of S comma A plus gamma of 0.8 into V of room up plus 0.1 into V of room down, 0.03 into room of V of room left plus 0.03 into V of room right. Now note that the value footprints will now change due to the fact that we are incorporating stochastically here. But this time we will not calculate those value footprints. Instead, we will let the robot to figure it out. Now, up until this point, we have not considered about rewarding the robot for its action of going into a particular room. We are only rewarding the robot when it gets to the destination. Now, ideally, there should be a reward for each action the robot takes to help it better assess the quality of the actions, but the rewards need not to be always be the same. But it is much better than having some amount of reward for the actions than having no rewards at all, right? And this idea is known as the living penalty. In reality, the reward system can be very complex, and particularly modeling sparse rewards is an active area of research in the domain of reinforcement learning. So by now we have got the equation which we have. So what we're going to do is now transition to Q learning. So this equation gives us the value of going to a particular state, taking the stochasticity of the environment into account. Now we have also learned very briefly about the idea of living penalty, which deals with associating each move of the robot with a reward. So Q-learning possesses an idea of assessing the quality of an action that is taken to move to a state rather than determining the possible value of the state which is being moved to. So earlier we had 0.8 into V of S1, 0.03 into V of S2, 0.1 into V of S3, and so on. Now if we incorporate the idea of assessing the quality of the action for moving to a certain state, so the environment with the agent and the quality of the action will look something like this. So instead of 0.8 V of S1, we'll have Q of S1, comma A1, we'll have Q of S2, comma A2, Q of S3. Now the robot now has 4 different states to choose from, and along with that there are 4 different actions also for the current state it is in. So how do we calculate Q of S comma A, that is the cumulative quality of the possible actions the robot might take? So let's break it down. Now from the equation V of S equals maximum of A R S comma A plus gamma summation S dash P S A S dash into V of S dash. If we discard the maximum function, we have Rs of A plus gamma into summation P and V. Now essentially in the equation that produces V of S, we are considering all possible actions and all possible states from the current state that the robot is in. And then we are taking the maximum value caused by taking a certain action And the equation produces a value footprint which is for just one possible action. In fact, we can think of it as the quality of the action. So Q of S comma A is equal to RS comma A plus gamma of summation P and V. Now that we have got an equation to quantify the quality of a particular action, we are going to make a little adjustment in the equation. We can now say that V of S is the maximum of all the possible values of Q of S comma A, right? So let's utilize this fact and replace V of S dash as a function of Q. So Q S comma A becomes R of S comma A plus gamma of summation P S A S dash and maximum of the Q S dash A dash. So the equation of V is now turned into an equation of Q, which is the quality. But why would we do that? Now, this is done to ease our calculations because now we have only one function Q, which is also the core of the dynamic programming language. We have only one function Q to calculate, and R of S comma A is a quantified metric which produces reward of moving to a certain state. Now the qualities of the actions are called the Q values, and from now on we will refer to the value footprints as the Q values. An important piece of the puzzle is the temporal difference. Now temporal difference is the component that will help the robot calculate the Q values with respect to the changes in the environment over time. So consider our robot is currently in the mark state and it wants to move to the upper state. One thing to note that here is that the robot already knows the Q value of making the action, that is moving to the upper state. And we know that the environment is stochastic in nature and the reward that the robot will get after moving to the upper state might be different from an earlier observation. So how do we capture this change, the real difference? We calculate the new Q S comma A with the same formula and subtract the previously known Q S A from it. So this will in turn give us the new QA. Now the equation that we just derived gives the temporal difference in the Q values, which further helps to capture the random changes in the environment which may impose. Now the new Q S comma A is updated as the following. So Qt of S comma A is equal to Qt minus 1 S comma A plus alpha TDT of A comma S. Now here alpha is the learning rate which controls how quickly the robot adapts to the random changes imposed by the environment. The Qt S comma A is the current state Q value and the Qt minus 1 S comma A is the previously recorded Q value. So if we replace the TD S comma A with its full form equation, we should get Qt of S comma A is equal to Qt minus 1 of S comma A plus alpha into R of S comma A plus gamma maximum of Q S dash A dash minus Qt minus 1 S comma A. Now that we have all the little pieces of Q learning together, let's move forward to its implementation part. Now this is the final equation of Q learning, right? So let's see how we can implement this and obtain the best path for any robot to take. Now to implement the algorithm, we need to understand the warehouse location and how that can be mapped to different states. So let's start by recollecting the sample environment. So as you can see here, we have L1, L2, L3 till L9. And as you can see here, we have certain borders also. So first of all, let's map each of the above locations in the warehouse to numbers or the states so that it will ease our calculations, right? So what I'm going to do is create a new Python 3 file in the Jupyter notebook and I'll name it as QLearning NumPy. Okay, so let's define the states. But before that, what we need to do is import NumPy because we're going to use NumPy for this purpose. And let's initialize the parameters, that is the gamma and alpha parameters. So gamma is 0.75, which is the discount factor, whereas alpha is 0.9, which is the learning rate. Now next what we're going to do is define the states and map it to numbers. So as I mentioned earlier, L1 is 0 and till L9 we have defined the states in the numerical form. Now the next step is to define the actions, which is, as mentioned above, represent the transition to the next state. So as you can see here, we have an array of actions from 0 to 8. Now what we're going to do is define the reward table. So as you can see here, it's the same matrix that we created just now, that I showed you just now. Now, if you understood it correctly, there isn't any real barrier limitation as depicted in the image. For example, the transition L4 to L1 is allowed, but the reward will be 0 to discourage that path. Or in tough situation, what we do is add a -1 there so that it gets a negative reward. Now in the above code snippet, as you can see here, we took each of the states and put ones in the respective state that are directly reachable from the certain state. Now if we refer to that reward table once again which we created, the above array construction will be easy to understand. But one thing to note here is that we did not consider the top priority location L6 yet. We would also need an inverse mapping from the states back to its original location, and it will be cleaner when we reach to the utter depths of the algorithms. So for that, what we're going to do is have the inverse map location. State to location, we will take the distinct state and location and convert it back. Now what we'll do is we'll now define a function getOptimal, which is the getOptimal route, which will have a start location and an end location. Don't worry, the code is big, but I'll explain you each and every bit of the code. Now the getOptimalRoute function will take two arguments, the starting location in the warehouse and the end location in the warehouse respectively. And it will return the optimal route for reaching the end location from the starting location in the form of an ordered list containing the letters. So we'll start by defining the function by initializing the Q values to be all zeros. So as you can see here, we have given the Q values to be 0, but before that, what we need to do is copy the reward matrix to a new one. So this is the rewards new. And next again, what we're going to do is get the ending state corresponding to the ending location. And with this information, automatically we'll set the priority of the given ending state to the highest one. Right? We are not defining it now, but we'll automatically set the priority of the given ending state as 999. So what we're going to do is initialize the Q values to be 0. And in the Q learning process, what you can see here, we are taking I in range 1000 and we're going to pick up a state randomly. So we're going to use the np.random rand int. And for traversing through the neighbor location in the same maze, we're going to iterate through the new reward matrix and get the actions which are greater than 0. And after that, what we're going to do is pick an action randomly from the list of the playable actions nearest to the next state. We're going to compute the temporal difference, which is TD, which is the rewards plus gamma into the Q of next state. And we'll take np.argmax of Q of next state minus Q of the current state. We're going to then update the Q values using the Bellman equation. As you can see here, we have the Bellman equation and we're going to update the Q values. And after that, we're going to initialize the optimal route with the starting location. Now here we do not know what the next location yet. So initialize it with the value of the starting location, which again is the random location. Now we do not know about the exact number of iterations needed to reach to the final location. Hence, while loop will be a good choice for the iteration. So we're going to fetch the starting state, fetch the highest Q value penetrating to the starting state. We go to the index of the next state, but we need the corresponding letter. So we're going to use that state to location function we just mentioned there. And after that, we're going to update the starting location for the next iteration. And finally, we'll return the route. So let's take the starting location of L9 and the end location of L1 and see what part do we actually get. So as you can see here, we get L9, L8, L5, L2, and L1. And if you have a look at the image here we have, if we start from L9 to L1, we got L8, L5, L2, L1, L8, L5, L2, L1. That would yield us the maximum value or the maximum reward for the robot. So now we have come to the end of this Q learning session, and I hope you got to know what exactly is Q learning with the analogy all the way starting from the number of rooms. And I hope the example which I took, the analogy which I took, was good enough for you to understand Q learning, understand the Bellman equation, how to make quick changes to the Bellman equation, and how to create the reward table, the Q table, and how to update the Q values using the Bellman equation. What does alpha do? What does gamma do?
Welcome to today's session on deep learning tutorial with TensorFlow. So let us move forward and have a look at the agenda for today. So this is the agenda for today, guys. We'll understand what exactly is deep learning and how it works. So we'll look at the motivation behind deep learning and how it actually evolved. Then we'll focus on single layer perceptron, which are nothing but the early deep learning models. We'll also look at various examples of single layer perceptron. And guys, when I talk about perceptron, these are nothing but the artificial neurons. And what are neurons? Neurons are your brain cells. Then we'll also understand the limitations of single layer perceptron that led to the evolution of multi-layer perceptron. We'll understand how multi-layer perceptron overcame those limitations, and we'll also look at various examples of multi-layer perceptron. In the beginning, I'll be also talking about the course structure, how the course is structured, what all topics will be covered in what all modules. So let us move forward and see how the course is structured. What are the various modules? So this is how our course looks like. We'll start with the introduction to deep learning. That is how deep learning evolved. What were the algorithms that were present before deep learning? Then we'll understand the fundamentals of neural networks. Neural networks are nothing but the networks that try to mimic your brain. Then we'll understand the fundamentals of deep networks. Deep networks are nothing but complex neural networks, or you can even say that these are subsets of neural networks. Then we'll introduce you to TensorFlow, which is nothing but a library of Python that is used for deep learning. Then we'll focus on various types of neural networks. First is convolutional neural networks that is used for image recognition. Then we'll focus on recurrent neural networks, and then finally RBM and autoencoders. So this is how our course will be structured. So guys, we'll move forward now and understand what exactly is deep learning and how it works. So guys, let us understand deep learning with an analogy. So how do you think our brain is able to identify the difference between a dog and a cat? So the reason is, since the day we are born, we are actually seeing different types of cats and dogs in our day-to-day life. And because of that, we are able to identify the difference or spot the difference between the two, that is dog and a cat. Even if we see different types of cats and dogs, we still know which is a cat and which is a dog. So this is because we have seen a lot of cats and dogs in our entire life. But what if I want a machine to do that task for me? So how will a machine identify whether the given image is of a dog or a cat? So one way of doing that is we can train our machine to a lot of images of different cats and dogs, that is different breeds of cats and dogs. And then what will happen once our training is done, we can provide it with an input image. Then we'll manually extract certain features. Features like nose, whiskers, colors, edges, it can be anything. The important features which actually helps us in classifying whether the input image is a cat or a dog. Then we make a machine learning model with that. And once it is done, our machine learning model is able to predict whether the input image is of a cat or a dog. But if you notice here, one very big disadvantage with this is we have to manually extract features. Features such as nose, whiskers, all those features we have to manually extract it and provide it to our machine learning model. And trust me guys, in every scenario it is not possible. If you have large number of inputs, you cannot do that. You cannot manually extract the features, or basically you can say columns which are important for you in order to predict what the object is, right? And that led to the evolution of deep learning. So what happens in deep learning? We skip the manual step of feature extraction. So what we do, we directly take the input image and feed it to our deep learning algorithm. And because of that, what happens, whatever features are we already manually provided, apart from that, there might be many other features which are important. For example, if our features don't include the length of the neck, and that is one of the major features in order to identify or classify whether it is a cat or a dog. Now what will happen, our algorithm will automatically determine that feature and will take into consideration, and then it will classify whether the input image is a cat or a dog. So what happens here, we provide an input image of a dog, and then it will automatically learn certain features even if we don't provide it with those features. And after that, it will give us the probability, and according to this particular scenario, it says 95% chances of being a dog, 3% chances of some other animal, similarly 2% chances of some other animal. So since the highest probability goes with the dog, so the prediction says that the object or the input image is nothing but a dog. Fine guys, so we'll move forward and we'll understand how exactly deep learning works. So the motivation behind deep learning is nothing but the human brain. As we have seen in the previous analogy as well, what we are trying to do, we are trying to mimic the human brain. We are trying to mimic the way we think, the way we take decisions, the way we solve problems. We are trying to make sure that we have a system that can mimic our own brain. So obviously the motivation for deep learning has to be our brain. and how our brain works with the help of our brain cells, which we call neuron. Now let us understand how a neuron works, and let me tell you guys, this is what we think how a neuron works. This is what our studies tell us. So yeah, so these are called dendrites. So dendrites receive signals from other neurons, and then it passes those signals to the cell body. Now this cell body is where we perform certain function. It can be a sigma function. That's what we believe. We believe it performs a sigma function. That is nothing but sums all the inputs. Then through axon, what happens? These signals are fired to the next neuron. And the next neuron is present at some distance, and that distance is nothing but synapse. So it fires only when the signals coming from the cell body exceeds a particular limit. Then only the cell or this neuron will fire the signals to the next neuron. And this is how the neuron or the brain cell works. And we take the same process forward and we try to create artificial neurons. So let us understand why we need artificial neurons with an example. So I have a data set of flowers, say, and that data set includes sepal length, sepal width, petal length, and petal width. Now what I want to do, I want to classify the type of flower on the basis of this data set. Now there are two options. Either I can do it manually. I can look at the flower manually and determine by its color or any means, and I can identify what sort of a flower it is. Or I can train a machine to do that. Now let me tell you the problem with doing this process manually. First of all, there might be millions of inputs that will be given to you. And for a human brain to perform that particular task is next to impossible. And at the same time, we always get tired at some point of time, right? So we cannot just continue working for a long period of time in single stretch. And the third point is human error risk, which is always there. So these are a few limitations with the human brain. So what we can do, we can train a machine to do that task for us, or we can put our brain inside a machine so that it can classify the flowers for us. So with this, what will happen? The machine will never get tired and it will make better predictions as well. So this is why we create artificial neurons, so that there's a system present that can mimic our brain. And this is what exactly happens. So this particular artificial neuron can actually classify the flowers, or you can say can divide the flowers on the basis of certain features. In our case, it is sepal length, sepal width, petal length, and petal width. So on that basis, it can classify the two flowers. So what we need here, we need some sort of a system that can actually separate the two species. And what is that system? Is nothing but an artificial neuron. So we need artificial neuron, and one type of artificial neuron is a perceptron. Now let me explain you perceptron with the flow diagram that is there in front of your screen. Now over here, what happens, we have set of inputs like x1, x2, dash, dash, dash till xn. Now these inputs will be multiplied with their corresponding weights, which is w1, w2, w3 till wn in our case. Now these weights actually define how important our input is. So if the value of weight is high, we know that this particular input is very, very important for us. After multiplication, all of these are summed together and then it is fed to an activation function. Now the reason of using activation function is to provide a threshold value. So if our signal is above that threshold value, our neuron, or you can say our perceptron, will fire, else it won't fire. So that is the reason why we use an activation function. There can be different types of activation function. There can be sigmoid, there can be step function, sine function. Depending on our use case, we define the activation function. Now the main idea was to define an algorithm in order to learn the values of the weights, which are W1, W2, W3 in our case, to learn the values of the weights that are then multiplied with the input features in order to make a decision whether a neuron fires or not. In context of pattern classification, which is in our case flowers, so we are trying to classify the two species of flowers, such an algorithm could be useful to determine if a sample belongs to one class or one type of a species or another class or another type of the flower. We can even call perceptron as a single layer binary linear classifier, to be more specific, because it is able to classify inputs which are linearly separable. And our main task here is to predict to which of the two possible categories a certain data point belongs based on a set of input variables. Now there's an algorithm on which it works, so let me explain you that. So the first thing we do is we initialize the weights and the threshold. Now these weights can actually be a small number or a random number, and it can even be 0. So it depends on the use case that we have. Then what we do, we provide the input and then we calculate the output. Now when we are training our model or we are training our artificial neuron, we have the output values for a particular set of inputs. So we know the output value. But what we do, we give the input and we see what will be the output of our particular neuron. And accordingly, we need to update the weights in order to reduce the loss, or you can say in order to reduce the difference between the actual output and the desired output. So what happens, let me tell you that. So we need to update the weights. So how we are going to update the weights is, we can say the new weight is equal to the old weight plus the learning rate. Learning rate, we'll discuss about it later in the session. But generally we choose learning rate somewhere between 0.5 to 0.01. After that, what happens, we find the difference between the desired output and the actual output. And then we multiply it with the input. So on that basis, we get a new weight. So this is how we update the weights. And then what happens, we repeat the steps 2 and 3. So we are going to repeat the steps 2 and 3. That is, we are going to apply this new weight. Again, we are going to calculate the output. Again, we are going to compare it with the desired output. And if it matches, then it's fine. Otherwise, we are going to update it again. So this is how the whole perceptron learning algorithm works. And don't worry guys, I'm going to show it to you practically how it actually works in my pie chart. Fine guys, so we'll move forward and we'll see the various types of activation functions. So these are the various types of activation functions that we use, although there can be many more activation functions. Again, I'm telling it depends on your use case. So we have a step function. So if our output is actually above this particular value, then only our neuron will fire, or you can say the output will be +1. Or if it's less than this particular value, then we'll have no output, or we'll say 0 output. Similarly for the sigmoid function as well, and same goes for sine function. So let us move forward and we'll focus on various applications of this perceptron. Now, as I've told you earlier as well, it can be used to classify any linearly separable set of inputs. Now, let me explain to you with the diagram that is there in front of your screen. So we have different types of dogs and we have horses, and we want a line that can separate these two. So our first iteration will produce this sort of a line. But here we can notice that we have error here. As we have classified one of the horses as a dog and a dog as a horse. So error is 2 here. Similarly, now what happens, we have updated the weights. Now after updating the weight, what happens, our error has reduced. So what happens now, we have actually classified all the horses correctly, but one dog we have classified wrong and we have considered it as a horse. So our error becomes 1. Once again, what will happen, if you can remember, the step 2 and 3 of our perceptron learning algorithm will be done. And then after that, our weights will be updated and our desired output will become equal to our actual output, and we get a line something like this. So what we have now, we have properly classified dogs and horses. So this line separates both of them. This is how we can actually use a single layer perceptron in order to classify any linearly separable set of inputs. Now we can even use it in order to implement logic gates, that is OR and AND. Now let me tell you how you can do that. First we'll look at OR gate. Now in OR gate, what happens here is the truth table. Truth table, according to that, we have two inputs, x1 and x2. So if both are 0, we get a 0. If any one of the input is high or any one of the input is 1, we get the output as 1. So what we need to do is we need to make sure that our weights are present in such a way that we get the same output. So how we have done that, when the value of weight is equal to 1, and then we provide the input x1 and x2, after passing through this activation function, we get this sort of a graph, which is the graph for our OR gate. Now, if you want, I could use a pen and I can explain it to you. Now we have x1 and x2 as inputs. So we provide first input as 0, x1, and this also as 0. So 0 into 0 is again 0, 0 into 0 is 0. And then we pass it through this activation function. Now we need to make sure that whatever value that comes here should be greater than 0.5, then only our neuron or the perceptron will fire. But since this value is actually less than 0.5, so the neuron won't fire and our output will be 0, as you can see it over here. Now let's take the other set of inputs. Now our x1 is 0 and our x2 is 1. So 1 into 1 will be obviously 1. Now in this case, our output is bigger than 0.5. Then what will happen? Our neuron will fire and will get 1, the output 1 here, as you can see it in the graph. Similarly, when my x1 is 1 and x2 is 0, in that case also, our output is greater than 0.5, our neuron will fire and will get this sort of a graph. When I talk about 1, 1, then our output will be 2, which is greater than 0.5. So we get an output that is 1. And this is how we get the graph. So this is how we get this graph. And now if you notice, with the help of the single layer perceptron, we are able to classify the ones and zeros. So this line, anything above this line is actually 1, and anything below this line, we have zeros. So this is how we are able to classify or able to implement OR gate. Similarly, when I talk about AND gate as well, so there's a difference in the truth table of AND gate. In AND gate, what happens? We need to make sure that both of our inputs are high in order to get a high output. If any of the input is low, we get a low output. And that's the reason we choose an activation function that is 1.5, which means that if our value or the output is above 1.5, then only our neuron will fire and we'll get 1 here. And there is only one case, that is when both the inputs are high. So when both the inputs are high, let me just use my pen again and I'll explain to you. So x1 is 1, x2 is 1, we get something which is 2, which is obviously greater than 0.5. Pardon me for my writing, but yeah, this is how it is. Yeah. So 1 plus 1, 2, which is obviously greater than 0.5. So what we get, our neuron fires and we get 1 here. But for the rest of the inputs, all will be less than 1.5. So that is why our neuron doesn't fire and we get a 0 output. Don't worry guys, I'll actually tell you how to implement it. I'll open my PyCharm and I'll be showing it to you practically how to implement these gates. So for that, what I'm going to do is I'm going to first import a Python library called TensorFlow. The installation guide of this particular library is present in an LMS for both Windows as well as for Linux. So you can just go through it and it's very easy to install that. And I'll actually execute this practically later in the session. You don't need to worry about it. So this is how we can implement and OR gate. So let's move forward guys and we'll actually understand with a use case that is of MNIST dataset. The reason for using MNIST dataset is because it is already clean and will be a perfect example for this. Now what this MNIST dataset contains, it basically contains handwritten digits from 0 to 9, and in that dataset we have 50,000 training images along with 10,000 testing images. So we will train our model with those 55,000 training images, and then we are going to test the accuracy of a model with the help of those 10,000 testing images. And for all of this, we need to understand first what exactly is TensorFlow. So let us move forward guys and we'll understand TensorFlow, and then we are going to implement all these things that we have discussed, that is AND gate, OR gate, and the MNIST dataset that I'm talking about. So let us move forward guys and understand what exactly is TensorFlow. Now what is TensorFlow? As I've told you earlier as well, we use this TensorFlow library in order to implement deep learning models. And the way the data is represented in the deep learning model is called tensors. Now what are tensors? Now tensors are just the multi-dimensional arrays, or you can say an extension of two-dimensional tables, matrices, to data with higher dimension. Now let me explain to you with the examples that are there in front of your screen. So this particular data is nothing but a tensor of dimension 6, because we have 6 rows and we have only one single column. Now over here we have 4 columns as well as 6 rows, so this becomes a tensor of dimension 6, 4. Similarly over here as well, so we have another dimension, that is the third dimension, in which we have 2 values. So we consider this as a tensor of dimension 6, 4 and 2. So this is nothing but a way of representing data in TensorFlow. Now if you consider the TensorFlow library, at its core it is nothing but a library that performs matrix manipulation. That is what TensorFlow is. Now let us move forward and understand TensorFlow in a bit detail. So as the name tells that it consists of 2 words, tensor as well as flow. Now we understood what exactly tensor is. We saw it in the previous slide as well. Now when I talk about flow, it is nothing but a data flow graph. So let me just give you an example that is there in front of your screen. So we talked about weights and inputs. So we provide these weights and inputs and we perform a matrix multiplication. So weight is one tensor, X input is one tensor, then we perform matrix multiplication. After that, we add a bias, which we'll actually see it later in the session. You don't need to worry about this term. Then what we do, we add all of these. So what is this? This is nothing but the sigma function in the perceptron that we have seen. Then we pass it through an activation function, and the name of that activation function is RELU or RELU, or you can say it, and then our neuron will fire. So this is nothing but a flow, or you can say a data flow graph. Now let us understand a few code basics of TensorFlow. Now the TensorFlow programs actually consist of 2 parts. One is building a computational graph and another is running a computational graph. So we'll first understand how to build a computational graph. Now you can think of a computational graph as a network of nodes, and with each node known as an operation and running some function that can be as simple as addition or subtraction, or it can be as complex as, say, some multivariate equation. Now let me explain it to you with the code that is there in front of your screen. So the first thing you do, you import the TensorFlow library. Then what you do, you define 2 nodes, and these nodes are constants. So we'll call that function, we'll call it as tf.constant, and we'll provide a value that is 3, and it is nothing but a float number of 32 bits. Similarly, we defined one more node, which is a constant, and it contains value 4. So these are nothing but your constant nodes. So this is basically what computational graph is. So basically we have built a computational graph, and in this graph each node takes 0 or more tensors as inputs and produces a tensor as an output. And one type of node is a constant that I've told you earlier as well. And these TensorFlow constants, it takes no inputs and it outputs a value which is stored internally. Now what I'll do, I'll actually execute this in my PyCharm. So for that I'll open it. So this is my PyCharm, guys, and I've already installed TensorFlow, and I'm telling it to you again that the installation guide for your TensorFlow in Windows as well as Linux is present in your LMS. So just go through it and it's pretty easy. So the first thing that I need to do is import the TensorFlow library. For that I'm going to type in here import TensorFlow as TF. So if you're familiar with the Python basics, you know what it means actually. So I'm importing TensorFlow library, and in order to call that I'm going to use the word TF. So after that, I'm going to define my node 1 and node 2, which are constant nodes. So for that, I'm going to type in here node 1 equal to tf.constant. And then I'm going to define the constant value in this. So it'll be 3, and it'll be a float value of tf.float of 32-bit. All right. And now I'm going to define my second constant node. So I'll type in here node 2 tf.constant. I'll put 4 in here and 4. That's it. And so the tf.float 32 will be present implicitly. I don't need to do that again and again. So I have created a computational graph here. So what if I print it now? So let us see what will be the output. Node 1 comma node 2. Let's go ahead and run this and see what happens. If you notice here that printing the nodes does not output the values 3 and 4. You might be expecting that, right? That it should print 3 and 4. But instead they are nodes that when evaluated would produce 3 and 4 respectively. So to actually evaluate the nodes, what we need to do is we need to run this computational graph. So let me show you that. For that, I'm again going to open the slides. So since I've told you earlier as well, we need to actually run this computational graph within a session. And what is this session? Its session actually encapsulates the control and state of the TensorFlow runtime. Now the code that is there in front of your screen, what it will do, it will actually create a session object, and then it invokes its run method to run enough of the computational graph in order to evaluate node 1 and node 2. And how it does that? By running the computational graph in a session. So now let me show it to you practically how it happens. So again, I'm going to open my PyCharm. This is my PyCharm, guys. So let me first comment this print statement, and now I'm going to run a session. So for that, I'm going to type in here ses equal to tf dot session, and now I'm going to print it. So for that, I'm going to type in print ses dot run, and what I want to run node 1 and node 2. So I'm going to type in here node 1 comma node 2. That's all. And now when I run this, it will actually give me the value 3 and 4. And yup, it does. It gives me the value 3 and 4. So what we did, we first built a computational graph. We first saw how to build basically a computational graph. And then we understood that these all are nodes. So in order to get their value, we need to evaluate those nodes, and how we can do that by running the computational graph inside a session. And when finally, when we run that session, we get the output 3 and 4, which is nothing but the values of those nodes. Fine, so I'll again open my slides. And the one thing that you must have noticed here is that it will always produce a constant result, right? So how to actually avoid that? So we saw how to run a computational graph as well. Now let me explain it to you with one more example. So this is one example in which we take 3 constant nodes A, B, and C, and we perform certain operations like multiplication, addition, and subtraction. And then we run the session, and then we finally close it. And this is the diagram how it looks like. So we have 3 constant nodes, C, B, A. A contains value 5, B contains 2, similarly C contains 3. So first we add C and B, then we add B and A. Then we get 2 other nodes, that is E and D. And then from that E and D, what we are going to do is we are going to subtract both of them, and then we get the final output. Now let me go ahead and execute this practically in my PyCharm. So this is my PyCharm again, guys. First thing I need to do is import TensorFlow as TF. Then we are going to define the 3 constant nodes. So first is A equals to tf.constant, and the value that will be there in A will be 5. Then I'm going to define one more constant node, that'll be btf.constant, and the value that'll be there in it will be 2. And then I'm going to define the last constant node, and tf.constant, the value that'll be there is 3. Alright, so we have 3 constant nodes, and now we are going to perform certain operations on them. For that, I'm going to define one node, let be d, which will be equal to tf dot multiply. So the two nodes that we want to multiply, so that'll be a comma b. And then there'll be one more node in order to perform some operation, that is addition. So tf dot add c and b. And then we're going to define one more node, let be f, and inside that node we're going to perform the subtraction operation, tf dot subtract d and e. So we have built a computational graph. Now we need to run it, and you know the process of doing that. Ses is equals to tf dot session. Then we are going to define a variable, let it be outs, outs, whatever name that you want to give in, and just type in a ses dot run f. Let's see if that happens or not. And then we're going to print it. So for that, I'm going to type in here print out. Let's go ahead and run this and see what happens. So we have got the value 5, which is correct, because if you notice our presentation as well, let me open it for you. Over here we get the value 5, similar to our implementation in PyCharm as well. So this is how you can actually build a computational graph and run a computational graph. I've given you an example. Now guys, let us move forward, because these are all the constant nodes. What if I want to change the value that is there in the node? So for that, we don't use the constant nodes. For that, we use placeholders and variables. Let me explain it to you. First, I'll open my slides. So since these are all constant nodes, so we cannot perform any operation. Once we have provided a value, it will remain constant. So basically, a graph can be parameterized except external inputs as well. And what are these? These are nothing but your placeholders. And these placeholders is basically a promise to provide values later. So there's an example that is there in front of your screen. Over here, these 3 lines are bit like a function or a lambda, in which we define 2 input parameters a and b, and then an operation possible on them. So we are actually performing addition. So we can evaluate this graph with multiple inputs by using feed underscore dict parameter. As you can see, we are doing it here. So we are actually passing all these values to our placeholders here. So these all values will be passed, and accordingly we'll get the output. So let me show you practically how it happens. So I'm going to open my PyCharm once more. I'll remove all of this, and yeah. So the first placeholder, I'm going to name it as a, tf dot placeholder, and what sort of a placeholder it'll be, so I'll consider it as float number of 32 bits. Similarly, I'm going to define one more variable as well, and I'm going to name it as b. Then I'm going to define an operation that I'm going to perform on them. So I'm just going to type in here adder underscore node equals to a plus b. And now our placeholders are currently empty. So as I told you earlier as well, placeholders are nothing but a promise in order to feed values later. So this is how we have built a computational graph. Now our next step is to start a session. So for that, I'm going to type in a ses equals to tf dot session, right? Since these placeholders are currently empty, and we know that these placeholders are nothing but a promise in order to provide them with certain values later. So let's go ahead and provide the values, or you can say a list of values. So I'm going to type in here print ses dot run adder underscore node, and then the values that I'm going to feed in. So basically I'm going to feed in a dictionary, a colon 3, a colon a list of integer values between 1 to 3, and one more will be b colon a list of integer values between 2 and 4. All right, so this is done. Now let us go ahead and execute this and see what happens. So we've got the output 3 and 7. So basically if you add 1 and 2, you get 3. Similarly, you add 3 and 4, you get 7. It's pretty easy mathematics, but my main focus was to make sure that you understand what are placeholders. So we understood what exactly are placeholders. Now it's the time to understand what are variables. So basically in deep learning, we typically want a model that can take arbitrary inputs. Now, in order to make the model trainable, we need to able to modify the graph to get new outputs with the same input. And what helps us to do that? Variables basically allows us to add trainable parameters to our graph. So in order to declare variables, what we do is, you can refer the code that is there in front of your screen. So we have taken two variables and one placeholder, and the first variable has a value 0.3, the another variable has minus 0.3, and the placeholder, obviously it will remain empty, and then later on we feed in some values to it. Then we create a linear model, or you can say some operation in which we are going to multiply this W with X, and then we are going to add a bias or a B value to it. Then what we need to do is we need to initialize all the variables in the TensorFlow program. So for that, you must explicitly call a special operation, which is a tf.global variable initializer, and then just directly run the session. Now let us go ahead and execute this practically, guys. Let me remove all of this. Yeah. So our first variable will be W, and we are going to call in tf.variable. And in that variable, we are going to store a value which is 0.3. And it is of a float type 32-bit. So just type in here tf.float 32. Yeah. Then we're going to define one more variable, let it be B. So I'm going to type in here tf.variable. And the value of this variable will be minus of 0.3. Again, it is float type of 32-bit. So just type in that tf.float 32. Now I'm going to define a placeholder, that is X. X is equals to tf dot placeholder, and it is again a float type 32-bit. And then some operation that we are going to perform. So I'm going to type in here linear underscore model equal to W multiplied by our X value, that is a placeholder, and then we want to add a bias to it or B value to it. All right. Now, as we have seen earlier as well, in order to initialize constants, we call tf.constant, and their value will never change. But by contrast, variables are not initialized when you call tf.variable. So to initialize all the variables in the TensorFlow program, what you need to do is you need to explicitly call a special operation. And how you're going to do it, just type in here init equal to tf.global underscore variables underscore initializer. That's all. And then we're going to run a session. So you know the process, ses is equals to tf.session init. Now let's print it. And before that, what we need to do is we need to provide the X placeholder with some values. We're actually going to do that in the print statement itself. So I'm going to type it ses.run. Run what? Run a linear model. And the values that we are going to pass in X will be a dictionary again. And let me show you how you can do that. So X colon, and it'll be a list of values from 1, 2, 3, 4. Yeah, that's all. And we are going to run it now. So this is how we get the output. It's simple mathematics. What we have, the first value of W will be 0.3. And the first value of a B will be a minus 0.3, and the first value of X will be 1. So it'll be 3 minus 3, which is again 0. Similarly, for other values as well, you can calculate it. It's absolutely correct. So what we have done, we have created a model, but we don't know how good it is yet. So let's see how we can actually evaluate that. For that, I'm again going to open my slides. So now in order to evaluate the model on the training data, we need a placeholder Y, as you can see in front of your screen, to provide the desired values, and we need to write a loss function. So this placeholder Y will actually be provided with the desired values for each set of inputs. And then we're going to calculate the loss function. And how are we going to do that? We're going to minus the actual output with the desired output, and then we're going to do the square of it. After that, we're going to sum all of these squared deltas, and then we're going to define one single scalar as loss. So this is how we are actually going to calculate the loss. And then after that, we need to provide the values to X and Y placeholders. So what I'm going to do, I'm going to open my PyCharm, and then I'm going to show you how correct our model is on the basis of the values that we provide to y placeholder. So guys, this is my PyCharm again, and since here what I'm going to do is I'm going to define a placeholder first. Y is equals to tf dot placeholder, tf dot float 32. So I'm going to type in a tf dot float 32 square delta. I've explained you all these things, but yeah, I'm going to tell it to you again as well. Don't worry about it. tf dot square the actual output minus the desired output, and then I'm gonna sum all of those losses, or you can say square deltas. tf dot reduce underscore sum. So I'm gonna type in here square deltas. Then finally print it. So I'm gonna type in sys dot run loss x colon 1 comma 2 comma 3 comma 4 0 comma minus 1 comma minus 2 comma minus 3, and that's all, and we are good to go. Let's run it and see what will be the loss. So the loss is 23.66, which is very bad. Now our next step is to realize how to actually reduce this loss. So let's go ahead with that. I'm going to open my slides once more. So in order to minimize the error, now in order to reduce this loss, TensorFlow provides optimizers that slowly change each variable in order to minimize the loss function. And the simplest optimizer is gradient descent. In order to do that, we have to call the function called tf.gradients. So as you can see it in the code itself, so we have a tf.train.gradient descent optimizer, and this is nothing but the learning rate 0.01. Then train equals to optimizer dot minimize the loss. So we're going to call this optimizer, which is nothing but the gradient descent optimizer, in order to minimize the loss. And then we are going to run it. So let's see if that happens or not. So for that, again, I'm going to open my PyCharm. And over here, let me first comment this print statement. And now I'm going to type in here optimizer equals to tf dot train gradient descent optimizer, and the learning rate will be 0.01. Now I'm going to type in here train equal to optimizer dot minimize loss. And then now let's go ahead and run this. Sys dot run init sys dot run, and we're going to feed in values to our x and y placeholders. Train comma x will have values 1 2 3 4, and y will have values 0 comma minus 1 comma minus 2 comma minus 3. Print sys dot run w comma p. Now let me first go ahead and comment these lines. All right, so I've just made a mistake here. This is in uppercase W, and yeah. So now we are good to go, and let's run this and see what happens. So these are our final model parameters. So the value of a W will be around 0.999969, and the value of our B will be around 0.9999082. So this is how we actually build a model, and then we evaluate how good it is, and then we try to optimize it in the best way possible. So I've just given you a general overview of how things works in TensorFlow. So now is the time to actually implement the AND and OR gate that I was talking about at the beginning of the session. So for that, let me first remove all of this. Yeah. Now in order to implement AND gate, our training data should consist of the truth table for AND gate. And we know that truth table, and we know that if any of the input is low, then the output will be low, and if both the inputs are high, then the output will be high. One thing to note here, guys, is that the bias is implemented by adding an extra value of 1 to all the training examples. So yeah, enough with the explanation. Let's go ahead and code it. So I'm going to type in here t comma f equal to 1 point comma minus 1 point. and bias will always be 1. So I'm going to type in here bias is equals to 1.0. And now I'm going to provide the training data. So for that, I'm going to type in train underscore in equal to, if one input is true and the another input is also true, then we have bias. Then again, if one input is true, the other input is false, then also we have bias. Similarly, one input is false, another input is true, then we have bias. And then finally, when both the inputs are false or 0, then we have bias, right? This is our training data, and the train out will type in here as the output basically, train underscore out will be equal to, so yeah, if both the inputs are true or both the inputs are 1, then the output is true. Oops, I forgot a comma everywhere. Let me just go ahead and do that. Yeah. So if both the inputs are true, the output will be true. If any of the input is false, the output will be false. So I'm just going to type in here false everywhere because there's only one condition in which we have the true output. All right. So this is done now. Now, as we know that TensorFlow works by building a model out of empty tensors, then plugging in known values and evaluating the model like we have done in the previous example. Since the training data that we have provided will remain constant, the only special TensorFlow object we have to worry about in this case is our 3x1 tensors of vectors. And now what we are going to do, we are going to define a variable and we are going to put in some random values in it. So I'm just going to type in tf.variable and generate the random function tf.random underscore normal 3,1. Now what it is basically a variable. So its value may be changed on each evaluation of the model as we train, with all values initialized to normally distributed random numbers. Now that we have our training data and weight tensor, we have everything needed to build our model using TensorFlow. So what we need to do, we need to define an activation function. And we are going to define a step activation function or step function. So for that, what I'm going to write here is a function step. We're going to define our own step function, although you can use the predefined function as well. That totally depends on you. I'm going to type in here is greater equal to tf dot greater x comma 0. Then we're going to define one more variable as float tf dot to underscore float is underscore greater. Then we're going to define one more variable, a doubled equal to tf dot multiply as underscore float comma 2. Then return tf dot subtract doubled comma 1. So now this is how we have defined our step function. So with the step function defined, the output error and the mean squared error of our model can be calculated in one short line each. Let me show you how you can do that. So just type in here output equal to, call that function that is step tf dot matrix multiplication matmul train underscore in comma w. Now for error, we're going to type in here error equals to tf dot subtract train underscore out comma output. And for mean squared error, I'm going to type in here MSC equal to tf dot reduce underscore mean tf dot square and then error. Now the evaluation of certain tensor functions can also update the values of variables like our tensor of weights w. So in our case, basically we're going to update the weights w. So first we calculate the desired adjustment based on error, then we add it to w. Now let me show you how we'll do that. So if you can recall, we have done that in the previous example as well, where we were updating the weights and biases. So now I'm going to type in here delta is equals to tf dot matmul, or you can say matrix multiplication, train underscore in, comma, error, comma, transpose underscore a equals to true. Then we're going to type in here train equal to tf dot assign w comma tf dot add w comma delta. So first matrix multiplication, and then we're going to add it all. The model has to be evaluated by TensorFlow session, which we have seen earlier as well. But before that, we also need to initialize all the variables. So first, let me just type in here ses equals to tf dot session, and then I'm going to type in here ses dot run tf dot initialize underscore all variables. So now what our next task is, in order to perform various iterations so that we get zero error. So what we're going to do, we're going to define a variable ERR and our target. So basically our ERR is nothing but our error, which can be equal to 1 or 0 because we are using binary output. So our error can be 1 and our target is to make it as 0, right? Now next what we're going to do, we're going to define epoch. Now you can consider right now epoch as nothing but the number of cycles, or you can say number of iterations that will be required in order to reach the desired output, or you can say in order to reduce the error to 0. So I'm just going to define that. So I'm going to type in here epoch, or you can give whatever variable name you want. And I'm going to type in here max underscore epoch equal to 0 comma 10. Which means that it'll start from the 0th epoch and our maximum value of epoch will be 10. Now I'm going to define while ERR is greater than target and epoch is less than maximum epoch, increase the value of epoch by 1. Then we're going to type in ERR ses.run mean squared error, comma train, and let's just finally print it and see what happens. Print epoch mean squared error colon ERR. So basically what it'll print the cycles or epoch and the error with respect to that particular cycle. So let us go ahead and execute this and see what happens. Oops, I've typed the spelling of square wrong. Pardon me for that. So I'm just going to make it right now. SQUARE. All right, let's go ahead and execute it once more. So yeah, in 3 epochs, we got the value of mean squared error as 0. That means it took us 3 iterations in order to reduce the output to 0. So this is how you can actually implement a logic gate, or you can say this is how you can actually classify the high and low outputs of a particular logic gate using single layer perceptron. Similarly, you can do that for OR gate as well. Consider this as an assignment. Come up with a code that can actually classify the high and low outputs of an OR gate. So what I'm going to do, I'm going to create a new Python file and I'm going to name it as mnist, which is nothing but the data set on which we are going to perform the classification of handwritten digits. So we're going to execute a use case, and I've told you earlier as well, in this mnist data set we have handwritten digits from 0 to 9, and it has 55,000 training sets as well as 10,000 test sets. So let us go ahead with that. So first thing I'm going to do is download the data set, but before that let me just import TensorFlow library as TF. And yeah, now let us download the data set. So for that I'm going to type in from tensorflow.examples.tutorial.mnist import input underscore data. And now I'm going to type in here mnist is equals to input underscore data underscore data dot read datasets. Type in here mnist underscore data comma 1 underscore hot equals to true. Now here mnist is nothing but a lightweight class which stores the training, validation and testing sets as numpy arrays. And when I talk about this 1 hot equals to true is nothing but 1 hot encoding. Now let me tell you what 1 hot encoding is. So for that, let me just comment few lines. So 1 hot encoding means that if I'm classifying something as a 7, so if I classify that my digit is 7, so how am I going to represent that? So I'm going to type in here 0, 1, 2, 3, 4, 5, 6. 7th bit will be active, so I'm going to type in there 1, then 8, and then 9. Similarly, if I want to represent, say, that my digit is 2, so I'm going to type in 0, 1. On the second digit, I'm going to type in here as 1, and the rest all zeros. So I hope you got the concept of what exactly 1 hot encoding is. So it's like only one output is active at a time. That's all. And I'm telling it to you again and again, we are going to discuss everything in detail in the upcoming sessions. So our next step is to start the session like we do every time. So I'm going to type in here ses equals to tf dot interactive session. So I'm just going to type in here interactive session. Yeah. And now we are going to build the computation graph by creating nodes for the input images and target output classes. So for that, I'm going to define some placeholders. For that, I'm going to type in x is equals to tf dot placeholder tf dot float 32, and the shape will be none, 784. Now the input images x will consist of 2D tensors of floating point numbers. Here we assign it a shape of say none, 784 as you can see. So where 784 is the dimensionality of single flattened 28 by 28 pixel MNIST image of handwritten digits. And what none indicates, it indicates that the first dimension corresponding to the batch size can be of any size. Means the first dimension can be of any size. We are not putting any restrictions on that. Now I'm going to define variable y, which will be nothing but our real labels, or you can say the desired output. Placeholder, and I'm going to type in here tf dot float 32, and I'm going to define the shape, which will be none, 10, because we have 10 classes. And similarly, y is also a 2D array where each row is one hot 10-dimensional vector indicating which digit class the corresponding MNIST image belongs to. And now next step is to define weight and biases for our model like we have done in the previous example. So we could imagine treating these like additional inputs, but TensorFlow has even a better way to handle them, and what it is nothing but variables. So let us go ahead and do that. I'm going to type in here w tf dot variable tf dot zeros. I'm going to initialize it to zeros, and the shape will be a 784, 10. So it's like 28 cross 28 pixels and 10 classes. Similarly, when I talk about bias, so it'll be tf dot variable tf dot zeros, initialize it to zeros, and the shape will be 10. We pass the initial value for each parameter in the call to tf.variable. Now over here, as we can see that we initialize both w and b as tensors full of zeros. And w is a 784 cross 10 matrix because we have 784 input features and 10 outputs. And when I talk about bias, b, it is a 10-dimensional vector because we have 10 classes. And we have learned that before we can use variables in a session, we need to first initialize it. So we're going to type in here ses a dot run, and after that I'm going to type in tf dot global underscore variables underscore initializer. All right, so we have initialized all the variables. So our next task is to predict the class and the loss function. So we can now implement our regression model. It takes only one line. We multiply the vectorized input image x by the weight matrix w and add the bias. So for that, I'm just going to type in here y equal to tf dot matmul, that is nothing but matrix multiplication, x comma w plus b. All right. So now we can specify a loss function very easily. So the loss indicates how bad the model's prediction was on single example. We try to minimize that while training across all the examples. So now we can specify a loss function, Now loss indicates how bad the model's prediction was on a single example, and we try to minimize that while training across all the examples. Now here our loss function will be cross entropy, or you can say the difference between the actual output and the predicted output. So for that, what I'm going to do, I'm going to make use of softmax cross entropy function. So here the loss will be the difference between the target output and the actual output. So for that, what I'm going to do is I'm just going to type in here a variable name. I'm going to name it as cross entropy. And yeah, entropy equals to tf dot reduce underscore mean. And then just type in here, let me just enter the next line, tf dot nn dot softmax underscore cross entropy with logits. And now over here I'm going to type in first our target output, which will be labels equals to y, comma our actual output, so it'll be logits is equals to y. That's all. So over here, let me just give you a brief idea what is happening. So labels is equals to y means that this is our target output and this is the actual output. So it'll be, we'll name it as y underscore. And so what exactly is happening? It will calculate the difference between the target output and for the actual output for all the examples. Then it is going to sum all of them and then find out the mean. So this is what basically this cross entropy variable will do. Now that we have defined our model and training loss function, it is straightforward to train using TensorFlow. Now we need to train our model. So TensorFlow has a wide variety of built-in optimization algorithms, as I've told you earlier as well. And for this example, we'll use steepest gradient descent with a length of about 0.5 to descend the cross entropy. So basically we're going to use a 0.5 learning rate, or you can say the step length. So for that, I'm going to type in here train underscore step equal to tf dot train dot gradient descent optimizer, and the step will be 0.5 and minimize the loss, so minimize cross entropy. That's it. So what this one line basically will do, it will minimize the cross entropy, which is nothing but the loss function that we have defined. Now in the next step, what we are going to do, we are going to load 100 training examples in each training iteration. So each time the training iteration happens, it will take 100 examples. We then run the train underscore step operation, which is nothing but to reduce the error, using feed underscore dict, which is nothing but we are going to feed the real values to our placeholder y. Now next what we are going to do, we're going to load 100 training examples in each training iterations, which means that for each iteration we'll take 100 training examples and we'll run the train underscore step operation, which is nothing but the optimizer here. And after that we are going to use a feed underscore dict to replace the placeholder tensors x and y with the training examples. So basically x will contain the input images and y will contain the actual outputs, or you can say the desired outputs. For that I'm going to type in here for underscore in range 1000 batch equals to mnist dot train dot next underscore batch 100 train underscore step dot run, and I'm going to feed in the values to x and y variable, feed underscore dict equal to x colon batch 0 comma y colon batch 1. That's it. Now we need to evaluate our model. We need to figure out how well our model is doing, and for that I'm going to make use of tf.argmax function. Now this tf.argmax function, let me tell you how it works. First I'm going to type in here correct underscore prediction equals to tf.equal tf.argmax y underscore comma 1 comma tf.argmax y comma 1. So basically this tf.argmax y underscore comma 1 is a label our model thinks is most likely for each input. That means it is our predicted value. While tf.argmax y comma 1 is a true label. It is there in our data set present already, and we know that it is true. So what we are doing, we are using tf.equal function to check if our actual prediction matches the desired prediction. So this is how it is working. So now what we're going to do, we're going to calculate the accuracy to determine what fraction are correct. We cast to floating point numbers and then take the mean and repeat. So now I'm going to define a variable for accuracy. So just going to type in accuracy equals to tf dot reduce underscore mean, tf dot cast correct underscore prediction, comma tf dot float 32. And what we can do finally, we can evaluate our accuracy on the test data. And this should give us accuracy of about 90%. So let us see if that happens. I'm going to type in here print accuracy dot evaluate eval feed underscore dict equal to x colon mnist dot test dot images comma y colon mnist dot test dot labels. That's it, guys. And I've done a mistake here. Instead of y, it will be y underscore, because this is our predicted value, not the actual value. And y we have considered as actual value, and this y underscore will be our predicted value. So this is the mistake that I made. So yeah, now I think the code looks pretty fine to me, and we can go ahead and run this. Let us see what happens when we run this. So guys, it is complete now, and this is the accuracy of a model, which is 91.4%, and which is pretty bad when you talk about a data set like MNIST. But yeah, with a single layer, it is very, very good. So we have got an accuracy of around 92% on the MNIST data set, which means that whatever the test data sets were there, that is like 10,000 test images. So on those test images, whatever the prediction our model has made are 91.4% correct. So guys, let me just give you a quick recap of what all things we have discussed. So first we saw what exactly is deep learning and how it is different from the traditional machine learning. Then we understood the motivation behind deep learning, which is nothing but your brain cells, which are called neuron. Then we understood the importance of why we need artificial neurons. And then we took the example of artificial neuron, which is called a perceptron. And we looked at a couple of examples in which we implemented the AND gate. We performed image classification on the MNIST datasets, which is nothing but handwritten images between 0 to 9. And we also implemented a couple of examples in order to understand what are placeholders, variables, and constants. So now there are certain limitations of single layer perceptron. Let us understand that. So in order to understand that, we'll take an example. So we have an XOR gate here, and this is the truth table. So according to this truth table, if any one of the input is high, then the output is high. And if both the inputs are low, output is low. And if both the inputs are high, output is low. So how can you classify the high and the low outputs with a single line? Definitely you can't. If you see the points, so one point is here, one is here, here, and here, in which these 2 points are high outputs and these two are low. So how can you classify with a single line? Definitely you can't. So now what's the answer to this? What if we use multiple neurons? So using multiple neurons, we can have 2 lines that can separate it. Now we can solve this problem if we have multiple neurons. So if we use 2 neurons, we can have 2 lines, and that can actually separate the high outputs as well as the low outputs. So this is where we use multi-layer perceptron with backpropagation. So what are multi-layer perceptron? Multi-layer perceptrons, they have the same structure like the single layer perceptron. The only difference is they have more than one hidden layer. So let me explain it to you with an example. So this is how a typical multi-layer perceptron looks like. So we have input layer, we have 2 hidden layers, and we have 1 output layer as well. Now typically each of these input layers are connected to the next hidden layer. Each neuron is connected to the next neuron present in the adjacent layer. But the neurons of the same layer are not connected to each other. Now what happens, a set of inputs are passed to these input layers, and the output of this input layer will be passed to the first hidden layer. Then after activation function of the first hidden layer, the output will be passed to the next hidden layer as the input, and similarly finally we get the output. Now you must be thinking how the model learns from here. So basically the model learns by updating the weights, and the algorithm that it uses is called backpropagation. So the backpropagation algorithm helps the model to learn and update the weights in order to increase the efficiency. So basically this process of from input layer to the output layer is called a feed forward process. And then when we backpropagate it in order to increase the efficiency or accuracy so that we can update the weights, that is called as backpropagation. We'll understand backpropagation in more detail. So let us move forward and understand what exactly is backpropagation. So what is backpropagation? Now let us understand this with an example. So we'll take the inputs as the leads generated from various sources. And my aim is to classify the leads on the basis of the priority. So there might be certain leads which won't make that much difference to me, whereas compared to the other leads. So in that case, I need to make sure the leads which are important gets the highest amount of weight. How am I going to do that? First, we'll see the output. Then accordingly, we'll calculate the error. And based on that error, we are going to update the weight. And this process is nothing but your back propagation in a nutshell, I can say, right? Although the algorithm is pretty complex, but yeah, this is basically what happens. So in order to classify the leads on the basis of priorities, we need to provide the maximum weight to the most important lead. And how are we going to do that? We're going to compare the actual output and the desired output, and according to the difference, we're going to update the weights. So what is backpropagation? So backpropagation is nothing but a supervised learning algorithm for multi-layer perceptron. Now let us understand what exactly is this algorithm. Let us understand this with an example that is there in front of your screen. So these two are our input neurons, these two are our hidden neurons, and these two are our output neurons. Now our aim is to get 0.01 and 0.99 as our output. And at the same time, we have inputs as 0.05 and 0.10. Initially, we take the weights as we can see it here. So 0.15 W1, 0.20 W2. So these are the weights. Plus we have two biases as well. Now what we need to do is we need to make sure that we have weights in such a way that we get output as 0.01 and 0.99. But let us see if we get that same output when we provide these kind of weights. The net input for this particular H1 will be what? It'll be W1 into I1, that is the first input, plus W2 into I2 plus B1 into 1, which gives us the answer as 0.3775. Similarly, the output for H1 will be nothing but the activation function, the output after the activation function. And we are using here sigmoid function because our brain also uses a sigmoid functions. That's what we believe in. And at the same time, it is easily differentiable. And if you differentiate it twice, you get the same number. So the output of H1 will be 0.59 something. So let me go back. So the output of this particular H1 will be 0.59 something. Then we're going to calculate the output of H2 as well similarly. And we get the output as 0.5968884378. Next up, we are going to repeat the process for the output layer neurons as well. So for the output layer, the net input will be W5 into out of H1, W6 into out of H2 plus B2, that is the bias. So we get the output somewhere like this. And then the net output for out O1 will be after the activation function, which will be 0.751. Similarly, the output for O2 will be 0.77. Now, if you notice that this is not the desired output. Our desired output was 0.01 and 0.99. What we got instead, we got 0.75 and 0.77. So what we need to do, we need to update the weight. So for that, we're going to calculate the error. Now error for output O1 is nothing but the sigma of 1 by 2 target minus output whole square. Target is nothing but your desired output and output is your actual output. So your error of output of O1 neuron will be 0.278. Similarly for O2 will be 0.023. So the total error comes down to 0.29 something. Next up, we need to update the weight so as to decrease this error. Now what we're going to do, we're going to first calculate the change in total error with respect to any of the random weight. We'll take W5 for example, just to show you. So we're going to calculate the change in the total error when we change with respect to the weight W5. So we're going to apply a chain rule here. So using partial derivative, we're going to calculate E total by delta of out O1 into delta of out O1 by delta of net O1 and then delta of net O1 by delta of W5. As you can see it from this particular example as well. E total, change in E total with respect to out O1, change in out O1 with respect to net O1 and change in net O1 with respect to W5. We're going to multiply that and we're going to get this particular term. And let us see how we do that. So how much the total error change with respect to the output? E total by E out 1, we're going to calculate it. It came around 0.741. Similarly, we're going to calculate how much does the output O1 change with respect to the net output. And we get this. After that, we're going to calculate it for net output change with respect to W5 also, we got this. And then finally what we did, we put all these values together and we found out the change in the error with respect to the change in weight W5, which came to up around 0.082167041. Now is the time to update the weight. So how are we going to update the weight? First thing we need to do is we need to follow this formula. So W5 plus is nothing but the updated weight, which is equal to W5 minus the learning rate into delta of E total by delta of W5. So which came to around 0.35891648. Similarly, we can calculate the other weights as well. So we're going to repeat the same process and we're going to calculate the other weights as well. Then again, we're going to see how much is the loss. If still the loss prevails, then we're going to repeat the same backpropagation learning algorithm again for all the weights. So this process will keep on repeating. So this is how backpropagation actually works. So now what I'm going to do, I'm going to make use of the same MNIST data set, and I'm going to increase the efficiency of that data set by 97 to 99% with the help of multi-layer perceptron. So guys, let us go ahead with that. So guys, as I've told you earlier as well, we are going to use the same MNIST data set which we have used in the single layer perceptron. So I'm going to perform a classification using multi-layer convolutional networks. Now, what are convolutional networks? Basically, these networks are used in order to classify images. We have a separate module on convolutional networks, so you don't need to worry about it right now. So basically what I'm doing is I'm just trying to show you that how we can increase the efficiency using the convolutional neural networks. You don't have to go in much detail about it because we'll be learning about it in the upcoming modules. I'm just giving you a general overview, or you can say a taste of how things work in convolutional neural networks. So we give an input image to this convolutional network. Then this input image is processed in the first convolutional layer using the filter weights. Now this result in 16 new images, one for each filter in the convolutional layer. The images are also downsampled, so the image resolution is decreased from 28 cross 28 to 14 cross 14. Now these 16 smaller images from the first convolutional layer are then processed in the second convolutional layer. We need filter weights for each of these 16 channels, and we need filter weights for each output channel of this layer. Now there are total 36 output channels, so there are total of 16 cross 36 equal to around 576 filters in the second convolutional layer. Now the resulting images are downsampled again to 7 cross 7 pixels. The output of the second convolutional layer is 36 images of 7 cross 7 pixels each. Now these are then flattened to a single vector of length 7 cross 7 cross 36, which is a 1764, which is used as the input to a fully connected layer with 128 neurons. And this feeds into another fully connected layer with 10 neurons, one for each of the classes, which is used to determine the class of the image, that is, which number is depicted in the image. So whatever number that we provide in, so basically the output layer, or you can say the last layer or the fully connected layer with 10 neurons, is used to determine the class or which digit is the input image of. Now the input image depicts the number 7, and the 4 copies of the images are shown here. So basically what happens, whatever filter we have in each layer, it will be present on the image pixels. So there'll be a dot product of the filter and the image pixel behind that. So we'll get a dot product there. We are going to repeat that same process in each of these layers, and for each of these layers and for each of these images. And we are calculating the dot product. So I hope you get the point. So let me just show you that we can increase the efficiency. So I've already run the code, and it will take time if I do it right now. So this is what the efficiency we ended up with. So it is 98.8%. So on the test sets, we had around 10,000 test samples, out of which we predicted 9,876 correctly. So which is pretty good actually, if you see. So because in the single layer perceptron example that we took, we were getting accuracy of around 92%. But here we are getting around 99%, which is actually very good. All right. So these are the topics that we have covered in today's session. We started with what exactly is deep learning. We took an analogy of classification of cats and dogs. We understood how humans identify the difference between a cat and a dog, and similarly how we can train a machine to do that. So we first looked at a machine learning model, and then we focused on certain limitations of that machine learning model, and then we understood that what exactly is deep learning. Then we saw how deep learning works. So the motivation behind deep learning is your brain cells. So we understood how our brain cells or neurons work. Then we focused on single layer perceptron, which are nothing but the early deep learning models, or you can say an artificial neuron, a single artificial neuron. We saw various examples of single layer perceptron as well as, for example, how to implement AND gate and how to perform classification on the MNIST data set. Then I introduced you to TensorFlow. We understood various code basics of TensorFlow. We understood what exactly are tensors as well. Then we focused on various limitations of single layer perceptron, and we took an example of XOR gate, in which I told you that if the data points are not linearly separable, then we cannot apply single layer perceptron. Then I introduced you to multi-layer perceptron that overcame the limitations of single layer perceptron. We understood the learning algorithm of multi-layer perceptron, that is the backpropagation algorithm. Finally, we saw a use case of the same MNIST data set in which we increased the efficiency from 92% to 99%. So the 92% was there in the single layer perceptron, but the same thing when we did with multi-layer convolutional networks, we got the efficiency which was around 99%. So these are the things that we have discussed today.
In
in this session, we are going to focus on certain fundamental questions and the thought processes you need to sit for a data science interview. And then from there on, we'll make the questions a bit more complex as we move on. And we will try to answer which kind of skill sets people normally look at when you appear for a data science interview in any company. So there are like various roles. Depending on that, the complexity and the variety in the questions might change. But this session will try to cover things in a fundamental level so that it prepares in a very common ground, irrespective of which role you are applying for. You might be able to at least get a perspective of what data science requires as such. Right. So with that note, let's see how we're going to structure the various questions that's going to come up in the session today. Majorly focusing on statistics, data analytics, machine learning, and probability. So these are the four headers under which the questions will come, and I'll discuss the question and how to approach a particular question in a structured approach, right? In a structured manner. And once we understand the problem well, we will see how does that thought process of coming out with the solution really works, right? So all of you know that data science is in booming state. Many openings are coming up in across the globe in various companies, irrespective of which company it is, which particular business it deals with. There is a potential of some applications from data science, right? They have a lot of data, different systems of their businesses generating the data with an enormous amount of volume, velocity, and variety. So with that sort of data asset that every company has now got, they want to now leverage it towards growing the business to the next level. So you have some of these stats here, like this is more than sufficient motivation that getting into data science would definitely land you in some really good professional career. Okay, so let's start with the questions here directly. We'll in the beginning start to focus on some of the fundamental questions, which is more for you to understand what is data science than a particular interviewer asking you that question. For instance, many people wonder what data science is all about, right? Though there are many online sources and blogs which describes data science, in a very nutshell, this is what it boils down to, right? A person who is very good in understanding the computer algorithms, a person who understands the statistics and mathematical ideas, and applying these two knowledges from the computer science and mathematics into a particular application, right? A business application where somebody sees a value coming out from the data. So how do you apply that? So that's how kind of data science approaches. So when you combine these two powerful concepts coming in from computer science and mathematics on a real world application, the sort of outcome that comes from particular data science project goes in a direction where people see a return on investment, right? So the people you bring in, the technology you bring in, the ideas you are working on, all of it should kind of give you some return on the investment you have put in. So that's where industries are started to looking at data science. So various subjects which are very important for you to know: statistics, computer science, applied mathematics, and then subjects like linear algebra, calculus, and a few more, right? So fundamentally, from computer science, algorithms and data structures might be very useful. From the mathematics or statistics and things like calculus, linear algebra, matrix factorization, and concepts like that. And from the application, it is more from your experiences from the industry. If you have worked for retail, you know how the business process in retail works, right? So people often also ask, from the technology end, do we need any sort of experiences in Python language, right? Python, or like, for example, R programming as well. So Python is one of the most looked out for kind of programming skills, particularly when you want to build solutions in data science domain. And with availability of libraries like NumPy, Pandas, Python has now established its ground very strongly in giving a very robust framework for designing data science solutions, right? And in particular, things which it has like list, dictionaries, tuples, and stats are one of its own capabilities, which sets Python in its own league of programming languages suitable for coming out with data science solutions. So there are many more other libraries as well apart from this. for building machine learning algorithms, but these are some common libraries that you would normally find people using it. And also with distributions like Anaconda, Python has shown its capabilities even for a production grade solutioning, right? Wherein you make sure that all the dependencies that one particular library has for building a data science solution is all in one place. So quite a popular programming language in the recent kind of happenings. Though R programming is also equally good in terms of producing a quick prototype for most of your modeling tasks, but Python is moving itself into a production grade where things can be deployed after the sort of prototype into a production environment, and it can face the customers from day one. So that sort of capabilities are coming up with Python. Right. So let's talk something a bit more specific with the data, right? So when people are doing any sort of data analysis, they normally face something that we know by the name selection bias, right? So what is actually a selection bias? The fundamental place where you start doing a data analysis is by selecting a representative sample, right? So that's where we normally start doing any analysis. So when you working for a company which has, let's say, 1 billion records in their databases, 1 billion is very large number, which represents various customers data, or it might also be depending on which feature you are working on and so on. So if you collect all of those, it might very easily come to 1 billion records, which is nothing but in a structured form number of rows. So with that an enormous amount of volume in the data, any analysis that you take up might have to have a lot of filters, like saying I only want to analyze a particular feature in my products, let's say, right? And I only want my customers from XYZ region, which is, let's say, top 4 region or top 5 regions. So you might put many features or filters like this. But later on, if you would like to do a kind of an analysis which covers most of your customer base, right? There comes the tricky situation of not being able to use the entire volume of 1 billion records. At the same time, you want to do a really good study or analysis based on what data you have. So in statistics, we normally use this idea of doing a kind of a randomized selection, right? So with this randomized selection, we make sure that out of these 1 billion records, we are choosing a small subset, let's say of 1 million, which is a true representation of the entire population. Right. But what happens with this is, while we do this 1 million record selection in a randomized way, there are chances that you might have certain bias in the analysis, obviously because you are not using the entire population. So selection bias is this particular sort of a characteristics while you are doing a sampling on a large population of data. Very common example for this is if you want to do a exit poll analysis of particular election, even before the election results are coming up, and you have not chosen a representative sample for doing that exit poll analysis, right? By that I mean you only have asked some questions for a selective few from the particular constituency, and they have an opinion towards one candidate, but that doesn't represent the entire opinion of the population in that constituency. So selection bias is very important to handle, and most of the time people employ things like randomized selection or selection sampling techniques like stratified sampling and so on. So by that you can minimize this selection bias. So these are some very generic questions. So let's start with some sort of statistical questions and also how to deal with different types of data. Okay. So doing any sort of data with a structured information. So structured information, I mean there are many rows and many columns, and it looks more like a tabular data, right? So with such a data in place, there are these two different formats, one saying the long and the wide. So let me show you an example here. You have a record of 2 customers, right? And you store just 2 values, which is the height and the weight. So these are in columns. So with these 2 customers, these height and weight being a separate column is one format, like a long format. Let's say transform this by having only one particular column which will say attribute, right? By that I will bring in these 2 columns as one column by calling that as an attribute and put the values in one column. So this sort of format is called the long one. So what really happens is, instead of having 2 separate columns for 2 of your attributes, you put both of those into one column. And by doing that, there are a lot of benefits with respect to the task you have in your hand, particularly in data visualization. Certain data visualizations would need you to not put your attributes as a separate column, but rather as the one column which can have the attribute names. So which might then go into building your legends, right? So these kind of techniques are kind of very common formats between like the long and the wide, and very frequently will people like deal with both these data formats, so depending on what task they are doing, particularly when we are building visualization dashboards. Okay, talking a bit more on the data analysis perspective, people like know that in stats normal distribution kind of is that one like the godfather of the distributions. You have many distributions which normally people try to see if is present in my data or not, but the moment people kind of see normal distribution coming up in any data, things are kind of bit easy to understand. And in typical case, any distribution, any data distribution that you would like to find out given data for analysis, it gives us a lot of characteristics around what the data is about. If I'm, let's say, analyzing the salaries of the employees in my company, right? I might see that there are some employees who are in that, like that thick crust in the center, where majority of the people are sitting with a moderate level of salary ranges. And then there are these sort of extremes on the left and the rights. So you are like very commonly people refer whenever you talk about salaries to a bell curve, right? And then they start talking about top 25% of the performers in my company, the bottom 25, and the middle one, which you like are sort of the normal performance. So this sort of bell curve distribution is very commonly understood and as well as used in doing many data analysis. So is the other distributions as well. But normal distribution has its own significance. So when somebody asks you around anything around normal distribution, the first thing you should visualize is the symmetrical bell-shaped curve, right? And the moment you get that bell-shaped curve in your imagination, start thinking of certain properties. Like what is the mean of a normal distribution? What is the standard deviation of a normal distribution? And in particular, a special case of normal distribution, which we call the standard normal distribution. So in that standard normal distribution, we know the mean is exactly 0 all the time, and the standard deviation is exactly 1, right? So there are different places where normal distributions are kind of used. And if you are comfortable with ideas like central limit theorem or the law of large numbers, you might want to relate that as well to normal distribution, particularly the central limit theorem, right? But the idea is a distribution which is symmetrical around the mean. So that's what a normal distribution is. So depending on which variable you are trying to analyze, even a given data set, whether it could be like an employee's salary or your sales in for a business of yours, right? Or your number of, let's say, interactions of the customers on your product. So any variable that you define can have a symmetrical bell-shaped distribution, which we normally refer by normal distribution. And the moment we understand that something follows a normal distribution, all these properties of that distribution is like revealed. So that's sort of the importance of doing any analysis around the distribution of data. And normal distribution, like very common one. And in many statistical techniques, in even model building exercises, if you have anything in a normal distribution, many other possibilities of applying certain modeling techniques comes out evidently there. And also there are many other modeling techniques in stats and machine learning where there is a fundamental assumption that things should follow a normal distribution. If it is not following, then the model is wrong. So there are many use cases of knowing what normal distribution is. But in simple terms, it's a symmetrical bell-shaped curve. Right. A/B testing. So quite a popular approach, people particularly who are working with product, right? And what happens is when you are as a company having many features inside a product. For instance, if LinkedIn is a company which has a web page, right? It has a lot of features inside that. You have some jobs portal in LinkedIn. You have places where you can connect to your professionals in the similar industry. You can also read about the posts people are doing in the portal and so on. So there are different places in the website with many features. So what happens is if LinkedIn as a company is looking for some changes, for instance, changing the entire website's design and aesthetics, or changing one particular feature inside their website, right? So these changes are normally accompanied by a sort of a process called A/B testing. So what happens as an analyst, you might be working with LinkedIn and say, on a fine day, they might come out with a new feature, new design, or new sort of changes in their website. So you as a person would tell, okay, this is my framework for testing this new change by defining a metric. So my metric could be in simple terms saying, if I change this website from A to B, is my number of footprints on the website going to go down or not? So this is my metric. And if I successfully establish the fact that after rolling out this new website, my number of customers who are going to visit my website is not going to go down, I can be confident that, okay, fine, this works. Now roll out this new feature. So in this framework, we normally have two set of users to identify the particular risk associated with getting this new feature into the platform, and in which we in a randomized way put one user group and expose them to an older website, and another user group and expose them to the new features, right, or the new website. And when we compare the results of a particular metric, like the number of clicks or the number of purchases and so on, we should be able to see that these two groups are either exactly the same or quite different. And if it is on the negative side of the difference, we say the feature is not good. And even if when the difference is not at all there, we say even if we bring this new feature, nothing is going to happen. So this A/B testing framework is quite robust in its own way, right? And a very common question, if you have like worked as data analyst, or if you are expecting to be like sitting for this data analyst kind of a role, knowing A/B testing framework is very important. Okay, so sometimes also when you do these kind of A/B testing sort of analysis, people normally come out with sort of saying what should be the sample size of my users whom I should be getting to participate in my A/B testing framework. Or also when you are building some models, you might see that there are certain statistical measures which has to be evaluated by the end of model building exercise. Like if you're building a machine learning model, let's say, and you want to see if those metrics on which I'm evaluating are really good or not, right? So in that, sensitivity is one of those methods or like metrics which we normally evaluate. And I'm going to show you something that we normally refer by the name confusion matrix. So I'll spend some time explaining this and then come to what do we mean by like sensitivity. So let's say you are building a model, right? A model for predicting whether a particular customer is going to purchase from my platform within 1 month or not. Right? So very simple problem statement, which might include many variables that we would bring in and then finally build this model saying, okay, this is my final model which says with 90% accuracy whether my customer is going to buy from my platform, let's say an online e-commerce platform, within next month or not. So this is my model. So now, without going into the details of the model, let's assume that after you build the model, you have got the results. So while we analyze and evaluate what the result is all about, we might come out with a confusion matrix. So what it says. So obviously when you are building a model which follows a supervised way of learning, you will see from the historical data, after people have purchased in the platform within next 1 month, whether they are buying or not. So I can obviously create a really good training data set, right, which will contain the information after people let's do the first transaction with me in next 1 month, whether they are buying the next product or not. So with that data set, I train my model, and the way confusion matrix puts that is by saying my actual data says something and you have predicted something, right? So let's kind of get into the details of that. So this particular box which says my actual data says the customer will buy, and you are also predicting the same. So this we call the true positive. The prediction is actually true, right, in a positive direction, saying the purchase happened. Now like move diagonally opposite to this TP, which is this TN, which is true negative, which means the prediction of your model saying the customer will not buy is actually matching with the actual data as well, right? So both of these values, the true positive and the true negatives for the two cases, is the right predictions from your model. But consider the off diagonal elements, the false negative and the false positive. And these two cases, this is sort of an error. Why? Because your actual data says the customer is not going to buy in this case, let's say, but your prediction says he is going to buy. So the prediction is actually positive, whereas the actual data is on the negative side. So this is a false prediction, right? So you have your, in this case, your FP, which is the false positive cases. And on the off diagonal element, if you look at this one, which is Fn, which is your false negative, for the cases where you are predicting the customer is not going to buy. But in the actual data, it says that customer actually has brought the product. So in this case, the model is wrong. So the type 1 and type 2 errors needs to be taken care of when you are building any machine learning model. If these errors are low, then your model is going to move towards that 100% accuracy mark. But normally any machine learning model has its own limitations. So particularly, there is one metric which we refer by calling sensitivity. So what happens is these true positives and true negatives needs to be controlled. Right? If my model is very good in true positive ones, like the positive cases of when the customer is buying, but it is doing very bad job when the customer is not buying, the cases in which the customer is not buying, then the model has some sort of issues, right? It is doing only good in one place, but doing very bad on the other case. So I need to find out that by some metric. So sensitivity help us to find that out, which is in simple terms is a ratio between the true positive. In the denominator, we have all the cases of positive predictions. So imagine now if the type 1 error is going to grow, my sensitivity is going to come down. So if my true positives are like very high, the sensitivity will also be high. So this is sort of what we call the statistical power. If this sensitivity is really good, I would say that my positive cases are predicted well. And the exact opposite of this sensitivity is what we know by specificity. So we need to make sure that in a very good machine learning model, sensitivity and specificity both are balanced, right? So in very simple terms, this is what will be like mean here, the ratio of true positive by the total positive events there. And as I mentioned, both of these sensitivity and specificity play a good role when you want to evaluate a model's output, right? And one more common problem. So these questions might be immediately following one another. When people ask you about sensitivity and specificity, as you know, it's about the machine learning model's output, right? When the model is done, you understand whether the model is good or not. So in those cases, we also come across some kind of issues like overfitting and underfitting given machine learning model, right? So these words are very common. And the idea is, depending on the complexity of your model, you might see that you want to adapt very sort of exactly to your data points, or you might want to do a generalization. So for instance here, if I have these red and blue dots here, right? And if I draw a curve like this, which separates the red from the blue, and when this separation happens, I am building actually a classifier using some sort of modeling technique. But now imagine by drawing a smooth curve like the one which is given in black, you might be overgeneralizing it, right? By which I mean there might be some red dots on the other side of this boundary. You can obviously see that. But the moment I am kind of a bit more flexible by drawing this green boundary, which actually covers all that issues which is coming out with these red dots on the other side of the boundary. So this green boundary has like taken care of that. But the problem, when we are building any model, right, the idea is you need to generalize to the pattern found in the data. So if you don't do that generalization well, you are underfitting. But if you do that generalization like too specific, you are overfitting. So this curve might be represented by some polynomial, right? But that zigzag kind of a polynomial might be a bit more complex than a smooth curve like the one which is shown in the black. So you need to be very careful when you are building a model, particularly in the cases of regression models, where it is represented by a line and a polynomial. You need to make sure that the polynomial is not so complex, at the same time not so simple. Then you will either end up in an overfitting situation versus an underfitting situation. So we need to have a good balance between these two. Right. So in summary, when kind of statistical questions comes in, it would mostly covering things like some basic statistical properties, as you would be like very aware of, like things like standard deviation, averages, how to interpret median, how to interpret quartiles, right? The first quartile, second quartile, and so on. And what do you mean by percentiles, right? These are some basic questions. A bit more complex in nature might be discussions around sensitivity, overfitting, underfitting. These are like statistical ideas. So you want to prepare maybe from a basics level using the properties like standard deviation, mean, and so on, till things like overfitting, underfitting, statistical, the sensitivity and specificity kind of ideas. So that will like make your ground a bit more stronger when you are going for the interviews. And these are at least the bare minimum for you to understand in the statistical concepts, right? Even anything less than that, you might like face some difficulties in the interview. Okay. But let's also talk about now questions which are related a bit more on data analysis. So let's see what kind of data analysis questions which might pop up in the interview. Okay, so some generic questions like this. People normally do analysis on structured data, which is in rows and columns, but there might be cases when the data is not so well structured, and those places the data might be textual. For instance, in Twitter, right? If you're doing any sort of algorithms like sentiment analysis, quite commonly known algorithms. So in that case, the sentiment analysis could be for a brand, for a election campaign, or maybe something else around your product features and so on. So text analytics in its own are really large domain, and in Python as well as R, there are number of libraries. So in particular, R has libraries like TM, right? The text mining package. Python as well, we have packages like pandas, packages like the NumPy ones, right? And also packages like NLTK, which is built only for natural language processing. So it can deal with many different sort of text mining approaches or text analytics approaches. So in comparison, if you talk about, as I said, the robustness in Python is much more than in R, but in terms of features, both are powerful enough with the libraries and packages that it offers, right? One of the fundamental sort of starting place when you do any analysis. So when you are given a data set and you are asked to do some sort of basic analysis of what that data tells you, maybe typically of questions like, I am in a retail business and my sales in a particular region is going down. So this is an analysis that is expected out of you, and you need to dig through in understanding what really is the problem in the sales going down. So if this is sort of the data which is given to you, you might want to first look at the transactional data which is present in the system. Then you might also want to go to data outside of your network. Maybe you might get the sentiments of your customers from social media platforms and so on. So there will be different sources of data that you will collect. But oftentimes collecting the data is not only the task, right? And not like only building a model or doing statistical analysis might like come very later in the stage. But what comes before that, after you have collected the data, is to make sure that the integrity of the data is maintained. You get rid of all the unwanted noise from the data, and then finally prepare the data for doing the sort of modeling exercise or doing descriptive analytics on top of it. So this cleaning and understanding the data, doing a lot of explorations with plot, in essence takes close to 70 to 80% of your time in any data analysis task. So if your company maintains the data in a very well structured way, this kind of heavy time which we spend on data analysis might be reduced, or the data cleaning might be reduced. Otherwise, you need to like take this up for any new project that you take up, for which the data is not available in a prior, or you don't have like any pipeline which do this cleaning. You have to write it down of your own. So very, very important. If you don't do the cleaning part and understanding the data well, the analysis or the models that you build might end up giving you a very, very bad performance, right? So very important. As I said, 80% of the time people normally spend on this task, right? And oftentimes when you are analyzing things like the example I told, my sales are going down, what do I do? It is not possible to come out with such answers to complex problems like this with just one variable, right? So you might also want sometimes to move beyond one variable and talk about, let's say, how to do multivariate or bivariate kind of analysis. So oftentimes this question comes up where you like asked to distinguish between this univariate, bivariate, and multivariate analysis. And the idea is very simple. In any sort of analysis, it is not only one variable which kind of decides the end output of your analysis, but there are multiple factors involved. So when there are multiple factors involved, you might also want to look at things like correlation. There are multiple variables. You want to see if there is any correlation between these things. Sales are going down, but because of what? Is it because my sales representatives are not going to the market, or is it my products are bad, or is there some other reasons? So with all the variables in one place, you might want to go and dig deeper to see if there is any relationships coming in the variables or not. And when we collectively get all these variables together and do some sort of coherent analysis around the problem, you come out with a really crisp answers to what you are trying to analyze, right? And moving on, there is also times when people do some sort of grouping, right, with the data. You do a sampling, right? You get a data set in your system or in whichever servers you are doing the analysis. But in that, there might be many number of times when even the randomized sampling of getting the true representative from the population like that might not work well, right? So in those cases, you might want to do some sort of systematic sampling or maybe a cluster-based sampling as well, wherein you might decide to say, I want to analyze the issue with only 5 regions in my mind, and with the 5 regions, I'm going to form different clusters. Or in the systematic sampling, you might also want to say that with the 5 regions that I have got, I might want to analyze only for one product, right, which is not doing that good in the sales. So these kind of sampling techniques, like the cluster-based one or the systematic sampling techniques, and there are different names for this, people might be able to give a very good interpretation of what really went wrong in whichever sort of analysis you're doing. So one example is like sales going down, but you can adapt this to other analysis as well. But the idea is instead of doing a randomized sampling by which we are not very sure which kind of data is coming in the data set which we want to use for analysis, but if you do it in a cluster basis, a cluster or a systematic sampling, you know exactly which clusters or which sort of regions in this example you are like analyzing, and in your end of the analysis you'll be very able to say this is not like a randomized sample that I have taken, but from these 5 regions. So there are many different ways of doing clustering, cluster or sort of the systematic sampling, which kind of helps in this particular final end results of your analysis, to put your end results in the right perspectives, right, instead of doing a randomized sampling. Okay, one more quite a useful sort of an idea, kind of widely borrowed from the field of linear algebra, and this is a bit related to what we earlier saw between moving from one variable to multiple variables, right? And eigenvalue and eigenvectors, kind of a concept borrowed from linear algebra, helps us to bring in some way a linear combination of different variables together. For instance, in some complex analysis, it might happen so that given a data set, it might have many columns, right? Let's assume you have a data set with 1 million rows, and let's assume 10,000 columns. So, and these 10,000 columns are some features. There are complex problems like that. But in most often, like most of the time, not all the 10,000 variables are useful, right? The input variables. So what we can do is, we might want to transform this data set in a lower dimensional space, by which we mean this 10,000 columns can be reduced to, let's say, only 100 columns, right? So eigenvalue and eigenvectors are these ideas which helps us in this transformation. And the idea is, can this 100 variables be represented as some sort of linear combinations of the 10,000 variables? And if I'm able to do that, my dimensionality is reduced, the time I take to do the analysis is kind of also reduced, and the representability which will come with only 100 variables will go up, right? So quite a powerful idea, eigenvalues and the eigenvectors. And as I said, the eigenvectors is kind of that linear combinations of many kind of variables there. And this calculations around eigenvectors normally happens for a correlation or a covariance kind of a matrix, which, as you know, the measure correlation is also about how two variables are related, or how strongly two variables are correlated, right? So that's why we are also saying this eigenvectors can help us to compress the sort of data that we have, right? And that's because of one eigenvector can be representing 100 column, 100 variables together, right? So that's sort of how it works. Quite a powerful idea, and commonly used methods for reducing the dimensions of a large data set, like the PCA, principal component analysis, is actually based on eigenvalue and eigenvectors. So if somebody asks you about eigenvalue and eigenvectors in an interview, also talk about the PCA, principal component analysis, which is actually based on these two concepts. So that gives them a good idea to the interview viewee that you know about eigenvalues and eigenvectors, and you are also able to think of its application like in PCA, right? So we talked about this false positive and the false negative cases in our confusion matrix example. So this is exactly the same. We also talked about the type 1 and type 2 error. Okay, so but let's now also drill further and say examples or kind of scenarios when the false positives are important and scenarios where the false negatives are sort of important. And by the term importance, we mean, are we like allowed to do this mistake? If we are building a machine learning model, are we even allowed to do a mistake on either of the cases, the positive or the negatives? So for instance here, if I take an example in a medical domain where we have, let's say, a process called chemotherapy, which is normally given to cancer patients, which is a radioactive kind of a therapy which kills the cancerous cells, right? So it is very focused sort of a therapy on the cancerous cells. So what will happen if you like predict, let's say you're building a model for detecting cancers, right, given a CT image, and this model would obviously not be 100% correct. All machine learning model has its limitations, but you are here required to predict this, whether a patient has cancer or not, and based on that, radiologists might decide that whether the chemotherapy is right for this patient or not. But imagine now, if you have predicted somebody to be positive for cancer, but the patient is actually not having the cancer cells there, right? So in those cases, you might end up saying, let's go ahead with the chemotherapy, but the side effects of chemotherapy are like very, very adverse, right? Because you're giving these therapies on the healthy cells if the patient is not having the cancers. So in these cases, sort of the false positives becomes a bit more important. So it will be absolutely fine if your model says the patient doesn't have cancer, even if there is like this slight possibility of cancer present in the cells of the patients. But in that case, you are not like exposing the patient with a chemotherapy there, right? Which is like more harmful than saying that the patient doesn't have the cancer, right? So in these cases, the false negative, though the false negative itself is not so good in this case, but at least with this particular example, the false positive gets the importance than the false negative. But both are bad, as you know, right, from the confusion matrix discussions. So in simple terms, it is better to not expose the patient with a false positive with a treatment like this, chemotherapy like treatment, then it is like much better than saying you don't have cancer. Okay, and a very similar example in some other context might also come up. So if you would like to think of some other examples in the same context. Okay, so where is the other case now, which is the false negative, right? So we talked about the false positives importance, but there might be also cases where false negative might become a bit more important there. And for examples like this, if you are, let's say, building a model where you want to convict a particular criminal basis all the records and the arguments which has happened in the court, right? And let's see what would happen if you make a criminal go free, right? Because your model says it's false negative. Though the person is actually a criminal, but because your model predicted based on all the evidences you had, the person is not a criminal, so you are letting a criminal like walk free in society. So that kind of is more harmful than convicting that person, and maybe for a prolonged period you might also want to get more evidences and build a stronger case. So it is fine to keep a suspect in behind the bars for a longer period than letting the suspect go free there when we like know that it might be a case of a criminal going free from the judicial systems there, right? So in these cases, the other case becomes more important. So keep in mind, it is very easy to get yourself confused between this false negative and false positive. But if you keep an example in mind always, and like don't give any room for confusion there, though it is a confusion matrix based on which these two ideas comes in, you will be able at every time put these examples in front and talk from that. So if you start to explain what false negative is in terms of the formula, you might get confused. But if you take an example and then explain, things are much more clear for you as well as the person who is hearing that in the interview, right? And in cases when both are important, typically the one which relates to banking industry. you are building up a model which will decide whether to give a loan to a person or not, basis many of the input attributes that around which you have like collected the application from the customer. But here you say, if the customer is really good and you are missing the opportunity there of not giving the loan, versus the customer is really bad in terms of his or her credit history and you are giving the loan. In both the cases, in one case you are losing the business, in the other cases you are taking a risk in which you will lose your money, right? So in this case, in this example, both kind of has an equal role. So if your positive or false negatives are in either of this is high, you will end up losing some chunk of your money there. Keep these three examples in mind, and every time you get to like hear false positive, false negatives, things should not be like confusing at all. Okay. So now let's also talk about building a machine learning model. So far we have discussed about what happens after building the model, right? But let's get one step back and see how do we normally build a machine learning model and what kind of processes we normally follow. So when we are like building a machine learning model, we know that we need to, given a data set, we need to divide it into different buckets or different parts. So the commonly known divisions that we like have is your training data, right? Then we also divide the data into something called test data. And sometimes people also divide or keep one portion of your large data set, which is called the validation data. So oftentimes people confuse between the test data and the validation data, right? So what happens is in the training process, there are certain models wherein while you are training, you will use the training data obviously, but in the process of training, you can also involve something like a validation step, right? Which will make sure that during the process, there is one part dedicatedly given for the validation of the model. And when the model is done, you might see that the final model is well trained on the data, at the same time validated. But when the model is completely done, then only you get into a process that we call testing, right? So you can imagine like this. You have a data of 1000 records. You keep some 700 records for training, 100 records for validation, and the remaining 200 records for testing. So there are three splits, right? If I would like to explain this with an example, this is how it will happen. So there is a process called k-fold cross validation, in which k can be any number like between 5 and 10. Mostly there are like standards saying 5-fold cross validation or 10-fold cross validation. And the idea is when you are building your model, you will work with a training set, right, and a validation set, in which a small portion of the data you keep for validation and the rest you use for training. So what you see here, test set, can be like replaced with a validation set, right? And you can see that this is a rolling sort of subset, and you keep changing it in each fold. So you go for the first fold of the iteration, you keep one validation set, and the rest of it is the training set. And the next fold, you move this window to another subset, and the rest is training data, and so on. And when this model is done using this k-fold cross validation approach, in the end you will get a model which you can then use on the testing data to see if the accuracies are good or not. So this kind of brings in a lot of performance improvements. People have also found validation set to be a really good way of tuning the parameters. In many machine learning models, as you might know, there are something called parameters, typically in the neural network models. And these parameters need to be tuned as the model is kind of proceeding. So we cannot use the testing data set for tuning these parameters. So validation set kind of comes very handy in those cases, right? So we just talked about the cross validation. So when you keep moving this validation set in each of the fold, first fold, second fold, third fold, and the validation set is keep changing, you kind of do this process of cross validation, right? And the idea behind doing cross validation is to see how well is your final model generalizes to the data that you have. So independent of which data you use for training, your model should generalize. Because oftentimes it happens when you train a machine learning model, it works very good in the training part, but when it comes to the testing, the model does very bad. The same problem with the overfitting and the underfitting cases. So in this approach of cross validation, you have made sure that your model has trained on various subsets of the data, right? And in the process, we also have this small validation set, so that every stage of the cross validation process, you are able to use a different subset. So that means you have trained your model very well. So irrespective of which data you use, your model is going to do well in the testing cases. So that's how cross-validation brings in the capabilities. Okay, so with the two pillars like the statistical analysis and the basic data analysis, I hope you are getting some sense of how people ask a particular question coming from either the model building perspective or from normal data analysis perspective, right? So we're going to now go a bit more deeper into questions which might relate directly to machine learning. So these are all the most questions that you have seen so far are either saying how do we do analysis after the model is built, or how do we normally perform simple data analysis like A/B testing frameworks and so on. But what if you are asked something very particularly from a machine learning domain, right? So the next set of questions will cover those part. Like people might also start with the basics like what do you mean by machine learning? So the idea I think must be very clear. You are given a set of data points particular to a given domain, right? And you would like to build a learning algorithm which will take the historical data and predict something for the future. So as we talked about in many examples, finding whether a convict is actually convict or not, like predicting if given the evidences if person is a convict there or not, or predicting whether we should be giving a loan to a customer or not, right? Predicting the onset of cancer in a given patient's by using the given patient's historical records and so on. And now this algorithms are now even becoming more complex, like it is starting to work on speech data, face data, which are mostly used for biometric authentication systems, right? So many use cases coming up from various industries, right? So in machine learning, the most commonly used two types of learning, the supervised and the unsupervised learning. There are like two other types as well, the semi-supervised and the reinforcement learning. And the idea is around if you are given a set of input attributes, do you have a label which can help to learn the input attributes around any data points that you have, or you don't have, right? So if you have, then the approach could be a supervised learning approach, versus if you don't have, then the approach is more an unsupervised. So some examples of the algorithms are like support vector machine, regression, naive-Bayes, decision trees. All of these are the supervised learning algorithms. So in a very simple terms, if I say you are given an input attributes for identifying, let's assume a sort of given an image of different fruits based on the characteristics of the fruit, can you like identify whether it is apples, bananas, or the oranges? So if I'm given that label with me, the model will run keeping in mind that given these characteristics, this is an apple, this is an orange, and this is a banana. But in the other case, if you go for a clustering approach where such a label of saying that it is an apple, banana, and orange is not available, then we might just simply segregate the data points with the input features, maybe with color, with texture, or with the shape, right? With that, we can maybe say that particular fruit with this shape is like into a bucket which we can like call banana, or another kind of a spherical shape, it might be apple or an orange. So depending on the presence of a label, we can say either to use supervised or an unsupervised learning. And both of these approaches are quite common. And sometimes there are certain algorithms which can have the both ways. It can also learn in an unsupervised manner and the supervised manner. So depending on how you model the problem. The fundamental difference comes from the fact on whether we have the label or not. Okay. So when we talk about the supervised learning algorithms, other name for supervised, kind of one of the types in the supervised learning algorithms is classification, right? And the classification is around given a set of input attributes, and the label is like categories, right? For instance, if it is fruit, bananas, apple, and oranges, like if it is a customer whom we want to predict into either kind of a defaulter type or a good customer. So the classes are two, like one which is saying the customer is going to be a defaulter. The other says the customer is going to be a good customer. Same is true for when you want to build a classification algorithm for detecting cancer, whether the patient has a cancer or not has a cancer, right? Or if you want to detect, let's say, a malicious content or a malicious file, which might be a virus, Trojan, or worm or something else, right? So in that case, the classes are now many. So more than one class can also be there. But the fundamental idea is we are following a supervised learning algorithm, but the type of problem we are solving is a classification problem. So instead of saying classification algorithm, we can also say it's a classification problem using supervised learning algorithm. So these are the various types of classification algorithms, like the linear regression, decision tree, then you have the support vector machines, and so on. Right. So now let's talk about one of the types of classification algorithm called the logistic regression. Right. So very commonly used algorithms, and banks or companies as big as like American Express sort of have leveraged the logistic regression algorithms to quite a extent, and they have like built a really robust implementations of these algorithms, particularly in banking sector. Cases like predicting whether a customer is going to be a defaulter or not, given if I issue the customer a credit card or give a loan. Right, these kind of decisions can very robustly be taken from a logistic regression algorithm, and these algorithms are best suited for two class problems or a binary problem, right, where you have either yes or no. Quite a common technique, as I mentioned, and in all the possible cases wherever you have these binary classes of problems, you might use a logistic regression. A political leader winning a election or not, somebody getting a success in an examination or not, and as I mentioned, whether to give a loan to a customer basis, whether he or she is going to become a defaulter or not, and many of these like binary types. So keep in mind, logistic regression works best for classification problems with two class. So one of another widely used algorithms like the recommender systems, and like I think this particular algorithm doesn't need introduction, so this is that common nowadays. Take an example in Amazon. You have a product which you are browsing, the products which comes in bottom of the widget which says you may also like, or customers who brought this also brought this, right? So these sort of recommendations is actually from a recommender system which is running in the backend. If you like take YouTube example, if you watch one video, the next videos like starts to come one after the other, right? That again is a recommender system working in behind the scene. Or if you take Netflix, if you watch a particular movie, it starts to adapt, right, to a movie which you might like. Netflix also uses recommender systems. The applications are like coming more and more as sophisticated systems are building in, right? Facebook uses it for recommending friends, right? You have a set of friends, and based on your data coming from the contact mail list, Facebook starts to curate friend suggestions, right? And all of these are algorithms which might benefit the business in some way or the other. For Amazon, it is if you give a recommendation below a page, people might buy more than one product in a transaction. For Facebook, they will grow their network of people, right? Their connection between the users are going to go stronger, and hence obviously the kind of ads that Facebook wants to sell will also starts to grow, right? And more the users, more the connections, more is the sort of interactions you know about the connections, as well as the behaviors that people show in a social network. So the fundamental idea behind all these recommender systems is to get a meaningful comparison between two users or between two items, right? For Amazon, between any two products, what's the similarity? If the similarity is really high, recommend that product to the for a given product in consideration. Or if you find that two users are very similar in, let's say, Facebook, you might want to show to each other that you have another friend whom you might want to connect, right? So there are like many such use cases which comes out the moment you get into the deeper understanding of recommender system. But the fundamental idea is, how do I compare two items? The items might be product, people, movies, and so on. And how do I compare two users in simple terms? So this is what a recommendation system works on. So there are quite famous examples like the collaborative filtering approaches, user-based collaborative filtering algorithms, or the item-based collaborative filtering algorithms. Both of the algorithms are quite commonly used in recommender systems. And nowadays people have also moved on to latent factor-based models like the SVD, singular value decompositions, and many others. So we talked about classification problem, and then we said logistic regression is a binary class problem, right? So you might also be asked something around linear regressions. So what if I don't want to have a class of a particular user or a patient or something like that, right? But instead, if I would ask you, can you give me a crisp value instead of a class, right? So when I'm like classifying a given file into good, bad, in which bad can be virus, worms, trojans, these are the classes. But if I don't want class, but rather, for example, if I want to know the exact value of a house in a particular locality in my city, how do I calculate that? Right? So linear regression models in machine learning is one such technique which can regress over a given input data, which might include the properties of the houses, like number of bedrooms, the area in square feet, and so on, and finally predict a value, a crisp value, which will be exactly in terms of, let's say, dollar or in any other currency, the value of the price. And the idea is, once again, that you have a training data with you which has labels. So from the past data, I know that given these attributes of the house, what should be the ideal price of a house. I'll use that as my training data and then build my model for future. So now with any such similar pattern in any data which is going to be coming in future, for maybe a new property which is built in some XYZ location, I can use the model and predict exactly, because these features are somewhere similar in that locality, the prices might be in a particular range. So a model like linear regression will learn those patterns in the given input attributes and try to predict the price of the house. Right? And the idea is, if I have a set of data points, I want to build a very generic model like drawing this line, which is as close as to all the points. Right? So you can like draw infinitely many number of points if you are given a set of data points like this in a two-dimensional space. But the one which is the shortest or the closest to the points is the best line. So the red line which you see here is like far away from all these points, right? So this is not a best line. But if I see this blue line, which is very close to all the data points, is like one of the best lines which I can get from these points, right? So the idea here is to fit a line passing through as closely as possible to all the data points that I have and minimize these so-called the error, which is nothing but the sum of all the distances. Right, so there are simple linear regression ideas, and the fundamental idea that we are following here is your variables are having a linear relationship, which means with the increase of one variable, the other also increases. But if you have a pattern which is not so linear in shape, like if you are like not able to draw a generic line, but the representation or the sort of points are aligned in a way that you can only create a model which is polynomial. So in that case, linear regression will not be so useful because the relationship is not linear anymore, right? So in that case, you might want to go for some other regression approach, maybe like a polynomial regression, which has a non-linear relationship between the independent attributes. So quite a common approach, and it has like a really large chunk of its explanation coming from the statistical ideas. Statistical ideas like hypothesis testing, p-values, confidence intervals, and so on. So if somebody is asking you around linear regression, better would be to start with saying how you build a linear regression model, right? And then you might give some examples of it. So at best, if you're not comfortable with these ideas like p-value or hypothesis testings, you might want to refresh that before you like go for any interview, because if linear regression comes up, these concepts needs to be a bit more explained, right? So when I talked about the recommendation algorithm, I mentioned something about collaborative filters, right? The user-based collaborative filtering or the item-based collaborative filtering. So these are the two commonly used sort of recommendation algorithms, right? Normally referred to as item-based, so IBCF and the UBCF. And the idea, as I mentioned, is to compare to users or to compare to movies, or let's say items in particular. So the item can be anything, a product, a movie, or a person. And the sort of way it builds the model is given a lot of users and their particular, let's say in this example, their rating to a movie, we now need to find out, can we recommend for some users based on the behaviors of other users or their ratings to the movie, some suitable movies or not. So for example, here for Carol has not seen the movie 21, right? So there is a question mark there. So can I predict this value? If it comes to be, let's say, like close to 2, I won't recommend the movie. But if it comes to, let's say, somewhere 3, 4, or 5, yep, the model says, yes, recommend this movie to Carol. Okay. So one more fundamental problems on when you build the models. So as I mentioned in the earlier discussions, that when we are doing some analysis with the data, after you collect the data, there requires a lot of cleaning, right? And exploration as well. So in that process of cleaning and exploring the data sets, you might often find there are some extreme points. So for instance, if I'm building a regression model for predicting the house prices, and there is this one house which somebody has sort of able to sell for a very high price by means of maybe some auction or some other sort of marketing gimmick there. The point might mislead the model to predict or get itself towards that outlier point, right? So we don't want to like move towards an outlier point, but we need to deal it separately. So if you don't have a better explanation for why that outlier is in terms of an input attribute, better is to remove it. So for instance, if I am like analyzing any data in an e-commerce world where I am going through all the products and the sales that the product has seen in last 1 week, and on the last 1 week there was a particular day when a kind of a sales day was there. Like nowadays e-commerce companies do this a lot. But in those sales days, you would obviously expect that the product's purchase is going to go very high, right? But does that mean that it's an outlier? To me, not, because if I'm able to explain an outlier by saying that this was a discount day, I might be able to handle it separately. Either I can like simply take all those points which are for the discounts day or sales day and keep it separately. Or if I would like to have the variable like saying whether the given day is a sales day and keep the outlier as well, then the analysis goes in a different direction. So it's important you handle the outlier before you start to build your model or do any analysis. Otherwise your insights or your model's output might totally give you a different direction. And there are very different ways to handle the outliers. So some people use approaches like removing any data points which is like outside of the range of mean plus 3 standard deviation, right? Or sometimes people also use the percentile way of doing it. Any point which is greater than the 99th percentile can be like removed. So these are like you are removing the toppers from the data points of yours of, let's say, a SAT examination or a CAT examination. So the outliers are sometimes can cause certain issues in explaining the model. So you can obviously imagine this in very intuitive terms also. If you have a set of scores for candidates who appeared for an examination and there was one outlier candidate who scored really, really high. So do you have a way of explaining that outlier? You might be simply calling that person a talented person, but does that like explain the model? Maybe difficult, right? So better is to keep those exceptional cases separate and do the analysis with the rest of it. So which gives you the good pattern or good insight from a data. So that's how you like normally handle an outlier, right? And this quite often is an important question to answer, that if you are given an analytics project with a lot of data, how do you normally approach it, right? In typical cases, the first step is to really go deep dive into the problem in hand. And the problem needs to be defined very crisply. So never define a problem which is broad in sense. So for example, if you are building a model for customer segmentation using a clustering approach. So instead of saying build a customer segmentation model for all the categories of products, that can be like a broad problem. But if I say build a customer segmentation model only for fashion category of products, right, then the problem becomes crisp. So defining a problem statement and its understanding is the foremost task. And then comes the kind of exercise of exploring the data, in which you will identify outliers, missing values, and if you need any transformations like converting from a log format to a wide format or the vice versa, you do all that steps in the second and the third step. And once we have found out that the data is very good now, after we have removed all the outliers and the missing values and so on, you then start to understand certain relationship, like given input attributes relate in some way or the other, right? So this is a stage where you start to prepare for any further insight building exercise or like model building exercise. And let's say if you build the model in this step, the immediate step is to validate it, right? Whether the model is really good or not by using a testing data, right? And once let's say all of these is done and you are either coming out with a insight or a model, you would like to see in long term how this model is going to perform. So it might happen so because every model is not static. Your data is growing on daily basis. So if you want to build a really robust model on a growing times, it should append, the model should update based on the new data which is available, right? So over a period of time, you should track and analyze how good the model is performing on a real world data. And if the performance is going down, then it's time to retrain the model and maybe come out with an updated model on the data that you are already given, right? Okay. So one more task, as I was explaining in the cleaning process, how do we treat the missing values? So there are quite a number of techniques to do that. So for instance, if you have an attribute, let's say age, right? And you are analyzing this age in various segment of people. people who are teenagers, people who are professionals, people who are still in their college and so on, right? And there is one value missing in one of these categories of people, let's say teenagers. So if the age is missing, because I know I am analyzing a group of people who are teenagers, by looking at the average age in the teenage group, right, I can maybe impute a value. So instead of discarding the entire row because I don't have the value of age, I might be able to impute it by some simple measures like this, calculating the average in that group and putting the value there, which will not be completely wrong because I know there is a very strong evidence teenagers would be more or less in the range of let's say 16 to 20, right? Even if I'm wrong in my average calculation, it might not be so high. It might be like just plus or minus 1 or 2 years. So which I'm like fine with if I want to keep my data retained. And you might see that in your many applications, sometimes having a kind of discarding a particular row because of missing values might be very costly because the data is limited in number. So that's why people normally do this at a sort of mean, minimum or maximum kind of a value, or they also calculate the average and impute the value there. So there can be some other pattern based imputation also possible, but I'll just give you an example. And in other cases, if nothing is possible, by putting a value, if everything is going to be misleading, then better is to like remove that. But that can only be done if you have a surplus of data with you. If not, then be cautious of removing any values, particularly the missing ones. Okay, so this question particularly pertains to a machine learning algorithm called k-means, right? Every time you run the algorithm, you have to define what should be the value of k, right? So there are approaches like elbow curve, which plots the kind of a plot, scatter plot between the x-axis, which is the number of clusters, versus y-axis, which is the WSS or within sum of square, which is also known by the name distortion. The idea is when we are building the k-means clustering algorithm, if we find at one point, if you like keep increasing the value of k, at one point we find that the distortion is low, which means the distance between the data points within a cluster is as close as possible, and the distances between two cluster points, like a point in cluster 1 and a point in cluster 2, is as far as possible. So if that's the case, then the distortion will be like very low. But if your points inside a cluster itself is very spread out and your clusters are very close to each other, then the distortion is going to be very high. So in those cases, the value of k needs to be maybe further increased. And at one point, using an idea called an elbow curve, which will show you a small kink from where there is a sharp dip in the distortion values, and that is an appropriate value for k while we are building a k-means algorithm. So this is how it looks like. So you can see here the x-axis is the number of clusters and your y-axis is your within group of sums of square. And at one point you can see there is a sharp dip here, and after this point, which is like circled in red, the value sort of almost saturates. So this maybe I can use as the appropriate value of k. So value of k can be like 6 in this case. So I hope you are now getting comfortable with questions around data analysis, statistics, and even the machine learning part. So the next pillar, which might very closely be associated with statistics as well, is around probability, right? So it is like sometimes in most of the standard literature, probability and statistics comes together. It is not inseparable anytime. So in the naive-Bayes algorithm, like this is one of the machine learning algorithm which is based on the Bayes theorem. Probability ideas are quite a lot used, and there are some really niche probability concepts like the probability graph models, which is actually based on the basics coming from Bayes theorem and the fundamental properties around probability. We'll not go to that detail of probability in interview questions. If you have an expertise around probability and probability graph models or naive-Bayes kind of algorithms, feel like confident to speak about it. But most of the time, the probability questions are quite basics and fundamentals, like the one at least which is asked in interviews, depending on obviously in which place you are giving the interview at. So let's also like see some sort of approach in attacking probability problems. Okay, so I'll like read it out for you what the problem is here. So it says in any 15-minute interval, there is a 20% probability that you will see a shooting star, like a good example rather. So what is the probability that you see at least one shooting star in a period of an hour? So there is unknown information given to us, that every 15-minute interval there is this 20% probability you will see at least one star. So we now want to calculate this probability in a period of 1 hour, right? So what is the sort of approach we would take here? So let's build this systematically. So we know one fact, that probability of not seeing the shooting star in every 15-minute interval is 20%, which comes down to 0.2 in probability terms. 20% chances or 0.2 probability. And as you know, probability is always between 0 and 1. So if I would like to calculate what is the probability of not seeing the shooting star in 15 minutes, which is like the opposite of this, right? If I take from, so these are like independent events, right? So if I take 1 minus of the probability of seeing one shooting star, 0.8 will then become the probability of not seeing the shooting star in 15 minutes interval. Okay, what I need to do is then probability of not seeing this shooting star in another 1 hour, because these are now independent events, like seeing a shooting star in first 15-minute interval, the second and third and the fourth in an hour's period is independent of each other. We can multiply this probability like this. So 0.8 into 0.8 into 0.8 into 0.8, which comes down to a value of 0.4. So the probability of not seeing the shooting star in a period of 1 hour is 0.4, right? And if we know the value of this probability here, all we have to do to get the value which we are interested in is, which is the probability of seeing the shooting star, is 1 minus the probability of not seeing it, right? So the probability here comes down to 0.5. Quite a simple approach in terms of how it works, right? So there might be similar tricky ways of putting the same questions, but if you know one approach and having the idea of independent event is, right, you may be able to get the understanding or formulation in this way. And also keep in mind, given a sort of a sample space and many events from the sample space, the sum of the probabilities cannot exceed 1, right? So that's why we are able to do this. If I'm saying tossing a coin, the probability of tail is going to be 0.5, and the probability of head is going to be the other event, which is going to be 1 minus the probability of tail, right? So similar is the case with here as well. We are treating this as a binary problem. So depending on which problem you are going to tackle, the approaches are going to be the same, but the language and sort of the trickiness in the question might increase, right? So this is how you can attack that. Okay, so there is this one more question, which is around generating a random number between 1 to 7 with only a die. Okay, so let's also think about this, how we can approach this problem. So we have seen how we generate random numbers from a given set of points, but this kind of says that we want to do this with a die, right? By rolling a die, we want to find out a random number between 1 to 7. So obviously we know that the die has numbers between 1 to 6. So the probability of getting any one digit in the die is 1 by 6. Like if I do 1, 2, 3, 1 divided by the total number of possibilities, that is 1 by 6. So that will be my probability of choosing any one of the digits there. But it is saying we want to generate this random number between 1 to 7. So where do we get the 7? So obviously the requirement is that we can roll the dice twice, right? Then the number of possibilities increases. So as I said, there is no way we can get the 7th one, right? Because we have only 6 digits. But if we roll the die twice, the number of possibilities of generating this 7 random numbers increases. So in this case, we have now 36 different outcomes possible. You can do the maths there, which is nothing but 6 cross 6. So 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, and for the rest of the digits the same way, right? 6 cross 6. So that's the different number of outcomes we can get. So now for us to get this 7 sort of random numbers, and imagine that this idea actually relates to a sampling technique as well. When we say we want to get the numbers between 1 to 7, all of those numbers should be equally likely, right? Otherwise it will happen that I might get 1 and maybe quite a number of times versus one particular digit like 2 only once or so on. But if I want to do a very good randomized selection, I need to be making sure the probability of picking any one digit between 1 to 7 is equally likely. If I'm not doing that, I might have a bias, right? So we have these 36 different outcomes. So how do we now make sure that this is kind of equally likely? So first we have to find out a number which is divisible by 7, which is close to 36. So maybe we can exclude one of the possibilities from the 36 combinations we have and keep only these 35 possible outcomes. So like excluding maybe 6, 6. This possibility if we remove, we are left with the remaining 35 possible outcomes. So with this one reduction in the possible outcome, all we are left out with is all the possible combinations starting from 1, 1 till 6, 5, right? Now if we divide this into 7 parts where each like contains 5 possible outcomes. So what will happen is with the 7 parts, each having 5 outcomes, whenever any one outcome comes in these 7 parts, I'm going to assign a value to it. So for instance, if I assign the first 5, because we are going to divide it into 7 parts, where each part will contain 5 possible outcomes. So maybe the first 5 outcomes I will assign to the part 1. So whenever that 5 outcomes comes up, I will say the random number which I have generated is 1. In the second part, I will keep the next 5 outcomes, and whenever that 5 outcomes comes in rolling these 2 dice, I will assign that a value 2, and so on. So this way, what we have done is we have made sure that the random number that we are picking between 1 and 7 are equally likely. If you don't do that, then there will be a bias. So you see here how sort of statistics is like merged with probability. That this is how the two ideas and subjects travel together. Okay. So one more question on the same line. So for instance, here if you have a couple and let's say they have 2 children, so at least one of which is a girl. So this is a given scenario. So the question asks you what is the probability that they have 2 girls, right? It becomes a bit more like tossing 2 coins problem, right? Where there are different combinations. So what you can see here is a couple has 2 children, so at least one of which is a girl. So we have a known fact with us. So now all we need to do to kind of calculate this probability is to generate all the possible combinations. The first child being boy, the second child being girl, the first being girl, the second being boy, and so on, right? If you write that down, this is what the possible combinations are, and all these 4 are equally likely, as you could see. So with this case, we have like in the question, at least one of the children is a girl. So that means only 3 combinations are left out with us. The combination where both the children were boys is excluded. So in a very simple manner, you can like just go ahead and calculate the probability of having 2 girl childs will be 1 by 3. So there are total 3 possibilities which comes in the denominator, and you have like the probability to choose. So there is only one event which favors this probability, like saying 2 girls out of the 3 that we have. So 1 by 3. So let's take up this question here, which says the jar has 1000 coins, of which there are like 999 coins which are fair, right? Which means the head, and there is one head and one tail, and there is one coin which is like tampered with, and both the sides of that coin is head. We need to now pick a coin at random from this jar and toss it 10 times, right? So given that we have seen then 10 heads already in that 10 times of tossing the coin, what is the probability that the next toss of the coin is also going to be head? Right? We are given a statement here that 10 heads are already seen. What is the probability that the 11th toss would be a head? Okay, so let's see how we approach this. So let's first put these 2 possibilities in place. There is this 999 fair coins and one doubly headed coin, right? Double headed coin. So we need to see the probability of how many times we can get that double headed coin. So if I look at from the jar's perspective, choosing a fair coin from this jar is 999 times out of all the 1000 possible coins, so which comes to be 0.9, so high probability. But for the unfair one, though there is a small probability, but it might also appear some point, right? So the probability of selecting 10 heads in a row would then be either you would get a fair coin and toss 10 heads continuously. So this is one possibility. The second possibility is to select an unfair coin where the possibility of head is like 100%, because there are both the sides of the coin is head. So the probability of selecting 10 heads in a row would be the selecting fair coin multiplied by probability of selecting 10 heads, which is nothing but each coin which you are picking up is independent of each other. Getting a head there is also independent there. So the probability is 0.5. That's why we are able to multiply it. So you have here the probability of picking a fair coin to be 0.9 and multiply that with 0.5 10 times. And that's your like probability which you get after that. So this probability of A is selecting a fair coin and getting 10 heads. And the probability of B is selecting an unfair coin, and we know whenever we select that, the surety is we always get a head. So then the probability of B becomes 0.001. So now what we need to find out is this probability where we can sort of say, given we have these two cases, what is the probability that we are able to come out with the 11th head, right? So how are we going to do that is by selecting this kind of combining this probabilities into a sort of form like this, where we are calculating, given these two possible cases, what is the sort of likelihood of with a fair coin getting 10 heads and with an unfair coin getting that one head, right? So those two are the probabilities written here, 0.49 and 0.50. So finally, with these two probabilities known to us, the probability of selecting one more head would mean that in the fair coin the probability is 0.5, right? So which you already know. And in the unfair coin the probability is always going to be 1 because we have both the sides as head. And both of these probabilities we are just going to multiply with the probability of the fact that already 10 coins have been seen and it's head, right? So that's what we are like multiplying in front of it. So if you put this into one formulation, you will finally get the probability of selecting another head is 0.75. So which is like slightly more if you didn't had this sort of one double-headed coin. If that coin would not have been present, the probability would be a bit more less here because all the coins are then fair. Okay. So thanks a lot for listening to this session. Hope this helps for you to prepare for your interviews. So reiterating the fact, give a very good emphasis on basic ideas from stats and probability. Also spend some amount of time understanding machine learning models and basic ways of doing data analysis and things like A/B framework testing and so on. So these are some broad concepts you need to know. Also spend some time on linear algebra kind of ideas like the eigenvalues and eigenvectors. It might also be helpful on certain questions. So all the very best for your interview, and hope you all get a really successful career in data science. Thank you.
I hope you have enjoyed listening to this video. Please be kind enough to like it, and you can comment any of your doubts and queries, and we will reply them at the earliest. Do look out for more videos in our playlist and subscribe to Edureka channel to learn more. Happy learning!